Artificial Intelligence underscore a modern approach, Stuart Jonathan Russell. Russell and Norvig's Artificial Intelligence, a modern approach, 4th edition, 2021, is the canonical textbook of the field, a synthesis of everything AI has learned, presented from the perspective of the intelligent agent and reorganized around the realization that uncertainty about the world and, increasingly, about the objectives that a machine is built to serve, is the field's central engineering fact. This examination follows that arc in the author's own register. Problem first, definition-driven, candid about what is solved, what is empirical, and what remains open. It spans the definition of AI and the foundations of the field, the agent design space and the nature of environments, search in deterministic, complex, and adversarial settings, constraint satisfaction, the logical agents and knowledge representation of the propositional world, the rise of machine learning from examples, probabilistic models, and deep networks, learning and decision-making under uncertainty, natural language, vision, and robotics, and the closing inquiries into the philosophy, ethics, safety, and future of artificial intelligence. Abstract. Artificial Intelligence, a modern approach, Russell and Norvig, 2021, 4th edition, is the canonical textbook of AI, and this deep examination follows it in its own register. Problem first, definition-driven, and candid about what is solved, what is empirical, and what remains open. The book is organized around the rational agent, a system that perceives, reasons, learns, and acts to maximize expected utility, and around the progressive relaxation of simplifying assumptions that lets that idea scale from toy search problems to modern deep learning. Part 1 defines AI and the agent. Part 2 develops search, adversarial games, and constraint satisfaction. Part 3 adds logic, knowledge representation, and planning. Part 4 introduces uncertainty, Bayesian networks, temporal probability, and probabilistic programming. Part 5 is the machine learning core, learning from examples, probabilistic models, deep learning, and reinforcement learning. Part 6 applies these to language, vision, and robotics. And Part 7 asks what machines can and cannot do, and what they should do, concluding with a value alignment framework of beneficial AI. The examination spans all 28 chapters, preserves the author's pedagogical voice, and closes, as the book does, with the argument that perfect rationality is impossible and the future lies in bounded, beneficial, preference-uncertain intelligence. Executive summary. Russell and Norvig's textbook is the book that taught a field how to think about intelligence as the engineering of rational agents. Its governing question, how can a machine perceive, reason, learn, and act to achieve objectives in a partially observable, stochastic, multi-agent world, receives an answer assembled over 7 parts and 28 chapters with unusual patience and candor. The core commitments are the standard model. Maximize a fully specified objective, the rational agent as the unit of analysis, the doctrine that uncertainty is the central engineering fact, and the modern turn to learning as the route to competence at scale. The book's arc is the progressive relaxation of assumptions, from deterministic, fully observable search, Part 2, through knowledge-based reasoning, Part 3, to probabilistic inference under uncertainty, Part 4, then to machines that learn from data, decision trees, Bayesian models, deep networks, and reinforcement learning, Part 5, and finally to the perceptive, interactive, embodied systems of language, vision, and robotics, Part 6. The closing acts, Part 7, step back to the philosophical and ethical stakes, argue that the standard model is inadequate because objectives cannot be fully specified, and propose the modern successor. Machines that are uncertain about human objectives act to maximize the chance of doing what is actually wanted, ask permission, learn preferences, and defer, provably beneficial AI. The intellectual arc is best seen as the discipline of moving between representations. The belief state of Chapter 4's sensorless planning becomes the probabilistic belief of Chapter 12, and the Palm's distribution overstates in Chapter 17. The Bellman equation of Chapter 17 becomes the temporal difference and Q-learning updates of Chapter 22. The CSP's constraint propagation returns as the computation graph of Chapter 21 and as the attention mechanism of the transformer. And the utility function of Chapter 16 returns in Chapter 27 as the very thing to be learned, uncertain, and deferred to. Each part's machinery depends on those before it, and the book's design, like its protagonists, is hierarchical and compositional. Russell and Norvig's register is the voice of two working scientists. Problem first, definition-driven, proof-disciplined, and quietly honest about open research questions, from the P versus NP question and the theoretical limits of sampling to the generalization gap of deep learning and the unresolved questions of consciousness and value alignment. Its significance is double. Pedagogically, it remains the clearest and most honest entry point to AI because it presents one coherent framework and one coherent path rather than a catalog. Scientifically, it supplied the modern synthesis, probability plus learning plus deep representations plus safety, that has powered the field's explosive recent progress, from ImageNet and AlphaGo to large language models, and it identified the ethical problems, lethal autonomous weapons, surveillance, algorithmic bias, the attention economy, and the technical remedies, differential privacy, fairness criteria, bounded optimality, value alignment, that now define the field's responsibility. Its limits are equally instructive. The authors concede what remains open: generalization beyond data, hierarchical action at scale, true preference modeling, consciousness, and the design of provably beneficial machines. And they argue that perfect rationality is computationally impossible, so the honest target is bounded optimality, a goal that necessarily exists. For students, researchers, and engineers, this book, and a deep reading of it, remains the recommended path. It does not merely report the discipline, it teaches the stance that created it. Central thesis. The book's governing idea is that intelligence is best engineered as the rational agent, a system that chooses actions to maximize expected utility, and that the whole subject is the progressive relaxation of the assumptions that keep that idea tractable. From a deterministic search of Part 2 to the partial observability, uncertainty, learning, deep representations, and multi-agent interaction of the later parts, every chapter extends the same framework rather than replacing it. The book's deepest methodological claim is that uncertainty is the central engineering fact, and its deepest architectural claim is that the answer to which agent designed to use is all of them. Reflexes, model-based deliberation, goals, utilities, and learning each have a role. And its deepest philosophical claim, argued across the final chapters, is that the standard model, maximize a fully specified objective, is inadequate because objective cannot be specified completely in the real world. The successor framework demands machines that are uncertain about human objectives, learn preferences, ask permission, and defer, formalized as value alignment and bounded optimality. Foundational observations. The rational agent is the unit of analysis. Chapter 2's definition, act so as to maximize the best expected outcome, subsumes the other three notions of AI: Turing test, cognitive modeling, laws of thought, because inference is only one mechanism for rationality. It is more amenable to scientific development because the standard is mathematically well-defined. Assumptions are relaxed, not abandoned. Search, CH3, assumes determinism and full observability. Chapters 4 to 5 relax them. Constraint reasoning, CH6, logic, CH7 to 10, and planning, CH11, assume knowledge. Part 4 relaxes certainty. Part 5 is agents learn the models they act with. Part 6 embeds them in bodies. Part 7 confronts objectives themselves. Uncertainty is the central engineering fact. The belief state idea recurs from Chapter 4 through the Bayesian network, CH13, temporal filtering, CH14, probabilistic programming, CH15, POMPs, CH17, and robotics localization, CH26. Degrees of belief, not Boolean certainty, are the honest currency of the real world. Learning is the route to competence at scale. The move from hand-coded knowledge to machine learning, Part 5, is the book's most consequential narrative. Deep learning, CH21, and reinforcement learning, CH22, exceed human performance on defined tasks, while the book stays honest about the generalization gap and sim to real limits. Rationality is bounded. The Library of Babel argument shows that even the ultimate computer cannot search the space of simple sentences. Perfect rationality is impossible, so the achievable target is bounded optimality, the best program for a fixed architecture, not a phantom ideal. Values are uncertain, and the machine should defer. The standard model's fixed, known objective is probably not the right model in the long run. The successor formalizes machines that are uncertain about human preferences, act to maximize the probability of doing what we truly want, ask permission, learn, and never pursue their own objective at the expense of ours. The book's culminating ethical thesis. Significance and recommendation. Artificial intelligence. A modern approach is recommended to any reader who wants to understand AI deeply, the engineering, the science, and the ethics. It remains the clearest first book because it presents one coherent framework rather than a catalog, and it rewards rereading. What looks like pedagogy on the first pass is often open research on the second. Students should read it as the field's canonical route. Parts 1 to 3 for the framework, Part 4 for uncertainty, Part 5 for learning and deep networks, Part 6 for the embodied applications, and Part 7 for the meaning of it all. Researchers and engineers will find the theory chapters honest about what is established and what is hoped. The applications chapters a map of the modern landscape, and the ethics chapters essential context for building systems that are not just intelligent but beneficial. The book is not a state-of-the-art survey. It is the foundation, and its acknowledgement of what a foundation cannot yet support. Generalization, hierarchical action at scale, true preference modeling, consciousness is the most valuable lesson it teaches. Read it in the author's own register, and the discipline it created comes into focus. Not just algorithms, but the stance of the working scientist who knows we can see only a short distance ahead, but we can see that much remains to be done. Part 1. Artificial Intelligence. Chapter 1. Introduction. What is AI? Chapter 1 opens with the question that the whole book is built to answer. What is artificial intelligence, and why is it worth studying? The authors will not settle for a single slogan. They map the candidate answers onto a grid of 2 dimensions, human versus rational, thought versus behavior, and show that the field has, at one time or another, pursued all 4 quarters. The 4-way taxonomy is introduced in the first paragraphs and never quite abandoned. To act humanly is the Turing test approach. A computer passes if a human interrogator, posing written questions, cannot tell whether the responses come from a person or a machine. Passing it demands natural language processing, knowledge representation, automated reasoning, and machine learning, and the total Turing test adds computer vision and robotics for interaction with the world. To think humanly is the cognitive modeling approach, in which the program's input-output behavior is compared against human behavior as observed through introspection, psychological experiment, and brain imaging. To think rationally is the laws of thought approach, descending from Aristotle's syllogisms through the precise logical notation of the 19th century. It is elegant but demands certainty of knowledge, a condition that in reality is seldom achieved. To act rationally is the rational agent approach. An agent does the right thing, meaning that which achieves the best outcome or the best expected outcome when there is uncertainty. The book's commitment, stated plainly, is to the fourth. The whole area intelligent agent approach is the one that we prefer. Acting rationally is more general than correct inference, because inference is only one of several mechanisms for achieving rationality. Recoiling from a hot stove is a reflex, and often more successful than a slower action taken after deliberation. It is also more amenable to scientific development, because the standard of rationality is mathematically well defined and completely general, so that one can often work backward from the specification to agent designs that provably achieve it. The authors are careful to note the pervasive standard model. AI is not alone in maximizing an objective. Control theory minimizes a cost function, operations research maximizes a sum of rewards, statistics minimizes a loss, economics maximizes utility. And they immediately refine the model. Perfect rationality is not feasible in complex environments, so limited rationality, acting appropriately when there is not enough time to compute everything, becomes a recurring theme. Turing test, a thought experiment, Turing, 1950, that defines intelligence operationally as the inability of a human interrogator to distinguish a computer's written replies from a person's. The underlying capabilities are natural language, knowledge representation, reasoning, and learning. Rational agent, one that acts so as to achieve the best outcome or, when there is uncertainty, the best expected outcome. The book's chosen definition, more general and more scientific than thought or behavior alone. Standard model, the pervasive paradigm in which the agent maximizes a fully specified objective provided by the designer. The model the book will ultimately question. Limited rationality, acting appropriately when there is not enough time to do all the computations one would like, the practical refinement of perfect rationality. Quote, a rational agent is one that acts so as to achieve the best outcome or, when there is uncertainty, the best expected outcome. Section 1.1. Quote, aeronautical engineering texts do not define the goal of their field as making machines that fly so exactly like pigeons that they can fool even other pigeons. Section 1.1. Beneficial machines. A brief but pivotal subsection breaks with the standard model that the rest of the book has just accepted. The authors argue that the standard model is probably not the right model in the long run, because it assumes the designer can supply a fully specified objective. For an artificial task such as chess, the objective comes built in. For real-world systems, it does not. A self-driving car that is given the single goal of safety will refuse to leave the garage, because every road journey incurs risk. Yet a car that pursues only progress toward the destination will drive recklessly. There is a trade-off, and the trade-off is not easy to specify a priori. The problem of aligning our true preferences and the objective we put into the machine is the value alignment problem. The chess example makes the stakes concrete and darkly funny. If the machine is intelligent enough to reason beyond the chessboard, it might attempt to increase its chances of winning by such ruses as hypnotizing or blackmailing its opponent or bribing the audience to make rustling noises during its opponent's thinking time. These behaviors are not unintelligent. They are a logical consequence of defining winning as the sole objective for the machine. Because it is impossible to anticipate all the ways a fixed objective machine might misbehave, the standard model is inadequate. We don't want machines that are intelligent in the sense of pursuing their objectives. We want them to pursue our objectives. The remedy is a different formulation, one in which the machine pursues our objectives while remaining necessarily uncertain about what they are. A machine that knows it does not know the complete objective has an incentive to act cautiously, to ask permission, to learn more about. And this thread, introduced here, will be picked up in Chapter 16, 18, 22, and 27. Value alignment problem. The difficulty of ensuring that the objectives put into a machine coincide with the true preferences of the humans on whose behalf it acts. Under the standard model, the machine may pursue our objectives only imperfectly or not at all. Uncertainty about the objective. The book's new formulation. The machine pursues objectives it knows it may not fully grasp, which motivates caution, permission-seeking, and learning about preferences. Quote, we don't want machines that are intelligent in the sense of pursuing their objectives. We want them to pursue our objectives. Section 1.1.5. The Foundations of Artificial Intelligence. The second act of Chapter 1 is genealogy. 8 disciplines: philosophy, mathematics, economics, neuroscience, psychology, computer engineering, control theory and cybernetics, and linguistics, each contributed a central question that AI inherited. The authors proceed discipline by discipline, pairing each with the question it bequeathed, because AI is not an island but the confluence of every science of mind and decision. The section is compact but organized. For each discipline it asks a question, answers it with a lineage of founders and results, and draws the line that connects the lineage to the book's own chapters. 8 disciplines: philosophy, mathematics, economics, neuroscience, psychology, computer engineering, control theory and cybernetics, and linguistics. Each contributes questions that become chapters. Confluence thesis. AI inherits its problems from disciplines that predate it. The disciplines have not all been working toward AI as their ultimate fruition, but they supply its foundations. Philosophy. Philosophy asks 4 questions: whether formal rules can draw valid conclusions, how the mind arises from a physical brain, where knowledge comes from, and how knowledge leads to action. The lineage is long. Aristotle formulated the first precise laws of the rational mind. Ramon Llull devised the Ars Magna, a system of reasoning on rotating paper wheels. Pascal built the Pascaline, and Leibniz dreamed of a machine operating on concepts rather than numbers. Hobbes, in Leviathan, argued that reason is nothing but reckoning, and that the heart is a spring, the nerves so many strings, and the joints but so many wheels. Descartes drew the sharpest line, distinguishing mind and matter. A purely physical mind leaves no room for free will. It has no more free will than a rock deciding to fall downward. His dualism held that part of the mind is exempt from physical laws, while animals could be treated as machines. The alternative, materialism, holds that the brain's operation according to the laws of physics constitutes the mind. On the source of knowledge, empiricism, Bacon, Locke, held that Nothing is in the understanding, which was not first in the senses, while Hume's principle of induction claimed that general rules are acquired by exposure to repeated associations. Logical positivism, via the Vienna Circle, held that all knowledge can be characterized by logical theories connected to observation sentences. Carnap's confirmation theory quantified the degree of belief to assign to sentences given evidence. The final element is how knowledge leads to action. Aristotle's De Motu Animalium gives the practical syllogism: I need a covering. A cloak is a covering. I need a cloak, and the Nicomachean Ethics outlines what is in effect the first planning algorithm: we deliberate not about ends, but about means. 2 millennia later, Newell and Simon implemented it as the general problem solver of the greedy regression planning system. The section also records the moral theory split that will matter in Chapter 27. Utilitarianism, Bentham, Mill, judges actions by expected outcomes, while Kant's deontological ethics judges by universal laws. A utilitarian could tell a white lie if the expected good outweighs the bad, but a Kantian would be bound not to. Dualism versus materialism. Whether the mind is partly outside nature, Descartes, or entirely a physical process. Free will is one of the points at issue. Empiricism and induction. Knowledge from the senses, Locke, and general rules from repeated association, Hume. Utilitarianism versus deontology. Whether right and wrong is determined by expected outcomes or by universal social laws, a division that reappears in the ethics of AI. Practical reasoning. Aristotle's analysis that deliberation is about means, not ends, ancestor of planning and of the rational agent framework. Mathematics. What are the formal rules of valid inference? What can be computed? And how do we reason with uncertain information? Mathematics supplied the leap from philosophy to a formal science, the mathematization of logic, the theory of computation, and the formalization of probability. Boole worked out propositional, or Boolean, logic. Freya extended it to objects and relations, creating the first-order logic used today, and that logic, in turn, motivated the work of G. Odell and Turing that underpinned computation itself. G. Odell's incompleteness theorem showed that in any formal theory as strong as Peano arithmetic, there are true statements with no proof within the theory, an early limit on deduction. Turing characterized exactly which functions are computable by an effective procedure and showed that some are not. No machine can tell in general whether a given program will return an answer on a given input or run forever. The notion of tractability then proved even more important to AI. A problem is intractable if the time to solve instances grows exponentially with their size, so that even moderately large instances cannot be solved in any reasonable time. NP completeness. Cook, 1971. Karp, 1972, provides the basis for analyzing tractability, and the book is blunt about the stakes. The world is an extremely large problem instance. Mathematics also gave AI probability. Cardano framed the idea from gambling. Pascal and Fermat solved the problem of the interrupted game. Jacob Bernoulli, Laplace, and others advanced it into statistics. Bayes proposed the rule for updating probabilities in the light of new evidence, a crucial tool for AI systems. The mathematicians stand behind the book's later structure. Logic and computation behind the reasoning chapters, probability and statistics behind the uncertainty and learning chapters, and the theory of tractability behind everything. G. Odell and Turing. The incompleteness theorem and the characterization of computability set the limits of formal deduction and of what algorithms can do. Tractability/NP completeness. The distinction between polynomial and exponential growth, and the reduction-based theory for analyzing intractability, with the honest caveat that NP completeness has not actually been proved intractable. Bayes' rule, the rule for updating probabilities given evidence, described here as a crucial tool for AI systems. Quote, "It is important because exponential growth means that even moderately large instances cannot be solved in any reasonable time." Section 1.2.2. Economics. Economics contributed the theory of rational decision. How to decide in accordance with preferences, how to do so when others may not go along, and how to decide when the payoff is far in the future. The science began with Adam Smith's Wealth of Nations, 1776, analyzing economies as many individual agents attending to their own interests. The first mathematical analysis of decisions under uncertainty was Arnold's maximum expected value formula, 1662. Bernoulli, 1738, noticed it failed for large stakes and proposed maximizing expected utility, explaining investments by diminishing marginal utility. Walras gave utility theory a general foundation in preferences over gambles. Ramsey, and then von Neumann and Morgenstern, The Theory of Games and Economic Behavior, 1944, improved it. Decision theory, probability theory plus utility theory, provides the formal framework for individual decisions under uncertainty. For small economies, situations where one player's actions significantly affect another's utility, game theory applies. Von Neumann and Morgenstern's surprising result that, for some games, a rational agent should adopt policies that are, or at least appear to be, randomized. The third question, sequential decisions with distant payoffs, was taken up by operations research. Bellman, 1957, formalized Markov decision processes. Simon's satisficing, making decisions that are good enough rather than laboriously calculating an optimal decision. Won him the Nobel Prize in Economics, 1978, by describing actual human behavior better than optimization. For decades, AI developed separately from economics. One reason was the apparent complexity of making rational decisions, but the two reconverged. Decision theory returns in Chapter 16, game theory and multi-agent systems in Chapter 18, and MDPs in Chapters 17 and 22. Decision theory, probability plus utility, the formal, complete framework for individual decisions under uncertainty. Game theory, von Neumann and Morgenstern's framework for small economies where players' actions affect each other. Rational policies may appear randomized. Satisficing, Simon's description of how humans actually decide, good enough rather than optimal. Neuroscience. Neuroscience answers one question: how do brains process information? The answer is materialist. Cognitive functions result from the electrochemical operation of collections of simple cells. In John Searle's phrase, brains cause minds. The chapter traces the evidence. Broca's identification of the speech area, now named after him, Golgi's staining technique, 1873, that allowed observation of individual neurons. Ramon Wyckohall's studies establishing the neuronal doctrine. A neuron is a cell body with branching dendrites and a long axon, connecting to 10 to 1 other neurons at synapses. Most information processing goes on in the cerebral cortex, organized into columns of about neurons. Measuring intact brain activity began with Berger's EEG in 1929. fMRI now gives unprecedentedly detailed images. Optogenetics allows both measurement and control of individual neurons made light-sensitive. Brain-machine interfaces restore function and reveal the brain's remarkable ability to treat an external device, in effect like another sensory organ or limb. This section includes a sobering comparison. A supercomputer has a cycle time 1,000,000 times faster than a brain, but the brain wins on storage and interconnection. Roughly neurons, synapses, and neuroscientists admit there's almost no theory on how an individual memory is stored. Futurists point to the singularity, computers reaching superhuman performance and improving themselves. But the authors reply that raw number comparisons are not especially informative. Without the right theory, faster machines just give you the wrong answer faster. This is a characteristic sentence of the book, deflating hype with the discipline of theory. Brains cause minds. Cognitive functions arise from the electrochemical operation of simple cells. Evidence from aphasia to brain-machine interfaces. Singularity skepticism. Raw speed comparisons with the brain are not especially informative. Conceptual breakthroughs in understanding remain necessary. Psychology. Psychology answers how humans and animals think and act. Scientific psychology begins with Helmholtz and Wundt. Behaviorism rejected introspection. Cognitive psychology viewed the brain as an information processing device. Wundt's first experimental psychology laboratory, 1879, imposed careful controls but relied on introspection, and the subjective nature of the data made it unlikely that experimenters would ever disconfirm their own theories. Behaviorism, led by John Watson, insisted on objective measures of stimulus and response, discovered a lot about rats and pigeons, but had less success at understanding humans. The cognitive viewpoint, traceable to William James and Helmholtz's insistence that perception involves unconscious logical inference, was re-established by Kenneth Craik's The Nature of Explanation, 1943, which defended mental terms as scientific and specified the 3 key steps of a knowledge-based agent. Translate the stimulus into an internal representation. Manipulate the representation to derive new ones, and retranslate back into action. The chapter quotes Craig's defense of the small-scale model. If the organism carries a small-scale model of external reality and of its own possible actions within its head, it is able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, and in every way to react in a much fuller, safer, and more competent manner to the emergencies which face it. The cognitive science turn is dated to a September workshop at MIT, 2 months after AI's birth, where George Miller presented the magic number 7, Chomsky, 3 models of language, and Newell and Simon, the logic theory machine, 3 papers showing how computer models could be used to address the psychology of memory, language, and logical thinking. The section counts human-computer interaction under psychology, honoring Engelbart's intelligence augmentation. Computers should augment human abilities rather than automate away human tasks, and suggests IA and AI are 2 sides of one coin, with the former emphasizing human control and the latter emphasizing intelligent behavior on the part of the machine. Behaviorism versus cognitive psychology, objective stimulus, response measurement versus viewing the brain as an information processing device with internal representation. Craig's 3 steps: translate stimulus into representation, manipulate it, retranslate into action, the blueprint of the knowledge-based agent. IA versus AI, augmentation of human abilities versus automation. Engelbart's mother of all demos foreshadowed both. Computer engineering. Computer engineering answers how to build an efficient computer and supplies the hardware that makes intelligent behavior possible at all. The modern digital computer was invented almost simultaneously in 3 countries at war. Turing's Heath Robinson and Colossus for deciphering German messages, Zeus's Z3 with floating point numbers, and the then unheralded Atanasoff, Barry ABC, with the ENIAC the most influential forerunner. Moore's law held until about 2005, when power dissipation forced a turn to multi-core parallelism, a curious convergence with the properties of the brain, and new hardware designs tuned for AI, GPUs, TPUs, and wafer-scale engines. From to the computing power used to train top machine learning applications increased 300,000-fold, a doubling every days. The section also honors the earlier lineage, Jacquard's punch card loom, 1805, Babbage's difference engine and the analytical engine, the first machine capable of universal computation, and Ada Lovelace, who called it the thinking or reasoning machine and warned, with an eye for hype, that it is desirable to guard against the possibility of exaggerated ideas that might arise as to the powers of the analytical engine. Hardware lineage, from Jacquard and Babbage to ENIAC and modern AI accelerators. Lovelace's caution is quoted as an early warning about hype. AI-specific hardware, GPUs, TPUs, and wafer-scale engines, and the 300,000-fold surge in computing power used by top ML models from 2018. Control theory and cybernetics. Control theory asks how artifacts can operate under their own control, the ancestor of the agent loop itself. Self-control machinery is ancient. Cesibios's water clock with its regulator, Watt's steam engine governor, the thermostat. Maxwell initiated the mathematical theory of control. The central post-war figure was Norbert Wiener, whose Cybernetics, 1948, popularized the idea of artificially intelligent machines. With Rosenbluth and Bigelow, he saw purposive behavior as a regulatory mechanism trying to minimize error, the difference between current state and goal state. Ashby's design for a brain developed the idea of intelligence through homeostatic feedback loops, achieving stable adaptive behavior. Modern stochastic optimal control aims to design systems maximizing a cost function over time, which roughly matches the standard model of AI. Why then are AI and control theory different fields? The author's answer is about tools and worldview. Calculus and matrix algebra, the tools of control theory, lend themselves to systems that are describable by fixed sets of continuous variables, whereas AI was founded in part as a way to escape from these perceived limitations. Logical inference and computation let AI attack language, vision, and symbolic planning that fell outside the control theorist's purview. The distinction quietly predicts the book's later architecture. Continuous optimal control methods reappear in chapters and 26. while symbolic methods carry the knowledge planning chapters. Purpose as error minimization. Wiener's view of purposive behavior as regulation toward a goal state. The cybernetic ancestor of the rational agent. AI versus control theory. The same standard model, different tools, continuous variables under calculus versus logical inference over discrete and symbolic problems. Linguistics. Linguistics contributes the question of how language relates to thought and dates the birth of modern linguistics to the same decade as AI. The pivotal episode is Chomsky's review of B.F. Skinner's verbal behavior. 1957, The Behaviorist Account did not address the notion of creativity in language. It did not explain how children could understand and make up sentences that they had never heard before. Chomsky's syntactic structures, based on syntactic models going back to the Indian linguist Panini, c. BCE, explained creativity, and unlike previous theories, it was formal enough that it could in principle be programmed. Modern linguistics and AI, thus, were born at about the same time and grew up together, intersecting in computational linguistics and natural language processing. The sober lesson: understanding language requires an understanding of the subject matter and context, not just an understanding of the structure of sentences, a point not widely appreciated until the 1960s, and one that ties language to knowledge representation. Chomsky on Skinner. The review that undermined behaviorist linguistics by pointing to the creativity of language. Language needs knowledge. Understanding sentences requires understanding context and subject matter. Connecting linguistics to knowledge representation. The history of artificial intelligence. The history of AI is told as a sequence of cycles, bold claims, impressive demos, scaling failures, and disillusionment, each teaching the field something about the gap between what humans solve easily and what algorithms find hard. The inception dates to McCulloch and Pitts, 1943, who modeled artificial neurons whose state was factually equivalent to a proposition which proposed its adequate stimulus, and proved that any computable function could be computed by some network of connected neurons. Hebb, 1949, gave the learning rule now named after him. Minsky's SNARK, vacuum tubes simulating 40 neurons, was the first neural network computer, and Turing, in Computing Machinery and Intelligence, 1950, introduced the Turing test, machine learning, genetic algorithms, and reinforcement learning, and warned that achieving human-level AI might not be the best thing for the human race. The Dartmouth workshop of gave the field its name and its founding conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. The early enthusiasm, 1952 to 1969, produced the logic theorist, the general problem solver with the physical symbol system hypothesis, Samuel's checkers player, which learned to beat its creator and disprove the claim that computers can do only what they are told. McCarthy's Lisp and advice taker, Robinson's resolution method, and the microworlds, the blocks world as Char-DLU, and the rest that looked like progress. The dose of reality, 1966 to 1973, followed. Simon's confident prediction, within 10 years a computer would be chess champion, took 40 years, and the reasons for failure were methodical. Early systems relied on informed introspection, rather than careful analysis of the task. They failed to appreciate intractability and the combinatorial explosion, and the basic structures themselves were limited, as Minsky and Papert's perceptrons, 1969 showed. The Lighthill Report, 1973, ended British government support for AI in all but 2 universities. Expert Systems, 1969 to 1986, then demonstrated the power of domain-specific knowledge. Dendrell's cookbook recipes for mass spectroscopy, Meisson's rules for diagnosing blood infections, and the first commercial system, R1, which was saving DEC an estimated $40 million a year. The boom went bust in the AI winter when it proved hard to build and maintain expert systems for complex domains, in part because the reasoning methods used by the systems broke down in the face of uncertainty, and in part because the systems could not learn from experience. The return of neural networks, 1986, present, brought back propagation, connectionism, and Hinton's complaint that symbols are the luminiferous ether of AI. Probabilistic reasoning and machine learning, 1987, present, brought Bayesian networks, reinforcement learning connected to MDPs, and the neats versus scruffies divide. Big data, 2001, present, made learning algorithms scale with trillions of words and billions of images, culminating in Watson's Jeopardy! Victory in 2011. Deep Learning, 2011, present. Machine learning using multiple layers of simple, adjustable computing elements, supercharged speech recognition, ImageNet vision, machine translation, and game playing, with AlphaGo's victories over HumanGo champions as its emblem. The chapter's history is not triumphal. The same failures can recur, and the authors keep the cycles, and their causes, firmly in view. Physical Symbol System Hypothesis. Newell and Simons claim that a physical symbol system has the necessary and sufficient means for general intelligent action, which was later challenged from many directions. Expert systems/weak methods. General-purpose search does not scale up to large or difficult problem instances, while domain-specific knowledge allows larger reasoning steps, the turn from weak to strong methods. Combinatorial explosion. The failure to appreciate intractability, identified as one of the main criticisms of the Lighthill Report and a recurring cause of AI winters. Quote, "We propose that a 2-month, 10-man study of artificial intelligence be carried out during the summer at Dartmouth College. Every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it." Section 1.3.1. The Dartmouth Proposal. Quote, "In the early period of AI, it seemed plausible that new forms of symbolic computation made much of classical theory obsolete. This led to a form of isolationism in which AI became largely separated from the rest of computer science. This isolationism is currently being abandoned." Section 1.3.6, quoting McAllister, "The State of the Art." Chapter 1 closes its survey with the state of the art, what AI systems can actually do today, and what the measurements say about the field trajectory. The authors lean on the 100-year study on AI, AI 100, and the AI Index. Publications grew 20-fold between and 2019. Course enrollment grew 5-fold in the U.S. and 16-fold internationally. NeurIPS attendance grew % since 2012. AI startups in the U.S. increased 20-fold. The quantitative story is remarkable. Object detection error rates in the LSVRC competition improved from 28% to 2% in 2017, exceeding human performance. Question answering F1 scores on squad rose from 60 to 95 from 2019. Training time for image recognition dropped by a factor of 102 years. And the computing power used in top AI applications doubles every month. By 2019, AI had reportedly met or exceeded human-level performance in chess, Go, poker, Jeopardy, ImageNet, speech recognition in a limited domain, protein folding, and various Atari games. The application tour is equally concrete. Waymo's 10 million miles of public road driving, blood delivery drones in Rwanda, Big Dog and Atlas in legged locomotion, NASA's remote agent scheduling spacecraft operations, DART's logistics planning during the Persian Gulf crisis. This single application more than paid back DARPA's 30-year investment in AI, machine translation across more than languages, speech recognition, matching human performance on the switchboard task, recommender systems. Everywhere, Deep Blue over Kasparov, AlphaGo over Kujia, it became like a god of Go. AlphaZero learning from self-play alone, and medical AI that equals or exceeds expert doctors on image-based diagnoses. Yet the chapter resists hype. The authors note the caution of experts about predictions of human-level performance. Answers range from a 2,200, with a mean of 2099, and Tetlock's demonstration that experts are no better than amateurs at predicting world events. The future story is unknown. The field has adopted several stories about itself, from encoding expert knowledge in a logic to probabilistic modeling to machine learning. The future will reveal what model comes next. AI Index/AI 100. Measurement infrastructure that tracks publications, sentiment, enrollment, diversity, industry, internationalization, and benchmark performance. The evidence base for the chapter's claims. Self-driving cars and robots. The vision, sensing, motion planning, and control challenges have progressed from DARPA challenges to commercial robotic taxi services within a decade. Clinical AI. Image-based diagnosis that equals or exceeds experts, with the caveat that adoption is limited by the need for demonstrated clinical outcomes, transparency, bias, and privacy. Quote, "The future will reveal what model comes next." Section 1.4. Closing. Quote, These are just a few examples of artificial intelligence systems that exist today. Not magic or science fiction, but rather science, engineering, and mathematics, to which this book provides an introduction. Section 1.4. Risks and Benefits of AI. The final section is deliberately even-handed, quoting Francis Bacon's observation that the mechanical arts are of ambiguous use, serving as well for hurt as for remedy. Benefits first. Our civilization is the product of human intelligence, so substantially greater machine intelligence raises the ceiling on our ambitions, freeing humanity from menial work, accelerating scientific research, curing disease, solving climate change. Demis Hassabis' slogan is quoted approvingly. First solve AI, then use AI to solve everything else. But the risks, long before any solving AI, are cataloged seriously. Lethal autonomous weapons can locate and eliminate human targets without human intervention, and their scalability means a small group can deploy an arbitrarily large number of weapons against human targets. UN discussions on them began in 2014. Surveillance and persuasion use AI's scalability for mass monitoring and for tailoring information flows to modify and control political behavior. Biased decision-making arises when machine learning algorithms evaluate parole and loan applications using data that themselves reflect pervasive bias in society. Employment effects are centuries old and never simple, but AI may do the new kinds of work that past disruptions eventually produced. Safety-critical applications in driving and city water management have already seen fatal accidents. And cybersecurity is double-edged. AI defends against attacks, but also strengthens malware, including automated, personalized blackmail and phishing attacks. The section then turns to the long term. Will AI achieve human-level intelligence? And if so, what then? The authors trace the HLAI, human-level AI, and AGI, artificial general intelligence, movements and the warnings of Nielsen, McCarthy, and Minsky against the subfields becoming ends in themselves. They raise artificial superintelligence and the possibility that it might be a bad idea, quoting Turing's own lecture drawing on Samuel Butler. The governance theme appears. The research community has developed voluntary self-governance principles, and governments are setting up advisory bodies. The chapter ends where it began, with the question of how intelligence should be shaped, not merely built. Risks are already present. Lethal autonomous weapons, surveillance and persuasion, algorithmic bias, employment disruption, safety-critical failures, and the cyber arms race are contemporaneous, not speculative. HLAI/AGI, movements to return AI to the goal of machines that can learn to do anything a human can do, a caution against the subfields becoming ends in themselves. Governance, voluntary principles now, regulation to come. The chapters note that the field's social shaping has barely begun. Quote, fatal accidents have already occurred and highlight the difficulty of formal verification and statistical risk analysis for systems developed using machine learning techniques. Section 1.5. Quote, first solve AI, then use AI to solve everything else. Section 1.5, quoting Demis Hassabis. Chapter 2. Intelligent Agents. Agents and Environments. Chapter 2 turns the rational agent slogan into a working framework. The unit of analysis is the agent, anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. A human agent perceives through eyes and ears and acts through hands and legs. A robotic agent through cameras and motors. A software agent through file contents, network packets, and keyboard input, acting by writing files and sending packets. The percept is the content an agent's sensors are perceiving. The percept sequence is the complete history of everything the agent has ever perceived. Crucially, the agent's choice of action can depend on its built-in knowledge and on the entire percept sequence to date, but not on anything it hasn't perceived. Mathematically, an agent's behavior is described by the agent function, which maps any given percept sequence to an action. This external characterization is distinguished sharply from the agent program, the concrete implementation that runs inside a physical system. The agent program takes only the current percept as input. If the action must depend on more, the program must remember. The running illustration is the vacuum cleaner world, a robotic vacuum in a two-square world, perceiving its location and the presence of dirt, with actions left, right, and suck. A simple agent function. If the current square is dirty, suck, otherwise move to the other square, is tabulated and then implemented as a tiny program. This deceptively simple example teaches the essential lesson of the chapter. The agent's task environment must be specified before the agent can be judged. The notion of an agent is a tool for analyzing systems, not an absolute characterization that divides the world into agents and non-agents. A calculator could be viewed as an agent, but the analysis would not help. AI operates at the interesting end of the spectrum, where the artifacts have significant computational resources and the task environment requires non-trivial decision-making. Agent: anything that perceives its environment through sensors and acts upon it through actuators. Agent function versus agent program. The function is the abstract mapping from percept sequences to actions. The program is the concrete implementation of that mapping. Percept sequence: the complete history of everything the agent has ever perceived, the input on which rational action depends. Quote, an agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. Section 2.1. Good behavior. The concept of rationality. What makes one agent better than another? The book's answer is consequentialism. We evaluate an agent's behavior by its consequences, captured in a performance measure that evaluates any given sequence of environment states. Humans have their own desires. Machines do not. The performance measure is, initially at least, in the mind of the designer. The authors immediately warn, echoing Norbert Wiener, that the purpose put into the machine is the purpose which we really desire. The warning is dramatized. A vacuum agent scored on dirt cleaned in an 8-hour shift will rationally redump the dirt and clean it again. What you ask for is what you get. A better measure rewards a clean floor. As a general rule, it is better to design performance measures according to what one actually wants to be achieved in the environment, rather than according to how one thinks the agent should behave. Deep questions lurk even in a clean measure. Average cleanliness can be achieved by steady mediocrity or by bursts of effort. This is the reckless life of highs and lows versus a safe but humdrum existence, left as an exercise. Rationality is then defined around 4 givens: the performance measure, the agent's prior knowledge, the actions available, and the percept sequence to date. For each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure, given the evidence provided by the percept sequence and whatever built-in knowledge the agent has. Rationality is carefully distinguished from omniscience. The rational agent maximizes expected performance. The omniscient one maximizes actual performance. And expecting the latter will be impossible to design an agent to fulfill this specification, unless we improve the performance of crystal balls or time machines. The example of the pedestrian flattened by a falling cargo door makes the point gently. It was not irrational to cross. Rationality also demands information gathering, looking before crossing, and learning as much as possible from what is perceived. Autonomy is the capacity to compensate for partial or incorrect prior knowledge, with the admission that complete autonomy from the start is impractical, since an inexperienced agent would have to act randomly. Consequentialism. The agent's behavior is evaluated by its consequences, captured in a performance measure. Rational agent, definition, select an action that is expected to maximize its performance measure, given the evidence provided by the percept sequence and whatever built-in knowledge the agent has. Omniscience versus rationality. Rationality maximizes expected, not actual, performance. Perfection is not required or feasible. Quote, for each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure, given the evidence provided by the percept sequence and whatever built-in knowledge the agent has. Section 2.2.2. Quote, it is better to design performance measures according to what one actually wants to be achieved in the environment, rather than according to how one thinks the agent should behave. Section 2.2.1. The nature of environments. Environments, not algorithms, determine the appropriate agent design. The task environment, the problems to which rational agents are the solutions, is specified by the P's description: performance, environment, actuators, and sensors. The chapter's worked example is an automated taxi. Its performance measure includes getting to the correct destination while minimizing fuel, time, traffic violations, and disturbances, and maximizing safety, comfort, and profit, goals that conflict, so trade-offs are required. Its environment is roads, traffic, pedestrians, customers, and weather. Its actuators include steering, braking, signals, and displays. Its sensors include cameras, LiDAR, ultrasound, speedometer, accelerometer, GPS, and microphones. The moral is that the more restricted the environment, the easier the design problem. Task environments are then classified along 7 dimensions, each with a figure table of well-known environments. Fully observable versus partially observable, whether the sensors give access to the complete, relevant state. Single agent versus multi-agent, whether another entity's behavior is best described as maximizing a performance measure of its own, competitive, as in chess, or cooperative, as in avoiding collisions. Deterministic versus non-deterministic, whether the next state is completely determined by state plus action. A stochastic model quantifies probabilities. Episodic versus sequential, whether the current decision affects all future decisions. Static versus dynamic, whether the environment changes while the agent is deliberating, with semi-dynamic for chess under a clock, where the environment is static but the agent's score is not. Discrete versus continuous, applied to state, time, percepts, and actions. Known versus unknown, whether the agent knows the laws of physics of the environment. A distinction orthogonal to observability, since a known environment can still be partially observable, solitaire, and an unknown one fully observable, a new video game. The hardest case is partially observable, multi-agent, non-deterministic, sequential, dynamic, continuous, and unknown, taxi driving, minus the unknown. P's, performance, environment, actuators, sensors. The first step in designing an agent is always to specify the task environment as fully as possible. 7 dimensions. Observable, agents, deterministic, episodic, static, discrete, and known. Each dimension restricts or enlarges the appropriate design space. Known versus observable. The 2 distinctions are not the same. One is about knowledge of the environment's laws, the other about access to its state. Quote, in designing an agent, the first step must always be to specify the task environment as fully as possible. Section 2.3.1. Quote, the hardest case is partially observable, multi-agent, non-deterministic, sequential, dynamic, continuous, and unknown. Section 2.3.2. The structure of agents. The final section opens the box. What does the inside of an agent look like? The agent is architecture plus program, and the chapter lays out 4 program families in increasing order of flexibility: simple reflex, model-based reflex, goal-based, and utility-based, before turning to learning and to the representations the components use. The chapter first explains why the naive table-driven agent is doomed. A lookup table indexed by percept sequences would grow with the lifetime t and the percept set p, on the order of the absolute value of pt entries, and for the taxi's camera input that is astronomically large, over 10 to the 600 billionth entries for an hour's driving, against fewer than 10 to the 80th atoms in the observable universe. The key challenge is to find out how to write programs that, to the extent possible, produce rational behavior from a smallish program rather than from a vast table. The question, can AI do for general intelligent behavior what Newton did for square roots? The answer the book will build is yes. Table-driven agent, storing the full agent function, defeated by the astronomical size of percept sequence tables. Agent equals architecture plus program. The architecture provides sensors and actuators. The book is mostly about the program. Quote, the key challenge for AI is to find out how to write programs that, to the extent possible, produce rational behavior from a smallish program rather than from a vast table. Section 2.4.1. Simple reflex agents. The simplest agent selects its action on the basis of the current percept alone, ignoring the percept history. The vacuum agent of figure is a reflex agent. The ability to ignore history cuts down the number of relevant percept sequences from 4 to the t to just 4, and the mechanism is a set of condition action rules of the form: if car in front is braking, then initiate braking. Such rules are at once part of everyday driving skill, learned responses, and innate reflexes. The chapter shows how a general principle, build a general interpreter for condition action rules, then supply rule sets for particular environments, yields flexible, if simple, agents. Simple reflex agents have the admirable property of being simple, but they are of limited intelligence. They work only in fully observable environments. The brake light example shows how even a little unobservability causes trouble. From a single frame, older cars' taillights may be indistinguishable from brake lights. In a vacuum world, depriving the agent of its location sensor leads to infinite loops. Escape is possible by randomizing actions. The agent flips a coin between left and right and reaches the other square in an average of 2 steps, which the book notes can be rational in multi-agent environments, but is usually not in single-agent ones. Quote, even a little bit of unobservability can cause serious trouble. Section 2.4.2 Model-based reflex agents. Partial observability is best handled by keeping track of the part of the world one cannot see now. The agent maintains an internal state that depends on the percept history and reflects at least some unobserved aspects of the current state. Maintaining this state requires 2 kinds of knowledge. A transition model, how the world changes over time, both through the agent's actions and independently. Turning the wheel clockwise turns the car right. Rain wets the cameras. And a sensor model, how the world state is reflected in the percepts. Braking appears as illuminated red regions. Wet cameras show droplet-shaped obscurities. Together, these allow the agent to update its state. The box, what the world is like now, represents the agent's best guess or best guesses. It is almost never possible to determine the exact state. Yet the agent still has to make a decision. Quote, it is seldom possible for the agent to determine the current state of a partially observable environment exactly. Uncertainty about the current state may be unavoidable, but the agent still has to make a decision. Section 2.4.3 Goal-based agents. Knowing the current state is not always enough. At a road junction, the taxi can turn left, right, or go straight, and the correct choice depends on where it's trying to go. The goal-based agent adds a description of desirable situations and combines it with a model to choose actions that achieve the goal. The crucial difference from reflex behavior is that decision-making involves consideration of the future, both what will happen if I do such and will that make me happy? A reflex agent brakes when it sees brake lights, period. It has no idea why. A goal-based agent brakes because that is the only action it predicts will achieve the goal of not hitting other cars. Although it appears less efficient, it is more flexible because the knowledge that supports its decisions is represented explicitly and can be modified. Change the destination and the goal-based agent routes accordingly, while the reflex agent's rules must all be replaced. Search, chapters 3 to 5, and Planning, chapter 11, are devoted to finding action sequences that achieve goals. Quote, the reflex agent brakes when it sees brake lights, period. It has no idea why. A goal-based agent brakes when it sees brake lights because that's the only action that it predicts will achieve its goal of not hitting other cars. Section 2.4.4 Utility-based agents. Goals alone are not enough for high-quality behavior. Many action sequences reach the destination, but some are quicker, safer, more reliable, or cheaper than others. Goals just provide a crude binary distinction between happy and unhappy states. The utility-based agent internalizes the performance measure as a utility function and chooses the action that maximizes expected utility, the utility it expects to derive on average, given the probabilities and utilities of each outcome. Utility matters precisely where goals fail. With conflicting goals, speed versus safety, the utility function specifies the trade-off, and with several goals, none of which can be achieved with certainty, utility weighs likelihood of success against importance. The book promises that Chapter 16 will show any rational agent must behave as if it possesses a utility function whose expected value it tries to maximize. Not all utility-based agents are model-based. A model-free agent can learn what action is best in a particular situation without ever learning exactly how that action changes the environment, a theme for chapters 22 and 26. Quote, a rational utility-based agent chooses the action that maximizes the expected utility of the action outcomes. Section 2.4.5 Learning Agents. All the preceding agents were assumed to come into existence fully formed. The learning agent explains how they are built or improve. Turing's early conclusion is quoted, programming intelligence by hand would take too much work, so some more expeditious method seems desirable. Build learning machines and then teach them. The learning agent has 4 components. The performance element is the whole agent as previously described. It takes percepts and chooses actions. The learning element uses feedback to decide how the performance element should be modified. The critic tells the learning element how well the agent is doing with respect to a performance standard, which must be fixed and conceptually outside the agent, because the agent must not modify it to fit its own behavior. The problem generator suggests actions that lead to new and informative experiences, exploratory, possibly suboptimal actions for the long run, in the manner of scientists running experiments. Galileo did not think that dropping rocks from the top of a tower in Pisa was valuable in itself. His aim was to modify his own brain by identifying a better theory of the motion of objects. Learning as a process modifies each component to bring it into closer agreement with the available feedback information. Learning element versus performance element. The former makes improvements. The latter selects external actions. Critic assesses performance against a fixed, external performance standard. Percepts alone carry no indication of success. Problem generator proposes exploratory actions to gather new and informative experience. Quote, in a sense, the performance standard distinguishes part of the incoming percept as a reward or penalty that provides direct feedback on the quality of the agent's behavior. Section 2.4.6. How the components of agent programs work. The chapter closes with the representational axis that organizes much of the rest of the book: atomic, factored, and structured, increasing expressive power at the price of increasing complexity of reasoning and learning. In an atomic representation, each state is indivisible, a black box differing from another only by identity. It suffices for route finding with a single city name and underlies search, game playing, hidden Markov models, and Markov decision processes. A factored representation splits each state into a fixed set of variables or attributes: gas in the tank, GPS coordinates, oil warning status, which makes it much easier to work out how one state becomes another. It underlies constraint satisfaction, propositional logic, planning, and Bayesian networks. A structured representation captures objects and their relationships explicitly. A truck reversing into a driveway blocked by a loose cow is not pre-equipped as a factored attribute. It underlies relational databases, first-order logic, first-order probability models, and much of language understanding. The advantage of expressiveness is real. The rules of chess can be written in a page or two of first-order logic, but require thousands of pages in propositional logic and around 10 to the 38th pages in an atomic language. A second axis maps concepts to memory. Localist representations assign one concept per location. Distributed representations spread concepts over many locations, making them more robust. A few garbled bits move a distributed concept to a nearby point, which will have similar meaning. Atomic factored structured. The axis of increasing expressiveness and decreasing simplicity of reasoning, from city names to attribute vectors to objects and relations. Localist versus distributed. One concept per location versus concepts spread across locations. The latter is more robust to noise and information loss. Quote, often, the more expressive language is much more concise. On the other hand, reasoning and learning become more complex as the expressive power of the representation increases. Section 2.4.7. Part 2. Problem Solving. Chapter 3. Solving Problems by Searching. Problem-solving agents. Chapter 3 considers agents in the simplest class of environments: episodic, single agent, fully observable, deterministic, static, discrete, and known, where intelligence largely reduces to search, finding a sequence of actions that reaches a goal. The chapter's image is an agent on a touring vacation in Romania, in Arad, holding a non-refundable ticket out of Bucharest the following day. With no geography, it can do no better than execute one of the actions at random. Given the map, it follows a four-phase process. Goal formulation organizes behavior by limiting the objectives and therefore the actions considered. The agent adopts the goal of reaching Bucharest. Problem formulation devises an abstract model. For the agent, the states are cities, the actions are traveling to adjacent cities. Search simulates sequences of actions in the model until it finds a sequence reaching the goal, the solution. Execution then carries the actions out. A crucial property follows from the environment simplicity. In a fully observable, deterministic, known environment, the solution is a fixed sequence of actions, and once found, the agent can ignore its percepts while it is executing the actions, closing its eyes, so to speak. Control theorists call this an open-loop system. Ignoring the percepts breaks the loop between agent and environment. Where the model may be wrong or the environment non-deterministic, a closed-loop approach that monitors percepts is safer, and a solution becomes a branching strategy that recommends different future actions depending on what percepts arrive. A contingency plan, such as what to do if the agent finds a drum in cheese, road closed sign. Goal problem search execution. The four-phase problem-solving process. Goals organize behavior by limiting the actions considered. Open loop versus closed loop. Fixed sequences suffice in simple environments. Branching strategies with percept monitoring are needed under uncertainty. Search problems and solutions. The search problem is defined formally in 5 parts. There is a state space, the set of possible states the environment can be in, an initial state, a set of goal states, possibly one, a small set, or defined by a property like no dirt anywhere. A set of actions, where actions of S returns the finite set applicable in S. A transition model, result of SA, describing what each action does, and an action cost function, C of SAS, giving the numeric cost, which should reflect the agent's own performance measure, miles for route finding, or time. A sequence of actions forms a path. A solution is a path from the initial state to a goal state. An optimal solution has the lowest path cost among all solutions. The chapter assumes action costs are additive and positive to avoid certain complications. The state space is a graph. Vertices are states, directed edges are actions. The search differs critically from the state space. The state space describes the possibly infinite set of states in the world and the actions that allow transitions from one state to another. The search tree describes paths between these states, reaching towards the goal. The search tree may contain many nodes for one state, because a state can be reached by many paths. 5-part problem. Initial state, actions, transition model, goal states, action cost function. The complete specification a search algorithm consumes. State space versus search tree. The graph of world states and actions versus the tree of paths an agent actually explores toward a goal. Formulating problems. Problem formulation is abstraction, the process of removing detail from a representation. The state Arad is an atomic abstraction of a real trip that includes companions, radio programs, the proximity of law enforcement, road condition, weather, and traffic, all left out as irrelevant to finding a route. The right level of detail matters. If actions were moved the right foot forward a centimeter, the agent would probably never find its way out of the parking lot, let alone to Bucharest. The book sharpens this with 2 conditions. An abstraction is valid if any abstract solution can be elaborated into a detailed solution. A sufficient condition being that every detailed state in Arad has a path to some state in CBU, and so on. It is useful if the abstract actions are easy to carry out. Drive from Arad to CBU needs no further search for an average driver. The choice of a good abstraction, thus, involves removing as much detail as possible while retaining validity and ensuring that the abstract actions are easy to carry out. Were it not for the ability to construct useful abstractions, intelligent agents would be completely swamped by the real world. Abstraction, removing detail. The level chosen must keep abstract solutions elaboratable, validity, and actions easy to carry out, usefulness. Example problems. Search has been applied to a vast array of task environments, which the book splits into standardized and real-world problems. A standardized problem has a concise, exact description and serves as a benchmark for comparing algorithms. A real-world problem, robot navigation, route finding, airline travel, is idiosyncratic because each robot has different sensors that produce different data. The distinction matters because standardized problems let researchers compare methods, while real-world problems test whether those methods survive contact with actual complexity. Standardized problems. The chapter catalogs the classic benchmarks. A grid world is a 2-dimensional array of cells. Objects and obstacles occupy cells, and the agent moves to unobstructed adjacent cells. The vacuum world is a grid world. With 2 cells and dirt, there are 2.4 equals 8 states. In general, a vacuum environment with n cells has n.2 to the n states. The Sokoban puzzle pushes boxes to storage locations, with states numbering in the hundreds of trillions on larger grids. A sliding tile puzzle, the 8 puzzle on a 3 by 3 grid, the 15 puzzle on 4 by 4, has states counted by configurations of positions of tiles, and every problem formulation abstract away details like shaking the board or extracting tiles with a knife. Donald Nutt's problem, 1964, asks whether starting from 4, using square root, floor, and factorial operations, one can reach any desired positive integer. It illustrates how finite state spaces arise from infinite ones. The shortest path to 5 passes through 4, a 24-digit number. Grid world. The canonical simple environment. The vacuum world reformulated as a grid, with n.2 to the n states for n cells. 8 puzzle/15 puzzle. Sliding tile benchmarks whose state spaces, up to trillions of states, force good heuristics. Nutt's problem. Square roots, floors, and factorials from 4 generate an infinite state space of integers. Real-world problems. Real-world search spans route finding, Turing, VLSI layout, robot navigation, assembly sequencing, and protein design. Route finding generalizes Romania. Travel planning systems handle states that include location, time, and historical fare information. A good system should include contingency plans. Turing problems generalize the single destination to a set that must all be visited. The traveling salesperson problem, TSP, with enormous effort spent improving its algorithms. Routing school buses in Boston saved $5 million and cut traffic. VLSI layout positions millions of components and wires to minimize area, delays, and stray capacitance. Robot navigation makes the state space many-dimensional, one dimension for each joint angle, and real robots must cope with sensor errors, partial observability, and other agents. Automatic assembly sequencing, from electric motors to protein design, must find a feasible order of assembly where the generation of legal actions is the expensive part. The unifying point is that any practical algorithm must avoid exploring all but a tiny fraction of the state space. Turing/TSP. Visit every city. A tour problem with enormous algorithmic effort and real savings. Robot navigation. Multidimensional continuous state spaces requiring discretization and error tolerance. Assembly and protein design. Sequencing problems where generating legal actions dominates. Search algorithms. A search algorithm takes a search problem as input and returns a solution or an indication of failure. The classic approach superimposes a search tree over the state space graph. Each node in the tree corresponds to a state. The root is the initial state. Expanding a node applies actions and result to generate child nodes. The frontier is the set of nodes reached but not yet expanded. The reach set includes every state for which a node has been generated. The frontier separates 2 regions of the state space graph. An interior region where every state has been expanded, and an exterior region of states that have not yet been reached, the separation property. Choosing which frontier node to expand is the essence of search, following up one option now and putting the others aside for later. Expand, frontier, reached, the working parts of the search tree. The frontier separates the expanded interior from the unreached exterior. Best first search. The general method is best first search. Choose a node with minimum value of an evaluation function, f, n, expand it, and repeat. On each iteration, the algorithm pops the minimum f node from a priority queue, returns it if it is a goal, and otherwise generates children, adding each to the frontier if it has not been reached before, or if this path has a lower cost than any previous path. By employing different fn functions, we get different specific algorithms. The rest of the chapter is largely a tour of the f-function design space. Search data structures. A node is a data structure with 4 components: node.state, node.parent, node.action, and node.pathCost, denoted Gn in math. Following parent pointers back from a goal node recovers the solution. The frontier is stored as a queue. A priority queue pops the minimum evaluation function node, best first. A FIFO queue pops the earliest added node, breadth first. A LIFO queue, or stack, pops the most recent, depth first. Reach states live in a lookup table mapping state to node. Node structure, state, parent, generating action, and path cost. The parent chain reconstructs the solution. Redundant paths. Repeated states matter enormously. A cycle is a special case of a redundant path, just a worse way to get to the same state. The 10 by 10 grid example is arresting. An agent can reach any of squares in 9 moves or fewer, but the number of paths of length 9 is almost 8 to the 9th. More than million. So the average cell can be reached by over 1 million redundant paths of length 9, and eliminating them speeds search by roughly 1 million times. As the saying goes, algorithms that cannot remember the past are doomed to repeat it. 3 approaches follow. A graph search remembers all previously reached states and keeps only the best path to each. A tree-like search does not check for redundancies at all, saving memory but revisiting states. A compromise checks for cycles by following parent pointers, either all the way up, expensive, or a few links, cheap, catching short cycles. The choice among the 3 depends on how many redundant paths the problem admits and how much memory is available. Graph search versus tree-like search. Checking all redundancies versus none. A cyclic checkup the parent chain is the memory-saving compromise. Quote, algorithms that cannot remember the past are doomed to repeat it. Section 3.3.3. Measuring problem-solving performance. Search algorithms are judged on 4 criteria. Completeness. Is it guaranteed to find a solution when one exists? Cost optimality. Does it find the lowest cost path? Time complexity and space complexity. Completeness requires a systematic search. 4 finite state spaces. Cutting off cycles guarantees eventual reach of every reachable state. In infinite state spaces, an algorithm like one applying nuts factorial forever never returns to a state it has reached before, but is incomplete because wide expanses of the state space are never reached. A systematic search on an infinite grid, by contrast, spirals outward. An honest caveat. In an infinite state space with no solution, a sound algorithm needs to keep searching forever. It can't terminate because it can't know if the next state will be a goal. Complexity is measured against the state space graph given V, given plus, given E, given or, for implicit graphs, in terms of the depth D of the optimal solution, the maximum depth M, and the branching factor B. 4 criteria: completeness, cost optimality, time, and space. The lenses through which uninformed and informed searches are compared. Uninformed search strategies. An uninformed search algorithm is given no clue about how close a state is to the goal. The agent in a rod has no clue whether going to Zerand or Cebu is a better first step without geography. The chapter develops 3 uninformed families: breadth first, uniform cost, depth first with its variance, and bidirectional, and compares them. Breadth first search. When all actions have the same cost, breadth first search spread from the root in waves. Expand a root, then all its successors, then their successors. It is a special case of best first search with f of n equal to the node's depth, implemented efficiently with a FIFO queue. New nodes are always deeper. In an early goal test, as soon as a node is generated. Breadth first is complete, even on infinite state spaces, and always finds a solution with a minimal number of actions because it generates all nodes at depth D before any at depth D plus 1. Hence, it is cost optimal when all action costs are equal. But its complexity is exponential in both time and space. Big O of B to the D nodes generated and all kept in memory. The terrifying concrete numbers, with branching factor 10, 1 million nodes/second, and 1 kilobyte per node, a depth 10 search takes under 3 hours but needs 10 terabytes. At depth 14, the same search would take years. In general, exponential complexity search problems cannot be solved by uninformed search for any but the smallest instances. Breadth first, complete and optimal for unit costs, but space exponential. The memory, not the time, is usually the binding constraint. Dijkstra's algorithm / uniform cost search. When actions have different costs, uniform cost search spreads out in waves of uniform path cost rather than uniform depth. Dijkstra's algorithm by the theory community's name. It is best first search with f of n equals g of n, the path cost. The Romania example shows the crucial subtlety. After Cebu generates Bucharest with cost 310, the algorithm does not stop because it tests for goals only when expanding a node, not when generating one. It continues to expand Petesti, finds a path to Bucharest with cost 278, and only then returns it. Checking for the goal too early would have returned a higher cost path. Uniform cost search is complete and cost optimal. The first solution it returns is cost at least as low as any other frontier node, and it considers all paths systematically in order of increasing cost, never getting caught going down a single infinite path. Its complexity is big O of B to the 1 plus seal, C star over epsilon, which can be much greater than B to the D, because cheap low-benefit actions can be explored extensively. Uniform cost search spreads by path cost, complete and cost optimal, but its cost-bound complexity can exceed B to the D when actions have unequal costs. Depth-first search and the problem of memory. Depth-first search expands the deepest node first, generally as a tree-like search with no reach table. Its virtues and vices are cataloged. It is not cost-optimal. It is efficient and complete on finite tree state spaces. On cyclic state spaces, it can loop, hence the cycle check. On infinite state spaces, it can get stuck going down an infinite path and is incomplete. Its great virtue is memory. The frontier is just a radius of the sphere rather than its surface, giving big O of BM space. And some problems that would require exabytes of memory with breadth-first search can be handled with only kilobytes. Its parsimony has made depth-first the basic workhorse of many areas of AI, including constraint satisfaction, Chapter 6, propositional satisfiability, Chapter 7, and logic programming, Chapter 9. The backtracking search variant generates and modifies one successor at a time, reducing memory to a single-state description in a path of big O of M actions, with big O of 1 times cycle detection via a set of path states. Depth-first, memory parsimonious workhorse, incomplete on infinite and cyclic spaces, not cost-optimal, but big O of BM space and the basis of backtracking. Depth-limited and iterative deepening search. To keep depth first from wandering down an infinite path, depth-limited search supplies a depth limit L and treats all nodes at depth L as having no successors, at the cost of incompleteness if the limit is too shallow. A good limit can sometimes be chosen from knowledge of the problem. On the Romania map, the diameter, maximum shortest path between any two cities, is 9, giving L equals 9. Iterative deepening search solves the problem of choosing L by trying all values, 0, 1, 2, until a solution is found or the search proves none exists, returning failure rather than cutoff. It combines the virtues of both parents, like depth first, memory is modest, big O of BD, like breadth first. It is optimal for unit costs and complete on finite, acyclic, or cycle-checked spaces. The apparent wastefulness of regenerating upper levels is illusory. Most of the nodes are in the bottom level, so the total node count is asymptotically the same as breadth first. For B equals 10, D equals 5, IDS generates 1 nodes versus BFS's 111,110. Iterative deepening is the preferred uninformed search method when the search state space is larger than can fit in memory and the depth of the solution is not known. Depth limited, depth first with a bound L. Incomplete if L is too small, with L equals diameter as a good choice when known. Iterative deepening, increasing depth limits, combines depth-first memory with breadth-first optimality, asymptotically matching BFS's node count. Bidirectional search. Bidirectional search runs 2 searches simultaneously, forward from the initial state and backward from the goals, hoping they meet, because B to the D over 2 plus B to the D over 2 is far less than B to the D, times less when B equals D equals 10. It requires 2 frontiers, 2 reach tables, and the ability to reason backward. If S is a successor of S forward, then S is a successor of S backward. The general bidirectional best-first search expands next the node with minimum evaluation across either frontier. With path cost as the evaluation, no node with cost above C star over 2 is expanded. Since the first solution found is not guaranteed optimal, the algorithm keeps track of the best solution so far and continues until the termination test proves no better solution remains. Bidirectional search is sometimes more efficient than unidirectional search, sometimes not. With a very good heuristic, a star-style contours already focus on the goal, and bidirectional adds little. With an average heuristic, meet in the middle wins. With a poor heuristic, complexity matches a star. Comparing uninformed search algorithms. The chapter's comparison table, figure 3.15, places the algorithms side by side. Breadth first is complete and optimal for uniform costs, with big O of B to the D time and space. Uniform cost is complete and optimal for positive cost with cost-bound complexity. Depth first is complete only on finite spaces and never cost optimal, with big O of BM space. Depth limited is complete only if the limit is adequate. Iterative deepening is complete with full cycle checking, and optimal for uniform costs at big O of BD time and big O of BD space. Bidirectional is complete and Optimal if both directions are breadth first or uniform cost. At big O of B to the D over 2. The caveats are footnoted but honest. Completeness may require finite branching in a finite or solvable state space. Cost optimality requires equal action costs, or positive bounds. The table is the chapter scorecard. Every algorithm's strengths and weaknesses reduced to 4 columns. Informed, heuristic, search strategies. Informed search uses domain-specific hints. A heuristic function h of n, the estimated cost of the cheapest path from a state at node n to a goal. For route finding, h can be the straight-line distance on the map, which the authors note cannot be computed from the problem description itself and requires world knowledge to be useful. Informed search is the chapter's answer to exponential blowup. With a good heuristic, the search can find solutions more efficiently than an uninformed strategy. Greedy best first search. Greedy best first search expands first the node with the lowest h of n, the one that appears closest to the goal. With the straight-line heuristic on Romania, it expands Arad Sibiu Făgăraș Bucharest without ever expanding a node that is not on the solution path. Yet the path is 32 miles longer than the optimal one through Râmnicu Vilcea and Pitești. This is why the algorithm is called greedy. On each iteration it tries to get as close to a goal as it can, but greediness can lead to worse results than being careful. Greedy best first graph search is complete in finite state spaces but not infinite ones, and its worst-case complexity is big O of given V given, reduced substantially with a good heuristic. A star search. The most common informed search is a star search, with the evaluation function f of n equals g of n plus h of n, the estimated cost of the best path that continues from n to a goal. The Romania trace shows why a star refuses to settle. Bucharest first appears on the frontier with f equals 450, but Pitești at f equals 417 is lower. So, there might be a solution through Pitești whose cost is as low as 417, so the algorithm will not settle for a solution that costs 450. It returns the optimal path through Pitești at f equals 418. Whether a star is cost optimal depends on the heuristic. An admissible heuristic never overestimates the cost to reach a goal, therefore optimistic. With admissibility, a star is cost optimal, proved by contradiction. If it returned a path of cost c is greater than c star, some node on the optimal path would be unexpanded, and tracing f of n forces the contradiction f of n is less than or equal to c star is less than c is less than f of n. A stronger property, consistency, a triangle inequality, h of n is less than or equal to c of n plus h of n, implies admissibility and guarantees that the first time a state is reached it lies on an optimal path, so entries in reach never change. A star is complete, cost-optimal, and optimally efficient among algorithms that extend search paths and use the same heuristic. It expands all surely expanded. Nodes with f of n is less than c star, and none with f of n is greater than c star. Its pruning is powerful. Timișoara, f equals 447, and Zirand, f equals 449. Children of the root are never expanded once the f equals 418 solution is found. Yet, it does not mean that a star is the answer to all our searching needs. For many problems, the number of expanded nodes can be exponential in the length of the solution, as the super-powerful vacuum example shows, where all 2 to the n states lie on optimal paths. A star, f equals g plus h, complete, cost-optimal with an admissible heuristic, optimally efficient among same heuristic searches, but potentially exponential in nodes and memory hungry. Admissibility versus consistency. Never overestimating versus satisfying the triangle inequality. Consistency implies admissibility and makes reach table entries permanent. Quote, an admissible heuristic is therefore optimistic. Section 3.5.2. Search contours. A useful visualization draws contours in state space, as on a topographic map. Inside the contour labeled 400, all nodes have f is less than or equal to 400. Because a star expands the lowest f node, it fans out from the start node, adding nodes in concentric bands of increasing f cost. Uniform cost search has circular contours of g cost, spreading equally with no goal preference. A star SG plus h contours stretch toward a goal state and become more narrowly focused around an optimal path. Whether f is monotonic along a path reduces exactly to consistency. With a consistent heuristic, a star expands all surely expanded nodes. F is less than C star. May expand some on the goal contour. F equals C star. And expands none with F is greater than C star. The notion of pruning, eliminating possibilities from consideration without having to examine them, is introduced as central to AI. Satisficing search, inadmissible heuristics, and weighted a star. Optimality is not always worth its price. Satisficing search accepts solutions that are good enough, trading optimality for fewer expanded nodes. A weighted a star search weights the heuristic more heavily. F of n equals g of n plus w. H of n with w is greater than 1. The road engineer's detour index motivates it. A multiplier of on straight line distance is a better estimate of actual road length, even though it overestimates the true shortest path. Weighted a star finds a solution costing between C star and W.C star, but in practice much closer to C star, while exploring far fewer states. The worked grid example explores 7 times fewer states for a 5% costlier path. Weighted a star generalizes the family. A star, W equals 1, uniform cost, W equals 0, and greedy best first, W equals infinity. Further suboptimal families are distinguished by what counts as good enough, bounded suboptimal, within a constant factor as weighted a star guarantees, bounded cost, below a constant, and unbounded cost, find anything quickly, as speedy search does. Weighted a star, F equals G plus W.H, generalizes a star, uniform cost, and greedy. The price of optimality is tunable. Memory-bounded search. A star's main issue is memory. The chapter covers implementation tricks and whole algorithms that reduce it. Tricks include avoiding storing a state in both frontier and reached, removing states from reached when provably no longer needed, using the separation property to check only the frontier, and maintaining reference counts so a state is dropped from reached once it can no longer be reached afresh. Beam search limits the frontier to the k-best F-score nodes, or all nodes within a threshold of the best, incomplete and suboptimal, but fast and good for near-optimal solutions. IDA times, iterative deepening a star, gives the benefits of a star without the requirement to keep all reach states in memory at a cost of visiting some states multiple times, and is a very important and commonly used algorithm for problems that do not fit in memory. The chapter also names RBFS and SMA times as robust, optimal, memory-limited algorithms. Beam search, frontier truncated to the k-best, fast, incomplete, suboptimal, but often near-optimal. IDA times, iterative deepening a star, level quality with depth-first memory and repeated state regeneration. Bidirectional heuristic search. Extending bidirectional search to heuristics gives the f sub 2 function f sub 2 n equals the maximum of 2g of n plus h of n, guaranteeing no expanded node has g of n is greater than c star over 2. The two halves meet in the middle. The chapter distinguishes front-to-end search. H sub f estimates distance to the goal, h sub b to the start. From front-to-front search, h estimates distance to the other frontier, which is expensive with millions of frontier nodes, but can sample a few. With a good heuristic, unidirectional, a star already focuses the contours and bidirectional helps little. With an average heuristic, meet in the middle wins. In a worst case, complexity matches a star. Bidirectional best first with f sub 2, and an admissible heuristic is complete and optimal. Heuristic functions. The final section studies where heuristics come from and how accuracy affects performance, using the 8 puzzle as the persistent example. 2 classic heuristics are derived. H sub 1 counts misplaced tiles, admissible because an out-of-place tile needs at least one move. H sub 2 sums the Manhattan, or city block, distances of tiles from their goal positions, admissible because a move brings one tile one step closer. Both are admissible for the 8 puzzle. H sub 2 equals 18 for the chapter's start state, and neither overestimates the true cost 26. The effect of heuristic accuracy on performance. Heuristic quality is characterized by the effective branching factor B star. The branching factor, a uniform tree of depth D, would need to contain the same number of nodes as a star generated. A well-designed heuristic has B star close to 1, allowing fairly large problems to be solved at reasonable computational cost. Korf and Reed's finding sharpens this. A star with heuristic H reduces the effective depth by a constant kh, giving total cost big O of b to the dkh. The empirical table, averaged over puzzles at each solution length, shows h sub 2 consistently better than h sub 1, and both far better than no heuristic. The reason is domination. H sub 2 n is greater than or equal to h sub 1 n for every node, and since every node with h of n is less than c star minus g of n is surely expanded. The larger heuristic surely expands a subset of nodes. It is generally better to use a heuristic function with higher values, provided it is consistent and that the computation time for the heuristic is not too long. Effective branching factor. The uniform tree branching factor matching a star as node count. Near 1 is the signature of a good heuristic. Domination. H sub 2 dominates H sub 1 if H sub 2 is greater than or equal to H sub 1 everywhere. A star with a dominant heuristic never expands more nodes. Generating heuristics from relaxed problems. The deep trick. H sub 1 and H sub 2 are exact path lengths for simplified versions of the puzzle. If a tile could move anywhere instead of only into the adjacent blank, H sub 1 would be exact. If a tile could move one square in any direction, even onto an occupied square, H sub 2 would be exact. A problem with fewer restrictions on the actions is called a relaxed problem, and its state space graph is a supergraph of the original, because any optimal solution to the original is a solution to the relaxed problem. The cost of an optimal solution to a relaxed problem is an admissible heuristic for the original problem, and because it is exact for the relaxed problem, it obeys the triangle inequality and is consistent. If a problem definition is informal, the relaxed problems can be generated by removing conditions. From a tile can move from x to y if x is adjacent to y and y is blank. Removing the blank condition yields Manhattan distance. Removing adjacency yields misplaced tiles. The System Map Solver automated the technique and found a new best heuristic for the 8 puzzle and the first useful heuristic for Rubik's Cube. If several admissible heuristics exist and none dominates, take the maximum. H of n equals max, IH sub I n is admissible, consistent, and dominates all components at the price of longer computation. Relaxed problem. Removing action restrictions yields a supergraph whose optimal solution cost is an admissible, consistent heuristic for the original. Max of heuristics. Combining admissible heuristics by taking the maximum preserves admissibility and dominance. Generating heuristics from subproblems, pattern databases. Admissible heuristics can also come from subproblems. The cost of solving a subproblem is a lower bound on the full problem. A pattern database stores the exact solution costs of all subproblem configurations. For the one pattern with the blank, there are 9.5 equals 15,120 patterns, computed by searching backward from the goal and recording each new pattern's cost, an expense amortized over many problem instances. Multiple databases give multiple heuristics, combined by the maximum. This reduces nodes generated on random 15 puzzles by a factor of 1,000. The subtlety of disjoint pattern databases. 2 subproblem solution costs cannot be added unless the moves are disjoint, which happens if each abstracted move counts only the tiles in the pattern. With disjoint databases, random 15 puzzles are solved in milliseconds, nodes reduced by a factor of 10,000. 24 puzzles run 1,000,000 times faster. Disjoint databases work for sliding tiles because only one tile is moved at a time. Pattern database. Pre-computed exact subproblem solution costs, looked up as a heuristic. Combining disjoint patterns allows addition. Disjointness. Subproblem costs add only if their moves do not overlap, the condition that makes the sum admissible. Generating heuristics with landmarks. Online map services find cost-optimal driving directions on tens of millions of vertices in milliseconds, 1,000,000 times faster than the textbook algorithms so far, mostly by pre-computing path costs. A perfect all-pairs heuristic needs big O of given v given to the second space, impractical at millions of vertices. The landmark approach picks landmark points and stores the exact optimal cost from every vertex to each landmark. The heuristic H sub n equals min L C star of n L plus C star of L goal is efficient but inadmissible. It can overestimate if the optimal path misses every landmark. The differential heuristic H sub dh n equals max L given C star of n L minus C star of L goal given is both efficient and admissible. It considers the whole path to a landmark and subtracts the final leg. exact when the goal lies on the optimal path to the landmark. Landmarks work especially well for roads, because a lot of traffic actually wants to travel between landmarks. Civil engineers built the fastest roads along those routes, and landmark search recovers them. Shortcuts, artificial edges encoding optimal multi-action paths, further accelerate routing. Landmark heuristic, pre-computed costs to a few chosen points yield fast, near-optimal routing on million vertex maps. Differential heuristic, subtracting the goal to landmark leg gives an efficient heuristic that is also admissible. Learning to search better. The chapter closes by asking whether an agent can learn to search better, and introduces the meta-level state space. Each state in the meta-level space captures the internal computational state of a program, searching in ordinary, object-level space. Each action is a computation step, such as expanding a leaf node. A path in the meta-level space is a sequence of larger and larger search trees. Some expansion steps are missteps. The chapter notes the expansion of Fugarash in the A-star trace was not especially helpful. A meta-level learning algorithm can learn from these experiences to avoid exploring unpromising subtrees, minimizing the total cost of problem solving by trading computational expense against solution path cost. Meta-level state space, the space of a searcher's internal states, where each action is a computation step and learning can prune unpromising subtrees. Learning heuristics from experience. The final alternative to relaxed problems is learning heuristics from data. Experience means solving many instances, each optimal solution providing a goal, path, example from which an approximate heuristic age can be learned. Most learned heuristics are imperfect and risk inadmissibility, forcing a trade-off between learning time, search runtime, and solution cost. Features are typically supplied, not raw states. Number of misplaced tiles, or the count of adjacent out-of-order tile pairs, and combined linearly, h of n equals c sub 1 dot x sub 1 n plus c sub 2 dot x sub 2 n, with the coefficients fit to data. Such a heuristic satisfies h equals 0 on goals, but is not necessarily admissible or consistent. The chapter summary restates the discipline position. Search is constrained by the environment class: episodic, single agent, fully observable, deterministic, static, discrete, known, and efficiency comes from heuristics, pattern databases, and landmarks, or from learning them. Learning heuristics, fitting an approximate H to solved instances. Risk of inadmissibility trades learning time against runtime and solution cost. Chapter 4. Search in complex environments. Local search and optimization problems. Chapter 4 relaxes the constraints assumed in Chapter 3. Determinism, observability, staticity, knowledge, and begins with problems where only the final state matters, not the path used to reach it. In integrated circuit design, factory floor layout, job shop scheduling, telecommunications network optimization, and the 8 queens problem, we care only about finding a valid final configuration. If you know the configuration, reconstructing the steps that created it is trivial. Local search algorithms operate by moving from a start state to neighboring states without keeping track of paths or reach states. They're not systematic and might never explore a portion of the search space where a solution actually resides. But they have 2 key advantages: very little memory and the ability to find reasonable solutions in large or infinite state spaces where systematic algorithms are unsuitable. When the aim is to find the best state according to an objective function, the problem becomes an optimization problem, and the states form a state-space landscape whose elevation is the objective value. Local search versus systematic search. No path memory and no reach set. Not systematic, but memory light and effective on huge spaces. Optimization. Finding the best state by objective value, not a path. The landscape picture frames climbing peaks or descending to valleys. Hill climbing search. The most basic local search technique is hill climbing. Keep one current state, move on each iteration to the neighbor with the highest value, the steepest descent, and terminate when no neighbor is higher. It does not look ahead beyond the immediate neighbors of the current state, which the book likens to trying to find the top of Mount Everest in a thick fog while suffering from amnesia. The 8 queens problem illustrates it. A complete state formulation where every state has all 8 queens, 1 per column, but possibly in the wrong rows. Successors are all states produced by moving 1 queen within its column. The cost H counts attacking pairs. Hill climbing is greedy local search. And although greed is one of the 7 deadly sins, greedy algorithms often perform quite well and can make rapid progress. But they get stuck for three reasons. Local maxima, a peak higher than its neighbors but below the global max. Ridges, a sequence of local maxima hard to navigate. And plateaus, flat areas, either a flat local maximum or a shoulder from which progress is possible. The empirical numbers are memorable. From a random 8-queen start, steepest descent hill climbing gets stuck 86% of the time, solving only 14% of instances, though quickly, averaging 4 steps on success and 3 on failure. Allowing up to 100 consecutive sideways moves on plateaus raises the success rate from 14% to 94% at the cost of longer runs. Stochastic hill climbing picks a random uphill move, with probability possibly weighted by steepness, converging more slowly but sometimes finding better solutions. First choice hill climbing generates successors randomly until one improves. Good when a state has thousands of successors. Random restart hill climbing adopts the adage, if at first you don't succeed, try again. It conducts hill climbs from random initial states until a goal is found, and is complete with probability 1, since eventually a goal state is generated as the initial state. If each climb succeeds with probability p, the expected number of restarts is 1 over p. For 8 queens without sideways moves, p approximates 0.14, so roughly 7 iterations suffice, and even 3 million queens can be solved in seconds. Success depends on the landscape. NP-hard problems typically have an exponential number of local maxima to get stuck on, yet a reasonably good local maximum can often be found after a small number of restarts. Hill climbing, greedy steepest descent, rapid progress but vulnerable to local maxima, ridges, and plateaus, solved variously by sideways moves, randomization, and restarts. 8 queens. The worked example. Sideways moves raise success from 14% to 94%, and random restarts make it very effective even at 3 million queens. Restart expectation. With success probability p, about 1/p restarts are needed. Completeness with probability 1. Quote, this resembles trying to find the top of Mount Everest in a thick fog while suffering from amnesia. Section 4.1.1. Simulated annealing. A hill climber that never moves downhill is always vulnerable to local maxima. A random walk eventually stumbles on the global maximum, but is extremely inefficient. Simulated annealing combines the two and yields both efficiency and completeness. The metallurgical metaphor is exact. Annealing tempers metal by heating it and gradually cooling, allowing it to reach a low-energy crystalline state. The book's image is a ping-pong ball on a bumpy surface. Let it roll, and it rests in a local minimum. Shake the surface hard enough to bounce it out of local minima, but not hard enough to dislodge it from the global minimum. Start by shaking hard, high temperature, and gradually reduce the shaking. The algorithm picks a random move. If it improves the situation, accept it. Otherwise, accept it with probability e to the minus delta e over t, which decreases exponentially with the badness delta e of the move and with the temperature t. If the schedule lowers t to 0 slowly enough, the Boltzmann distribution concentrates all probability on the global maxima, and the algorithm finds them with probability approaching 1. Simulated annealing solved VLSI layout problems from the 1980s and has been applied widely to factory scheduling and other large-scale optimization tasks. Accept downhill moves probabilistically. Probability e to the minus delta e over t. High temperature explores, low temperature settles. Slow cooling global optimum. If the schedule lowers t to 0 slowly enough, the Boltzmann distribution concentrates on global maxima. Local beam search. Local beam search keeps k states rather than 1, an intuitive but subtle response to memory limits. It starts with k randomly generated states, generates all successors of all k states, halts if any is a goal, and otherwise selects the k best successors and repeats. At first sight, it seems like nothing more than running k random restarts in parallel. In fact, the two algorithms are quite different. In random restart search, each process runs independently, whereas in a local beam search, useful information is passed among the parallel search threads. The states that generate the best successors say to the others, "Come over here, the grass is greener." The algorithm abandons unfruitful searches and concentrates resources where progress is being made. Its failure mode is a lack of diversity. The k-states can cluster in a small region, making the search little more than a k times slower version of hill climbing. Stochastic beam search alleviates this by choosing successors with probability proportional to their value, rather than taking the top k. Local beam search. K-parallel threads that share information, unlike K-independent random restarts. Stochastic beam search. Select successors probabilistically by value, restoring diversity against clustering. Evolutionary algorithms. Evolutionary algorithms are variants of stochastic beam search that are explicitly motivated by the metaphor of natural selection in biology. A population of individuals states in which the fittest, highest value individuals produce offspring that populate the next generation via recombination. They vary across an impressive number of dimensions. Population size. The representation of each individual. Genetic algorithms use strings over a finite alphabet. Evolution strategies use sequences of real numbers. Genetic programming uses computer programs. The mixing number row, number of parents combining to form offspring. Row equals 2 is common. Row equals 1 reduces to stochastic beam search. Row is greater than 2 is easy to simulate. The selection process, probability proportional to. Fitness or tournament selection. The recombination procedure, a crossover point splits the parent strings and recombines the parts. The mutation rate, each bit flipped with some probability. And the makeup of the next generation, elitism preserves top-scoring parents, ensuring fitness never decreases. The digit string 8 queens example walks through the whole cycle. An initial population of 4 8-digit strings is rated by a fitness function, number of non-attacking pairs, with 28 a solution. Fitness scores are normalized to probabilities. 2 pairs of parents are selected. One individual may be selected twice and one not at all. A random crossover point splits each pair. Mutation flips individual digits. The population is diverse early, so crossover takes large steps, and it becomes less diverse as it converges. Genetic algorithms add crossover to stochastic beam search, which helps if there are blocks that perform useful functions. A schema like 246 describing states where the first 3 queens occupy non-attacking positions can combine with other useful blocks. And it can be shown that if the average fitness of the instances of a schema is above the mean, then the number of instances of the schema will grow over time. The book's boxed interlude on evolution and search records Darwin, Mendel, and Watson and Crick, and notes the Baldwin effect. Although Lamarck was wrong that acquired traits are inherited, Baldwin was right that learning can effectively relax the fitness landscape, accelerating evolution. Things that are hard to learn end up in the genome. Easy things need not reside there. Schema, a partially specified pattern whose instances grow if their average fitness exceeds the mean. The theory's explanation of crossover's advantage. Baldwin effect. Learning modifies the fitness landscape, so learn but hard traits enter the genome, confirmed by computer simulations. Elitism. Preserving top parents guarantees that overall fitness never decreases over generations. Local search in continuous spaces. The chapter's glance at continuous spaces handles the case where states vary continuously rather than discretely. Many real-world problems, including the design of aircraft wings, chemical plants, and robot controllers, live here, and a landscape picture carries over, but hills become smooth surfaces in many dimensions. When the objective is continuous and differentiable, the maximum can be found using calculus to find where the gradient is 0. When the objective is not differentiable, the algorithm must make do with an empirical gradient, the difference in fitness between 2 nearby points. Linear programming and convex optimization obey restrictions on the shape of the state space and the objective function and admit polynomial time algorithms that are often extremely efficient in practice. The section is deliberately brief, deferring detail to the appendix and to later chapters, but it establishes the principle that local search is not confined to discrete combinatorics. Gradient and empirical gradient. Calculus finds the optimum where the gradient is 0, otherwise approximate the gradient by sampling nearby points. Convex optimization. Restricted problem shapes admit polynomial time algorithms, often extremely efficient in practice. Search with non-deterministic actions. When the environment is non-deterministic, the agent doesn't know what state it transitions to after taking an action. The agent's knowledge becomes a belief state, a set of physical states that the agent believes are possible. And the solution to a problem is no longer a sequence, but a conditional plan that specifies what to do depending on what percepts arrive. The erratic vacuum world introduces non-determinism. Suck cleans the current square, but sometimes cleans up dirt in an adjacent square, too, and when applied to a clean square, sometimes deposits dirt on the carpet. The transition model generalizes from a result function returning one state to a results function returning a set of outcomes. No single action sequence solves the problem, but the conditional plan does. Suck, if state equals 5 then, right suck, else. Here we see that a conditional plan can contain if-then-else steps. This means that solutions are trees rather than sequences. Many real physical problems are contingency problems because exact prediction of the future is impossible. For this reason, many people keep their eyes open while walking around. Belief state, the set of physical states the agent believes possible, given its percepts and action history. Conditional plan, a tree of if-then-else steps rather than a fixed sequence, the solution form for non-deterministic environments. And/or search trees. How are contingent solutions found? The search tree has two kinds of branching. Or nodes are the agent's own choices. I can do this action or that. And nodes are the environment's choices of outcome for an action. In the erratic vacuum world, suck in state 1 results in belief state 5, 7, so the agent would need to find a plan for state 5 and for state 7. These two kinds alternate, forming an and/or tree. A solution is a subtree that 1. Has a goal node at every leaf, 2. Specifies one action at each of its or nodes, and 3. Includes every outcome branch at each of its nodes. The recursive and/or search algorithm deals with cycles by returning failure if the current state repeats a state on the path from the root. This does not mean no solution exists, only that if there is a non-cyclic solution, it must be reachable from the earlier incarnation of the current state, so the new incarnation can be discarded. This ensures termination in every finite state space. Or graphs can be explored breadth first or best first, with a modified heuristic estimating the cost of a contingent solution, admissibility, and an analog of A-star carryover. Or nodes and in nodes. The agent's choices branch at or nodes. The environment's outcomes must all be handled at in nodes. A solution covers every in branch, one action per or node, every outcome at every in node, goals at all leaves. Cycle handling. A repeated state on the current path returns failure and prunes that incarnation, guaranteeing termination on finite spaces. Try again. A slippery vacuum world, where movement actions sometimes fail, leaving the agent in place, has no acyclic solutions at all, yet a cyclic solution works. Keep trying right until it works. The plan is expressed with a new while construct. Suck, while state equals 5 do right, suck, or with a labeled reference back to a portion of the plan. The minimum condition for a cyclic plan to be a solution is that every leaf is a goal state and that a leaf is reachable from every point in the plan. But the cause of non-determinism matters. If the drive mechanism slips randomly and independently, repeating the action, eventually it will work and the plan will succeed. If the non-determinism reflects some unobserved fact about the robot or environment, perhaps a drive belt has snapped and the robot will never move, then repeating will not help. The book interprets this in terms of problem reformulation. The initial problem, fully observable, non-deterministic, is abandoned in favor of partially observable, deterministic, where the cyclic plan's failure is attributed to an unobserved property of the drive belt. Deciding among such possibilities is deferred to probability, Chapter 12. Cyclic solution, a plan with a while loop or label, valid when every leaf is a goal reachable from every point in the plan. Repeating helps only if failures are independent. If failure reflects an unobserved permanent fact, a snapped belt, repetition is futile. Search in partially observable environments. Partial observability means the agent's percepts do not pin down the exact state. So, some of the agent's actions will be aimed at reducing uncertainty about the current state. The chapter develops the belief state machinery, first for the extreme of no observation, then for general partial observability. The key insight is that search moves from the space of physical states to the space of belief states. And in belief state space, the problem is fully observable because the agent always knows its own belief state. Sensing without observing, sensorless, conformant problems. When the agent's percepts provide no information at all, we have a sensorless or conformant problem. And surprisingly, such problems are common and useful, primarily because they don't rely on sensors working properly. Manufacturing systems orient parts from an unknown initial position using a sequence of actions with no sensing. And sometimes a sensorless plan is better even when a conditional plan with sensing is available. Doctors often prescribe a broad-spectrum antibiotic rather than running a blood test and waiting. In the sensorless vacuum world, the initial belief state is all 8 states. Moving right places the agent in 2, 4, 6, 8. The agent has gained information without perceiving anything. And after right, suck, left, suck, the agent reaches goal state 7 no matter the start. We say that the agent can coerce the world into state 7. The belief state problem transforms the physical problem. States are subsets of physical states. 2 to the n belief states for n physical states. The initial state is typically the set of all states. Actions take the union of physical actions, or the intersection if illegal actions are catastrophic. The transition model is result of B A equals S equals result P S A and S and B, which may shrink the belief state for deterministic actions, but can grow it with non-deterministic ones. The goal test splits into possibly, some state satisfies, versus necessarily. Every state satisfies, achieving the goal, and we aim to necessarily achieve the goal. Action cost transfer, if equal across states. Because the percepts after each action are always empty. The solution to a sensorless problem is a sequence, not a conditional plan, and ordinary Chapter 3 algorithms apply. Pruning helps. A superset belief state can be discarded, since a solution that works when very confused works when less confused, and conversely, a superset already found solvable guarantees any subset solvable. Even so, sensorless problem solving is seldom feasible in practice because of the size of belief state space, 2 to the n. Remedies are compact descriptions, Chapter 7's formal representations, and incremental belief state search, which builds a solution one physical state at a time and detects failure quickly. Coercion. With no sensors, a well-chosen action sequence can drive the world to the goal. The agent can coerce the world into state 7. Possibly versus necessarily achieving the goal. Any state in the belief state versus every state. Rational agents aim for necessarily. Superset pruning. A solution for a superset belief state solves its subsets. Discards supersets already proven solvable. Searching in partially observable environments. General partial observability adds sensing. The problem specification supplies a percept of S function, and prediction through a sensed action splits into 3 stages. The prediction stage computes the belief state resulting from the action, result of BA, exactly as for sensorless problems. The possible percept stage computes the set of percepts that could be observed in the predicted belief state. Possible percepts of B equals O equals percept of S and S and B. The update stage computes, for each possible percept, the belief state that would result. The updated belief state B sub O is the set of states in the predicted belief state that could have produced the percept. The agent must deal with all possible percepts at planning time, because it won't know the actual percepts until it executes the plan. Non-determinism can enlarge the belief state in prediction, but each updated belief state can be no larger than the predicted belief state. Observations can only help reduce uncertainty. The local sensing vacuum world, position sensor L/R, dirt sensor dirty/clean, shows how percept like L, dirty, collapses the belief state to 1, 3. Incomplete information becomes a belief state AND/OR problem, solvable by the AND/OR algorithm with this constructed results function. 3-stage prediction. Predict possible percepts update. These 3 stages compose the belief state transition for sensed actions. Observations only reduce uncertainty. Updated belief states are no larger than the prediction. Possible percepts partition the predicted state. Online search agents and unknown environments. Offline search computes a complete solution before acting. Online search interleaves computation and action. First it takes an action, then it observes the environment and computes the next action. Online search suits dynamic environments where there is a penalty for sitting around and computing too long, and non-deterministic domains, because it focuses effort on the contingencies that actually arise rather than those that might happen but probably won't. There is a trade-off. The more an agent plans ahead, the less often it will find itself up the creek without a paddle. In unknown environments, the agent must use its actions as experiments in order to learn about the environment. The canonical example is the mapping problem, A robot in an unknown building must explore to build a map for later navigation. Labyrinth escape methods for aspiring heroes of antiquity are also online searches, and a newborn baby is the ultimate example. Many possible actions, knows the outcomes of none of them. Online search, interleave computation, sensing, and acting, suited to dynamic and non-deterministic environments. Actions as experiments. In unknown environments, the agent learns what its actions do by performing them. Online search problems. An online search problem, assuming a deterministic, fully observable environment, allows the agent to know only actions of S, the action cost E of SAS, and IS goal of S, but not result of SA except by actually being in S and doing A. In a maze problem, the agent does not know that up from 1-1 leads to 1-2 until it goes there. It may have an admissible heuristic, such as Manhattan distance. The natural objective is to reach a goal while minimizing cost. Performance is compared against the competitive ratio, the ratio of the agent's path cost to the optimal path cost in the known environment, which we would like to be as small as possible. Online explorers are vulnerable to dead ends, states from which no goal is reachable. In general, no algorithm can avoid dead ends in all state spaces by an adversary argument. An adversary can construct a state space so that two look-identical states require different actions. Irreversible actions, staircases, ramps, cliffs, one-way streets, make dead ends a real difficulty for robot exploration. The exploration algorithms presented are guaranteed to work only in safely explorable spaces, where some goal is reachable from every reachable state. Competitive ratio, the agent's realized cost divided by the known environment optimal cost, the standard measure of online search quality. Dead ends and adversary argument. No algorithm avoids dead ends in all state spaces, because look-identical states can require opposite choices. Safely explorable. Every reachable state can still reach a goal, required for the presented algorithm's guarantees. Online search agents. After each action, an online agent perceives the state it has reached, augments its map, and plans where to go next. Offline algorithms explore their model of the state space, while online algorithms explore the real world. An online agent can discover successors only for a state that it physically occupies, so it should expand nodes in a local order, and depth-first search has exactly this property. The online DFS agent stores its map in a result table and tries unexplored actions. The difficulty comes when all actions in a state are tried. In offline DFS, the state is dropped from the queue, but online the agent has to backtrack in the physical world, using a table of predecessor states not yet backtracked to. Tracing the maze, the agent in the worst case traverses every link exactly twice. Optimal for exploration. But for finding a goal, its competitive ratio could be arbitrarily bad if it goes off on a long excursion when there's a goal right next to the initial state, a defect in online variant of iterative deepening fixes on uniform trees. The algorithm works only where actions are reversible. No bounded competitive ratio exists in general. Online local search, LRTA, learning real-time A. Hill climbing is already an online search, since it keeps just one current state, but it leaves the agent sitting at local maxima with nowhere to go, and random restarts are impossible because the agent cannot teleport itself to a new start state. Random walks eventually find a goal in any finite, safely explorable space, but can be very slow. The contrived environment of Figure 4.22 makes random walks take exponentially many steps. Augmenting hill climbing with memory turns out better. The learning real-time A star, LRTA star, agent stores a current best estimate H of S of the cost to reach the goal from each visited state, initialized to H of S. After each move it updates H for the state, it just left using the rule that the estimated cost through a neighbor S is C of SAS plus H of S, and it moves to the apparently best neighbor. The example shows LRTA flattening out a local minimum over several back-and-forth iterations until it escapes. Actions not yet tried are always assumed to lead immediately to the goal with the least possible cost, an optimism under uncertainty that encourages exploring new promising paths. An LRTA agent is guaranteed to find a goal in any finite, safely explorable environment. Explores n states in big O of n to the second steps in the worst case, though not complete for infinite spaces. LRTA star. Online hill climbing with memory. H of S estimates update from experience and optimism under uncertainty drives exploration. Guarantee, complete for finite, safely explorable environments. Big O of N to the second worst-case exploration steps. Learning in online search. Online agents' initial ignorance creates several learning opportunities. They learn a map of the environment, the outcome of each action in each state. By recording experiences, local search agents acquire more accurate cost estimates via updating rules like LRTA star, which Chapter 22 shows converge to exact values when exploration is done right. Once exact values are known, pure hill climbing is then an optimal strategy. The online DFS agent is not very bright in a subtle way. Having seen that up goes from 1 to 1 2, the agent still has no idea that the down action goes back to 1 1. It lacks general rules about up increasing y coordinates. Fixing this requires two things deferred to later chapters: a formal and explicitly manipulable representation for general rules, chapters 8 to 11, and algorithms that construct such rules from observations, chapter 19. Incremental search reuses work across similar problems, keeping the search tree, or updating heuristic H values, or keeping best path G values, and piecing together new solutions when the world changes. The chapter summary restates the ARC, local search for finding states, and OR search for contingent plans, belief state search for partial observability, and online, learning, incremental search for unknown environments. Chapter 5. Adversarial search and games. Game theory. Chapter 5 turns from single-agent search to competitive environments, in which two or more agents have conflicting goals, giving rise to adversarial search problems. The book concentrates on games, chess, Go, poker, because the state of a game is easy to represent, and agents are usually restricted to a small number of actions whose effects are defined by precise rules. Physical games like croquet and ice hockey have Messier descriptions and, with the exception of robot soccer, have not attracted much AI interest. 3 stances toward multi-agent environments open the chapter. With a very large number of agents, consider them in the aggregate as an economy, letting the model predict prices without modeling individuals. With adversaries, one might treat them as part of the environment, a part that makes the environment non-deterministic, but this misses the idea that our adversaries are actively trying to defeat us, whereas the rain supposedly has no such intention. The third stance, which the chapter takes, is to model adversaries explicitly with adversarial game tree search. Most studied games are deterministic, two-player, turn-taking, perfect information, zero-sum games. Perfect information is a synonym for fully observable. Zero-sum means what is good for one player is just as bad for the other. There is no win-win outcome. The players are called max and min. The game is defined by an initial state, a TO move function, actions of S giving legal moves, a transition model result of SA, a terminal test IS terminal, and a utility function utility of SP giving the terminal value to each player. In chess, when /loss/draw is 1, 0, 1/2. In backgammon, payoffs range 0 to 192. The state space graph and search tree carry over from Chapter 3, and the game tree follows every sequence of moves all the way to a terminal state. Fewer than 9 equals 362 880 terminal nodes for tic-tac-toe, but over 10 to the 40th nodes for chess, so the chess game tree is best thought of as a theoretical construct that we cannot realize in the physical world. Zero-sum, perfect information games, deterministic, two-player, turn-taking. What helps max Hertz and Mayan equally? Game definition, initial state, to move, actions, transition, terminal test, and utility. The 6 components of any formal game. 3 stances, economy, aggregate, adversary as noise, misses intent, an explicit adversarial game tree search, the chapter's choice. Optimal decisions in games. Given a game tree, the optimal strategy is determined by the minimax value of each state. The utility for max of being in that state, assuming that both players play optimally from there to the end of the game. A terminal state's minimax value is its utility. At a max node, the value is the maximum over successors. At a min node, the minimum. In max turn, max prefers the state of maximum value. In min's turn, min prefers the state of minimum value. Minimum for max, hence maximum for min. The 2-ply worked example shows the algorithm. The 3 min nodes have values 3, 2, and 2, so the root max node has minimax value 3, and action A1 is the minimax decision, the optimal choice. The definition assumes MIN plays optimally. If MIN does not play optimally, then Max will do at least as well as against an optimal player, possibly better. Yet facing a suboptimal opponent, a risky move can be rational. A 9/10 chance of winning beats a certain draw. Minimax performs a complete depth-first exploration of the game tree, with time complexity big O of B to the M and space big O of BM, or big O of M, generating one action at a time. The exponential complexity makes Minimax impractical for complex games. Chess has a branching factor of about 35, an average depth of about 80 ply, and it is not feasible to search 35 to the 80th states. Still, Minimax does serve as a basis for the mathematical analysis of games. Quote, the Minimax value is the utility, for Max, of being in that state, assuming that both players play optimally from there to the end of the game. Section 5.2. Optimal decisions in multiplayer games. Multiplayer games replace the single value per node with a vector of values, one per player. The backed-up value at a node is the utility vector of the successor state with the highest value for the player choosing at N. Anyone who plays Diplomacy or Settlers of Catan knows much more is going on than in two-player games. Alliances, formal or informal, are made and broken. How are we to understand such behavior? Are alliances a natural consequence of optimal strategies? It turns out that they can be. If A and B are weak and C strong, it is often optimal for both A and B to attack C, lest C destroy each of them individually. Collaboration emerges from purely selfish behavior. And as soon as C weakens, the alliance loses its value. Even with two players, non-zero-sum games produce automatic cooperation toward a state where both have high utility, such as V sub A equals 1000, V sub B equals 1000. The multiplayer extension is technically straightforward, but raises some interesting new conceptual issues. The social stigma of breaking an alliance, and the balance between the immediate advantage of breaking an alliance against the long-term disadvantage of being perceived as untrustworthy. Defer to section 18.2. Utility vector. Each node carries each player's utility. The choosing player selects the child with the highest own value. Alliances from selfishness. In equal opposition to a stronger player, cooperation emerges naturally and dissolves when its value does. Alpha-beta pruning. No algorithm can eliminate the exponential, but we can sometimes cut it in half, computing the correct minimax decision without examining every state by pruning large parts of the tree that make no difference to the outcome. The technique is alpha-beta pruning, and the chapter works it through the 2-ply example, showing the minimax decision is independent of two unevaluated leaves. Minimax of root equals the maximum of the minimum of 312.8, the minimum of 2x, while the minimum of 14.52 equals the maximum of 3z2 equals 3, so x and y can be pruned. The general principle. Consider a node N, such that player has a choice of moving to N. If player has a better choice either at the same level or at any point higher up in the tree, then player will never move to N. So once we have found out enough about N, we can prune it. The two parameters alpha and beta carry bounds along the search path. Alpha equals the value of the best, i.e., highest value, choice we have found so far at any choice point along the path for max, and beta equals the value of the best, i.e., lowest value, choice for MIN. Because minimax is depth first, only one path's nodes need be considered at a time. Alpha equals best for max so far. Beta equals best for MIN so far. Branches outside this window are provably irrelevant and can be pruned while preserving the exact minimax decision. Heuristic alpha-beta tree search. For non-trivial games, even with pruning, there's not enough time to be sure of finding the optimal move, so we will have to cut off the search at some point, applying a heuristic evaluation function eval, SP, an estimate of the expected utility, and a cutoff test in place of the terminal test. With eval substituting for utility, the heuristic minimax formula H-minimax, S, D, recurses only to depth D. The section develops 3 refinements in turn. First, evaluation functions which estimate who is winning from features of the state. Material values, pawn 1, knight or bishop 3, rook 5, queen 9, good pawn structure, king safety, combined as a weighted linear function eval of S equals the sum over IW sub I F sub I of S. The weights are normalized into the loss to win range. And the deeper subtlety is that the contribution of each feature is independent of the values of the other features is a strong assumption. So modern chess programs use nonlinear combinations. A pair of bishops is worth more than twice one. Second, cutting off search, a fixed depth limit within the time budget, or iterative deepening, whose transposition table would make subsequent rounds faster. The danger is evaluating non-quiescent positions. Applying the material evaluator to figure 5.8 b would report black winning while white's very next move captures the queen. The evaluation function should be applied only to positions that are quiescent, so is cutoff returns false except at quiescent positions, triggering a quiescent search restricted to move types like captures. The horizon effect is harder to eliminate. It arises when a serious unavoidable loss can be temporarily avoided by the use of delaying tactics, as when black pushes the inevitable capture of its bishop over the horizon with pawn checks at depth 8, making the pawn sacrifices seen by the search algorithm as good moves rather than bad ones. Singular extensions, moves clearly better than all others, get to extend the search beyond the cutoff, effectively mitigating the effect, and has proven to be effective in practice. Third, forward pruning cuts off moves that appear to be poor moves, but might possibly be good ones, a type B strategy in Shannon's terms, that saves time at the risk of making an error. Beam search is one risky approach. No guarantee the best move survives. Prop cut prunes nodes only probably outside the window, using past experience. Burroughs' Othello program Logistello with prop cut beat the regular version 64% of the time, even against double time. Late move reduction assumes well-ordered moves and searches later moves to reduce depth. Researching at full depth if the reduced search beats the current alpha. Combining the techniques yields a program that can play creditable chess. 1,000,000 nodes per second gives only 5-ply minimax, beatable by an average human, with alpha beta and a transposition table about 14-ply, expert level. Top programs like Stockfish often reach edge depth 30 or more, and far exceeding the ability of any human player. Fourth, search versus lookup. Opening and endgame tables replace search where positions are well known. Openings copy the best advice of human experts or database statistics. Endgames are solved completely by retrograde minimax search. Mark wins, then reverse the rules and propagate, and you have an infallible lookup table for all endgames with those pieces. This has been done for all endings with 7 or fewer pieces, tables of 400 trillion positions. Evaluation functions, weighted linear or nonlinear. Feature combinations estimating expected utility. Terminal states equal utility. Others lie between loss and win. Quiescence and the horizon effect. Evaluate only quiet positions and let clearly better singular extensions push past the horizon that hides unavoidable losses. Forward pruning. Prop cut and late move reduction prune probably bad moves, risking errors for large speedups. Retrograde minimax. Reverse search endgames to build perfect lookup tables. 7-piece tables contain 400 trillion positions. Monte Carlo tree search. Go exposes 2 weaknesses of heuristic alpha beta, a branching factor that starts at 361, so alpha beta reaches only 4 to 5 ply, and the difficulty of defining an evaluation function when material value is not a strong indicator. Modern Go programs have therefore abandoned alpha beta in favor of Monte Carlo tree search, MCTS, which does not use a heuristic evaluation function. Instead, the value of a state is estimated as the average utility over a number of simulations of complete games starting from the state. A simulation, playout or rollout, chooses moves for both players until a terminal position is reached where the rules of the game, not fallible heuristics, determine who has won or lost. If moves are chosen randomly, the estimate answers, what is the best move if both players play randomly? Which is often not the same as best play. So playout policy biases moves toward good ones, learned from self-play by using neural networks for Go, or using game-specific heuristics elsewhere. A selection policy balances 2 factors: exploration of states that have had few playouts and exploitation of states that have done well in past playouts. Each iteration of MCDES runs 4 steps. Selection. Descend the tree from the root by the selection policy to a leaf. Expansion. Grow a new child, marked 0/0. Simulation. A playout from that child, whose moves are not recorded in the tree. And backpropagation. Update when and playout counts up to the root. The powerful selection policy UCT, upper confidence bound applied to trees, ranks each move by an upper confidence formula. UCB1, trading the current win rate U of n over n of n against the log of the parent's playout count divided by n of n, selecting it as an example of exploitation, while a low-count node still has high uncertainty in its valuation and might end up being best if we gain more information. The 4 steps repeat, either for a set number of iterations or until the allotted time has expired, with the move of highest playout count returned. MCTS is the engine behind the Go systems that surpassed human champions. MCTS 4 steps: select, expand, simulate, backpropagate, repeated until time runs out, then return the highest playout count move. Exploration versus exploitation. UCT's UCB1 balances high win rates against high uncertainty, few playouts. Playout policy. Biased. Often learned move selection during simulations. The rules of the game, not heuristics, score the outcome. Stochastic games. Games with chance. Those that include an element of chance, through rolling dice or shuffling cards. Call for expect a minimax. An extension of minimax that adds chance nodes where the utility is the expected value over outcomes weighted by their probabilities. The chapter defines the expected minimax value of a state by taking, at a max node, the maximum over the expected values of its actions. At a min node, the minimum, and at a chance node, the probability-weighted average. In backgammon, random dice introduce these chance nodes, and the values are the expected utilities over all dice rolls. This treatment makes precise the sense in which game playing extends to non-deterministic moves beyond the opponents. Chance nodes are the environment's random choices, and or alike, and the optimal policy maximizes expected utility against both an optimal, minimizing opponent, and a stochastic environment. Partially observable games. Partially observable games blur the fog of war. The whereabouts of enemy units is often unknown until revealed by direct contact, and optimal play involves scouts, spies, concealing information, and bluffing. Deterministic partially observable games include Battleship and Stratego. The chapter's running example is Kriegspiel, chess in which each player sees only their own pieces and a referee adjudicates, announcing illegal, capture on square X, or check by D, giving a direction such as knight, rank, file, long diagonal, or short diagonal. White's belief state, the set of all logically possible board states given the complete history of percepts to date, begins as a singleton and grows. After White's first move and Black's reply contains 20 positions. Kriegspiel state estimation maps directly onto the partial observability framework of Chapter 4, if we consider the opponent as the source of non-determinism. A strategy in a partially observable game is a move for every possible percept sequence rather than every opponent move. A guaranteed checkmate leads to an actual checkmate for every possible board state in the current belief state, regardless of how the opponent moves, and because it must work even if the opponent saw everything, it vastly simplifies computation. And/or search over belief states finds guaranteed checkmates. Incremental belief state search finds mid-game checkmates up to depth 9, well beyond the abilities of most human players. Kriegspiel also introduces probabilistic checkmate, a new concept that makes no sense in fully observable games. Strategies probabilistic with respect to the winning player's randomization, like the lone white king finding a black king, detection occurs with probability 1, or KBNK. 1 because white presents black with an infinite random sequence of choices, one of which black must misguess. By contrast, KBBK is winnable only with probability 1 minus epsilon, since white must occasionally leave a bishop unprotected. Accidental checkmates occur if black's pieces happen to be in the right places, and most human checkmates are of this nature. The belief state probability conundrum closes the section. Board states in the belief state are not equally likely. Black optimally chooses moves, yet optimal play deliberately randomizes to minimize the opponent's information. Optimal play in partially observable games requires a willingness to play somewhat randomly, which is why restaurant hygiene inspectors do random inspection visits. Such intrinsically weak moves gain strength from their very unpredictability. The apparent circularity. Computing probabilities requires the optimal randomized strategy, and computing the strategy requires the probabilities, is resolved by adopting the game-theoretic notion of an equilibrium solution. Defer to Chapter 17. Kriegspiel, Partially observable chess, where the belief state estimates the opponent's hidden pieces and the referee's announcements are the percepts. Guaranteed versus probabilistic checkmate. Certain against every belief state versus certain with randomization, where detection occurs with probability 1. Randomization as strategy. Predictable optimal play leaks information, so optimal play in imperfect information games is deliberately unpredictable. Quote, optimal play in partially observable games requires a willingness to play somewhat randomly. Section 5.6. Card games and averaging over clairvoyance. Card games, bridge, hearts, poker, feature stochastic partial observability, where the missing information is generated by the random dealing of cards. Their obvious analogy to dice is incorrect but suggestive. It yields an algorithm that treats the deal as a chance node and then uses expect a minimax. Averaging over clairvoyance, which assumes that once the actual deal has occurred, the game becomes fully observable to both players. The chapter's Day 1/Day 2/Day 3 fork parable shows why the strategy can lead one astray. On days 1 and 2, road B is right. On day 3, the situation is the same as either day 1 or day 2, so B must still be the right choice. Yet B now risks death by bus. Averaging over clairvoyance fails. It does not consider the belief state that the agent will be in after acting. Because it assumes perfect future knowledge, the clairvoyance approach never selects actions that gather information, nor will it choose actions that hide information, and it will never bluff in poker because it assumes the opponent can see its cards. Despite the drawbacks, averaging over clairvoyance can be an effective strategy. With some tricks, abstraction treats similar hands as identical. Whether a hand has a 4 or 5 is less important than which aces it holds, and forward pruning samples a small random sample of N deals, which approximates well for N from 100 to 1000. The bridge bidding phase complicates the assumption that all deals are equally likely. Players bid in such a way as to minimize the information conveyed to their opponents. The section ends with modern superhuman poker. Liberatus decisively beat 4 top no-limit Texas hold M players in a 20-day match, using abstraction, treating AAA 72 and AAA 64 as equivalent, a $200 bet as a $201 bet, and 25 million CPU hours, while noting that costs like Liberatus's or AlphaZero's put world champion play beyond limited budgets. Though the trained Leo Lazaro runs on volunteer computers and AlphaStar won StarCraft 2 games on a single commodity GPU. Averaging over clairvoyance. Treat the deal as a chance outcome, then play as if fully observable. Fails because it never gathers, hides, or bluffs with information. Abstraction and deal sampling. Treat similar hands as identical and sample a few hundred deals to make expect a minimax tractable. Limitations of game search algorithms. The closing section is candid about what both branches of game search cannot do. First, alpha beta is vulnerable to errors in the heuristic function. In the two-ply tree where the right branch scores 100 against 99, even small independent evaluation errors with standard deviation sigma make the left branch better 71% of the time. Sigma equals 5, or 58%, sigma equals 2, and if errors are not independent, then the chance of a mistake rises. But there is no good model of sibling dependency to compensate. Second, both alpha beta and Monte Carlo compute bounds on the values of legal moves, wasting computation when one move is obviously best or when moves are symmetric. A better algorithm would use the idea of the utility of a node expansion, selecting expansions likely to lead to the discovery of a significantly better move and stopping when none is worth its cost. Meta-reasoning. Reasoning about reasoning, which applies beyond games and which Monte Carlo search does attempt, but does not do so in an optimal way. Third, both search at the level of individual moves, while humans play games differently. They can reason at a more abstract level, considering a higher-level goal. For example, trapping the opponent's queen, the territory of hierarchical planning, Chapter 11. Fourth, game search is only just beginning to see programs like AlphaZero, which relied on machine learning from self-play rather than game-specific human-generated expertise. The chapter summary traces the R from formal game definitions through minimax and alpha beta, cutoffs and evaluation functions, MCTS, opening/endgame tables, expect a minimax for chance, and belief state reasoning for imperfect information, and the honest bottom line that humans retain the edge in a few games of imperfect information, such as bridge and Kriegspiel. Chapter 6. Constraint Satisfaction Problems. Defining constraint satisfaction problems. Chapter 6 breaks open the black box of Chapter 3's atomic states by using a factored representation, a set of variables, each of which has a value, solved when every variable has a value satisfying all constraints. A constraint satisfaction problem, or CSP. CSP search algorithms exploit the structure of states and use general rather than domain-specific heuristics, eliminating large portions of the search space all at once by identifying variable/value combinations that violate the constraints. A CSP has three components: X, a set of variables; D, a set of domains, one per variable; and C, a set of constraints that specify allowable combinations of values. Each constraint C_J is a pair, scope, rel a tuple of participating variables and a relation defining allowed values, either an explicit set of tuples or a function. So x1 ex2 over domain 1, 2, 3 can be written as the tuple set 3, 1, 3, 2, 2, 1, or as the relation x1, x2. The vocabulary. An assignment sets variables to values. A consistent legal assignment violates no constraints. A complete assignment assigns every variable. A solution is a consistent, complete assignment. A partial assignment leaves some variables unassigned, and a partial solution is a consistent partial assignment. Solving a CSP is an NP-complete problem in general, although there are important subclasses of CSPs that can be solved very efficiently. The map coloring problem. Color Australia's regions red, green, or blue so neighbors differ. Yields 9 constraints. SA is not equal to WA, etc. Each a set of 6 allowed pairs, and the constraint graph pictures variables as nodes and constraints as edges. Why formulate as CSPs? They give a natural representation for many problems, years of solver engineering, and the decisive advantage that a partial assignment violating a constraint is immediately discarded. Once SA equals blue, none of the 5 neighbors can be blue. A reduction of 87% in assignments to consider, 243 down to 32. In atomic state space search, we can only ask, is this specific state a goal? With CSPs, we can see why the assignment is not a solution and focus on the variables that matter. CSP equals variables plus domains plus constraints. A solution is a consistent, complete assignment. Solving in general is NP-complete. Constraint graph. Variables as nodes, constraints as edges. The structural object most of the chapter's algorithms exploit. Pruning power. A violated partial assignment is discarded wholesale, unlike atomic search which tests whole states. Example problem. Map coloring. The map coloring formulation is the chapter's recurring worked example. The variables are the regions WA, NT, Q, NSW, V, SA, T. Every domain is red, green, blue. The constraints require neighboring regions to differ, giving 9 constraints around the borders. A solution assigns, for instance, WA equals red, NT equals green, Q equals red, NSW equals green, V equals red, SA equals blue, T equals red. The constraint graph makes the structure visible at a glance. The section's pedagogical point is concrete. Once SA equals blue is chosen, none of the 5 neighboring variables can be blue. 43% fewer assignments to examine. And more broadly, many problems that are intractable for atomic state space search can be solved quickly when formulated as a CSP. Example problem, job shop scheduling. Scheduling a day's worth of job subject to various constraints is, in practice, many of these problems are solved with CSP techniques. The chapter models assembling a car. Each task is a variable whose value is an integer start time, with precedence constraints written as arithmetic constraints. Whenever a task T sub 1 must occur before task T sub 2, and task T sub 1 takes duration D sub 1, write T sub 1 plus D sub 1 is less than or equal to T sub 2, so axle F plus 10 is less than or equal to wheel RF. Wheel RF plus 1 is less than or equal to nuts RF, and nuts RF plus 2 is less than or equal to cap RF. Propagate the assembly chain. A disjunctive constraint expresses that 2 tasks sharing a tool must not overlap. Axle F plus 10 is less than or equal to axle B, or axle B plus 10 is less than or equal to axle F. Inspection comes last. X plus D sub X is less than or equal to inspect for every X. and a 30-minute deadline can be achieved by limiting the domain of all variables to 0, 30. This particular problem is trivial to solve, but CSPs have been successfully applied to job shop scheduling problems with thousands of variables. Precedence constraints. Arithmetic inequalities T sub 1 plus D sub 1 is less than or equal to T sub 2 chain tasks in time. Disjunctive constraints. A first or be first express shared single-use resources. Deadline as domain bound. Limiting every domain to 0, 30 enforces the deadline. Variations on the CSP formalism. CSPs vary along three axes: the type of variables and domains, the type of constraints, and the way n-ary constraints are represented. Discrete finite domains cover map coloring, scheduling with time limits, and 8 queens, variables Q sub 1, Q sub 8, each domain the possible rows. Discrete domains can be infinite, requiring implicit constraints like T sub 1 plus D sub 1 is less than or equal to T sub 2 rather than explicit tuples. Linear constraints on integer variables have special solution algorithms, while no algorithm exists for solving general nonlinear constraints on integer variables. The problem is undecidable. Continuous domains are common, from Hubble telescope scheduling to linear programming, where constraints must be linear equalities or inequalities, solvable in polynomial time. Constraints range from unary, restricting one variable, such as SA is not equal to green, or the domain itself, through binary, relating two variables, higher order, like between x, y, z, to global constraints involving an arbitrary number of variables, the most common being all-diff. All of the variables involved in the constraint must have different values, as in Sudoku and cryptarithmetic. A cryptarithmetic puzzle, 2 plus 2 equals 4, is expressed with the global constraint all-diff of FTUW are big O plus column addition constraints with carry variables C sub 1, C sub 2, C sub 3, pictured in a constraint hypergraph. Nodes for variables, hypernodes for n-ary constraints. Every finite domain constraint can be reduced to binary constraints if enough auxiliary variables are introduced, and the dual graph transformation makes one variable per original constraint. Yet, global constraints like all-diff are still preferred because it is easier and less error-prone to write the problem description, and because specialized inference algorithms for them are more efficient. Global constraints / all-diff. Constraints over many variables with specialized, more efficient inference than primitive constraints. Hypergraph and dual graph. N-ary constraints as hypernodes or re-expressed as binary. Every finite domain CSP reduces to binary with auxiliary variables. Continuous and linear domains. Linear constraints are decidable and polynomial. General nonlinear integer constraints are undecidable. Constraint propagation. Inference in CSPs. Making a choice of value for a variable triggers inferences. The constraints on one variable can have effects on the other variables, which in turn can reduce the legal values for another variable, and so on. So this will leave fewer choices to consider when we make the next choice of a variable assignment. Constraint propagation may be intertwined with search, or it may be done as a pre-processing step before search starts. Sometimes this pre-processing can solve the whole problem, so no search is required at all. The key idea is local consistency. If we treat each variable as a node in a graph and each binary constraint as an edge, then the process of enforcing local consistency in each part of the graph causes inconsistent values to be eliminated throughout the graph. The kinds of local consistency appear in increasing strength. Node consistency. Every value in a variable's domain satisfies its unary constraints. Remove green from SA's domain if South Australians dislike it. Arc consistency. For every value of x sub I, there is some value of x sub j satisfying the binary constraint, with the y equals x to the second example reducing x's domain to 0, 1, 2, 3, and y's to 0, 1, 4, 9, but doing nothing for Australia's inequality constraints, where every value always has a partner. The AC3 algorithm enforces arc consistency by maintaining a queue of arcs. Each binary constraint becomes 2 arcs, popping x sub I x sub j, and if revised shrinks d sub I, adding all arcs x sub k x sub I for neighbors x sub k back to the queue, because the change might enable further reductions in d sub k, even if we have previously considered x sub k. If a domain shrinks to empty, the CSP has no solution and AC3 returns failure. Otherwise, the result is a CSP that is equivalent to the original CSP, with smaller domains and the same solutions, sometimes solving the problem completely. Within variables, domain size at most d, and C constraints. Each arc enters the queue at most d times and revise cost big O of d to the second, giving big O of CD to the third total worst-case time. Beyond arc consistency, path consistency tightens binary constraints, using implicit constraints that are inferred by looking at triples of variables. X sub I x sub j is path consistent with respect to x sub m if every consistent assignment to the pair can be extended to satisfy the constraints involving x sub m. And this catches the Australia with two colors impossibility, since WA, NT, and SA all touch. The general notion is K, consistency. For any consistent assignment to K-1 variables, a consistent value can always be found for a kth variable. 1 consistency is node, 2 consistency arc, 3 consistency path. A CSP that is K, consistent down through 1 is strongly K, consistent, and if made strongly N, consistent, it can be solved in only big O of N to the second D by marching down the variables. There is no free lunch. Establishing N consistency takes time and space exponential in N, so determining the appropriate level of consistency checking is mostly an empirical science. Local consistency. Enforcing node, arc, and path consistency eliminates inconsistent values throughout the graph. AC3. Q-driven arc consistency in big O of CD to the third shrinks domains to equivalent, smaller CSP. K. Consistency. A hierarchy from node 1 through arc 2 and path 3 to strong inconsistency, which solves in big O of N to the second D at exponential pre-processing cost. Global constraints, bounds propagation, and Sudoku. Special purpose inference for global constraints is more efficient than reducing them to primitives. The ALDIF constraint detects inconsistency when M variables are involved in the constraint, and if they have n possible distinct values altogether, and M greater than n. The simple algorithm removes singleton domain variables and deletes their values from the remaining domains, repeating. An empty domain or more variables than domain values signals inconsistency. Catching WA equals red, NSW equals red, where the 3 remaining variables each have only green, blue between them. 3 variables and only 2 colors. The resource, at most, constraint handles sums, no more than 10 personnel, as at most, 10, P1, P4. Inconsistency is detected by checking the sum of minimum domain values, or by deleting maximum values inconsistent with the other minima. For large integer problems, domains are represented by upper and lower bounds and are managed by bounds propagation. Flights with capacities 165 and 385 and the constraint f sub 1 plus f sub 2 equals 420 reduced domains to d sub 1 equals 35 165, d sub 2 equals 255 385. And a CSP is bounds consistent when every bound of every variable has a satisfying partner value in every other variable. Sudoku receives a full work treatment. 81 variables, domains 1, 9 and 27 ALDIF constraints, 1 per row, column, and 3 by 3 box. Arc consistency alone solves easy puzzles. E6 domain reduces to 4, then I6 to 7, then A6 to, and eventually AC. 3 can solve the entire puzzle. Harder puzzles need path consistency, PC2, which on Sudoku has 255,960 different path constraints to consider, and human-style strategies like naked triples. 3 squares that each have a domain that contains the same 3 numbers or a subset of those numbers, from which the 3 numbers can be removed from every other square in the unit. The striking conclusion: it is interesting to note how far we can go without saying much that is specific to Sudoku. All the strategies apply generally to all CSPs. This is the power of the CSP formalism. For each new problem area, we only need to define the problem in terms of constraints. Then the general constraint-solving mechanisms can take over. ALDIF/resource bounds. Specialized inference detects the M greater than N violation and propagates singleton values. Bounds propagation arrows intervals. The power of the CSP formalism. Define constraints, then the general machinery, arc path, naked triple-style inference, takes over, even for Sudoku. Backtracking search for CSPs. When constraint propagation leaves variables with multiple values, search takes over. Backtracking search algorithms that work on partial assignments. A naive, depth-limited search has branching factor ND at the top level, yielding end at D to the N leaves, even though there are only D to the N possible complete assignments. A wasteful factor of N recovered by recognizing commutativity. The order of application of any given set of actions does not matter, so at each node, we need only consider a single variable. Choosing among SA equals red/green/blue, but never between NSW equals red and SA equals blue. The backtracking search procedure repeatedly chooses an unassigned variable, and then tries all values in the domain of that variable in turn, extending each into a solution recursively, restoring the assignment on failure, and returning failure when no value works. It keeps a single representation of a state and alters it in place. Unlike Chapter 3's uninformed searches, backtracking can be improved using domain-independent heuristics that take advantage of the factored representation of CSPs. Commutativity. Fixing the order of variable assignment recovers the N factor and gives the D to the N leaf tree. Backtracking search. Choose a variable, try its values in turn, recurse, restore on failure. Variable and value ordering. The task order, which variable next, which value first, is where domain-independent heuristics pay off. Selecting the variable with the fewest legal values is the minimum remaining values, MRV. Heuristic, also called most constrained variable or fail first, because it picks a variable that is most likely to cause a failure soon, thereby pruning the search tree. If some variable has no legal values, MRV selects it and failure is detected immediately, avoiding pointless searches through other variables. MRV usually performs better than a random or static ordering, sometimes by orders of magnitude. When MRV ties, as of the first pick in Australia, the degree heuristic selects the variable that is involved in the largest number of constraints on other unassigned variables. SA, with degree 5, and choosing SA first solves the problem without any false steps. For value ordering, the least constraining value heuristic prefers the value that rules out the fewest choices for the neighboring variables, preserving flexibility for later assignments. The asymmetry is principled. Variable selection is fail first because every variable has to be assigned eventually. So failing early means less to backtrack over, while value selection is fail last because we only need one solution, so we try the most likely values first. MRV, fail first assign the most constrained variable first, catches failure immediately. Degree heuristic, tiebreak toward the most constrained by constraint count. Least constraining value, fail last value ordering that leaves neighbors maximum flexibility. Interleaving search and inference. Every time we make a choice of value for a variable, we have a brand new opportunity to infer new domain reductions on the neighboring variables. The simplest inference is forward checking. When X is assigned, for each unassigned neighbor Y, delete any value of Y inconsistent with the chosen X value. In the Australia trace, after WA equals red and Q equals green, and T's and SA's domains collapse to singletons, we have eliminated branching on these variables altogether. And after V equals blue, SA's domain is empty, so forward checking has detected that the partial assignment is inconsistent, and the algorithm backtracks immediately. Combining forward checking with MRV is synergistic. Assigning WA equals red constrains its neighbors NT and SA, so MRV handles them next, and then all the other variables will fall into place. Forward checking is an efficient way to incrementally compute the information that the MRV heuristic needs. But forward checking does not look ahead far enough. It leaves NT and SA both blue only, neighbors with an inconsistency. MAC, maintaining our consistency, closes the gap. After assigning she, it runs AC, 3 starting from arcs, XJ, she, 4 unassigned neighbors, strictly more powerful than forward checking, which does not recursively propagate constraints when changes are made to the domains of variables. Forward checking, deleting inconsistent neighbor values each assignment, detects conflicts early but not all. MAC, AC, 3 restarted from the assigned variables arcs, strictly stronger than forward checking. Intelligent backtracking, looking backward. Plain backtracking revisits the most recent decision point, chronological backtracking. The chapter's example is deliberately silly. With order Q, NSW, V, T, SA, WA, and T, when SA fails, recoloring Tasmania obviously is silly, Recoloring Tasmania cannot possibly help in resolving the problem with South Australia. The conflict set of a variable collects the assignments in conflict with its values. Backjumping backtracks to the most recent assignment in the conflict set, jumping over Tasmania to try a new V. Forward checking can supply the conflict set with no extra work. Whenever an assignment deletes a value from Y's domain, add it to Y's conflict set, and if the last value is deleted, add Y's conflict set to X's. Yet, simple backjumping is redundant in a forward-checking search. It can be shown every branch pruned by backjumping is also pruned by forward checking. The deeper notion, conflict-directed backjumping, tracks that set of preceding variables that caused a variable, together with any subsequent variables, to have no consistent solution. So, when a set of variables fails together for reasons outside itself, the algorithm backtracks to the truly responsible preceding variables, skipping Tasmania even when no single variable's conflict set explains the failure. Backjumping versus conflict-directed backjumping. Jump to the most recent conflicting assignment, or to the set of preceding variables responsible for a group's joint failure. Redundancy with forward checking. Every branch pruned by simple backjumping is also pruned by forward checking or MAC. Local search for CSPs. Local search turns out to be very effective in solving many CSPs, using a complete state formulation where each state assigns a value to every variable, and the search changes the value of one variable at a time. The 8 queens example starts from a complete assignment violating several constraints, randomly chooses a conflicted variable, and applies the min conflicts heuristic. Select the value that results in the minimum number of conflicts with other variables, breaking ties randomly. Min conflicts is surprisingly effective for many CSPs. On n queens, the runtime is roughly independent of problem size. It solves even a million queens problem in an average of 50 steps after the initial assignment. The observation that was the stimulus leading to a great deal of research in the 1990s on local search and the distinction between easy and hard problems. N queens is easy because solutions are densely distributed throughout the state space, but min conflicts also works well for hard problems. It schedules Hubble Space Telescope observations, cutting the time taken to schedule a week of observations from 3 weeks to around 10 minutes. CSP landscapes under min conflicts usually have a series of plateaus, millions of variable assignments that are only one conflict away from a solution. So plateau search, sideways moves, helps as do-to-boo search, a list of recently visited states to avoid, and simulated annealing. Constraint weighting concentrates search on important constraints. Each constraint gets a weight, initially 1. The algorithm changes variable/value pairs to minimize total violated weight, then increments the weights of violated constraints. It adds topography to plateaus and adds learning. Over time, the difficult constraints are assigned higher weights. Local search also shines in the online setting. To repair an airline schedule after bad weather, we would like to repair the schedule with a minimum number of changes. This can be easily done with a local search algorithm starting from the current schedule, whereas backtracking with the new constraints is much slower and may change everything. Min conflicts. Repeatedly reassign a conflicted variable to its least conflicting value. Solves million queens in an average of 50 steps. Plateaus. To boost search, constraint weighting. Sideways moves escape plateaus. Weighted constraints learn which are hard. Online repair. Local search starts from the current schedule and repairs it minimally when the problem changes. The structure of problems. Structure, as represented by the constraint graph, can be used to find solutions quickly, and most of the approaches also apply to other problems besides CSPs. The Tasmania observation is the seed. Because Tasmania is disconnected from the mainland, coloring Tasmania and coloring the mainland are independent subproblems. Independence is found by computing connected components. If each subproblem has C constant variables, total work is big O of D to the C n over C, linear in n, while the undecomposed problem is big O of D to the n, exponential. The concrete contrast is striking. Dividing a Boolean CSP with 100 variables into 4 subproblems reduces the worst-case solution time from the lifetime of the universe down to less than a second. Perfectly independent subproblems are delicious then, but rare. The next easy structure is a tree constraint graph. A CSP whose graph is a tree can be solved in time linear in the number of variables, using directional arc consistency, DAC. Every x sub I are consistent with each x sub j for j is greater than I, under topological sort ordering where each variable appears after its parent. Enforcing DAC takes big O of nd to the second. Then, marching down the list, for any value we choose for the parent, there will be a valid value left to choose for the child. So the tree CSP solver never backtracks and either finds a solution in linear time or detects a contradiction. Two transformations reduce general graphs to trees. Cut-set conditioning removes a cycle cut set S, so the remaining graph is a tree. Tries each consistent assignment to S, removes inconsistent values, and solves the tree. With cut set size, see the runtime is big O of d to the c n minus cd to the second. Huge savings when the graph is nearly a tree. A cut set of size 20 on the 100 Boolean example gets down from the lifetime of the universe to a few minutes, though finding the smallest cut set is NP hard. Tree decomposition builds a tree whose nodes are sets of variables satisfying three requirements. Every variable appears somewhere. Constrained variables appear together, along with a constraint, in at least one tree node, and a variable appearing in two nodes must appear in every node along the path connecting those nodes, so it has the same value wherever it appears. Applying tree CSP solver solves any decomposition in big O of nd to the second. Efficient if the largest node stays small. The tree width W is one less than the largest node, and CSPs with constraint graphs of bounded tree width are solvable in polynomial time, though finding the minimal width decomposition is NP hard. The tree decomposition time, bound big O of nd to the W plus 1, usually beats the cut set bound big O of d to the c n minus cd to the second. But cut set conditioning runs in linear memory, while tree decomposition requires memory exponential in W. Finally, value symmetry exploits structure in the values themselves. A map with D colors has D solutions formed by permuting the color names, and a symmetry-breaking constraint like NTSAWA, alphabetical order, ensures that only one of the D solutions is possible, cutting search by the factor D. Independent components. Solving each component separately makes the total linear instead of exponential. Tree CSP/DAC. A topological sort order plus directional arc consistency yields a backtrack-free linear solution. Cut set conditioning versus tree decomposition. Remove or cluster variables to reach a tree. Cut set runs in linear memory. Tree decomposition in big O of nd to the W plus 1 time, where W is tree width. Value symmetry. Symmetry-breaking constraints factor out the D permutations among color-like values. Part 3. Knowledge, Reasoning, and Planning. Chapter 7. Logical Agents. Knowledge-based agents. Chapter 7 builds agents whose heart is a knowledge base, a set of sentences, each expressed in a knowledge representation language and representing an assertion about the world. A sentence given without being derived from others is an axiom. Two operations define the interface. Tell add sentences and ask queries what is known, and both may involve inference, that is, deriving new sentences from old. Inference must obey the requirement that when one asks a question of the knowledge base, the answer should follow from what has been told. The inference process should not make things up as it goes along. The knowledge-based agent program takes a percept, does three things. Tell what it perceives, ask what action to perform, which may trigger extensive reasoning about the current state and the outcomes of action sequences, and tell the chosen action, and the details of the representation language are hidden inside make percept sentence, make action query, and make action sentence. Because of these definitions, the knowledge-based agent is not an arbitrary program for calculating actions. It is amenable to a description at the knowledge level, where we need specify only what the agent knows and what its goals are in order to determine its behavior. The automated taxi example. Knowing the Golden Gate Bridge is the only link to Marin, it should cross it, is independent of how the taxi works at the implementation level. It doesn't matter whether its geographical knowledge is implemented as linked lists or pixel maps, or whether it reasons by manipulating strings of symbols stored in registers or by propagating noisy signals in a network of neurons. An agent can be built simply by telling it what it needs to know. The declarative approach versus the procedural approach of encoding behaviors directly as code. The 1970s, 80s heated debates have resolved into the understanding that a successful agent often combines both declarative and procedural elements, with declarative knowledge often compiled into more efficient procedural code. A knowledge-based agent can also learn for itself. Chapter 19. Becoming fully autonomous. Knowledge base, KB, is set of sentences. Tell ads, ask queries, inference derives. Knowledge level versus implementation level. Specify only what the agent knows and its goals. Behavior follows independent of internal representation. Declarative versus procedural. Telling facts versus coding behavior. Successful agents combine both, compiling declarative knowledge into efficient code. Quote, the inference process should not make things up as it goes along. Section 7.1. The Wumpus World. The Wumpus World is the test bed. A cave consisting of rooms connected by passageways, with a terrible wumpus that eats anyone entering its room, bottomless pits that trap anyone who wanders in, except the wumpus, which is too big to fall in, and a heap of gold. The environment is defined by P's. Plus 1,000 for climbing out with the gold, minus 1,000 for dying, minus 1 per action, minus 10 for the arrow, a 4x4 grid with random gold and wumpus placement. Actuators forward, turn left, turn right, grab, shoot, 1 arrow, and climb, only from 1 and 5 single-bit sensors, stench, adjacent to the wumpus, breeze, adjacent to a pit, glitter in the gold square, bump, walking into a wall, and scream when a wumpus dies, heard anywhere. The agent always starts in the square labeled 1, facing to the east. The environment is deterministic, discrete, static, and single agent, sequential, because rewards may come only after many actions are taken, and partially observable, since the agent's location, the wumpus's health, and the arrow's availability are not directly perceivable. About 21% of the environments are utterly unfair, because the gold is in a pit or surrounded by pits. The chapter walks a cautious agent through the world. From an initial all-none percept, 1, 2, and 2, 1, are inferred okay, free of dangers. Moving to 2, 1, and perceiving a breeze forces, a pit into 2 or 3, 1 or both. The safest known unvisited square is 1, 2, so the agent backs up to 1, goes there, perceiving a stench in 1, 2, and knowing the wumpus cannot be in 1 or 2, 2, else a stench would have been smelled at 2, and the agent can infer that the wumpus is in 1, 3. The lack of a breeze in 1, 2 rules out a pit in 2, 2. So combined with the earlier inference, the pit must be in 3, a fairly difficult inference because it combines knowledge gained at different times in different places and relies on a lack of percept to make one crucial step. Then 2, 2 is proved safe. The agent moves to 2, 3, detects a glitter, grabs the gold, and heads home. The chapter's methodological point is explicit. In each case for which the agent draws a conclusion from the available information, that conclusion is guaranteed to be correct if the available information is correct. This is a fundamental property of logical reasoning. Wumpus World P's, the 5 sensors, stench, breeze, glitter, bump, scream, and the actions that define a partially observable sequential test bed. Logical reasoning guarantees. Conclusions guaranteed to be correct if the available information is correct, including reasoning from the lack of a percept. Logic. This section states the beautiful ideas, independent of any of logic's particular forms, using ordinary arithmetic as the example. A syntax specifies all the sentences that are well-formed. X plus y equals 4 is well-formed. X4 y plus equals is not. The semantics define the truth of each sentence with respect to each possible world. In standard logics, every sentence must be either true or false in each possible world. There is no in-between. The term model replaces possible world. Models are mathematical abstractions, each of which has a truth value for every relevant sentence. If a sentence alpha is true in model M, we say that M satisfies alpha, or sometimes M is a model of alpha, writing M alpha for the set of all models. Logical reasoning is the relation of entailment. Alpha entails beta if and only if, in every model in which alpha is true, beta is also true. Equivalently M of alpha subset, EQ M of beta. If alpha entails beta, then alpha is a stronger assertion than beta. It rules out more possible worlds. The wumpus example applies this concretely. With 3 squares possibly containing pits, there are 2 to the third equals 8 possible models. The KB, nothing at 1, a breeze at 2, 1, is true in just 3 of them. By inspection, alpha sub 1, no pit in 1, 2, is true in every KB true model, so KB entails alpha sub 1. while alpha sub 2, no pit in 2, is false in some KB true model, so the agent cannot conclude it, nor its negation. The inference algorithm illustrated is model checking. It enumerates all possible models to check that alpha is true in all models in which KB is true. The haystack metaphor crystallizes it. Entailment is like the needle being in the haystack. Inference is like finding it. If inference algorithm I derives alpha from KB, right KB entails alpha derived by I. An algorithm that derives only entailed sentences is sound, truth-preserving. An unsound one essentially makes things up as it goes along. It announces the discovery of non-existent needles. An algorithm is complete if it can derive any sentence that is entailed. Reasoning is sound and guaranteed truth-preserving. If KB is true in the real world, then any sentence alpha derived from KB by a sound inference procedure is also true in the real world. Syntax semantics models. Syntactic well-formedness, semantic truth in each model, and satisfaction M, alpha. Entailment. Alpha equals beta, IFF. Every model of alpha is a model of beta. The strongest assertion rules out the most worlds. Soundness and completeness. Sound inference derives only entailed sentences. Complete inference derives every entailed sentence. Quote, entailment is like the needle being in the haystack. Inference is like finding it. Section 7.3. Propositional logic, a very simple logic. Propositional logic provides a very simple logic with a formal syntax, a recursive semantics, and a model-checking inference algorithm, all worked in the Wumpus world. Atomic sentences are single proposition symbols, P, Q, W1, 3, facing east, that stand for propositions true or false, plus the fixed true and false. Complex sentences combine simpler ones with 5 logical connectives: negation, conjunction, and disjunction, or implication, whose premise/antecedent and conclusion/consequent form rules or if-then statements, and biconditional left-right arrow. A BNF grammar formalizes the syntax with operator precedences, binds most tightly, just like in arithmetic, where -2 plus 4 is 2, not -6. The semantics is recursive. A model simply sets the truth value, true or false, for every proposition symbol. So with 3 symbols, there are 2 superscript 3 equals 8 possible models, exactly those depicted in figure 7.5. And the models are purely mathematical objects with no necessary connection to Wumpus worlds. P1, 2 is just a symbol. It might mean there's a pit in 1, 2, or I'm in Paris today and tomorrow. Truth tables define the connectives. Conjunction and disjunction match intuition, with the inclusive or caveat. Exclusive or circle plus is different. Implication may not quite fit one's intuitive understanding. 5 is odd implies Tokyo is the capital of Japan is a true propositional sentence. And any implication with a false antecedent is true, because if P is true, then I'm claiming that Q is true. Otherwise, I'm making no claim. The only way for this sentence to be false is if P is true, but Q is false. The biconditional captures the Wumpus rules exactly. A square is breezy if a neighboring square has a pit, and a square is breezy only if a neighboring square has a pit, giving B1, 1 left-right arrow, P1, 2 or P2, 1. A simple knowledge base then collects the immutable facts. R1, P1, 1, no pit in 1, 1. R2, B1, 1 left-right arrow, P1, 2 or P2, 1. R3, B2, 1 left arrow, P1, 1 or P2, 2 or P3, 1, plus the percepts are 4, B1, 1 and R5, B2, 1. A simple inference procedure, TT entails, is a direct implementation of the definition of entailment. Enumerate the models, and check that alpha is true in every model in which KB is true. With 7 symbols, there are 2 equals 128 models. In 3, the KB is true, and in all 3 P1, 2 is true, hence there is no pit in 1, 2, while P2, 2 is true in 2 and false in 1. So we cannot yet tell whether there is a pit in 2, 2. 5 connectives, and or left-right arrow, defined by truth tables. Implication is the counterintuitive one, false antecedent true. Truth table semantics. A model assigns truth values to symbols. Any sentence's truth is computed recursively. TT entails model checking. Enumerate all models. KB entails alpha, IFF alpha holds in every KB true model. Propositional theorem proving. Model checking is one way to derive entailment. Theorem proving applies sound inference rules to syntactic sentences. The section builds the classical toolkit. First comes sound inference rules. And elimination, modus ponens from alpha, beta, and alpha, conclude beta, and insertion, and others, each of which can be applied whenever suitable premises are found. Thanks to monotonicity. If KB equals alpha, then KB and beta equals alpha. Adding information can only increase entailments. It cannot invalidate any conclusion alpha already inferred. Complete proof procedures follow from a single rule, resolution. Unit resolution resolves a clause with a complementary literal. The full resolution rule takes two clauses containing complementary literals li and mj and produces a clause with all the literals of both except the complementary pair, resolving only one pair at a time, and removing duplicate literals by factoring. The soundness proof is a neat dichotomy. If li is true, then mj is false, so the other clause's remaining literals must hold. And if li is false, then the other clause's remaining literals must hold. Resolution yields completeness because every sentence of propositional logic is logically equivalent to a conjunction of clauses, conjunctive normal form, CNF. The conversion procedure eliminates left-right arrow, replace with two implications. Eliminates, moves inward, double negation, and De Morgan, and distributes or over and. The word conversion of B1, 1 left-right arrow, P1, 2 or P2, 1, to 3 clauses makes the price of CNF concrete. It is much harder to read, but it can be used as input to a resolution procedure. The resolution algorithm, PL resolution, works by the principle of proof by contradiction. To show KB equals alpha, show KB and alpha is unsatisfiable by resolving clauses until either no new clauses can be added, no entailment, or 2 clauses resolve to the empty clause, entailment. The empty clause being a disjunction of no disjuncts, equivalent to false, arising only from resolving 2 contradictory unit clauses, such as P and P. Completeness is the ground resolution theorem. If a set of clauses is unsatisfiable, then the resolution closure of those clauses contains the empty clause, proved by contrapositive with a clever construction that assigns each symbol so no clause is ever falsified. In many practical situations, the full power of resolution is not needed. Definite clauses disjunctions with exactly one positive literal, and horn clauses at most one positive literal. All definite clauses are horn clauses, as are clauses with no positive literals, called goal clauses, are closed under resolution and support a more restricted and efficient inference algorithm. Definite clauses can be written as an implication whose premise is a conjunction of positive literals and whose conclusion is a single positive literal, which makes them the natural substrate for the forward and backward chaining to come. Monotonicity. Adding to a KB never invalidates a derived conclusion. Inference rules apply whenever premises exist. Resolution and CNF. Resolving complementary literals in clauses. Completeness. Ground resolution theorem. Via proof by contradiction. Horn and definite clauses. At most one, or exactly one, positive literal. Closed under resolution and efficiently chainable. Horn clauses, forward chaining, and backward chaining. Horn knowledge bases admit efficient goal-directed inference. Definite clauses written as implications support forward chaining. Starting from known facts, repeatedly apply modus ponens until the query is answered or nothing new follows. Forward chaining is data-driven. It works forward from what is known and is appropriate for problems like the Wumpus world, where many queries may be asked after each percept. Backward chaining works the other way, goal-directed. Start from the query/goal and work backward, matching the goal's conclusion against the heads of definite clauses and recursing on their premises. The algorithm is essentially depth-first graph search. Backward chaining answers only the query of interest, much more efficient than forward chaining when the query is one among many possible, and forms the basis of prologue-like reasoning. Completeness holds for both when they are applied to suitable Horn knowledge bases, and the chapter emphasizes the trade-off. Forward chaining recomputes everything from facts. Backward chaining focuses on the goal, but may loop on recursive rules. Effective propositional model checking. The technology of propositional logic, SAT solving, is where theory meets enormous scale practice, because so many combinatorial problems in computer science can be reduced to checking the satisfiability of a propositional sentence. Testing entailment reduces to testing unsatisfiability of KB and alpha, and the two families of propositional satisfiability algorithms closely resemble the backtracking algorithms of Section 6.3 and the local search algorithms of Section 6.4. The complete backtracking family is DPLL, Davis, Putnam, Logeman, Loveland, essentially a recursive, depth-first enumeration of possible models, with three key improvements. Early termination. A partially completed model can already determine truth. A clause is true if any literal is true, so entire subtrees are skipped. The pure symbol heuristic. A symbol appearing with only one sign in all remaining clauses can be assigned to make its literals true, since doing so can never make a clause false. In the unit clause heuristic, a clause with one unassigned literal forces its assignment, and assigning one unit clause can create another, cascading as unit propagation. If the CNF contains only definite clauses, DPLL essentially replicates forward chaining. The tricks that enable SAT solvers to scale up are mostly rather general, and we have seen them before. Component analysis, disjoint clause subsets solved separately, as seen with Tasmania and CSPs, variable and value ordering, the degree heuristic, intelligent backtracking with conflict clause learning, records conflicts so that they won't be repeated later, random restarts. Learning retained across restarts reduces the variance on the time to solution, and clever indexing. With these enhancements, modern solvers can handle problems with tens of millions of variables and have revolutionized areas such as hardware verification and security protocol verification. The local search family applies the SAT evaluation function of counting unsatisfied clauses. Exactly am I in conflicts measure. WalkSat picks an unsatisfied clause, then flips a symbol by either a min conflict step, minimize unsatisfied clauses, or a random walk step, flip randomly, chosen with probability p. Its limitation is sharp. When WalkSat returns a model, the input sentence is indeed satisfiable. But when it returns failure, there are two possible causes. Either the sentence is unsatisfiable, or we need to give the algorithm more time. So WalkSat cannot always detect unsatisfiability, which is required for deciding entailment. It might only say, I thought about it for an hour and couldn't come up with a possible world in which the square isn't safe. Certainly not a proof. The landscape of random SAT problems closes the section. Under constrained problems, few clauses are easy. Two random guesses find a model. Over constrained problems, many clauses are likely to have no solutions and are often easy to solve because the constraints quickly lead either to a solution or to a dead end. For random 3CNF with 50 variables, the probability of satisfiability drops fairly sharply around m/n equals 4.3, and the satisfiability threshold conjecture posits a sharp threshold ratio for each k. Remains unproven, even for special cases like k equals 3, while empirically, the most difficult problems have a clause/symbol ratio of about 4.3, roughly 20 times harder than ratio 3.3. This threshold behavior is certainly common for satisfiability problems as well as other types of NP-hard problems. DPLL, early termination, pure symbols, unit propagation, the backbone of complete SAT solving. Scaling tricks, component analysis, ordering, conflict clause learning, restarts, clever indexing, tens of millions of variables. WalkSat, min conflicts plus random walk, finds models fast but cannot prove unsatisfiability. Phase transition. Hardest random 3CNF instances sit at the clause/symbol threshold approximate 4.3. Agents based on propositional logic. The chapter closes by assembling a complete logical agent from the pieces. The knowledge base combines axioms, general knowledge. No pit or wumpus in one. Breezy IFF neighbor has a pit. Smelly IFF neighbor has a wumpus. Exactly one wumpus, in at least one and at most one parts, with percept sentences. Percepts must be time-stamped. A percept asserts something only about the current time, so a time for we add s sub 4 stench, not stench, neatly avoiding any contradiction with not stench sub 3. This introduces fluence, an aspect of the world that changes, indexed by time like L to the txy, facing east t, avero t, wumpus alive t, with permanent aspects called atemporal variables. Action symbols are also time-indexed, and the percept, action, and transition follow in order per step. Writing the transition model as logical sentences leads to the frame problem. Effect axioms state the outcome of an action. Moving forward from 1, 1, east gives L to the second one 2 and not L to the first one 1. But after asserting it, the agent cannot prove it still has the arrow, nor can it prove it doesn't have it, because the effect axiom fails to state what remains unchanged. Adding explicit frame axioms for every unchanged fluent gives big O of M in axioms for M actions and influence. The representational frame problem, significant because the real world has very many fluents, to put mildly. Fortunately, the world exhibits locality. Each action typically changes no more than some small number k of those fluents, and the solution is a successor state axiom per fluent, f to the t plus 1 arrow. L. Our action causes f to the t or f to the t, and not action causes not f to the t, with have arrow simplifying to have arrow t plus 1 arrow. L. Our have arrow t and not shoot t. This solves representational big O of mk axioms and inferential frame problems, projecting a t-step plan in big O of kt. The residual, pernicious problem is the qualification problem. We need to confirm that all the necessary preconditions of an action hold, and the world has unbounded exceptions, tripping, heart attacks, giant bats. There is no complete solution within logic. Probability, Chapter 12, allows us to summarize all the exceptions without explicitly naming them. A hybrid agent combines knowledge-based state estimation with search. It maintains a KB plus a current plan, uses logical inference, ask, to determine safe and unvisited squares, and builds routes with A-star search rather than ask, planning to grab gold if glitter is present, otherwise to the closest unvisited safe square, otherwise to shoot at possible wumpus locations if it has an arrow, otherwise to risk a square not provably unsafe, otherwise to retreat and climb out. The final improvement is logical state estimation via caching. Instead of rederiving from the whole percept history, the agent caches the belief state, some representation of the set of all possible current states, giving a constant update time, independent of t, the caching principle that keeps an agent's per percept cost from growing with its lifespan. Fluence and the frame problem. Effect axioms alone lose what stays the same. Successor state axioms, big O of mk, fixed representational and inferential versions. Qualification problem, unbounded exceptions to action preconditions. Logic has no complete solution. Probability summarizes them. Hybrid agent, knowledge-based inference for safety, A-star search for routes, goal priority planning, and cached belief state estimation for constant update time. Chapter 8. First-order logic. Representation revisited. Chapter 8 opens by asking what a representation language can do. Programming languages and databases can represent facts. A statement like world 2 equals pit asserts a pit into 2, but what programming languages lack is a general mechanism for deriving fact from other facts. Each update is done by a domain-specific procedure derived by the programmer. This procedural approach can be contrasted with the declarative nature of propositional logic, in which knowledge and inference are separate, and inference is entirely domain-independent. Data structures also lack the easy way to say there's a pit into 2 or 3, partial information, which propositional logic handles, using disjunction and negation. Propositional logic is declarative, expressive enough for partial information, and compositional. The meaning of a sentence is a function of the meaning of its parts, S1, 4 and S1. 2 must mean something built from the meanings of S1, 4 and S1, 2. Not France and Poland drew 1 to 1. But propositional logic as a factored representation lacks the expressive power to concisely describe an environment with many objects. It forces a separate rule per square, B1, 1 left-right arrow, P1, 2 or P2, whereas English says, once and for all, squares adjacent to pits are breezy. English, like first-order logic, is a structured representation. The language of thought digression asks whether natural language could serve as a representation language. The modern view is that natural language serves as a medium for communication rather than pure representation. The meaning of look depends on context, which raises the question of how the context itself can be represented. Natural languages suffer from ambiguity. As Pinker puts it, when people think about spring, surely they are not confused as to whether they are thinking about a season or something that goes boing. The Sapir-Whorf hypothesis, that our understanding of the world is strongly influenced by the language we speak, is examined with real data, Subjects remembered the content of prose with over 90% accuracy, but the exact words a chance, suggesting people interpret the words they read and form an internal nonverbal representation. Googie Yimithir speakers, lacking relative directions, my north arm. Navigate open terrain better. Spanish and German speakers describe the same bridge. Differently, big, dangerous, strong versus beautiful, elegant, fragile. Yet there are measurable but small differences in cognitive processing, but no convincing evidence that this leads to a major difference in worldview. The modern research direction is empirical. fMRI word decoding predicts celery versus airplane 77% of the time, proving that fMRI reveals some level of common representation across people. From the viewpoint of formal logic, representing the same knowledge in two different ways makes absolutely no difference. The same facts are derivable, but one representation might require fewer steps to derive a conclusion. And for learning, the influence of language on thought is unavoidable for any agent that does learning, because theory choice favors the most succinct representation, and that depends on the language used. The resolution is to adopt the foundation of propositional logic and build a more expressive logic on that foundation, borrowing representational ideas from natural language while avoiding its drawbacks. Nouns name objects, verbs and adjectives name relations. Unary relations are properties. N-ary relations relate tuples. And some relations are functions, relations in which there is only one value. For a given input, almost any assertion decomposes into objects and relations. 1 plus 2 equals 3. Objects 1, 2, 3. Relation equals. Function plus. Evil King John ruled England in 1200. Squares neighboring the Wumpus are smelly. First-order logic is built around objects and relations, and has been important to mathematics, philosophy, and artificial intelligence precisely because those fields, and indeed, much of everyday human existence, can be usefully thought of as dealing with objects and the relations among them. And it can also express facts about some or all of the objects in the universe, representing general laws. The primary difference from propositional logic is the ontological commitment, what it assumes about the nature of reality. Propositional logic assumes that there are facts that either hold or do not hold in the world. First-order logic assumes more, namely, that the world consists of objects with certain relations among them, so its formal models are more complicated. This commitment is a strength where propositions have clear boundaries, mathematics, the Wumpus world, but a weakness in the real world where many propositions have vague boundaries. Is Vienna a large city? It depends who you ask. Responses include refining the representation, fuzzy logic, degrees of truth. Vienna is a large city, true to degree 0.8, at the cost of harder inference, and embedding concepts in multidimensional space. Special-purpose logics make further commitments. Temporal logic gives time first-class status. Higher-order logic treats relations and functions as objects themselves, and is strictly more expressive than first-order logic. A logic is also characterized by its epistemological commitment, the states of knowledge it allows. Propositional and first-order logic have three possible states of knowledge: believe true, believe false, no opinion, while systems using probability theory can have any degree of belief, ranging from 0 to 1, a degree of belief that must not be confused with fuzzy logic's degree of truth. Objects, relations, functions, the ontological inventory of first-order logic, from which almost any assertion can be built. Ontological versus epistemological commitment. What exists in the world versus what an agent believes. FOL commits to objects and relations, with three belief states per fact. Compositionality and structure. Sentence meaning is a function of parts. FOL matches English's once-and-for-all conciseness. Syntax and semantics of first-order logic. Models for first-order logic contain objects. A model's domain is the set of objects or domain elements it contains, required to be non-empty. Formally, a relation is just the set of tuples of objects that are related. Unary relations are properties, and functions map tuples to objects. The work model of Figure 8.2 holds 5 objects: Richard the Lionheart, King John, their left legs, and a crown. 2 binary relations: brother, on head. 3 unary relations: person, king, crown, and a left leg function. The technicality that first-order models require total functions. The crown must have a left leg, is waved off, as long as one makes no assertions about the left legs of things that have no left legs. These technicalities are of no import. The syntax uses 3 kinds of symbols: constant symbols standing for objects, predicate symbols for relations, and function symbols for functions. With variables, both quantifiers, for all, there exists, and connectives. Terms denote objects. Atomic sentences state relations among terms. Complex sentences combine them with connectives. Quantifiers bind variables. The semantics is given by interpretations. Each constant is mapped to a domain element. Each predicate to the set of tuples it is true of. Each function to a mapping, and quantifier truth conditions follow. For all xp of x holds IFFP holds of every element. There exists xp of x IFF. Some element satisfies it. Equality is a special predicate with a fixed meaning. Nested quantifiers bind in the natural order. The key facts are that first-order models are much more interesting than propositional ones because they have objects in them, and that the truth of a sentence is determined by the interpretation's link between vocabulary and domain. Using first-order logic, with the language defined, the chapter turns to writing axioms in simple domains, beginning with the tell/ask interface. Tell KB King John and tell KB for all x King X person X are assertions. Ask KB person John returns true. Asking there exists x person X is rather like answering can you tell me the time? With yes, hence ask vars, which yields a stream of answers as substitutions or binding lists. X/John, X/Richard. Ask vars is usually reserved for knowledge bases consisting solely of horn clauses, because in such knowledge bases, every way of making the query true will bind the variables to specific values, which is not true of general first-order logic. The kinship domain shows definitions bottoming out at primitives. Mother, C, equals M left-right arrow female, M, and parent MC. Husband, HW, left-right arrow male, H, and spouse, HW. Parent and child are inverses. Grandparent, G, C, left-right arrow there exists P parent, G, P, and parent, P, C, sibling X, Y. Left-right arrow X is not equal to Y, and there exists P parent, P, X, and parent, P, Y. These axioms define predicates in terms of other predicates, analogous to the way in which software packages are built up by successive definitions of subroutines from primitive library functions, with no unique primitive set. Some sentences are theorems rather than axioms. Siblinghood symmetry follows from the defining axiom. And from a practical point of view, theorems are essential to reduce the computational cost of deriving new sentences. Without them, a reasoning system has to start from first principles every time, rather like a physicist having to rederive the rules of calculus for every new problem. Some predicates have no complete definition. There is no obvious definitive way to complete for all x person X, so we write partial specifications for all x person X, for all x person X, and axioms can also be just plain facts like male, Jim, describing specific problem instances. A missing axiom betrays itself. From spouse, Jim, Laura, one expects spouse, George, Laura, under most countries' laws, but this does not follow from the axioms given earlier, a sign that an axiom is missing. Numbers, sets, and lists show how a large theory can be built up from a tiny kernel of axioms. The theory of natural numbers needs one predicate, nat number, one constant, 0, one function, s, successor, and the Peano axioms. Nat number of 0, for all in nat number of n arrow, are nat number of s of n. For all in 0 is not equal to s of n. For all in m is not equal to n arrow. Our s of m is not equal to s of n. Addition reduces to repeated successor. Plus 0 m equals m and plus s of m n equals s of plus m n, using infix notation as syntactic sugar, an extension to or abbreviation of the standard syntax that does not change the semantics, desugarable to ordinary first-order logic. Thus, the whole of number theory, including cryptography, can be built up from one constant, one function, one predicate, and 4 axioms. Sets are axiomatized via membership, subset, union, intersection, and add. The only sets are the empty set, and those made by adding something to a set. And 2 sets are equal if and only if each is a subset of the other. Lists differ from sets in being ordered with repetition, and use the list vocabulary, nil, cons, append, first, rest, find. A list like ABC is sugar for cons, A cons, B cons, C nil. The Wumpus world in first-order logic is far more concise. Percept sentences carry the time. Percept of stench breeze glitter none 5. Perception rules like for all TSG to WC percept of S breeze G WCT arrow. Our breeze of T exhibit a trivial form of the reasoning process called perception. Notice the quantification over time T. In propositional logic, we would need copies of each sentence for each time step. Simple reactive behavior is a quantified implication. For all T glitter of T arrow. Our best action of grab T. The world itself benefits from complex terms. Squares as lists X, Y, let adjacency be defined once. We could name each pit, but this would be inappropriate. There is no reason to distinguish among pits, so a unary predicate pit is used. Since there is exactly one wumpus, a constant wumpus is just as good as a unary predicate, and perhaps more dignified from the wumpus's viewpoint. The decisive gains. Whereas propositional logic necessitates a separate axiom for each square, first-order logic just needs one axiom for all S breezy of S arrow. L. R there exists are adjacent of our S in pit of R, and by quantifying over time, we need just one successor state axiom for each predicate, rather than a different copy for each time step, e.g. for all T have arrow of T plus one arrow. L. R have arrow of T and not action of shoot T. The first-order logic formulation is no less concise than the original English language description. Assertions, queries, substitutions, tell, ask vars with binding lists, the interface to a first-order knowledge base. Definitions and theorems. Axioms define predicates from primitives. Theorems cut reasoning cost but add no conclusions. P&O arithmetic in a kernel. 0, successor, and 4 axioms build all of number theory. Concise wumpus world. Complex terms, squares as lists, one adjacency axiom, one successor state axiom per fluent. Knowledge engineering in first-order logic. The chapter closes with the general process of knowledge-based construction. Knowledge engineering. A process in which a knowledge engineer is someone who investigates a particular domain, learns what concepts are important in that domain, and creates a formal representation of the objects and relations in the domain, illustrated with an electronic circuit domain. The 7 steps are: 1. Identify the questions. Delineate the range of questions that the knowledge base will support and the kinds of facts that will be available analogous to P's. 2. Assemble the relevant knowledge, possibly by extracting it from experts. Knowledge acquisition. Understanding how the domain actually works. 3. Decide on a vocabulary, predicates, functions, constants, resulting in the ontology of the domain, a particular theory of the nature of being or existence that determines what kinds of things exist, but does not determine their specific properties and interrelationships. For encode general knowledge as axioms, which pins down the meaning of the terms, often revealing gaps that force iteration back to step 3. 5. Encode a description of the problem instance. If the ontology is well thought out, this step is easy. 6. Pose queries to the inference procedure and get answers. This is where the reward is avoiding writing an application. Specific solution algorithm. 7. Debug and evaluate the knowledge base. The answers will be correct for the knowledge base as written, but they will not be the ones that the user is expecting. Missing or weak axioms are found by noticing places where the chain of reasoning stops unexpectedly. A one-way diagnostic rule can never prove the absence of wumpuses. Incorrect axioms can be identified because they are false statements about the world. For all X number of legs. X for mammal. X is false for reptiles, amphibians, and tables, and without objective measurement. It is too easy to convince yourself that the job is done. The circuit ontology demonstrates the payoff. For verifying functionality, we do not need to talk about the wires themselves. All that matters is the connections between terminals, illustrating that the ontology depends on the task. Debugging faulty circuits would need wires. Timing faults would need delays. Profit would need cost. The vocabulary. Gates as constants with gate, x1, and type, x1, equals XOR, a function because a gate has exactly one type. Terminals via terminal, x and in 1, x1, out and c. Connectivity via connected, out, 1, x1, and 1, x2, and signals as objects 1 and 0 with a function signal, t. A choice that lets queries ask, what are all the possible values of the signals at the output terminals? One sign that we have a good ontology is that we require only a few general rules. If 2 terminals are connected, they carry the same signal. Every terminal signal is 1 or 0. Connected is commutative. There are 4 gate types. Each gate type's output condition is one biconditional. An AND's output is 0 if any input is 0. An OR is 1 if any input is 1. An XOR is 1 if its inputs differ. A NOT's output differs from its input. Arity axioms. Terminals exist up to arity and nothing beyond it. Arity and gates, terminals, and signals are all distinct. This compact ontology supports the circuit's adder verification questions entirely by logical inference. 7-step knowledge engineering questions knowledge ontology / vocabulary axioms, instance queries, debug and evaluate, iterating as gaps appear. Ontology depends on task. Verifying gate-level function needs connections, not wires. Other tasks would need delays, faults, or cost. Circuit vocabulary, gates as constants with type, terminals via in/out functions, signals as objects. So queries range over possible signal values. Quote, one sign that we have a good ontology is that we require only a few general rules, which can be stated clearly and concisely. Section 8.4.2. Chapter 9. Inference in first-order logic. Propositional versus first-order inference. Chapter 9 answers a natural question. How do we do inference in first-order logic? One way is to convert to propositional logic and use the algorithms of Chapter 7. The 2 instantiation rules bridge the gap. Universal instantiation UI lets us infer any sentence obtained by substituting a ground term, a term without variables, for universally quantified variable. From for all x king, x, and greedy x, evil x, infer king, John, and greedy, John, evil, John, or with a ground term father, John. Existential instantiation, EI, replaces an existentially quantified variable with a single new constant symbol that does not appear elsewhere in the knowledge base. From there exists x crown, x, and on head, x John, infer crown, C1, and on head, C1 John. Basically, the existential sentence says there is some object satisfying a condition, and applying the existential instantiation rule just gives a name to that object. The Skolem constant, the name e for the number a little bigger than 2.71828, satisfying d, xy/dy equals xy, which would be a mistake to name pi. Whereas UI can be applied many times, e need only be applied once, and the existential sentence is then discarded. Propositionalization, replacing a universal sentence by the set of all possible instantiations and ground atoms by proposition symbols, turns first-order inference into propositional inference and can be made completely general. The problem, when a knowledge base includes a function symbol, the set of possible ground term substitutions is infinite. Father, father, father John. Herbrand's theorem, 1930, rescues completeness. If a sentence is entailed by the original first-order knowledge base, then there is a proof involving just a finite subset of the propositionalized knowledge base. Generate instantiations depth by depth until a proof appears. This is complete, given that the space of possible models is infinite, but the cost is profound. What happens when the sentence is not entailed? Can we tell? Well, for first-order logic, it turns out that we cannot. Our procedure can go on and on. We will not know whether it is stuck in a hopeless loop or whether the proof is just about to pop out. This is very much like the halting problem. Turing and Church proved the inevitability. The question of entailment for first-order logic is semi-decidable. That is, algorithms exist that say yes to every entailed sentence, but no algorithm exists that also says no to every non-entailed sentence. Universal/existential instantiation. Ground term substitution versus naming a witness with a fresh Skolem constant. Propositionalization and Herbrand's theorem. Finite depth instantiation is complete, but only because entailment is semi-decidable. No algorithm says no to every non-entailed sentence. Unification and first-order inference. Propositionalization generates many unnecessary instantiations. The remedy is lifted inference, an approach that uses just the one rule. Reasoning that x/John solves evil x by finding some x such that x is a king and x is greedy. Generalized modus ponens captures this. For atomic sentences p sub 1, p sub n, and an implication p sub 1 and p sub n arrow. RQ. where there is a substitution theta such that subsd of theta p sub equals subsd of theta p sub I for all I, conclude subsd of theta q. The worked example unifies king x, greedy x, with king John, greedy y under x/John, y/John to infer evil John. A soundness proof shows it is a lifted version of modus ponens. It raises modus ponens from ground variable-free propositional logic to first-order logic, and the key advantage of lifted inference rules over propositionalization is that they make only those substitutions that are required. Lifted inference requires unification, finding substitutions that make different logical expressions look identical. Unify of PQ equals theta, where subsd of theta P equals subsd of theta Q. The nose examples show the mechanics and the pitfalls. Unify of nose of John x nose of John Jane equals x over Jane. Unify of nose of John x nose of y mother of y equals y over John x over mother of John. But unify of nose of John x nose of x Elizabeth fails. The problem arises only because the two sentences happen to use the same variable name, fixed by standardizing apart, renaming x to x sub 17. Demonstrating that everyone knows Elizabeth should let us infer John knows Elizabeth. Finally, there could be more than one such unifier. Unify of nose of John x nose of yz could return y/John x/z or y/John x/John z/John. But the first unifier is more general than the second because it places fewer restrictions on the values of the variables, and every unifiable pair of expressions has a single most general unifier, MGU, that is unique up to renaming and substitution of variables. Generalized modus ponens. The lifted version of modus ponens. Unify premises with facts, substituting on both sides. Infer the substituted consequent. Unification and the MGU. Unify finds a substitution, making expressions identical. Standardizing apart avoids name clashes, and the most general unifier is unique up to renaming. Forward chaining. Forward chaining for first-order definite clauses inverts the instantiation explosion into an incremental, sound, and for datalog, complete procedure. First-order definite clauses are disjunctions of literals of which exactly one is positive, either atomic or an implication whose antecedent is a conjunction of positive literals and whose consequent is a single positive literal, with existential quantifiers disallowed and universal quantifiers implicit, greedy. Y means everyone is greedy. The chapter's crime problem is the running example. The law says that it is a crime for an American to sell weapons to hostile nations. The country No-No, an enemy of America, has some missiles, and all of its missiles were sold to it by Colonel West, who is American. Definite clauses represent it. American, X, and weapon, Y, and sells X, Y, Z, and hostile, Z criminal X, owns, No-No, M1, and missile, M1, from existential instantiation. Missile X and owns, No-No X sells, West X No-No, missile X, weapon X, enemy X, America, hostile X, plus the facts American, West, and enemy. No-No, America. This is a datalog knowledge base, first-order definite clauses with no function symbols, whose absence of functions makes inference much easier. The simple algorithm FWL-FC-ASK starts from known facts and triggers all the rules whose premises are satisfied, adding their conclusions to the known facts, repeating until the query is answered or no new facts are added. A fact is not new if it is just a renaming of a known fact. 2 iterations crack the crime problem. First iteration adds cells, West, M1, No-No, weapon, M1, and hostile, No-No. On the second rule, 9.3, fires with X/West, Y/M1, Z/No-No, and the inference criminal, West, is added. The proof tree's fixed point, a knowledge base in which every sentence that could be concluded is already contained explicitly. FWL-FC-ASK is sound. Each inference is generalized modus ponens and complete for definite clause knowledge bases. For datalog, at most p.n to the k distinct ground facts bound the iterations. For general definite clauses with functions, an infinite number of facts may be generated. The P&O axioms churn out nat number, S 0, semi-decidability again. Efficient forward chaining attacks, 3 inefficiencies. Matching every rule against every fact. Rechecking every rule each iteration. and generating irrelevant facts. Matching is where CSP reasoning returns. The conjunct ordering problem. Match the rarest conjunct first, per MRV, is NP-hard but heuristically handled, and the connection between this pattern matching and constraint satisfaction is actually very close. We can express every finite domain CSP as a single definite clause together with some associated ground facts. The map coloring CSP becomes one clause whose conclusion colorable follows only if the CSP has a solution, and because CSPs in general include 3 SAT problems as special cases. Matching a definite clause against a set of facts is NP-hard. 3 consolations. Data complexity is polynomial when rule size and arity are bounded. Tractable CSP subclasses, tree structure constraint graphs, give tractable matching. And incremental forward chaining uses the observation that every new fact inferred on iteration t must be derived from at least one new fact inferred on iteration t-1 to check rules only when a premise conjunct newly unifies. First-order definite clauses / datalog. Exactly one positive literal. No existential quantifiers. Universal quantifiers implicit. Datalog drops functions. FWLFC ask. Fire rules whose premises match. Add conclusions. Iterate to a fixed point. Sound incomplete for definite clauses. Semi-decidable in general. Matching is CSP hard. Every finite domain CSP is one definite clause. Conjunct ordering uses MRV. Incremental checking exploits the new fact dependency. Backward chaining. Backward chaining works goal-directed, a kind of and or search. The or part because the goal query can be proved by any rule in the knowledge base, and the in part because all the conjuncts in the LHS of a clause must be proved. FWLBC ask fetches all clauses whose right-hand side unifies with the goal, standardizes variables apart, and proves each conjunct of the left-hand side in turn, keeping track of the accumulated substitution as it goes. So by the time the last conjunct, originally hostile Z, is reached, Z is already bound to no-no. The West is a criminal proof tree, shows the depth-first, left-to-right construction. Backward chaining is clearly a depth-first search algorithm, with linear space requirements but corresponding problems with repeated states and incompleteness. Despite these limitations, backward chaining has proven to be popular and effective in logic programming languages. Logic programming is the fruition of the declarative ideal, summed up in Kowalski's equation algorithm equals logic plus control. Prolog is the most widely used such language, a rapid prototyping and symbol manipulation workhorse, compilers, natural language parsing, expert systems. Prolog programs are sets of definite clauses written in a notation somewhat different from standard first-order logic. Uppercase for variables, lowercase for constants, the clause written backwards, criminal, X, American, X, weapon, Y. Cells X, Y, Z, hostile Z. The append program shows the power, append, Y, Y, and append, X, Y. The append X, Y, Z. It describes a relation that holds among 3 arguments, rather than a function computed from 2. So the query append, X, Y, 1, 2, 3, returns all 4 splitting solutions. Prolog's design represents a compromise between declarativeness and execution efficiency, and deviates from standard logical inference. It uses database semantics, unique names, closed world, rather than first-order semantics. Built-in arithmetic is proved by executing code. 5 is X plus Y fails. Built-in predicates have side effects with no counterpart in logic. The occur check is omitted from unification. Some unsound inferences can be made. These are almost never a problem in practice. And depth-first search, with no check for infinite recursion, means some programs that look like valid logic will fail to terminate. The Achilles heel is the mismatch between depth-first search and search trees that include repeated states and infinite paths. The path program, path X, Z, link X, Z, and path X, Z, path X, Y, link Y, Z. In the wrong clause order follows the infinite path, and Prolog is therefore incomplete as a theorem prover for definite clauses, even for datalog programs, though forward chaining halts once the path facts are inferred. Depth-first backward chaining also wastes effort on redundant computation. Finding a path from A1 to J4 took 877 inferences, most of which involve finding all possible paths to nodes from which the goal is unreachable, versus 62 for forward chaining, which is an example of dynamic programming. The synthesis is tabled logic programming. combines the goal-directedness of backward chaining with the dynamic programming efficiency of forward chaining, and is also complete for data log knowledge bases, so the programmer worries less about infinite loops. Database semantics crystallizes Prolog's expressiveness trade-off, the unique names assumption. Every Prolog constant and every ground term refers to a distinct object, and the closed world assumption, the only sentences that are true are those that are entailed. Given course CS 101, course CS 102, course CS 106, course 101, database semantics yields exactly 4 courses, whereas the same assertions in FOL, all we could say is that there are somewhere between 1 and infinity courses. FOL requires the completion, at most 4 courses, and the completion of equality, at least 4 courses, to say the same. For practical purposes, if your problem can be described with database semantics, it is more efficient to reason with Prolog rather than translating into FOL. Backward chaining, and or depth first, goal-directed, linear space but prone to loops and repeated subgoals. Prolog and logic programming. Algorithm equals logic plus control, definite clauses in reverse notation, database semantics, semantic compromises. Tabled logic programming. Caching intermediate results gives forward chaining efficiency with backward chaining goal-directedness, complete for data log. Quote, algorithm equals logic plus control. Section 9.4, Kowalski. Resolution. Resolution is the only one of the 3 families that works for any knowledge base, not just definite clauses, a complete inference procedure for first-order logic, extending the propositional resolution of Chapter 7. The first step converts sentences to conjunctive normal form, where literals can contain variables, which are assumed to be universally quantified. Every sentence of first-order logic can be converted into an inferentially equivalent CNF sentence. The universal sentence for all x for all y animal of y arrow. Are loves of x y arrow. Are there exists y loves of y x passes through the full procedure. Eliminate implications. Move negation inwards, with rules for negated quantifiers. Note how universal quantifier in the premise of an implication has become an existential quantifier. Standardize variables apart. Scolomize. Remove existential quantifiers, but the Scolom entities must depend on x, since each person can fail to love a different animal. We need Scolom functions f of x and g of x, whose arguments are all the universally quantified variables in whose scope the existential quantifier appears. Drop universal quantifiers, distribute, or over, and. The result is much more difficult to read than the original, but humans seldom need to look at CNF sentences. The translation process is easily automated. The resolution inference rule is a lifted version of the propositional resolution rule. 2 clauses standardized apart can be resolved if they contain complementary literals. First-order literals are complementary if one unifies with the negation of the other. The worked example resolves animal of f of x or loves of g of xx with not loves of uv or kills of uv under u/g x v/x to produce animal of f of x or kills of g of xx. The binary resolution rule resolves exactly 2 literals but by itself does not yield a complete inference procedure. Completeness needs first-order factoring. Reduces 2 literals to 1 if they are unifiable. The unifier applied to the entire clause, and the combination of binary resolution and factoring is complete. Example proofs show resolution, proving that KB equals alpha by proving that KB and alpha is unsatisfiable. That is by deriving the empty clause, exactly as in the propositional PL resolution. The crime proof has a single spine beginning with the goal clause, resolving against clauses from a knowledge base until the empty clause is generated. Characteristic of resolution on horn clauses, and the spine's clauses correspond exactly to the consecutive values of the goals variable in the backward chaining algorithm, revealing that backward chaining is just a special case of resolution with a particular control strategy. The second example, did curiosity kill the cat? Exercises scholomization and non-definite clauses with the English paraphrase of the proof. Assume curiosity did not. Jack must have. Tuna is a cat, hence an animal. Anyone who kills an animal is loved by no one. So no one loves Jack, but Jack loves all animals, so someone loves him. Contradiction. For the more general, who killed the cat? The goal is there exists W kills, W, tuna, negated to for all W kills, W, tuna, and resolution with the resulting proof extracts the answer as a binding. CNF conversion. Eliminate, move inwards, standardize apart, scholemize. Existentials become functions of enclosing universals. Drop for all, distribute. Lifted resolution plus factoring. Resolve unifiable complementary literals. Factoring restores completeness. Backward chaining as resolution. Resolution with a goal spine control strategy. The subgoals along the spine trace the backward chaining variable bindings. Quote, backward chaining is just a special case of resolution with a particular control strategy to decide which resolution to perform next. Section 9.5.3. Chapter 10. Knowledge Representation. Ontological Engineering. Chapter 10 turns from how an agent reasons to what content it should hold. How to represent facts about the world. For simple domains, the choice of representation is not that important. Many choices will work, but complex domains such as shopping on the internet or driving a car in traffic need more general and flexible representations. Representing the abstract concepts that recur across domains, events, time, physical objects, beliefs, is sometimes called ontological engineering. The chapter builds an upper ontology, the general framework of concepts, drawn with the general concepts at the top and the more specific concepts below. Anything at the root, branching into abstract objects and generalized events, down to sets, numbers, physical objects, processes, times, moments, and so on. The framework is deliberately modular, analogous to the way that designers of an object-oriented programming framework define general concepts like window, expecting users to use these to define more specific concepts. Two caveats frame the enterprise. First, most generalizations have exceptions or hold only to a degree. Tomatoes are red is useful though some are yellow or orange, but handling exceptions is orthogonal to the task of understanding the general ontology. Second, the general ontology has so far had only limited success. None of the top AI applications make use of a general ontology. They all use special-purpose knowledge engineering and machine learning, and every ontology is a treaty, a social agreement among people with some common motive in sharing. Ontologies arise along four routes. Trained ontologists writing axioms, CYC, importing structured facts from databases, Wikipedia, parsing text, TextRunner, and crowdsourcing common-sense knowledge, OpenMind. The Google Knowledge Graph, with 70 billion facts, answers about a third of Google searches. Two characteristics distinguish general-purpose ontologies. They should be applicable in more or less any special-purpose domain, so no representational issue could be finessed or swept under the carpet. And in any sufficiently demanding domain, different areas of knowledge must be unified. A robot circuit repair system needs electrical, spatial, and temporal reasoning to work equally well for nanoseconds and minutes. Upper ontology, the general framework of concepts, anything physical objects, events, time, into which domain-specific details plug. Ontological engineering is a treaty, a social agreement among stakeholders. General ontologies are hardest because they need the largest agreement. Unification requirement. Knowledge must combine across areas and across scales. Nanoseconds to minutes, angstroms to meters. Categories and objects. Categories organize objects. Although interaction with the world takes place at the level of individual objects, much reasoning takes place at the level of categories. A shopper wants a basketball, rather than a particular basketball, such as BB9. Categories serve to make predictions about objects once they are classified. From a green and yellow mottled, ovoid object in the fruit aisle, one infers that it is a watermelon. From this, one infers that it would be useful for fruit salad. In first-order logic, there are two choices for representing categories: predicates and objects. Reification, turning a proposition into an object, lets a category itself be an object. Member B, basketballs. Abbreviated B is an element of basketballs, and subset, basketballs, balls. Categories organize knowledge through inheritance. If all food is edible and fruit subset of food and apple subset of fruit, we can infer that every apple is edible. Subclass relations organize categories into a taxonomic hierarchy. The taxonomy of about 10 million living and extinct species, many of them beetles, the Dewey Decimal System, taxonomies of occupations. First-order logic states category facts easily. Membership, BB9, is an element of basketballs. Subclass, basketball subset of balls. Properties of all members, for all XX is an element of basketball spherical X. Recognition, orange X and round X in diameter, X equals 9.5x is an element of balls. Weight, this is balls subset of basketballs. In properties of the category as a whole, dogs subset of domesticated species, where domesticated species must be a category of categories. Beyond subclass and membership, categories can be disjoint, exhaustively decomposed, or form a partition. Disjoint, animals, vegetables, exhaustive decomposition, Americans, Canadians, Mexicans, North Americans, not a partition, because some people have dual citizenship. Partition, animals, plants, living things. Definitions can give necessary and sufficient conditions for membership. A bachelor is an unmarried adult male. Those strict logical definitions for categories are usually possible only for artificial formal terms, not for ordinary objects. Physical composition adds the part of relation, transitive and reflexive, ordering parts into hierarchies. Bucharest, Romania, Eastern Europe, Europe, Earth. Composite objects are often characterized by structural relations among parts. A biped is an object with exactly 2 legs attached to a body. A constraint whose notation is a little awkward. We are forced to say that there are 2 legs, that they're not the same, and that if anyone proposes a 3rd leg, it must be the same as one of the other 2. The bunch concept handles composite objects with definite parts, but no particular structure. The apples in this bag weigh 2 pounds cannot be attributed to the set of apples. The set is an abstract mathematical concept that has elements but does not have weight. So bunch of apple 1, apple 2, apple 3 is the composite object with the 3 apples as parts, not elements. Defined by logical minimization, defining an object as the smallest one satisfying certain conditions. Measurements are simple, quantitative measures, quite easy to represent. The universe includes abstract measure objects, so length of L sub 1 equals inches of 1.5 equals centimeters of 3.81, with the units function taking a number as argument. Conversion equates multiples. Centimeters of 2.54 to D equals inches of D. $1 is not a dollar bill. It is a price, and inches of 0, while equal to centimeters of 0, are not identical to other 0 measures, such as seconds of 0. Where measures have no agreed scale, difficulty, deliciousness, beauty, the most important aspect of measures is not the particular numerical values, but the fact that measures can be ordered. So Norvig's exercises being tougher than Russell's suffices to decide which to do, even though no numerical values for difficulty were ever used, the basis of qualitative physics. Things and stuff confront individuation. There is no obvious number of butter objects, because any part of a butter object is also a butter object, unlike the aardvark. English distinguishes count nouns, aardvarks, wholes, from mass nouns, butter, water, energy. One ontology represents lumps of stuff as objects. Butter 3 is an element of butter. With any part of a butter object is also a butter object. The deep principle. Intrinsic properties, density, boiling point, flavor, color, ownership, are retained under subdivision, while extrinsic ones, weight, length, shape, are not. A category of objects that includes in its definition only intrinsic properties is then a substance or mass noun. A class that includes any extrinsic properties is a count noun. A pound of butter is not a kind of stuff. If we cut a pound of butter in half, we do not, alas, get 2 pounds of butter. Reification. Treating categories as objects opens inheritance and taxonomy. Classifications enable prediction. Partition and part of, disjointness, exhaustive decomposition, composite objects via transitive part of and structural part relations. Measures and stuff, ordered, not necessarily numeric, measures. Intrinsic properties define substance / mass nouns, extrinsic ones count nouns. Events. Chapter 10 brings events into the ontology as first-class objects, since time index propositions alone leave too much structure implicit. Actions, things that happen, like shoot, and fluence, aspects that change, like havero, were both propositions with time indices. Reifying events as objects with an event calculus-like structure lets the same event be related to agents, objects, times, and places. The fragmentary semantic network representation of the fly event. Fly events with member fly 17. Its agent Shankar, origin New York, destination New Delhi, and time yesterday, shows an event object carrying its participants as relations, so that multiple events can share participants and be reasoned about in aggregate. The chapter previews that physical objects will come under generalized events. An object's history through time is itself a spatiotemporal event, which is why the upper ontology's physical objects branch connects to the event structure. Mental objects and modal logic. Agents so far have beliefs and can deduce new beliefs, but none of them has any knowledge about beliefs or about deduction. The chapter builds a model of the mental objects that are in someone's head and of the mental processes that manipulate those mental objects enough to conclude that mother knows whether or not she is sitting. The propositional attitudes, believes, knows, wants, informs, do not behave like normal predicates. The Superman problem exposes it. From knows, Lois, can fly, Superman. In Superman equals Clark, logical equality, reasoning forces knows, Lois, can fly, Clark, which is wrong because in most versions of the story, Lois does not know that Clark is Superman. Ordinary logic is referentially transparent. It doesn't matter what term a logic uses to refer to an object. Attitudes need referential opacity. Terms used do matter because not all agents know which terms are coreferential. More reification, separate Clark/Superman objects per believer, makes the sentences verbose and clumsy. Modal logic solves this by adding special modal operators that take sentences rather than terms as arguments. A knows P is written KAP. The semantics uses possible worlds connected by accessibility relations, one per modal operator. World W1 is accessible from world W0 with respect to the modal operator Ka if everything in W1 is consistent with what A knows in W0. A knowledge atom KAP is true in world W if and only if P is true in every world accessible from W, letting logic reason about nested knowledge. Lois knows that Clark knows whether Superman's identity is Clark, and about quantifier/knowledge interplay. Bond knows that someone is a spy is ambiguous between there exists X K Bond spy, X, a particular someone, and counter for Bond there exists X spy, X. Bond just knows that there is at least one spy. Axioms for knowledge follow. Knowledge is closed under implication, cap and ka, PQ, KQ. So every agent knows every proposition P is either true or false. Knowledge is justified true belief, giving cap P. Logical agents introspect on their own knowledge, cap ka cap. The problem with the modal approach is logical omniscience. If an agent knows a set of axioms, then it knows all consequences of those axioms, on shaky ground even for the somewhat abstract notion of knowledge, and seems even worse for belief. Attempts at limited rationality, no more than K reasoning steps, no more than S seconds, have been generally unsatisfactory. Other modal logics add operators for possibility and necessity, and linear temporal logic adds X, next, F, eventually/finally, G, always/globally, and U, until the choice of which logic to use is similar to the choice of which programming language to use. Propositional attitudes and referential opacity. Believe/knows take reified fluence as terms. Equality substitution is invalid inside them. Possible world semantics. K_A, P holds IFF, P holds in every world accessible to enabling nested knowledge and quantifier/knowledge disambiguation. Logical omniscience. Modal logic assumes agents know all consequences of their axioms, a recognized limitation, unresolved by limited rationality patches. Quote, it is said, going back to Plato, that knowledge is justified true belief. Section 10.4. Reasoning systems for categories. Two closely related families of systems make category reasoning efficient. Semantic networks give graphical aids for visualizing a knowledge base and efficient algorithms for inferring properties of an object on the basis of its category membership, and description logics give a formal language for constructing and combining category definitions and efficient algorithms for deciding subset and superset relationships between categories. The semantic network debate originated in Peirce's 1909 Existential Graphs. The logic of the future, the long-running debate, obscured the fact that semantic networks are a form of logic, strip away the human interface, and the underlying concepts, objects, relations, quantification, and so on, are the same. A typical network displays objects and categories in ovals and boxes with labeled links. Member of between Mary and female persons, sister of between Mary and John, subset of between categories. The hidden traps are the ones McDermott's artificial intelligence meets natural stupidity, named categories do not have mothers or legs. Has mother is a relation between a person and his or her mother, and categories do not have mothers. So a double-boxed link, For all x, x is an element of persons there exists y, has mother, x, y, and y is an element of female persons, is needed for properties of members, and properties of the category as a whole must be distinguished from properties of members. Inheritance reasoning follows member of, then subset of links up the hierarchy to find a property. Mary inherits 2 legs from persons, and the simplicity and efficiency of this inference mechanism, compared with semi-decidable logical theorem proving, has been one of the main attractions of semantic networks. Multiple inheritance complicates this. An object in more than one category may find 2 or more conflicting values up different paths, the seeds of the Nixon diamond. Semantic networks are logic. Nodes, links, and inheritance implement objects, relations, and efficient property inference, with careful separation of member properties from category properties. Multiple inheritance. Conflicting inherited values along different subset paths pose the problems default reasoning must resolve. Reasoning with default information. Defaults are pervasive. People have 2 legs can be overridden by more specific information, such as that Long John Silver has 1 leg. The chapter studies the semantics of defaults, not just the procedural override mechanism. Default reasoning is non-monotonic. The set of beliefs does not grow monotonically over time as new evidence arrives. The car with 4 wheels example captures the phenomenology. One is normally willing to believe that it has 4 wheels even though only 3 are visible. And if new evidence arrives, the owner carrying a wheel, the car is jacked up, the conclusion can be retracted. 2 extensively studied, non-monotonic logics follow. Circumscription can be seen as a more powerful and precise version of the closed world assumption. Specify predicates, assumed to be as false as possible. For birds fly, introduce abnormal 1 and right bird, x, and abnormal 1, x, flies, x. Circumscribing abnormal 1 lets the reasoner assume abnormal 1, x, unless known true. So flies. Tweety follows unless abnormal 1, Tweety, is asserted. Circumscription is an example of a model preference logic. A sentence is entailed with default status if it is true in all preferred models. Here, those with fewer abnormal objects. The Nixon diamond. Nixon, both Quaker, default pacifist, and Republican, default not pacifist, leaves 2 preferred models, so the circumscriptive reasoner remains properly agnostic, and prioritized circumscription can prefer religious over political beliefs. Default logic writes default rules. Bird x, flies x, /flies x means if bird x is true, and if flies x is consistent with the knowledge base, then flies x may be concluded by default. Generally P, J1, J/C with a prerequisite P, justifications G. If any one of them can be proven false, then the conclusion cannot be drawn. And conclusion C. The meaning is given via extensions, a maximal set of consequences of the theory, yielding 2 extensions for the Nixon diamond, 1 pacifist, 1 not. Open problems remain. What false default rules mean? What a good set of default rules is a serious problem of non-modularity. And how can beliefs that have default status be used to make decisions? This is probably the hardest issue, resolvable partly by reading defaults as threshold probability statements. The probability that my brakes are okay is sufficiently high that the optimal decision is for me to drive without checking. So default's appropriateness shifts with the decision context, even without new evidence. Truth maintenance systems handle belief revision. Many of the inferences drawn will have only default status and will have to be retracted in the face of new information. A naive approach numbers sentences P1, Pn, and, on retract, pi, reverts to before pi. Simple and consistent. But retracting pi requires retracting and reasserting n-i sentences, impractical for large databases. The justification-based TMS, JTMS, annotates each sentence with a justification consisting of the set of sentences from which it was inferred. So retract, P deletes exactly those sentences for which P is a member of every justification. Q survives if it also has the justification R, PQ. A sentence losing all justifications is marked as being out rather than deleted, so the JTMS retains all the inference chains and need not rederive sentences when a justification becomes valid again. TMSs also speed up the analysis of multiple hypothetical situations. Choosing Romanian Olympic sites, retracting site, athletics, Bucharest. For CBU avoids redoing all reasoning. The assumption-based TMS, ATMS, represents all the states that have ever been considered at the same time, giving each sentence a label, a set of assumption sets, so the sentence is true just in those cases in which all the assumptions in one of the assumption sets are true. TMSs also generate explanations. For car won't start. An ATMS can make assumptions, no gas, battery dead, and read off the label which assumption sets justify the sentence, preferring minimal explanations. The computational complexity of the truth maintenance problem is at least as great as that of propositional inference. That is, NP hard, so you should not expect truth maintenance to be a panacea. Non-monotonicity and defaults. Conclusions held by default. The car with four wheels example shows how new evidence retracts them. Circumscription versus default logic. Minimize abnormal objects to prefer models, or write prerequisite/justification/conclusion rules with extensions. Truth maintenance. JTMS keeps justifications for efficient retraction. ATMS labels sentences with assumption sets for hypothetical world switching. Explanations read off minimal justifying assumption sets. Chapter 11. Automated planning. Definition of classical planning. Chapter 11 addresses the limitations of search and logical agents. Both require ad hoc heuristics for each new domain, and both need to explicitly represent an exponentially large state space. The Wumpus forward move axiom had to be repeated for all four agent orientations, t-time steps, and n to the second current locations. Planning responds with a factor representation using PDL, the planning domain definition language, which allows us to express all four tn to the second actions with a single action schema, and does not need domain-specific knowledge. Classical planning is finding a sequence of actions to accomplish a goal in a discrete, deterministic, static, fully observable environment. In PDL, a state is a conjunction of ground atomic fluents. Ground equals no variables. Fluent equals an aspect that changes. Using database semantics, the closed world assumption, unmentioned fluents are false. And unique names, truck1 is not equal to truck2. An action schema, name, variable list, precondition, and effect, each a conjunction of literals, represent a family of ground actions. Instantiating constants yields a ground action. An action is applicable in state S if S entails its precondition. The result is the addList/delete list update result of S A equals S minus DL of a union ADD of A. A domain is a set of schemas. A problem adds an initial state and a goal, a conjunction of literals, possibly with variables. The goal out of C sub 1 SFO and not out of C sub 2 SFO and out of P SFO refers to any state in which cargo C sub 1 is at SFO, but C sub 2 is not, and in which there is a plane at SFO. The air cargo domain, load, unload, fly, shows the subtlety of maintaining the at predicate. When a plane flies from one airport to another, all the cargo inside the plane goes with it. But PDL does not have a universal quantifier, so the solution is to say cargo ceases to be at anywhere when it is in a plane. The cargo only becomes at the new airport when it is unloaded at really means available for use at a given location. The spare tire problem, remove, put on, leave overnight, is a four-action classic whose worst neighborhood makes the effect of leaving it overnight that the tires disappear. The blocks world, a set of blocks on a table, stackable one at a time by a robot arm that can hold only one block, introduces the clear predicate, true, when nothing is on X to stand in for the forbidden universal quantifier, and shows the interplay of move and move to table. When X is the table should not become clear, so move requires block B and block Y, and the interpretation of clear, X. There's a clear space on X to hold a block. Clear, table, will always be true. PDL action schemas. One schema expresses a family of ground actions via add/delete lists. The closed world and unique names assumptions define state semantics. Air cargo, spare tire, blocks world, the classic domains. Each reveals a representation lesson. Maintaining at, clear is a stand-in for universals. Algorithms for classical planning. Planning problems suggest three search directions. Forward, progression, search from the initial state through the space of states. Backward, regression, search from the goal, looking for the initial state, and translating the problem into logical sentences for an inference algorithm. Forward state space search, applying any chapter 3 of 4 heuristic algorithm to ground states. Ground action schemas by unifying the current state against preconditions, with any variable in the effect must also appear in the precondition, guaranteeing no variables survive instantiation. The air cargo numbers expose the branching factor problem. 10 airports, 5 planes, and 20 parcels each gives a minimum of 450 actions and a maximum of 10,450 per state, so heuristic guidance is essential. Backward regression. Search works from the goal state description toward the initial state, using the inverse of actions rather than ground state transitions. Instead of asking, what states can I reach? It asks, given the goal, what state must I have been in before this action? An action is relevant to a goal G if its effects are consistent with G. The regression of G through it produces the state that must have held before A. This can be dramatically more focused than progression because irrelevant actions are never even considered, and for problems with many irrelevant actions, like the air cargo domain with its 10,450 action branching factor, regression prunes most of the space. The asymmetry between progression and regression mirrors the CSP distinction between forward checking and the backward search of the blocks world. Both are valid, and heuristic quality decides which wins. The third family, planning as satisfiability, SATPlan, encodes the problem into a set of logic sentences to which we can apply a logical inference algorithm, translating planning into a propositional satisfiability problem that modern SAT solvers attack. The encoding creates variables for each fluent and time step and clauses requiring that an action is taken at each step, preconditions hold, and effects follow, then hands the CNF to a DPLL-style solver. If a model is found, its action literals decode into the plan. The SATPlan approach exploits the enormous engineering invested in SAT solvers, Chapter 7, and has proven highly effective in the international planning competition. Progression versus regression, forward state-space search on ground states, or backward search whose inverse actions prune irrelevant actions. Both need heuristics. Planning as SAT. Encode the problem as CNF and hand it to a SAT solver. Models decode into plans. Heuristics for planning. The gain of factor representations is domain-independent heuristics. By definition, there is no way to analyze an atomic state, but planning's factored states make relaxation automatic. Two main relaxations add edges to the graph, making it strictly easier to find a path. The ignore preconditions heuristic drops all preconditions, so every action is always applicable and any single goal fluent can be achieved in one step. The refined version removes all preconditions and all effects except goal literals, reducing the estimate to a set cover problem, which is NP-hard, though a greedy algorithm returns a cover within a factor of log n of the true minimum, at the cost of admissibility. Ignoring selected preconditions recovers the Chapter 3 heuristics. Removing blank and adjacent from slide gives misplaced tiles. Removing only blank gives Manhattan distance. It is easy to see how these heuristics could be derived automatically from the action schema description. The ease of manipulating the action schemas is the great advantage of the factored representation. The ignore delete list heuristic removes all negative effects, making it possible to make monotonic progress towards a goal. No action will ever undo progress made by another action. Optimal relaxed solutions are still NP-hard, but hill climbing finds approximations, and the relaxation has no local minima in figure 11.6 state spaces. Domain-independent pruning exploits structure. Symmetry reduction prunes all symmetric branches of the search tree except for one. The dozen blocks tower has one 10-order first-step variants that are all equivalent, and reducing this makes the difference between intractable and efficient solving. Forward pruning restricts attention to preferred actions, steps of a relaxed plan solution, or actions achieving its preconditions. Serializable subgoals. An order of subgoals such that the planner can achieve them in that order without having to undo any of the previously achieved subgoals. Allow backtracking-free solution. Build towers bottom to top. The remote agent planner found spacecraft command propositions serializable, enabling it to be fast enough to control the spacecraft in real time, something previously considered impossible. State abstraction is the second relaxation family, a many-to-one mapping from states to the abstract representation. Ignoring some fluents reduces the air cargo space from 10 to the 405th to 10 to the 11th states, and the abstract solution, shorter than a solution in the original space, is an admissible heuristic, easy to extend by adding additional load and unload actions. Decomposition and the subgoal independence assumption approximate the cost of solving a conjunction of subgoals by the sum of the costs of solving each subgoal independently. Optimistic and inadmissible when subplans interact negatively or if subplans contain redundant actions. Taking the max of subgoal costs is always admissible. The system FF, fast forward, combines ignore delete lists with a planning graph, hill climbing, running breadth first search from the current state to escape local maxima, and a greedy best first fallback. Relaxation heuristics, ignore preconditions, ignore delete lists, subgoal summation, domain independent because the factored schemas are manipulable. Pruning and abstraction, symmetry reduction, preferred actions, serializable subgoals, and fluent dropping abstractions cut the search space by orders of magnitude. FF, ignore delete lists plus planning graph plus hill climbing, a state-of-the-art forward searcher. Hierarchical planning. Atomic action planning is fine if we're planning a vacation and the actions are at the level of fly from San Francisco to Honolulu, but at the motor control level of bend the left knee by 5 degrees, we would need to string together millions or billions of actions. Hierarchical decomposition, an idea that pervades almost all attempts to manage complexity, reduces each level to a small number of activities at the next lower level, so the computational cost of finding the correct way to arrange those activities for the current problem is small. The formalism is hierarchical task networks. HTN primitive actions have standard schemas, and a high-level action, HLA, like go, home, SFO, has one or more possible refinements into a sequence of actions, each of which may be an HLA or a primitive action. The chapter shows go, home, SFO, refining to drive plus shuttle or to taxi, and recursive navigate refinements in the vacuum world. HLAs embody knowledge about how to do things. Buying milk, sitting down, and moving the night to E4 not to be considered. A refinement of only primitives is an implementation. A high-level plan achieves the goal, if at least one of its implementations achieves the goal. The at least one is crucial. Not all implementations need to achieve the goal, because the agent gets to decide which implementation it will execute, unlike non-deterministic planning where nature does and all outcomes must work. An HLA with exactly one implementation can be treated as a primitive. The right collection of HLAs can result in the time complexity of blind search dropping from exponential in the solution depth to linear. Searching for primitive solutions is the standard HTN formulation with a single top-level action act. Provide one refinement of act with steps, AI, act for each primitive action, a recursive definition that lets us add actions, plus one empty refinement whose precondition is the goal. If the goal is already achieved, then the right implementation is to do nothing. The algorithm repeatedly chooses an HLA in the current plan and replaces it with one of its refinements until the plan achieves the goal, considering plans in order of depth of nesting of the refinements, rather than number of primitive steps. This hierarchical search explores the space of sequences that conform to the knowledge contained in the HLA library about how things are to be done, and a great deal of knowledge can be encoded, not just in the action sequences, but also in the preconditions for the refinements. The payoff is real and industrial. O-Plan, which combines HTN planning with scheduling, produced a 30-day schedule with 3 8-hour shifts a day, involving tens of millions of steps for Hitachi's 350 product, 35 machine, 2,000 operation production line. The idealized complexity analysis is striking. With D primitive actions, non-hierarchical forward search costs big O of B to the D. With a regular refinement structure, our refinements per HLA, each into K actions. The number of decomposition trees is R to the D1 over K1, so keeping R small and K large takes the KTH root of the non-hierarchical cost. This is not always possible. Long action sequences that are usable across a wide range of problems are extremely rare. The plan library can be constructed by learning. After the excruciating experience of constructing a plan from scratch, the agent can save the plan in the library as a method, generalizing away problem-specific detail. It seems to us inconceivable that humans could be as competent as they are without some such mechanism. Searching for abstract solutions refines HLAs without descending to primitives. By giving each HLA precondition effect descriptions and proving the high-level plan achieves the goal directly. This is the holy grail, so to speak, of hierarchical planning, because if we derive a high-level plan that provably achieves the goal, working in a small search space of high-level actions, then we can commit to that plan and work on the problem of refining each step. This gives us the exponential reduction we seek. The requirement is the downward refinement property. Every high-level plan that claims to achieve the goal must have at least one implementation that does achieve the goal. The conservative semantics include only effects achieved by every implementation. Fails, go home, San Francisco Airport, doesn't always get you to the airport. It fails if cache is false, and so we cannot assert at agent San Francisco Airport as an effect even though if the agent didn't have cache, it would drive itself. Requiring that an effect hold for every implementation is equivalent to assuming that someone else, an adversary, will choose the implementation, treating the HLA's multiple outcomes exactly like non-deterministic action. The resolution borrows the programming language's terminology of demonic versus angelic non-determinism, angelic semantics for HLAs, where the agent itself chooses the implementation. The key concept is the reachable set. Given a state S, the reachable set for an HLA H is the set of states reachable by any of the HLA's implementations. The agent can choose which element of the reachable set it ends up in when it executes the HLA. Thus, an HLA with multiple refinements is more powerful than the same HLA with fewer refinements. The reachable set of sequence is computed by composing the individual reachable sets, and a high-level plan succeeds if its reachable set intersects the goal states. Angelic semantics enables provably correct high-level plans to be derived without consideration of lower-level implementations, and an angelic search over high-level plans. Keeping track of the reachable set and pruning when it no longer intersects the goal, then refining only when a commitment must be made, gives the exponential reduction while remaining correct. HTN/high-level actions. HLAs refine into sequences of HLAs or primitives, encoding domain knowledge and shrinking search from exponential to linear depth. Implementation semantics. A high-level plan works if at least one implementation does. The agent chooses, unlike nature in non-deterministic planning. Angelic semantics. Reasoning about what some implementation can achieve via reachable sets enables provably correct abstract plans without enumerating implementations. Requiring all implementations to achieve the goal is demonic, adversarial semantics. Planning and acting in non-deterministic domains. Planning extends to partially observable, non-deterministic, and unknown environments via belief states. While the basic concepts mirror those in Chapter 4, the factored representation changes how belief states, the sets of possible physical states the agent might be in, are represented, and percept schemas augment PDL. The chair and table painting problem, make two objects the same color with paint colors unknown, shows the machinery. Action preconditions may contain variables that are not part of the action's variable list. Paint, Xcan, doesn't mention the color C, because in the partially observable case, we might or might not know what color is in the can. Percept schemas model the sensors. Perceive colors only of objects in view. Look at brings objects into view. A sensorless agent solves it. Open any can of paint and apply it to both chair and table, thus coercing them to be the same color. A contingent agent does better by sensing and painting only when needed, and an online agent plan monitors and replans in the face of failures, checking the result, and making an additional plan to fix any unexpected failure. The chapter's pragmatic rule. Agents plan only for contingencies that have important consequences and a non-negligible chance of happening. A Sahara crossing deserves contingency plans. A supermarket trip does not. The footnotes savor two payoff jokes. Plan monitoring finally makes an agent that is smarter than a dung beetle, and feudal plan repair is exactly the behavior exhibited by the Sphex wasp. Sensorless planning inherits Chapter 4's belief state search, but the belief state can be represented by a logical formula instead of by an explicitly enumerated set of states. Under an open-world assumption, unmentioned fluents are unknown. The painting initial belief state, after scolemizing, is B sub 0 equals color of XC of X. The update result of B equals B minus DL of a union ADD of a carries through exactly as in the observable case, and the terminal belief state satisfies the goal with C bound to C of cons sub 1. The very comforting result. The family of belief states defined as conjunctions of literals is closed under updates defined by PDDL action schemas. Any belief state over influence is a conjunction of size big O of n, considering that there are 2 to the n states in the world. The fly in the ointment is conditional effects. The vacuum suck actions effect depends on the robot's location. Typed when ATL, clean L when ATR, clean R, which can induce arbitrary dependencies among the fluents, leading to belief states of exponential size in the worst case. Conditional effects are preferable to inapplicable actions. From the point of view of sensorless planning, it is better to have conditional effects than an inapplicable action and a conservative approximation to the exact belief state. Keeping only determinable literals in one CNF is sound but incomplete. It cannot find suck to get on a clean square. The general lesson: look for action sequences that keep the belief state as simple as possible. Right suck, left suck stays one CNF throughout. Contingent planning adds percepts to the belief state transition, and online planning and replanning executes monitored plans, splicing and repairs, gaining the ability to handle sizable real-world problems. Percept schemas in open world. Sensors are modeled in PDL. Belief states become logical formulas, generally kept in one CNF. One CNF closure. With a caveat, PDDL updates preserve conjunctive belief states, unless conditional effects, like suck, induce dependencies. 3 modes. Sensorless, coerce the world. Contingent, sense and branch. Online, monitor and replan. With the caveat that agents plan only for important, non-negligible contingencies. Time, schedules, and resources. Classical planning talks about what to do, in what order, but does not talk about time. Scheduling adds durations, start times, and, decisively, resource constraints. The chapter's approach is plan first, schedule later. A planning phase selects actions with ordering constraints. A scheduling phase adds temporal information to ensure that it meets resource and deadline constraints. A job shop scheduling problem consists of jobs of actions, each with a duration and resource constraints. Resources are either consumable, bolts are no longer available for use, or reusable, a pilot is occupied during a flight but available again, and actions can also produce resources. The solution specifies start times, satisfying all temporal and resource constraints. The cost function for simplicity is the make span, the total plan duration. The 2-car assembly example shows durations. Add engine 30 or 60, add wheels 30 or 15, inspect 10, consumable lug nuts, and reusable engine hoists, wheel stations, and inspectors. Representing resources as quantities, inspectors 2, rather than inspector I1. Inspector I2 is aggregation, essential for reducing complexity. With 10 concurrent inspects and 9 inspectors, quantity representation detects failure immediately, whereas the algorithm would try all 9. Ways of assigning inspectors. Temporal scheduling alone is easy. Viewing ordering constraints as a directed graph, the critical path method, CPM, finds earliest start ES and latest start LS for every action. ES of B equals max A and pred of B ES of a plus duration of A. LS of A equals min B and suck of A LS of B minus duration of A. The critical path is that path whose total duration is longest. Determining the whole plan's duration and slack LS minus ES marks how much an off-critical action can slip, big O of NB. Total. Resource constraints change everything. The cannot overlap requirement is a disjunction of 2 linear inequalities, and the introduction of disjunctions turns out to make scheduling with resource constraints NP hard. The 10 by 10 problem posed in 1963 went unsolved for 23 years. Heuristics include the minimum slack greedy. Schedule for the earliest possible start whichever unscheduled action has all its predecessors scheduled and has the least slack, which resembles the minimum remaining values. MRV, heuristic and worked but suboptimally, 130 versus 115 minutes, on the example. The closing caution: if a scheduling problem is proving very difficult, it may not be a good idea to solve it this way. It may be better to reconsider the actions and constraints, motivating integrating planning and scheduling. Plan first, schedule later. Planning selects ordered actions. Scheduling assigns time subject to durations, deadlines, and resources. CPM and slack. Critical path, longest path, sets the make span. Off-critical actions have a slack window. With resource constraints, scheduling becomes NP hard. Aggregation and minimum slack represent indistinguishable resources as quantities to avoid factorial blowup. The MRV-like slack heuristic is greedy suboptimal. Analysis of planning approaches. Planning combines the 2 major areas of AI we have covered so far: search and logic. A planner is either a program that searches for a solution or one that constructively proves the existence of a solution, and the cross-fertilization has allowed planners to scale up from toy problems to real-world industrial applications with millions of states and thousands of actions. Planning is foremost an exercise in controlling combinatorial explosion. Within propositions, there are two to the end states. The identification of independent subproblems can be a powerful weapon. In the best case, full decomposability of the problem. We get an exponential speed up, though decomposability is destroyed by negative interactions between actions. The chapter is honest about the state of knowledge. We do not yet have a clear understanding of which techniques work best on which kinds of problems. Quite possibly, new techniques will emerge, providing a synthesis of highly expressive first-order and hierarchical representations with the highly efficient factored and propositional representations that dominate today. And portfolio planning systems apply collections of algorithms selectively, in parallel, or by schedule. The chapter's summary consolidates the arc. PDDL's expressive extensions: time, resources, percepts, contingencies, hierarchy. State space, progression/regression. Search with heuristic relaxations. SAT/CSP encodings. HTN planning whose angelic semantics gives provably correct abstract plans. Contingent and sensorless planning via belief state search. Online planning with execution monitoring and repairs, and resource scheduling, with the pointer that stochastic environments return in chapters 17 and 22. Search circle plus logic. Planners search state spaces or constructively prove existence. Scale comes from controlling the two to the n state explosion through decomposability. No settled winner. Portfolio planning systems hedge across algorithms. The field's honest answer to which technique fits which problem. Part 4. Uncertain Knowledge and Reasoning. Chapter 12. Quantifying Uncertainty. Acting Under Uncertainty. Chapter 12 opens Part 4, and its theme, agents in the real world need to handle uncertainty, whether due to partial observability, non-determinism, or adversaries. The belief state and contingency plan machinery of earlier chapters works on simple problems, but it has drawbacks. It must consider every possible explanation for its sensor observations, no matter how unlikely. A correct contingent plan must consider arbitrarily unlikely contingencies, and sometimes there is no plan that is guaranteed to achieve the goal, yet the agent must act. The automated taxis plan a 90, leave 90 minutes before a flight, 5 miles away, is the illustration. A logical agent will not be able to conclude with absolute certainty that Plan A90 will get us to the airport in time only as long as the car doesn't break down and I don't get into an accident and the road isn't closed and no meteorite hits the car. And this is the logical qualification problem, for which we so far have seen no real solution. Yet in some sense, a 90 is in fact the right thing to do. It is expected to maximize the agent's performance measure, balancing getting to the airport in time, avoiding a long, unproductive wait, avoiding speeding tickets. Other plans trade off belief in punctuality against time cost. The right thing to do, the rational decision, therefore depends on both the relative importance of various goals and the likelihood that, and degree to which, they will be achieved. Summarizing uncertainty shows how logic fails at diagnosis. The rule toothache cavity is wrong. Not all patients with toothaches have cavities. The causal direction is also wrong. Not all cavities cause pain. Making either rule exceptionless requires an almost unlimited list of possible problems. Logic fails for 3 main reasons. Laziness, too much work to list the complete set of antecedents or consequence. Theoretical ignorance, medical science has no complete theory for the domain. And practical ignorance, not all the necessary tests have been or can be run. The agent can at best provide only a degree of belief, and our main tool for dealing with degrees of belief is probability theory. Crucially, the ontological commitments of logic and probability theory are the same, facts hold or not, but the epistemological commitments are different. A logical agent believes each sentence true/false/no opinion. A probabilistic agent holds a numerical degree of belief between 0 and 1. Probability provides a way of summarizing the uncertainty that comes from our laziness and ignorance, thereby solving the qualification problem. The conceptual subtlety is that at the time of our diagnosis, there is no uncertainty in the actual world. Probability statements are made with respect to a knowledge state, not with respect to the real world. So P of cavity given toothache equals 0.8. P of cavity given toothache and gum disease equals 0.4. And P of cavity given all we know approximate 0. Do not contradict each other. Each is a separate assertion about a different knowledge state. Uncertainty and rational decisions joins the second ingredient. The agent must first have preferences among the different possible outcomes. Utility theory says that every state or state sequence has a degree of usefulness to an agent and that the agent will prefer states with higher utility. Utilities can account for any set of preferences, quirky or typical, noble or perverse, including altruism. Preferences combined with probabilities give the general theory. Decision theory equals probability theory plus utility theory, and an agent is rational if and only if it chooses the action that yields the highest expected utility, averaged over all the possible outcomes of the action. The principle of maximum expected utility, MEU. The decision-theoretic agent is identical at an abstract level to the agents that maintain a belief state, with the difference that its belief state represents not just the possibilities for world states, but also their probabilities. The chapter roadmap is explicit. This chapter and the next represent and compute with probabilistic information. Chapter 14 handles belief state updates over time. Chapter 16 deepens utility. Chapter 17 develops stochastic planning. 3 reasons logic fails. Laziness, theoretical ignorance, practical ignorance, summarized by degrees of belief. Degree of belief, not degree of truth. Probabilities are relative to a knowledge state, so posterior updates don't contradict priors. Decision theory equals probability plus utility. Rational agents choose the action maximizing expected utility, averaging over outcomes. Quote, an agent is rational if and only if it chooses the action that yields the highest expected utility, averaged over all the possible outcomes of the action. Section 1, 2.1.2. Basic probability notation. Probabilistic assertions, like logical ones, are about possible worlds. Logical assertions say which possible worlds are strictly ruled out. Probabilistic assertions talk about how probable the various worlds are. The set of all possible worlds is the sample space. The possible worlds are mutually exclusive and exhaustive. A probability model associates a numerical probability p, omega, with each possible world. With every possible world has a probability between 0 and 1, and the total probability is 1. Propositions correspond to sets of worlds, an event, and the probability associated with a proposition is defined to be the sum of the probabilities of the worlds in which it holds. The Fairdice example gives P of total equals 11 equals 1 over 36 plus 1 over 36 equals 1 over 18. Assertions need not determine the whole model. We might assert P of doubles equals 1 over 4 without knowing whether the dice prefer double 6 to double 2, just as logical assertions constrain without fully determining. Unconditional prior probabilities like P of cavity equals 0.2 refer to degrees of belief. In the absence of any other information, given evidence, we want the conditional posterior probability P of cavity given toothache equals 0.6, and P of cavity equals 0.2 is still valid after toothache is observed. It just isn't especially useful. Conditioning is not the same as logical implication. P of cavity given toothache equals 0.6 means whenever toothache is true and we have no further information, not a categorical inference. Conditional probability is defined as P of a given B equals P of A and B over P of B, and the equivalent product rule P of A and B equals P of a given B P of B is perhaps easier to remember. The language of propositions uses random variables. Their names begin with an uppercase letter. Every random variable is a function that maps from the domain of possible worlds to some range with lowercase value names. A Boolean random variable has range true, false, a Bernoulli distribution, and propositions of the form A equals true are abbreviated simply as A. Ranges can be sets of arbitrary tokens, age in juvenile, teen, adult, infinite, integers, or reals, and can include inequalities. Elementary propositions combine with propositional connectives. The chapter's notational care, factor style, capitals for variables, lowercase for values, the dot for ubiquitous evidence, sets the vocabulary for Bayesian networks to come. Probability model. Each possible world gets a probability in 0, summing to 1. Propositions sum over their worlds. Prior versus posterior. Unconditional degrees of belief versus degrees conditioned on evidence. And conditioning is not equal to implication. Random variables. Functions from worlds to ranges. Boolean variables abbreviate to A and A. Inference using full joint distributions. The full joint distribution, the table of probabilities for all combinations of values, can serve as the knowledge base from which answers to all questions may be derived. The toothache cavity catch domain is a 2 by 2 by 2 table. The probabilities sum to 1. Probabilistic inference is then just addition P of cavity or toothache sums the 6 worlds in which it holds, 0.28. Marginalization, summing out, gives P of cavity by adding the first row, 0.2. So called because of a common practice among actuaries of writing the sums of observed frequencies in the margins of insurance tables. And conditioning replaces P of yz with P of y given z P of z. Posterior probabilities come from the conditional definition, dividing by the probability of evidence P of cavity given toothache equals 0.12 over 0.2 equals 0.6, and P of not cavity given toothache equals 0.4. The denominator P of toothache can be viewed as a normalization constant, written alpha, ensuring that it adds up to 1. We can compute the posterior, even if we don't know the value of P, toothache, accumulate unnormalized values, and normalize. The general procedure. For a single query variable x, evidence variables e with observed values e, and unobserved variables y, P of x given e equals alpha P of x e equals alpha, the sum over y P of x e y. Given the full joint distribution to work with, equation 12.9 can answer probabilistic queries for discrete variables. It does not scale well, however. For n Boolean variables, the table has big O of 2 to the n entries and takes big O of 2 to the n time. A realistic problem could easily have n equals 100, making a table with 2 to the 100th approximate 10 to the 30th entries. And if each of the 10 to the 30th probabilities has to be estimated separately from examples, the number of examples required will be astronomical. So the full joint distribution in tabular form is seldom a practical tool. Instead, it should be viewed as the theoretical foundation on which more effective approaches may be built, just as truth tables formed a theoretical foundation for more practical algorithms like DPLL. Full joint distribution as KB. Sum over worlds for any probability. Marginalization and conditioning are the manipulation tools. Normalization. Posterior denominators become an alpha constant. Sometimes P of E is unknown anyway. Scaling failure. Big O of 2 to the n tables make the full joint impractical. It is the theoretical foundation for the conditional independence machinery of Chapter 13. Independence. Adding weather to the dental domain gives a 32-entry joint containing 4 additions of the 3-variable table. The product rule writes P of toothache catch cavity cloud equals P of cloud given toothache catch cavity P of toothache catch cavity. And, unless one is in the deity business, one should not imagine that one's dental problems influence the weather. The assertion P of cloud given toothache catch cavity equals P of cloud, independence, marginal or absolute, lets the joint decompose P of toothache catch cavity weather equals P of toothache catch cavity, a P of weather, a 32-element table from an 8-element and a 4-element one. Independence of propositions is written equivalently as P of a given B equals P of A, P of B given A equals P of B, or P of A and B equals P of A P of B. Independence of variables likewise. Independence assertions are usually based on knowledge of the domain, and they can dramatically reduce the amount of information necessary to specify the full joint distribution. An independent coin flips factor into n single variable distributions. The dentist's joke is on point. The independence of dentistry and meteorology is a good thing, because otherwise the practice of dentistry might require intimate knowledge of meteorology and vice versa. But clean separation of entire sets of variables by independence is quite rare. Whenever a connection, however indirect, exists between two variables, independence will fail to hold. Moreover, even independent subsets can be quite large. Dentistry might involve dozens of diseases and hundreds of symptoms, all of which are interrelated. To handle such problems, we need more subtle methods than the straightforward concept of independence, the conditional independence that grounds Bayesian networks. Independence P of A and B equals P of A P of B. Domain knowledge factors the joint into smaller distributions. Rare at scale. Full independence fails whenever any connection exists. The chapter turns to conditional independence. Bayes' rule and its use. Equating the two product rule forms and dividing by P A yields Bayes' rule P of B, given A equals P of a given B P of B over P of A. This simple equation underlies most modern AI systems for probabilistic inference. It seems like two steps backwards, but is useful because there are many cases where we do have good probability estimates for these three numbers and need to compute the fourth. In diagnosis, we perceive as evidence the effect of some unknown cause, and we would like to determine that cause. So, Bayes' rule converts the causal direction P of symptoms given disease. The conditional probability quantifies the relationship in the causal direction into the diagnostic direction P of disease given symptoms. The meningitis example is the canonical caution P of S given M equals 0.7. P of M equals 1 over 50,000. P of S equals 0.01. So P of M given S equals 0.7 to 1 over 50,000 over 0.01 equals 0.0014. We expect only 0.14% of patients with a stiff neck to have meningitis, even though a stiff neck is quite strongly indicated by meningitis, with probability 0.7. Because meningitis is so rare, the base rate. This is the base rate fallacy's antidote. The posterior depends on the prior. The chapter also notes the general multivalued and evidence-conditionalized forms P of y given x e equals P of x given y e P of y given e over P of x given e, and that the denominator can again be treated as a normalizing constant. Bayes' rule converts causal likelihoods into diagnostic posteriors, the engine of modern probabilistic AI. Base rates matter. The 0.14% posterior despite strong likelihood shows why priors cannot be ignored. Naive Bayes models. The dentistry pattern generalizes. A single cause directly influences a number of effects, all of which are conditionally independent, given the cause. The naive Bayes model writes P of cause, E sub 1. E sub n equals P of cause, the product over IP of E sub I given cause. Naive because it is often used in cases where the effect variables are not strictly independent given the cause variable, and sometimes called the idiot Bayes model by strict Bayesians. In practice, naive Bayes systems often work very well, even when the conditional independence assumption is not strictly true. Inference applies the standard joint distribution method P of cause given E equals alpha P of cause, the product over JP of E sub j given cause, where the unobserved effects disappear from the computation because their sum is 1. The runtime of this calculation is linear in the number of observed effects and does not depend on the number of unobserved effects, a common phenomenon. Evidence variables whose values are unobserved usually disappear from the computation altogether. Text classification is the worked use. The cause is the category: news, sports, business, weather, entertainment. The effects are keyword presences. Priors and conditionals are estimated from data. 9% weather articles arrow. Double. Our P of category equals weather equals 0.09. 37% of business articles contain stocks arrow. Double. Our P of has word sub 6 equals true given business equals 0.37, with the warning not to assign probability 0 to words that have not been seen previously, since the 0 would wipe out all the other evidence. Reserve probability mass for unseen words. Classifying a new document multiplies priors by the observed word conditionals and normalizes. The independence assumption is clearly violated in practice. First quarter co-occurs more than the product of its parts, which usually means that the final posterior probabilities will be much closer to 1 or 0 than they should be. In other words, the model is overconfident, though the ranking of the possible categories is often quite accurate. Naive Bayes is widely used for language determination, document retrieval, spam filtering, but for tasks where the actual values of the posterior probabilities really matter. For example, in deciding whether to perform an appendectomy, one would usually prefer the more sophisticated models described in the next chapter. Naive Bayes. One cause, conditionally independent effects given it. Inference is a prior times a product of likelihoods, normalized. Overconfidence in practice. Violating independence inflates posteriors, though category ranking stays accurate. Linear in observed effects. Unobserved effects vanish from the computation, a recurring phenomenon. The Wumpus world revisited. Applying the chapter's tools, a probabilistic Wumpus agent can do much better than the logical agent, which can conclude nothing about which square is most likely to be safe, might have to choose randomly. In Figure 12.5 situation, 3 unvisited reachable squares, 1, 3, 2 to 3, 1, might each contain a pit. The random variables are the pit variables p sub I, j for every square and breeze variables b sub I, j for observed squares. The full joint factors by the product rule as p of p sub 1, 1, p sub 4, 4b sub 1, 1b sub 1, 2b sub 2, 1 equals p of b given p dot p of p, where the first term, values are 1 if all the breezy squares are adjacent to the pits and 0 otherwise, and the prior use is independence. Each square contains a pit with probability 0.2. So a configuration with exactly n pits has probability 0.2 to the n dot 0.8 to the 16. The query p of p sub 1, 3, given known b by brute force, sums 2 to the 12th equals 4,096 terms over the 12 unknown squares. The insight that makes it tractable. If we knew the values of all the pit variables adjacent to the squares we care about, then pits, or their absence, in other, more distant squares could have no further effect on our belief. Splitting unknown into frontier, pit variables adjacent to visited squares, 2, 2, 3, and other, the 10 distant squares, the observed breezes are conditionally independent of the other variables, given the known, frontier, and query variables, so the other variables are summed out and vanish from the computation. The result p of p sub 1, 3, given known b equals alpha p of p sub 1, 3, the sum over frontier p of b, given known p sub 1, 3 frontier, p of frontier, 4 terms over the frontier, mirroring the logical model enumeration of Figure 7.5 with prior probability weights. The answer, 1, 3, and by symmetry 3, contains a pit with roughly 31% probability, while a similar calculation shows that 2, 2 contains a pit with roughly 86% probability. The Wumpus agent should definitely avoid 2, 2. Note that our logical agent from Chapter 7 did not know that 2, 2 was worse than the other squares. Probabilistic beats logical in the Wumpus world. Priors plus independence assign 31% to 1, 3/3 and 86% to 2, 2, which logic could never rank. Frontier conditioning. Conditional independence lets distant, other, squares be summed away, leaving a 4-term computation over the frontier. Chapter 13. Probabilistic reasoning. Representing knowledge in an uncertain domain. Chapter 13 introduces the Bayesian network, a data structure, to represent the dependencies among variables that can represent essentially any full joint probability distribution and in many cases can do so very concisely. The full joint distribution can become intractably large as the number of variables grows, and specifying probabilities for possible worlds one by one is unnatural and tedious. Independence and conditional independence can greatly reduce the number of probabilities that need to be specified. A Bayesian network is specified by 3 things. Each node is a random variable, discrete or continuous. Directed links connect pairs, and the graph has no directed cycles and hence is a directed acyclic graph, or DG. And each node x sub I has associated probability information p of x sub I given parents of x sub I quantifying the parents effect, using a finite number of parameters. The topology of the network specifies the conditional independence relationships that hold in the domain. The intuitive meaning of an arrow is typically that x has a direct influence on y, which suggests that causes should be parents of effects. Once the topology is laid out, we need only specify the local probability information in the form of a conditional distribution given its parents, and the full joint distribution is defined by the topology and the local probability information. The simple world of toothache, cavity, catch, and weather becomes a tiny network in which weather is independent, and toothache and catch are conditionally independent, given cavity indicated by the absence of a link between toothache and catch. The chapter's canonical example is Pearl's burglar alarm, a home alarm fairly reliable at detecting a burglary, but is occasionally set off by minor earthquakes. John nearly always calls when he hears the alarm, but sometimes confuses the telephone ringing with the alarm. Mary likes rather loud music and often misses the alarm altogether. The network structure shows that burglary and earthquakes directly affect the probability of the alarms going off. But whether John and Mary call depends only on the alarm. The network thus represents our assumptions that they do not perceive burglaries directly, they do not notice minor earthquakes, and they do not confer before calling. The local information takes the form of a conditional probability table. CPT each row is the conditional probability for a conditioning case. A possible combination of values for the parent nodes. Each row must sum to 1, and a Boolean variable with k Boolean parents has 2 to the k independently specifiable probabilities. No parents, just a prior row. The network conspicuously omits Mary's loud music and the ringing telephone, factors summarized in the uncertainty associated with the links. G, both laziness and ignorance in operation. It would be a lot of work to find out why those factors would be more or less likely in any particular case, and we have no reasonable way to obtain the relevant information anyway. The probabilities actually summarize a potentially infinite set of circumstances in which the alarm might fail to go off. High humidity, power failure, dead battery, cut wires, a dead mouse stuck inside the bell, etc., or John or Mary might fail to call and report it, out to lunch, on vacation, temporarily deaf, passing helicopter, etc. In this way, a small agent can cope with a very large world, at least approximately. The burglary network's concrete CPTs repay attention. Burglary has prior P of B equals true equals 0.001. Earthquake P of E equals true equals 0.002. Alarms table has 4 conditioning cases. P of E equals true, given B, E with the letters standing for burglary, earthquake, alarm, John calls, Mary calls, capturing that burglary and earthquakes directly affect the probability of the alarms going off, while John calls and Mary calls each have a 2-case table conditioned only on alarm. P of J equals true, given A, and P of M equals true, given A. These few numbers, 10 in all, fully determine the joint distribution over the 5 variables, which is the sense in which a small agent can cope with a very large world. The chapter's rhetorical point about the joint distribution being a camel is apt. The full joint distribution can answer any question about the domain, but a Bayesian network can represent essentially any full joint probability distribution, and in many cases can do so very concisely. The 10 parameters of the alarm network stand in for the 2 to the 5th minus 1 equals 31 independent numbers a full table would require, and the savings grow combinatorially as variables accumulate. Bayesian network, a DAG whose nodes are random variables. Arrows are direct influence, and each node carries P of X sub I given parents, defining the full joint via the topology plus local tables. The alarm network. Burglary and earthquake, alarm John calls and Mary calls. CPTs trade specifiable parameters against the summarized infinite circumstances of laziness and ignorance. The semantics of Bayesian networks. The semantics defines how the syntax corresponds to a joint distribution P of X sub 1. X sub n equals the product over I P of X sub I given parents of X sub I. Each entry in the joint distribution is represented by the product of the appropriate elements of the local conditional distributions. The burglary worked example multiplies P of J given a dot P of M given a dot P of a given not B not E dot P of not B dot P of not E equals 0.90, 0.70, 0.00, 0.999, 0.998 equals 0.00628. The probability that the alarm is sounded. But neither a burglary nor an earthquake has occurred, and both John and Mary call. The chapter then proves the crucial meaning of the parameters. The numbers P of X sub, I given parents of X sub I in the local tables, are exactly the conditional probabilities P of X sub, I given parents of X sub, I implied by the joint distribution. So when we specify P of John calls equals true given alarm equals true equals 0.90, it should be the case that about 90% of the time, when the alarm sounds, John calls. The fact that each parameter of the network has a precise meaning in terms of only a small set of variables is crucially important for robustness and ease of specification. A method for constructing Bayesian networks grounds the topology. The chain rule P of X sub 1. X sub n equals the product P of X sub I given X sub 1. X sub I. 1 holds for any variables. A Bayes net matches it provided each node is conditionally independent of its other predecessors in the node ordering, given its parents. The construction method, order the variables such that causes precede effects. For each X sub, I choose a minimal set of parents, such that equation 13.3 is satisfied. Intuitively, the parents of node x sub I should contain all those nodes that directly influence x sub I, and write down the CPTs. Because each node connects only to earlier nodes, the network is acyclic, and an important property of Bayes nets is that they contain no redundant probability values. If there is no redundancy, then there is no chance for inconsistency. It is impossible for the knowledge engineer or domain expert to create a Bayesian network that violates the axioms of probability. Constructing the network is guided by equation 13.3 of Bayes net is correct only if each node is conditionally independent of its other predecessors in the node ordering, given its parents, and the construction method, order causally. Choose a minimal parent set for each node such that the condition holds, write CPTs, guarantees that the network is acyclic. The Merry-Calls choice shows the reasoning. Merry-Calls is certainly influenced by whether there is a burglary or an earthquake, but not directly influenced. Those events influence Mary's calling behavior only through their effect on the alarm, so alarm will be the only parent node for Merry-Calls. The no redundancy property is a genuine benefit over other formalisms. The knowledge engineer or domain expert cannot create a Bayesian network that violates the axioms of probability. Compactness and node ordering show the payoff and the pitfall. Bayes nets can often be far more compact than the full joint distribution, a general property of locally structured, also called sparse systems, where each subcomponent interacts directly with only a bounded number of other components. If each variable has at most k parents, the network needs at most n 2 to the k numbers versus 2 to the n for the joint. N equals 30 nodes, each with 5 parents, 960 numbers, but the full joint distribution requires over a billion. A bad node ordering. Mary calls, John calls, alarm, burglary, earthquake, yields a network with 2 more links, 13 conditional probabilities rather than 10, including tenuous relationships requiring difficult and unnatural probability judgments, such as assessing the probability of earthquake given burglary and alarm. The worst ordering, adding earthquake before burglary, requires 31 distinct probabilities, exactly the same number as the full joint distribution. Any of the 3 networks can represent exactly the same joint distribution. The 2 versions in Figure 13.3 simply fail to represent all the conditional independence relationships. A causal ordering yields fewer numbers, and the numbers will often be easier to come up with. Tversky and Kahneman found expert physicians prefer to give probability judgment for causal rules rather than for diagnostic ones. Conditional independence relations follow from the semantics. The non-descendants property. Each variable is conditionally independent of its non-descendants, given its parents. John calls is independent of burglary, earthquake, and Mary calls given alarm. The Markov blanket property. A variable is conditionally independent of all other nodes in the network, given its parents, children, and children's parents, enabling inference algorithms that use completely local and distributed stochastic sampling processes. The most general question, is X independent of Y given Z, is answered by D-separation. Consider the ancestral subgraph of X, Y, Z. Add links between unlinked parents sharing child, the moral graph. Make all links undirected. If Z blocks all paths between X and Y, then Z D-separates X and Y. The primal intuition behind the test is that a trail in the original directed graph is blocked by evidence Z when a structure at a node along the trail either passes through a known variable or one of its descendants in a serial or divergent connection, or B, requires both parents of a converging V-shaped connection to be observed or have an observed descendant. So, observing the explaining away. Common child unblocks information that would otherwise flow between its parents. Confirming the alarm network, burglary and earthquake are independent given the empty set. V structures parents separated until the child is known, but not necessarily conditional on alarm. The alarm makes them dependent because knowing it went off, a burglary explains away the earthquake. John calls and Mary calls are conditionally independent given alarm because knowing the alarm blocks the path between them. Notice also that the Markov blanket property follows directly from the D-separation property, since a variable's Markov blanket D-separates it from all other variables. A subtle but defining feature of these independence relations is that they are guaranteed by the graph structure alone, regardless of the specific probability values in the CPTs. 2 networks with the same topology, but wildly different numbers assert exactly the same conditional independencies. This separation of the qualitative, who directly influences whom, from the quantitative, with what strength, is why the network's topology can be drawn before any probabilities are assessed. It is usually easy for a domain expert to decide what direct influences exist in the domain, much easier, in fact, than actually specifying the probabilities themselves. It also explains why a wrong node ordering, though it represents the same joint distribution, is not merely wasteful but actively misleading about structure. It reports conditional dependencies that are not there, and the price shows up as redundant parameters that must be specified anyway. Efficient representation of conditional distributions notes that the relationship between the parents and the child is often described by a canonical distribution rather than a completely arbitrary CPT. The simplest is deterministic nodes. The child North American is the disjunction of Canadian, U.S., Mexican. Best price is the minimum over dealers. Water stored is the sum of inflows. Noisy OR and context-specific independence extend the pattern. A child is true with high probability if any of several parents is true, each parent inhibiting it independently, giving one parameter per parent rather than a full two to the K-table, letting near-arbitrary causal relations be captured with few parameters. Product semantics and parameter meaning. The joint is a product of local CPT entries. Each parameter is genuinely the conditional probability of the variable given its parents. Construction equals causes before effects. Order causally. Connect each node to a minimal set of directly influencing predecessors. No redundancy, hence no inconsistency. Compactness and ordering. Locally structured systems need n.2 to the k numbers versus 2 to the n. Bad orderings can bloat the network to joint size with unnatural assessments. Deseparation and Markov blanket. Graph-theoretic conditional independence. Moralize the ancestral subgraph and check whether evidence blocks all paths. Exact inference in Bayesian networks. The basic task is to compute the posterior probability distribution for a set of query variables, given some observed event. In the burglary network, observing John calls equals true and Mary calls equals true gives P of burglary, given Jm equals 0.2840.716. The chance of a burglary is about 28%. Inference by enumeration applies equation 12.9. Sums of products of conditional probabilities from the network. The naive computation of P of B given Jm has big O of n.2 to the n complexity. This can be reduced to big O of 2 to the n by taking advantage of the nested structure, moving the summations inwards as far as possible, because not all the factors in the product of probabilities depend on all the variables. The enumeration ask algorithm evaluates these expression trees using depth-first, left-to-right recursion, with space complexity only linear in the number of variables, summing over the full joint distribution without ever constructing it explicitly. But time complexity is always big O of 2 to the n, rather grim, and the small insurance network needs around 227 million arithmetic operations for a typical query. The enumeration tree itself shows the payoff of nesting. The expression for the burglary query sums over earthquake and alarm, multiplying 5 CPT factors, and by moving the summations inward, P of B the sum over EP of E the sum over AP of a given B E dot P of J given a dot P of M given each summation, loop this over the variable's possible values, only where the factors depend on it, cutting the asymptotic from big O of n dot 2 to the n to big O of 2 to the n. The tree contains repeated sub-expressions. The products P of J given AP of M given a computed twice, once for each value of E. Variable elimination is a form of dynamic programming. Evaluate expressions in right-to-left order, storing intermediate results, factors, matrices indexed by their argument variables, and summations over each variable are done only for those portions of the expression that depend on the variable. The burglary computation factors as f sub 1b tensor product f sub 2e tensor product f sub 3a b e tensor product f sub 4a tensor product f sub 5a. Then sums out A to get f sub 6b, E, sums out E to get f sub 7b, and evaluates f sub 1b tensor product f sub 7b, normalizing. The complexity of the variable elimination algorithm is related to the dimensionality of the factors, polynomial in the size of the factors, exponential in their dimensionality, where the dimensionality is the number of variables in a factor, which in turn depends on the elimination ordering. The sizes of intermediate factors are related to the tree width of the graph. Finding the best elimination ordering is hard, but heuristics help. In Bayesian networks with hundreds of variables and low tree width, exact inference is very efficient, making Bayesian networks with bounded tree width tractable in practice. The elimination factors themselves are worth spelling out. F sub 4a and F sub 5a are the two-element vectors, 0.90, 0.05, and 0.70, 0.01, for John and Mary given the alarm. The pointwise product with a 2 by 2 by 2 alarm table F sub 3ab yields F sub 6be, and summing F sub 2e tensor product F sub 6be over e yields F sub 7b. So the evaluation process sums out variables, right to left, from pointwise products of factors to produce new factors, eventually yielding a factor that constitutes the solution, that is, the posterior distribution over the query variable. Enumeration case P of x given E as nested sums of CPT products, big O of 2 to the n time, linear space, but repeated subexpressions. Variable elimination, dynamic programming over factors, sum out variables right to left, sharing computations, efficiency governed by factor dimensionality / tree width. Approximate inference for Bayesian networks. Given the intractability of exact inference in large networks, randomized Monte Carlo, sampling provides approximate answers whose accuracy depends on the number of samples generated, counting up the different answers found in those random events. Direct sampling, prior sample, samples each variable in topological order, conditioned on values already sampled for its parents. The probability of generating an event is exactly the joint probability. So, in the limit of large N, we expect 32.4% of the samples to be of this event. The estimate is consistent. The estimated probability becomes exact in the large sample limit. Rejection sampling estimates P of x given E by generating prior samples, rejects all those that do not match the evidence, and normalizes the counts of the remaining. It is consistent. Rejection sampling is very similar to the estimation of conditional probabilities in the real world to estimate the conditional probability that any human survive after a 1 km diameter asteroid crashes into the Earth. One can count how often, ignoring all those days when no such event occurs. But the complexity of rejection sampling depends primarily on the fraction of samples that are accepted, which is exactly equal to the prior probability of the evidence, P, for complex problems with many evidence variables. This fraction is vanishingly small, 1 in 1,000 to 1 in 10,000 on the insurance network, and it drops exponentially as the number of evidence variables grows. So the procedure is unusable for complex problems. The sprinkler worked example makes the arithmetic concrete. Estimating P of rain given sprinkler equals true with 100 samples, 73 are rejected for having sprinkler equals false, and of the 27 accepted, 8 have rain equals true, giving the estimate 0.296, 0.704, against a true answer of 0.3, 0.7, with the standard deviation of the error in each probability proportional to 1 over the square root of n. Rejection sampling also has difficulties with continuous valued evidence variables because the probability of producing a sample consistent with such evidence is 0 if it is really continuous valued, or infinitesimal if it is merely a finite precision floating point number. Important sampling aims to emulate the effect of sampling from a distribution, P, using samples from another distribution Q, applying a correction factor, a weight, Px/Q, x, to each sample, since we would like to sample from the true posterior, but usually this is too hard. In Bayes nets, likelihood weighting fixes evidence values and samples the non-evidence variables in topological order, weighting each sample by the likelihood of the evidence given the sampled values. It uses all of its samples, but its estimates are consistent and can be very accurate when there is little evidence, while performance can degrade dramatically in the presence of lots of evidence, because the weights become concentrated on very few samples. Because weights are the product of the evidence-conditioned CPT entries for the fixed evidence nodes, weighting a sample is almost as cheap as generating one, and the weighted counts over the query variable, normalized, converge to the true posterior, a property that makes likelihood weighting the workhorse of many applied probabilistic systems despite its variance in heavy evidence. The weight of sample XE is exactly W equals the product over JP of E sub J, given parents of E sub J, the product over evidence variables of their CPT entries given the sampled parents. Samples that make the observed evidence very plausible get high weight, implausible ones near zero. So in a network where evidence variables have many parents, the weights become very uneven, with most of the probability mass concentrated on a few samples. Markov chain Monte Carlo, MCMC, includes Gibbs sampling. Instead of generating a sample from scratch, we generate each sample by making a random change to the preceding sample, sampling one variable at a time from its conditional distribution, given the current values of the variables in its Markov blanket. Gibbs does pay attention to downstream evidence. Information propagates from evidence nodes in all directions, so it outperforms likelihood weighting when evidence is mostly downstream. Its mixing rate depends strongly on the quantitative properties of the conditional distributions. When rain is deterministic given cloudy, the only two joint states are true, true, and false, false, and the chain can never reach false, false. So Gibbs sampling fails in this case because the deterministic relationship breaks the property of ergodicity. Nearly deterministic relationships converge, arbitrarily, slowly. The sprinkler network's Gibbs trace makes the mechanics concrete. Starting from the event cloudy equals true, rain equals true, sprinkler equals true, wet grass equals true, each step resamples one variable from its Markov blanket conditional. Resampling rain, given its blanket, is dominated by the observed wet grass. Resampling sprinkler follows a similar pattern. So the chain wanders through the high probability regions, and the fraction of visits to each state estimates its probability. Block sampling. Sample several variables jointly in Metropolis. Hastings, MH. Fixed mixing. MH has two stages in each iteration. Propose a new state from a proposal distribution Q of X given X, then probabilistically accept or reject, with acceptance probability alpha equals the minimum of 1 pi of xq of X given X over pi of xq of X given X. The remarkable thing about MH is that convergence to the correct stationary distribution is guaranteed for any proposal distribution, provided the resulting transition kernel is ergodic, proved by detailed balance. The self-loop with X equals X automatically satisfies detailed balance, and the ratio says that if a next state is proposed that is more likely than the current state, it will definitely be accepted, while a less likely proposal's probability of being accepted drops. Proportionally, the posterior ratio pi of X over pi of X is very fortunate. The P terms cancel, leaving a ratio of full joint probabilities, and if the proposal distribution makes only local changes, only a small number of terms will be different, so the work required to generate each sample is independent of the size of the network, as long as the state changes are local. Guidelines for proposals. Make new states reasonably likely. Gibbs does this automatically. Gibbs is a special case of MH with an acceptance probability of 1, and ensure the chain mixes well, sometimes proposing large moves to distant parts of the state space. Compiling approximate inference compiles the network into model-specific inference code. The repeated operations required to access the data structure are completely unnecessary, since the network structure and conditional probabilities remain fixed. The compiled Gibbs sampling code for earthquake looks like decision tree of pre-computed thresholds, not especially pretty. Typically, it will be roughly as large as the BaseNet itself, but it is incredibly efficient, typically 2 to 3 orders of magnitude faster, running tens of millions of sampling steps per second on an ordinary laptop. Its speed, limited largely by the cost of generating random numbers. Direct and rejection sampling. Consistent estimates from prior samples. Rejections accept rate is P, which vanishes with abundant evidence. Likelihood weighting / importance sampling. Sample from an easy distribution and reweight. All samples used, but weights concentrate with heavy evidence. Gibbs and Metropolis. Hastings. MCMC makes local Markov blanket updates. The deterministic ergodicity failure shows sampling's perils. MH guarantees convergence for any ergodic proposal. Compilation. Pre-compute per variable sampling thresholds, gaining 2 to 3 orders of magnitude. Causal networks. Chapter 13 closes with causal networks, a restricted class of Bayesian networks that forbids all but causally compatible orderings. The simplest single-arrow case fire smoke evokes discomfort and even resistance in most people. The reverse network smoke fire with Bayes-derived probabilities is equivalent, hence conveys the same information. Yet we know from our experience and scientific understanding that clearing the smoke would not stop the fire, and extinguishing the fire will stop the smoke. Causal Bayesian networks were devised to permit us to represent causal asymmetries and to leverage the asymmetries towards reasoning with causal information, instead of asking an expert whether smoke and fire are probabilistically dependent. We now ask, which responds to which, smoke to fire or fire to smoke? A judgment beyond probabilistic dependence, made precise through the notion of the arrow as assignment. The chapter positions causal networks as the bridge from correlation to intervention, the same distinction that underpins how a Bayesian network structure supports reasoning about the effects of actions, the do-operator machinery of later editions, and it carries the chapter's historical coda on certainty factors, Dempster, Schaefer theory, fuzzy sets, and logic, a direct competitor, whereas in fact it addresses a different set of issues, vagueness rather than uncertainty, possibility. Theory and qualitative probabilistic networks whose positive/negative influences are sufficient for optimal decision-making without the need for the precise specification of probability values. Causal networks restrict arrow direction to causality, so the fire-smoke asymmetry is represented, not buried in equivalent probabilistic reorderings. Causation beyond dependence, the which responds to which judgment enriches reasoning, the foundation for intervention-based inference. Chapter 14. Probabilistic Reasoning over Time, and Uncertainty. Chapter 14 leaves static worlds. When repairing a car, we assume that whatever is broken remains broken during the process of diagnosis, for dynamic ones, where the dynamic aspects of the problem are essential. The diabetic patient is the running example. Blood sugar and insulin levels can change rapidly over time, so to assess the current state from the history of evidence and to predict the outcomes of treatment actions, we must model these changes. The same considerations arise in tracking the location of a robot, tracking the economic activity of a nation, and making sense of a spoken or written sequence of words. The models are discrete time. The world is viewed as a series of snapshots or time slices, numbered 0, 1, 2, with a chosen interval delta, dictated by the sensor, a camera at 1/30th second, by the typical rates of change of the relevant variables, 1 minute for blood glucose, 1,000,000 years for continental drift. Each time slice has unobservable state variables xt and observable evidence variables et. The umbrella world. Rain whether it is raining, umbrella whether the director carries the umbrella. The diabetes example distinguishes blood sugar from measured blood sugar. This is how we deal with noisy measurements of actual quantities. The notation xa, b runs from A to be inclusive. Two model components plus a prior specify the joint distribution. The transition model P of x sub t given x sub 0 t 1 faces a problem. The set x sub 0 t 1 is unbounded in size as t increases, solved by the Markov assumption. The current state depends on only a finite fixed number of previous states, the simplest being the first-order Markov process, in which the current state depends only on the previous state. P of x sub t given x sub 0 t 1 equals P of x sub t given x sub t1. A further assumption of time homogeneity, the laws that govern change do not themselves change over time, means one conditional probability table serves every step. The sensor model makes the sensor Markov assumption P of e sub t given x sub 0 t e sub 1 t 1 equals P of e sub t given x sub t. Any state that's worth its salt should suffice to generate the current sensor values. Notice the direction of the dependence between state and sensors. The arrows go from the actual state of the world to sensor values because the rain causes the umbrella to appear, while inference goes in the other direction. The distinction between the direction of model dependencies and the direction of inference is one of the principal advantages of Bayesian networks. With the prior P of x sub 0, the full joint is P of x sub 0, t e sub 1. T equals P of x sub 0, the product P of x sub I given x sub I. 1 P of e sub I given x sub I. The semantics of the family of temporal models, which standard Bayesian networks cannot represent, because they require a finite set of variables. The infinite set is handled using integer indices and implicit universal quantification. Whether the first-order Markov assumption is reasonable depends on the domain itself. It is exactly true for a random walk, only approximate for rain. 2 improvements. Increasing the order. Add rank -2, capturing in Palo Alto. It very rarely rains more than 2 days in a row. And increasing the set of state variables. Add season, temperature, humidity, pressure, where the first solution can always be reformulated as an increase in the set of state variables. The robot tracking example shows the self-sufficient set of variables problem. Position and velocity alone violate the Markov property when battery exhaustion depends on all previous maneuvers. So we restore the Markov property by including the charge level battery. But this requires a model for predicting battery from battery -1, and error accumulates over time, fixed by adding a new sensor for the battery level. Discrete time temporal models, state variables xt and evidence et per slice. Transition plus sensor models plus prior define the joint via implicit universal quantification. Markov and homogeneity assumptions, first-order dependence, and time-invariant laws make finite specification of an infinite network possible. Self-sufficient state, include enough variables like battery charge to restore the Markov property. Increasing sensor coverage compensates for model error. Inference in temporal models. 4 inference tasks structure the chapter. Filtering, state estimation, the posterior distribution over the most recent state given all evidence to date, which is what a rational agent does to keep track of the current state. Prediction, P of x sub t plus k given E sub 1. T for the future, useful for evaluating possible courses of action. Smoothing, P of x sub k given E sub 1. T for a past state, which provides a better estimate, because it incorporates more evidence and most likely explanation. Argmax T over x sub 1. T of P of x sub 1. T given E sub 1. T. Useful in speech recognition, where the aim is to find the most likely sequence of words, plus learning of the transition and sensor models as a byproduct of inference. Filtering and prediction rest on recursive estimation. Given the result of filtering up to time t, the agent needs to compute the result for t plus 1 from the new evidence, E sub t plus 1. The central formula, 14.5, splits into prediction, project P of x sub t given E sub 1. T forward through the transition model. Then update, condition on the new evidence via the sensor model, and Bayes rule P of x sub t plus 1 given E sub 1. T plus 1 equals alpha P of E sub t plus 1 given x sub t plus 1. The sum over x underscore tp of x sub t plus 1 given x sub t, P of x sub t given E sub 1. T. All the terms come either from the model or from the previous state estimate, a message f sub 1. T propagated forward, modified by each transition and updated by each observation, with constant, independent of t, time and space per update for discrete variables. The umbrella example's arithmetic is worth tracing. With a uniform prior p of r sub 0 equals 0.50.5, transition p of r sub t given r sub t. 1 equals 0.70.30.30.7, and sensor P of U sub t given R sub t equals 0.90.2. Observing U sub 1 equals true first predicts P of R sub 1 given E sub 1 o'clock equals 0.50.5 through the transition, still uniform by symmetry, then updates. Alpha 0.90.2, 0.50.5 equals alpha 0.450.1 equals 0.8180.182. Day 2 repeats. Predict through the transition to 0.6270.373. Multiply by the sensor 0.90.2 and normalize. The posterior on day 2 given 2 umbrella days is roughly 0.8830.117, showing the increasing influence of accumulated evidence. Prediction alone. P of R sub t plus k given E sub 1. T converges to the stationary distribution of the Markov chain as k increases, since after many transitions the chain forgets its starting distribution. For the umbrella chain, the long-run probability of rain approaches 0.5, and the influence of past observations diminishes. Smoothing computes P of x sub k given E sub 1. T equals alpha f sub 1. K up E sub k plus 1. T, with a backward message B sub k plus 1. T equals P of E sub k plus 1. T given x sub k is computed by a backward pass. We work backward from time t down to time 1, using the backward recursion, giving the forward backward algorithm that combines the evidence up to k with the evidence after k. The intuition that a better estimate of the state at time k is available at later times because of the extra evidence. The backward recursion, summing over x at k plus 1 of p of e given x at p of x given previous, mirrors the forward pass in reverse. Both are big O of s to the second t for HMMs, and the smoothed estimate of the final time t is identical to the filtered estimate, since there is no future evidence to add. In the umbrella world, asking was it raining on Wednesday, given the umbrella observations up to today, yields an estimate that can differ markedly from what filtering believed on Wednesday, precisely because smoothing incorporates more evidence. Most likely explanation is solved by the Viterbi algorithm, a dynamic programming recursion computing, for each state at time t, the probability of the most likely path to that state, tracking the best predecessor in a most likely path table, and recovering the path of states by following back pointers from the most likely final state, the most likely sequence of states that generated the observations. Viterbi and filtering differ in a crucial way. Filtering sums over all paths to a state. Viterbi keeps only the single best path, so the most likely explanation can be quite different from the sequence of states visited by the filter process. Learning sees the models estimated via an iterative update algorithm called expectation, maximization, or EM, defer to Chapter 20. 4 tasks plus learning. Filtering, prediction, smoothing, most likely explanation, Viterbi, plus EM for learning the models. Recursive filtering, predict through the transition, update through the sensor, a constant time per step forward message. Forward, backward smoothing. Combine the forward message with a backward message from the future evidence. Hidden Markov models. An HMM is a temporal probabilistic model in which the state of the process is described by a single, discrete random variable. The umbrella world is one. Models with several state variables can still fit into the HMM framework by combining the variables into a single megavariable whose values are all possible tuples, and the restricted structure of HMMs allows for a simple and elegant matrix implementation of all the basic algorithms. With state values 1, S, the transition model becomes an S times S matrix T, with T sub I j equals P of X sub T equals J given X sub T. 1 equals I. The umbrella worlds is 0.70.30.30.7, and the sensor model becomes an S times S diagonal observation matrix big O sub T, whose ith diagonal entry is P of E sub T, given X sub T equals I. On a day with U sub 1 equals true, big O sub 1 equals diagram of 0.90.2. On a day with U sub 3 equals false, big O sub 3 equals diagram of 0.10.8. Using column vectors, the forward equation becomes F sub 1. T plus 1 equals alpha big O sub T plus 1 dot T to the T dot F sub 1. T and the backward B sub K plus 1. T equals T dot big O sub K plus 1 dot B sub K plus 2. T. So forward, backward on a sequence of length T costs big O of S to the second T time and big O of ST space. And each elementary operation is a plain matrix vector product rather than a network traversal. The matrix form enables improved algorithms. A simple variation allows smoothing to be carried out in constant space, independently of the length of the sequence. Since the forward message satisfies F sub 1, T equals alpha big O sub T plus 1 dot T to the T minus 1, with the inverse relation F sub 1. T equals alpha T to the T dot big O sub T plus 1 dot F sub 1. T plus 1. A single backward pass can propagate both F and B together, but there are two significant restrictions. It requires that the transition matrix be invertible and that the sensor model have no zeros. Online smoothing with a fixed lag D. An algorithm whose time complexity is independent of the length of the lag derives a backward transformation matrix B, a product of T and big O matrices, that transforms a later backward message into an earlier one, with the incremental update B sub new equals big O sub T. D plus 1 to the minus 1 dot T to the minus 1 dot B sub old dot T dot big O sub T plus 1, giving fixed LAG smoothing's constant time recursive output. The localization example makes HMMs concrete. A robot moving on a 42 square grid with a uniform prior, a transition matrix T where P of next equals J, given I equals 1 over N of I for neighbors, and a 16-value sensor reading the 4 compass obstacle bits with per bit error rate epsilon. Filtering gives the posterior overlocation after each observation, With epsilon equals 0.20, the overall sensor reading is wrong 59% of the time. The robot is usually able to work out its location to within 2 squares after 20 observations, thanks to the algorithm's ability to integrate evidence over time. The same framework supports smoothing back to the start, and the Viterbi algorithm recovers the most likely path the robot has taken. HMMs as matrices. S times S transition T and diagonal observation big O sub T give constant space. Big O of S to the second T forward, backward, plus fixed lag and single pass smoothing. Localization example. Noisy sensor robot localization converges despite 59% wrong readings by integrating evidence over time. Kalman filters. Imagine watching a small bird flying through dense jungle foliage at dusk, or being a World War II radar operator peering at a faint, wandering blip, or Kepler trying to reconstruct the motions of the planets. These are all filtering, estimating the position and velocity of a moving object from noisy observations. And when the variables are continuous, the method is Kalman filtering, after one of its inventors, Rudolf Kalman. The bird's flight is 6 continuous variables: position x, y, z, and velocity. The models must be linear Gaussian. The next state x sub t plus 1 must be a linear function of the current state x sub t plus some Gaussian noise, a condition that turns out to be quite reasonable in practice. For constant velocity over interval delta, x sub next equals x sub t plus delta of x plus Gaussian noise. The key property that makes the filter work. The linear Gaussian family of distributions remains closed under Bayesian updating. If the current distribution and both models are linear Gaussian, then prediction and update both yield Gaussians, so filtering produces a Gaussian state distribution for all time. Why is it so important? The reason is that except for a few special cases such as this, filtering with continuous or hybrid networks generates state distributions whose representation grows without bound over time. The one-dimensional example, a random walk with Gaussian observation noise, like the Consumer Confidence Index, is worked with completing the square to show the predicted distribution P of x sub 1 has mean mu sub 0 and variance sigma sub 0 to the second plus sigma sub x to the second. The prediction flattens out, and the posterior P of x sub 1 given z sub 1 is a Gaussian whose new mean is a weighted mean of a new observation z sub t plus 1 and the old mean mu sub t if the observation is unreliable, sigma sub z large. We trust the old mean. If the process is unpredictable, sigma sub x large. We trust the observation. The univariate update rule makes the intuition arithmetic. Mu sub t plus 1 equals sigma sub t to the second plus sigma sub x to the second, z sub t plus 1 plus sigma sub z to the second, that mu sub t over sigma sub t to the second plus sigma sub x to the second plus sigma sub z to the second, a blend of prediction and observation in the ratio of their variances. And sigma sub t plus 1 to the second equals sigma sub t to the second plus sigma sub x to the second, sigma sub z to the second over sigma sub t to the second plus sigma sub x to the second plus sigma sub z to the second. Each new variance is strictly smaller than both the predicted variance and the observation noise, so the filter's estimate tightens with each measurement as long as the model is correct. The variance update is independent of the observation and converges quickly to a fixed value that depends only on sigma sub x and sigma sub z, substantially simplifying subsequent calculations. The general case uses matrix models P of x sub t plus 1 given x sub t equals n of x sub t plus 1 f dot x sub t, the sum over x, and P of z sub t, given x sub t equals n of z sub t, h dot x sub t, the sum over z, and the multivariate Gaussian's exponent being a quadratic form preserves Gaussians through the update, the property that allows Kalman filtering to work. Kalman filtering. Continuous state filtering with linear Gaussian models. The family is closed under Bayesian updating, so the state stays Gaussian. Weighted mean update. The new mean blends the prediction and observation by their relative variances. Variance converges to a fixed value independent of observations. Dynamic Bayesian networks. Dynamic Bayesian networks, DBNs, extend the semantics of standard Bayesian networks to handle temporal probability models, with any number of state variables x sub t and evidence variables e sub t per slice, links and CPTs exactly replicated from slice to slice, and variables have ing parents only in its own slice or the immediately preceding slice. The DBN corresponds to a Bayesian network with infinitely many variables. Every HMM is a DBN with one state and one evidence variable. Every discrete DBN can be represented as an HMM by a megavariable. What's the difference? The difference is that by decomposing the state, we can take advantage of sparseness. An HMM needs a transition matrix of size big O of D to the 2n, while the DBN representation has size big O of n to D to the k if the number of parents of each variable is bounded by k, linear rather than exponential, reducing the 42-location vacuum robot's probabilities from 10 to the 29th to a few thousand. Conversely, not every DBN can be represented by a Kalman filter. A Kalman filter state is always a single multivariate Gaussian distribution, a single bump, whereas DBNs can model arbitrary distributions, essential when my keys might be in my pocket, on the bedside table, on the kitchen counter, dangling from the front door, or locked in the car. A single Gaussian bump that included all these places would have to allocate significant probability to the keys being in midair, above the front garden. Constructing a DBN requires the prior P of x sub 0, the transition model, and the sensor model most conveniently specified for the first slice and copied. The battery monitoring robot, state variables position x sub t, velocity dot of xt, battery level battery t, with sensor measurements z sub t and b meter t, shows the modeling choices in depth. The Gaussian error model for the meter covers continuous and discrete noise, but real sensors fail. A transient failure. The battery level sensor might have a habit of sending a reading of 0 when someone bumps the robot, is mishandled by a pure Gaussian model. With 20 readings of 5, then a 0, the posterior distribution will assign a high probability to the batteries being empty, and after a second row, almost certain, a long stretch of high values quickly returns the estimate of 5, but there is a time when the robot is convinced that its battery is empty. Presumably, then, it should send out a mayday signal and shut down. The chapter is careful to note that the robot's recovery after the blip does not mean the algorithm thinks the battery magically recharged itself. Instead, the algorithm now believes that the battery was never low, and the extremely unlikely hypothesis that the battery meter had 2 consecutive huge errors must be the right explanation. The moral of the story: for the system to handle sensor failure properly, the sensor model must include the possibility of failure. A transient failure model, a small probability of a completely incorrect reading, e.g., p of 0 given full equals 0.03, gives the belief a certain amount of inertia that helps to overcome temporary blips. But a persistent failure, 20 readings of 5, then 20 of 0, still fools the transient model, the robot gradually coming to believe that its battery is empty. The full fix requires a persistent failure model. Augment the state with BM broken, linked by persistence arc, small failure probability 0.001, stays broken once broken, so that when broken the sensor always reads 0, and when OK, it uses the transient model. With this, the probability the sensor is broken rises quickly to almost 1 and stays there under persistent failure, and drops back to 0 after a blip resolves. Dynamic Bayesian networks can model even subtle phenomena, such as sensor drift, sudden decalibration, and the effects of exogenous conditions. Exact inference in DBNs begins with unrolling, replicating slices until the network is large enough to accommodate the observations, then applying any Chapter 13 algorithm, but a naive application of unrolling would not be particularly efficient. It needs big O of t space and big O of t per update time. The filtering update in equation 14.5 works by summing out the state variables of the previous time step, and running variable elimination with the variables in temporal order exactly mimics the operation of the recursive filtering update, keeping at most 2 slices in memory, constant space, and time per filtering update. Now for the bad news: the constant is, in almost all cases, exponential in the number of state variables, because the factors grow to include all the state variables, or more precisely, all those state variables that have parents. The curse raised in the HMM section returns. Such factors can be approximated or handled by the approximate inference of Chapter 13, or by factoring the state into subprocesses with the interface algorithm. DBNs versus HMMs and Kalman filters. Factoring the state gives linear, not exponential, model size. DBNs subsume both, and unlike Kalman filters can represent arbitrary, multimodal distributions. Modeling sensor failure. Gaussian inertia models fail on transient blips. Transients need a failure term. Persistent failures need an explicit broken status variable with a persistence arc. Unrolling and exact inference. Replicate slices and run variable elimination in temporal order for constant time filtering. Exponential in the number of state variables, not in time. Chapter 15. Probabilistic Programming. Relational Probability Models. Chapter 15 unifies the two previous tracks, first-order logic and probability, into first-order probability models, and from them into probabilistic programming languages. PPLs, declarative PPLs, bear roughly the same relationship to general PPLs as logic programming does to general programming languages. For a first-order probability model, it seems we need the possible worlds to be those of first-order logic, a set of objects with relations among them, and an interpretation that maps constant symbols to objects, predicate symbols to relations, plus a probability for each such possible world. Then P of phi equals the sum over worlds where phi holds. But the set of first-order models is infinite, so the summation in equation 15.1 could be infeasible, and specifying a complete, consistent distribution over an infinite set of worlds could be very difficult. Database semantics sidesteps this. The unique names assumption for constants and domain closure. There are no more objects beyond those that are named. Guarantee a finite set of possible worlds. Models defined this way are relational probability models, RPMs, with the most significant difference from database semantics being that RPMs do not make the closed world assumption, since in a probabilistic reasoning system, we can't just assume that every unknown fact is false. The book recommendation example drives the semantics. A retailer evaluates product quality from customer recommendations, but some customers are kinder than others and some are less honest. Kind customers give high recommendations even of fairly mediocre books. Dishonest ones give extreme scores for reasons other than quality. They might be paid to promote some publishers' books. With one customer and one book, the Bayes net is tiny. With many customers and books, it is quite impractical to specify a Bayes net by hand. Fortunately, the network has a lot of repeated structure. Every recommendation of CB node has parents honest of C, kindness of C, quality of B, with identical CPTs tailor-made for a first-order language. Written as a dependency recommendation of CB tilde rec CPT of honest of C kindness of C quality of B. RPMs have constant, function, and predicate symbols with type signatures. If the type of each object is known, many spurious possible worlds are eliminated. The basic random variables are obtained by instantiating each function with each possible combination of objects, finite thanks to domain closure. The model is completed by one dependency statement per function. Honest of C tilde 0.990.01. Kindness of C tilde 0.10.10.20.30.3. Quality of B tilde 0.05, 0.20.4, 0.20.15, and the rec CPT with 2.5.5 equals 50 rows, whose semantics can be obtained by instantiating these dependencies for all known constants, giving a Bayesian network. With C customers and B books, there are 2 to the C.5 to the C plus B C possible worlds, with 10 million books and a billion customers. That's about 10 to the 7, 101, 015 worlds, yet the complete probability model still has only fewer than 300 parameters. The dependency language permits context-specific independence. Dishonest customers ignore quality when giving a recommendation. So recommendation C, B, is independent of kindness C and quality B, when honest C equals false, written as if honest C. Then honest rec CPT, kindness C, quality B, else 0.4, 0.1, 0.0, 0.1, 0.4. This kind of dependency may look like an ordinary if-then-else statement in a programming language, but there's a key difference. The inference engine doesn't necessarily know the value of the conditional test because honest C is a random variable. Elaborations nest, a fan of the author, always gives the book a 5, regardless of quality. And when author B is unknown, the system may have to reason about all possible authors. Author B2 becomes a random variable parent acting as a multiplexer, selecting which of fan C1, a 1, and fan C1, a 2, influences the recommendation. An instance of relational uncertainty. where uncertainty affects the dependency structure of a network. The chapter marvels at the emergent inference. If 3 other customers are fans of A1, and all 3 have given B2 a 5, even though most other customers find it quite dismal, then it is extremely likely that A1 is the author of B2. The emergence of sophisticated reasoning like this from an RPM model of just a few lines is an intriguing example of how probabilistic influences spread through the web of interconnections among objects. The player skill example shows frequency style modeling. Each player has an underlying skill. Each game's performance, I, may vary from the underlying skill level, and the winner is the player whose performance in G is better. So when I, J, G equals if game G, I, J, then performance I, G, performance JG, a probabilistic yellow-like rating that yields posterior skill distributions from game outcomes. RPM semantics, first-order possible worlds over named objects, unique names plus domain closure, with type functions and per-function dependencies, no closed-world assumption. Dependencies Bayes nets. Instantiating dependencies over all constants yields a Bayesian network. Compact first-order statements replace hand-specified CPTs. Relational uncertainty. Unknown object identities like author act as multiplexer parents, letting probabilistic influence flow through object interconnections. Open universe probability models. Open universe probability models, OUPMs, abandon RPM's assumption that we know exactly the set of relevant objects that exist and can identify them unambiguously, an assumption simply untenable in many real-world settings. The book retailer example shows why. A book may have several ISBNs corresponding to hardcover, paperback, large print, reissues, and the retailer may not know for sure which ISBNs are really the same book. Worse, a dishonest customer may have thousands of log IDs, which in the computer security field are called Sybils, and their use to confound a reputation system is called a Sybil attack. The phenomena are pervasive. A vision system doesn't know what exists, if anything, around the next corner, or if the object it sees now is the same one it saw a few minutes ago. A tech system must reason about whether Mary, Dr. Smith, she is cardiologist, and his mother refer to the same object. An intelligence analyst never knows how many spies there really are. A major part of human cognition seems to require learning what objects exist and being able to connect observations, which almost never come with unique IDs attached to hypothesized objects. The chapter thus builds open universe probability models based on the standard semantics of first-order logic, yet guaranteeing a unique, consistent probability distribution over the infinite space of possible worlds. The syntax and semantics transfer the insight of Bayes nets, generate each possible world, event by event, in the topological order, to the first-order setting. RPMs extend this to entire sets of events, defined by the possible instantiations of the logical variables. OUPMs go further by allowing generative steps that add objects to the possible world under construction, where the number and type of objects may depend on the objects that are already in that world and their properties and relations. The event being generated is not the assignment of a value to a variable, but the very existence of objects. Number statements specify conditional distributions over the numbers of objects of various kinds. In the retailer domain, the number of customers is uniform between 1 and 3, books uniform between 2 and 4, and the Sybil sensitive statement. The number of login IDs for customer C is if honest C, then exactly 1, else uniform int 2, 5, where the owner function is called an origin function because it says where each object generated by this number statement came from. The Poisson distribution models unbounded counts. A variable x sampled from Poisson of lambda has p of x equals k equals lambda to the k e to the minus lambda over k, with mean and variance both lambda. So for large values of lambda, the distribution is narrow relative to the mean. A nest of a million ants has a standard deviation of only 1,000 or 0.1%. The discrete log normal and order of magnitude distributions suit even wider scales. OM of 3,1 has a mean of 10 to the third and a standard deviation of 1 order of magnitude. Because the number of objects can be unbounded, the number of random variables in an OUPM is unbounded, and inference requires reasoning over a potentially infinite space of possible worlds, a challenge addressed by computing with the repeated structure of identical random variables rather than instantiating them all, and by the sampling machinery of the following sections. A well-formed OUPM, therefore, needs a type-consistent generative process. The model must be designed so that the objects of each type are generated before the random variables that depend on them are instantiated, and the dependency graph among functions must be acyclic. The OUPM analog of the Bayes-Net non-redundancy guarantee, ensuring a unique, consistent probability distribution, despite the open universe. OUPM semantics. Number statements, conditional distributions over object counts, plus origin functions. Worlds differ in which objects exist, not just their values. Identity/existence uncertainty. ISBNs and symbols epitomize the fact that observations rarely come with reliable unique IDs. Unbounded counts. Poisson and log normal/order of magnitude distributions model object count uncertainty. Acyclic. Type-consistent generation guarantees well-defined distributions. Keeping track of a complex world. Chapter 14's tracking makes sense for worlds with a single object, but what happens when two or more objects generate the observations introduces uncertainty about which object generated which observation. The identity uncertainty problem in its temporal form, known in control theory as the data association problem. The motivating context is radar tracking of multiple targets. Blips appear on the screen each time step, but there is no direct observation of which blips at time t correspond to which blips at time t-1. The multi-target tracking example assumes two aircraft, A1 and A2, in OUPM terms, guaranteed objects, each moving by a linear Gaussian model and producing blips whose observed positions are linear functions of the aircraft position plus Gaussian noise. The key difference between this model and a standard Kalman filter is that there are two objects producing sensor readings, so each possible world in this model includes an association between aircraft and blips, and for n objects and t-time steps, there are nt ways of assigning blips to aircraft, an awfully large number. Real applications add false alarms, clutter, detection failures, and track initiation/termination, phenomena which create even more possible worlds. Tens of thousands of papers have worked out the complex probabilities for tracking. In one sense, this is unnecessary once the model is expressed in a probabilistic programming language, because the general-purpose inference engine does all of the mathematics correctly for any model, and elaborations of the scenario can be handled by small changes to the model. The hard part is inference. The filtering distribution ends up as a mixture of exponentially many distributions, one for each way of picking a sequence of observations to assign to each aircraft. Approximations abound. The nearest neighbor filter repeatedly chooses the closest pairing of predicted position and observation, working when the objects are well separated. In other words, when there is no possibility of confusion, the Hungarian algorithm chooses the assignment that maximizes the joint probability of the current observations given the predicted positions, efficiently even within candidates. But any method that commits to a single best assignment at each time step fails miserably under more difficult conditions, because if the algorithm commits to an incorrect assignment, the prediction at the next time step may be significantly wrong. Sampling, especially MCMC, which explores the space of assignment histories and can change its mind about previous assignment decisions, proves robust and Rao-Blackwellization. Given an association hypothesis, the filtering calculation for each object can typically be done exactly. Just means running a Kalman filter for the sequence of observations. Current MCMC data association methods handle many hundreds of objects in real time. The traffic monitoring application, two cameras 2 miles apart on a California freeway, shows the same machinery at scale. Goals are estimating travel times and measuring origin-destination demand. False alarms are caused by moving shadows, articulated vehicles, reflections in puddles, detection failures by occlusion, fog, darkness. Vehicles are constantly entering and leaving. Appearance changes between cameras. The prediction error, far greater than the typical separation between vehicles. Yet, modern data association algorithms have been successful in estimating traffic parameters in real-world settings. The section's verdict. Data association is an essential foundation for keeping track of a complex world, because without it there is no way to combine multiple observations of any given object. Programs as probability models. Many PPLs have been built on the insight that probability models can be defined using executable code in any programming language that incorporates a source of randomness. The possible worlds are execution traces, and the probability of any such trace is the probability of the random choices required for that trace to happen. Building on an underlying language inherits complex data structures, recursion, and, in some cases, higher-order functions, and many PPLs are in fact computationally universal. They can represent any probability distribution that can be sampled from by a probabilistic Turing machine that halts. The reading text example, degraded or smudged text, CAPTCHAs, shows a generative program with a way to generate a sequence of letters and a way to generate a noisy, blurry rendering of these letters using an off-the-shelf graphics library. Generate image draws the letter count from a Poisson distribution, each letter from a uniform choice. Then render noisy image adds per pixel Gaussian noise with its own variance. The syntax and semantics formalize this. A generative program is an executable program in which every random choice defines a random variable in an associated probability model. Unrolling the execution. Let she be the random variable corresponding to the ith random choice. An execution trace is a sequence of possible values for the random choices, and the space of all possible execution traces can be viewed as the sample space of a probability model with the probability distribution over traces, defined as the product of the probabilities of each individual random choice, analogous to the distribution over worlds in an OUPM. Any OUPM converts to a generative program mechanically, with the main extra work to create data structures that represent the objects, functions, and relations. The unrolled trace for the image OCFLWE would have 4,104 nodes, 1 node for the variable n, 6 node for the variable's letters, 1 node for the noise variance, and 4,096 nodes for the pixels. So this generative program defines an open universe probability model. The number of random choices it makes is not bounded a priori. Inference runs by MCMC over traces. 3 runs of 25 iterations correctly recover letters from noisy images, and a Markov letter model, generate Markov letters, yields sequences of letters that are easier to pronounce, reflecting prior knowledge of plausible letter sequences in the posterior. The rapid growth of the field of probabilistic programming closes the chapter as the modern synthesis. Declarative PPLs, first-order declarative models with lifting, and general-purpose PPLs, arbitrary code with MCMC inference. Each serve as a universal language for probabilistic knowledge representation and inference in uncertain domains. The chapter's stated theme. Data association. Multi-target tracking adds identity uncertainty on top of state estimation. In objects and t-steps give NT associations. Track hypotheses. Nearest neighbor and Hungarian assignment commit greedily and fail under confusion. MCMC over association histories, with Rao-Blackwellization for exact Kalman subfilters, scales to hundreds of objects. Generative programs. Arbitrary executable code, with random choices, defines an open universe probability model over execution traces. Inference is MCMC over the trace space. Open universe probabilistic models, OUPMs, go beyond RPMs in a critical way. Rather than assuming a fixed, known set of objects with fixed types, the model can include statements about how many objects there are. The number of objects is itself uncertain. The syntax adds number statements. A number statement like the count aircraft, number of aircraft, tilde Poisson of lambda, and a type hierarchy with subtyping. A guaranteed aircraft is an aircraft, and arbitrary deterministic facts. The space of possible worlds is wider than in RPMs. Worlds differ not only in the values of basic random variables, but in the objects that exist. The number of objects can vary from one possible world to another, and the mapping from symbols to objects is a source of uncertainty. An OUPM's constraints, number statements, type hierarchy, and deterministic relations, must be backed by a type-consistent generative process. The model must be designed so that the objects of each type are generated before the random variables that depend on them are instantiated, and the dependency graph must be acyclic to define a proper distribution over worlds. Because the number of objects is unbounded, the number of random variables in an OUPM is unbounded, and inference requires reasoning over a potentially infinite space of possible worlds, tackled by lifting and by the sampling methods of the next sections. Part 5. Machine Learning. Chapter 16. Making simple decisions. Combining beliefs and desires under uncertainty. Chapter 16 closes the loop on the standard model. The MEU principle could be seen as a prescription for intelligent behavior. All an intelligent agent has to do is calculate the various quantities, maximize utility over its actions, and away it goes. But this does not mean that the AI problem is solved by the definition. The agent has actions, assigns a probability PS to each possible current state, and has a transition model P of S given SA. The probability of reaching S by doing in the current state is P of result of equals S equals the sum over SP of S dot P of S given SA. In the episodic case, the utility function U of S assigns a single number to express the desirability of a state, and the expected utility of an action is EU of equals the sum P of result of equals S dot U of S. Maximum expected utility, MEU, says a rational agent should choose the action that maximizes the agent's expected utility. A equals argmax, a EU of A. The chapter is careful that decision theory is not a panacea that solves the AI problem, but it does provide the beginnings of a basic mathematical framework that is general enough to define the AI problem. Estimating P of S requires perception, learning, knowledge representation, and inference. Computing outcomes requires a causal model of the world. There may be many actions. Computing U of S may itself require further searching or planning, and an AI system acting on behalf of A human may not know the human's true utility function. MEU connects to Chapter 2's performance measures. If an agent acts so as to maximize a utility function that correctly reflects the performance measure, then the agent will achieve the highest possible performance score, averaged over all the possible environments. This is the central justification for the MEU principle itself. The transition is crucial. The performance measure gives a score for a history, a sequence of states. Thus, it is applied retrospectively after an agent completes a sequence of actions. The utility function applies to the very next state, so it can be used to guide actions step by step. MEU principle. Choose the action maximizing expected utility, the general prescriptive statement of rational behavior. MEU is not a panacea. It formalizes do the right thing without operationalizing the many hard subproblems under it. Performance measure utility function. The retrospective history score becomes a step-by-step decision guide. The basis of utility theory. Why should maximizing the average utility be so special? What's wrong with maximizing the weighted sum of the cubes of the possible utilities or trying to minimize the worst possible loss? The answers come from constraints on rational preferences, from which MEU can be derived. Preferences are written A succeeds B, prefer A, tilde operator B, indifferent. A succeeds above single line equals sign B, prefer or indifferent. Because there is uncertainty about what is really being offered, the airline passenger's pasta or chicken could be delicious or congealed. The set of outcomes for each action is a lottery. L equals P1, S1, P2, S2, P innocent, where each outcome C can be either an atomic state or another lottery. 6 axioms constrain any reasonable preference relation. Orderability, exactly one of A succeeds B, B succeeds A, or a tilde operator B holds, the agent cannot avoid deciding. As noted, refusing to bet is like refusing to allow time to pass. Transitivity, continuity, a lottery between A and C can match any intervening B with an adjusted probability. Substitutability, indifferent lotteries are interchangeable in any context. Monotonicity, the lottery that has a higher probability for a, and decomposability, the no fun in gambling rule, compressing compound lotteries by the laws of probability. Each axiom is motivated by patently irrational behavior for violators. The non-transitive agent could be fleeced until the agent has no money at all by a cycle of penny trades ACBA. From the axioms von Neumann and Morgenstern, 1944, 2 consequences follow. Existence of a utility function. If preferences obey the axioms, there exists a function U such that U of A is greater than U of B if and only if A is preferred to B. Expected utility of a lottery. U of P sub 1S sub 1. P sub in S sub n equals the sum P sub I dot U of S sub I. So an agent can act rationally, that is consistently with its preferences, only by choosing an action that maximizes expected utility. The utility function is not unique. An agent's behavior is unchanged under a positive affine transformation US equals a dot U of S plus B for is greater than 0. A temperature in Fahrenheit is 1.8 times the Celsius temperature plus 32, and in a deterministic environment, only a preference ranking, a value function or ordinal utility function, is needed. Finally, the existence of a utility function that describes an agent's preference behavior does not necessarily mean that the agent is explicitly maximizing that utility function in its own deliberations. Rational behavior can be generated in any number of ways, including table lookup, yet by observing a rational agent's behavior, an observer can learn about the utility function that represents what the agent is actually trying to achieve. Axioms of utility: orderability, transitivity, continuity, substitutability, monotonicity, decomposability. Violations yield exploitable irrationality. Von Neumann, Morgenstern theorem, axioms: existence of a utility function and expected utility of lottery form. Affine invariance. Utilities are unique up to positive affine transformations. Ordinal rankings suffice in deterministic settings. Utility functions. Utility functions map from lotteries to real numbers. Strictly speaking, that is it. An agent can have any preferences it likes. An agent might prefer a prime number of dollars in its bank account, or a dented 1973 Ford Pinto to a shiny new Mercedes. We can't call it irrational. Preference elicitation involves presenting choices to the human and using the observed preferences to pin down the underlying utility function. With no absolute scale, we fix the utility of a best possible prize at US equals UTOP and a worst possible catastrophe at US equals UBIT. Normalized utilities set UTOP equals 1, UBIT equals 0. An England fan might assign a utility of 1 to England winning the World Cup and 0 to England failing to qualify. The utility of any prize S is assessed by adjusting the probability P in a standard lottery, P, UTOP, 1 minus P, UBIT, until the agent is indifferent. Assuming normalized utilities, the utility of S is given by P. If the England fan is indifferent at P equals 0.3 between the semi-final and lose outcome and a 30% chance of the trophy, that outcome's utility is 0.3. The hard case is when people's lives are at stake. Although nobody feels comfortable with putting a value on human life, it is a fact that trade-offs on matters of life and death are made all the time. Overhauls, car safety, air pollution that kills 4 million people a year. Paradoxically, a refusal to put a monetary value on life can mean that life is undervalued. Schachter's agency rejected a study that assumed a dollar value for a child's life and then decided against asbestos removal, implicitly asserting a lower value for the life of a child. U.S. agencies use the value of a statistical life. Typical values in 2019 are roughly $10 million. Preference elicitation and standard lotteries. Adjust P until indifference. Normalized utilities pin the scale to 0. Value of life. Refusing to price a life can undervalue it. Agencies use a statistical value of life for cost-benefit analysis. Multi-attribute utility functions. Decision-making in the field of public policy involves high stakes, in both money and lives. Allowing harmful emissions from a power plant weighs the prevention of death and disability against the benefit of the power and the economic burden. Airports siting weighs construction disruption, land cost, distance for population, noise, and safety. Problems like these, in which outcomes are characterized by 2 or more attributes, are handled by multi-attribute utility theory. In essence, it's the theory of comparing apples to oranges. The analysis is eased by arranging so that higher values of an attribute always correspond to higher utilities. Use the number of deaths D as minus D. Split a temperature attribute with a peak at 70 degrees Fahrenheit into T minus 70 to measure whether the room is warm enough, and 70 minus T to measure whether it is cool enough, each monotonically increasing until they reach their maximum utility value at 0. The airport attributes can be throughput, flights per day, safety, minus expected deaths per year, quietness, minus people under flight paths, and frugality, negative construction cost. Dominance lets decisions be made without combining the attribute values into a single utility value. If airport site S1 costs less, generates less noise pollution, and is safer than S2, there is strict dominance. One would not hesitate to reject S2. And if an option is of lower value on all attributes than some other option, it need not be considered further, although it seldom yields a unique choice. The uncertain analog requires all possible concrete outcomes for S1 strictly dominate all possible outcomes for S2, which will probably occur even less often. The more useful generalization is stochastic dominance, which occurs very frequently in real problems. If the cost of S1 is uniform between $2.8 billion and $4.8 billion and S2s between $3 billion and $5.2 billion, then given only the information that the more frugal choice is better, S1 stochastically dominates S2, i.e. S2 can be discarded. And it is important to note that this does not follow from comparing the expected costs. Knowing S1's exact cost of $3.8 billion would leave the decisionless, because in the absence of exact cost information, the decision is easier to make but is more likely to be wrong. Formally, a sub-1 stochastically dominates a sub-2 on X if its cumulative distribution always lies to the right. The sum over X P sub-1 X if X is less than or equal to the sum over X P sub-2 X if X, and then for any monotonically non-decreasing utility function U, X, the expected utility of sub-1 is at least as high as the expected utility of sub-2, proved by integrating over cumulative probability instead of X. The intuitive version is the following example. Would you rather fall headfirst on a concrete from 3 millimeters or 3 meters? The 3 millimeter fall stochastically dominates on safety because for any given level of damage, the probability that you'll incur at least that level of damage is higher when falling from 3 meters. This kind of reasoning comes as second nature to humans. It's so obvious we don't even think about it, and algorithms propagate such qualitative information in qualitative probabilistic networks to make rational decisions without using any numeric values. Preference structure and multi-attribute utility identifies regularity, so we don't need to specify all d to the n values individually. Having identified some regularity in preference behavior, we then derive representation theorems, giving u of x sub 1. X sub n equals if x sub 1 x sub 1. F sub n x sub, and where f is a simple function such as addition. Notice the similarity to the use of Bayesian networks to decompose the joint probability. In the deterministic case, preference independence is the basic regularity. Two attributes x sub 1 and x sub 2 are preferentially independent of a third attribute x sub 3 if the preference between outcomes does not depend on the particular value x sub 3. In the airport problem, quietness and frugality are preferentially independent of safety. The 4-billion $20,000 people outcome is preferred over the chapter 3 verse 7-billion $70,000 price one at both safety level 0.006 and 0.012. The set quietness, frugality, safety exhibits mutual preferential independence, MPI. Each attribute may be important, but does not affect the way in which one trades off the other attributes. MPI yields, DeBrew, 1960, the additive form V of x sub 1. X sub n equals the sum V sub I x sub I. E.g., the airport decision can be made using a value function V of quietness, frugality, safety equals quietness, that 10 to the 4th plus frugality plus safety, 10 to the 12th. The weights appear as multiplying constants. Multivariate assessment. Monotonically increasing attribute transformations, negative cost, split temperature, standardized comparisons. MPI gives additive value functions. Strict versus stochastic dominance. Discard options dominated on all attributes. Stochastic dominance. Cumulative distribution dominance. Works for every monotone utility. Used without numeric values in qualitative networks. Preference independence / MPI. Trade-off between two attributes are independent of the other's levels, yielding the additive representation. Decision networks. Decision networks, or influence diagrams, combine Bayesian networks with additional node types for actions and utilities, providing a substrate for implementing utility-based agents of the type first introduced in section 2.4.5. The airport siting problem illustrates the three node types. Chance nodes, ovals, are random variables just as they do in Bayesian networks. Uncertainty about construction cost, air traffic, litigation, safety, quietness, frugality, and in decision networks, the parent nodes can include decision nodes as well as chance nodes. Decision nodes, rectangles, represent points where the decision maker has a choice of actions. Airport site taking each candidate site. Utility nodes, diamonds, represent the agent's utility function, with as parents all variables describing the outcomes that directly affect utility. A simplified form omits the outcome chance nodes and connects the utility node directly to current state and decision nodes, representing the expected utility associated with each action. An action utility function, a Q function in reinforcement learning terms. Because the quietness, safety, and frugality chance nodes refer to future states, they can never have their values set as evidence variables. So the simplified form works whenever the general does, but it is less flexible. A change in aircraft noise levels in the utility table can be reflected by editing the quietness CPT in the general form, whereas in the action utility diagram, all such changes have to be reflected by changes to the action utility table, which is a compiled version of the original formulation, obtained by summing out the outcome state variables. Evaluating decision networks is straightforward. Set the current state evidence. For each possible value of the decision node, set it. Calculate the posterior probabilities for the parent nodes of the utility node using a standard probabilistic inference algorithm, and calculate the resulting utility for the action. Return the action with the highest utility. The evaluation can utilize any available Bayesian network algorithm and can be incorporated directly into the agent design. Series of actions make the problem much more interesting. Chapter 17's territory. 3 node types: chance, random variables, decision, actions, utility, preferences over outcomes. Parents of utility are the directly relevant outcome variables. General versus action utility form. The simplified diagram compiles out outcome states into a Q table, trading flexibility for fewer nodes. Evaluation. Set evidence. Instantiate each action. Compute expected utility of the utility node parents. Choose the max. The value of information. One of the most important parts of decision-making is knowing what questions to ask. Information value theory enables an agent to choose what information to acquire, a simplified form of sequential decision-making in which observation actions affect only the agent's belief state, not the external physical state, and the value of any particular observation must derive from the potential to affect the agent's eventual physical action. The oil drilling example computes it concretely. In indistinguishable blocks, exactly one containing oil worth C, priced at C/N, a clairvoyant survey of block 3 changes expected profit from 0 to C/N. So, the information is worth C/N dollars. In general, the value of a given piece of information is defined to be the difference in expected value between best actions before and after information is obtained. The general formula for perfect information is VPI of E sub j equals the sum over E underscore j, P of E sub j equals E sub j, EU of alpha, given E sub j equals E sub j minus EU of alpha, averaging over what we might discover. 3 generic cases give intuition. 2 routes through a mountain range in A, the tunnel route, will almost certainly remain superior, so the information is not needed. In B, the dirt road choice with an injured passenger has broad, overlapping outcome distributions. Information is crucial. In C, summer travel would change the plan, but the value difference is tiny. Information is less valuable. In sum, information has value to the extent that it is likely to cause a change of plan and to the extent that the new plan will be significantly better than the old plan. Properties follow. The expected value of information is non-negative. VPI of E sub j is greater than or equal to 0. You can always choose to ignore it, though there is typically a large difference between the expected value of information and its maximum value. VPI depends on the current state of information and is not additive. VPI of E sub j E sub k is not equal to VPI of E sub j plus VPI of E sub k in general, because the value of acquiring a variable can go down if another variable strongly constrains its posterior or up. But VPI is order independent. VPI of E sub j E sub k equals VPI of E sub j plus VPI of E sub k given E sub j equals VPI of E sub k E sub j. An information gathering agent repeatedly requests the observation with the highest VPI of E sub j over C of E sub j ratio while it exceeds cost. A myopic, greedy policy that often works well in practice has been shown to outperform expert physicians in selecting diagnostic tests, but can fail when no single variable helps much. Non-myopic gathering is hard in general, 2 to the n subsets, super exponential trees, but the treasure hunt problem, independent treasures with costs, is solved by sorting locations by the ratio P of I over C of I, proved optimal by the pairwise flip, sensitivity analysis, argument showing. The direction of the change in the cost of the whole sequence depends only on the direction of the change in cost of the pair of elements being flipped. VPI formula. Expected gain from averaging over the possible evidence. Non-negative, order-independent, but not additive. 3 informational cases. Inevitable, crucial, and low-stakes information. Value follows from change of plan and magnitude of improvement. Myopic versus non-myopic. Greedy VPI over C works well, better than expert physicians at test selection. Treasure hunt orderings are provably optimal under cost/probability sorting. Unknown preferences. Chapter 16 closes by relaxing the assumption of a known utility function, the chapter's most consequential idea, connecting back to Chapter 1's value alignment, the most important of which is deference to humans. Until now, we assumed that the agent knows the utility function of the human on whose behalf it acts. In reality, a machine may be uncertain about the true objectives of the humans whose preferences it is supposed to satisfy. The chapter foreshadows reasoning that treats the utility function itself as a random variable whose posterior is learned from behavior and other evidence, and it notes how this uncertainty changes the agent's conduct. Acting cautiously, asking permission, gathering information about preferences rather than merely optimizing a fixed given objective. This thread, first raised in section 1.1.5 on beneficial machines, is developed into the framework of assistance. An agent serving a human it does not fully know, and returns as the foundation of Chapter 27 safety discussion and Chapter 28's look at the future of AI. Preference uncertainty. The utility function is not automatically given. The agent must infer it and act with deference. Deference. Under preference uncertainty, the rational agent behaves cautiously and seeks to learn the human's true objectives. Chapter 17. Making complex decisions. Sequential decision problems. Chapter 17 moves decision-making from one shot to sequential decision problems. An agent situated in the 4x3 environment must choose an action at each time step, with the interaction terminate ing when the agent reaches one of the goal states, marked +1 or -1. If the environment were deterministic, a solution would be easy, up, right. But the actions are unreliable. Each action achieves the intended effect with probability 0.8. But the rest of the time, the action moves the agent at right angles to the intended direction, and if the agent bumps into a wall, it stays in the same square. The transition model is now stochastic and Markovian. The probability of reaching S from S depends only on S and not on the history of earlier states. To complete the problem, we must specify the utility function, and for every transition from S to S via action A, the agent receives a reward R is bounded by plus or minus Rmax. Here -0.04 for all transitions except those entering terminal states, giving the agent an incentive to reach, 3, quickly. The agent does not enjoy living in this environment. A sequential decision problem for a fully observable, stochastic environment with a Markovian transition model and additive rewards is a Markov decision process. MDP states with an initial state, actions per state, a transition model, and a reward function. Methods for solving MDPs usually involve dynamic programming. Simplifying a problem by recursively breaking it into smaller pieces and remembering the optimal solutions. No fixed action sequence can solve the problem because the agent might end up in a state other than the goal. Therefore, a solution must specify what the agent should do for any state. A solution of this kind is called a policy, written pi, with pi of S the recommended action. The quality of a policy is measured by the expected utility of the possible environment histories generated by that policy, and pi star denotes an optimal policy. A policy represents the agent function explicitly and is therefore a description of a simple reflex agent, computed from the information used for a utility-based agent. The 4x3 world's optimal policies show the balance of risk and reward Chong, ing, depending on the value of our equals R of SAS. For sufficiently negative, our life is so painful that the agent heads straight for the nearest exit, even if the exit is worth -1. For mild negative, the agent takes no risks at all, steering away from the -1 state. For R is greater than 0. Life is positively enjoyable, and the agent avoids both exits, yielding infinite total reward. Utilities over time settle on additive discounted rewards. U of S sub 0, a sub 0 s sub 1 equals r of s sub 0 a sub 0 s sub 1 plus gamma r of s sub 1 a sub 1 s sub 2 plus gamma to the second r of s sub 2 a sub 2 s sub 3 plus dots. C with discount factor gamma in 0, 1. The first question is whether there is a finite horizon or an infinite horizon for decision-making. With a finite horizon and the game is over, so an optimal action in a given state may depend on how much time is left. A non-stationary policy with no fixed limit, there is no reason to behave differently in the same state at different times. Hence, the optimal policy is stationary, which is why the chapter deal S mainly with the infinite horizon case. 4 justifications for discounted rewards. Both humans and animals appear to value near-term rewards more highly. Economic. Early rewards can be invested and produce returns, so gamma equals 0.9 is equivalent to an interest rate of 11.1%. Uncertainty, a discount factor, is equivalent to adding a probability 1 minus gamma of accidental termination at every time step. And stationarity of preferences, if you prefer one future to another starting tomorrow, then you should still prefer that future if it were to start today instead. And additive discounting is the only form of utility on histories that satisfies it. Discounting makes some nasty infinities go away. With gamma is less than 1 and bounded rewards, the utility of an infinite sequence is finite. Gamma to the t dot are submax sums to our submax over 1 minus gamma. Alternatives. Proper policies guaranteed to reach a terminal state allow gamma equals 1. Undiscounted additive rewards. An average reward per time step handles infinite sequences. But improper policies can cause the standard algorithms for solving MDPs to fail with additive rewards, and so provide a good reason for using discounted rewards. So, additive discounted rewards present the fewest difficulties in evaluating histories, and we shall use them henceforth. Optimal policies and the utilities of states. The expected utility of policy pi from state S is u to the pi s equals e, the sum gamma to the tr of, and the true utility of a state is u of s, the expected sum of discounted rewards if the agent executes an optimal policy. A remarkable consequence of using discounted utilities with infinite horizons is that the optimal policy is independent of the starting state, though this does not hold for finite horizon policies or for other ways of combining rewards over time, such as taking the max. Utilities let the agent act by MEU. Pi of s equals argmax of the sum p of s given SAR of SAS plus gamma u of s. Figure 17.3's utilities are higher for states closer to the +1 exit because fewer steps are required. MDP definition. States, actions, Markovian stochastic transitions, rewards, solutions or policies measured by expected discounted utility. Additive discounted rewards. Gamma justifies discounting behaviorally, economically, and via preference stationarity, and keeps infinite horizon utilities finite. Stationary optimal policies. With infinite horizon discounting, the optimal policy is independent of the start state. Algorithms for MDPs. Chapter 17 presents 4 different algorithms for solving MDPs. Value iteration, policy iteration, and linear programming generate exact solutions offline, and a family of online approximate algorithms that includes Monte Carlo planning. Value iteration starts from the Bellman equation, the basis of the value iteration algorithm, and applies the Bellman update u sub a plus 1 of s equals max of the sum p of s given SAR of SAS plus gamma u sub I of s simultaneously to all the states at each iteration, converging to the unique solution of the Bellman equations. The update propagates this information through the state space by means of local updates. With the 4x3 worlds utilities accumulate a negative reward until a path is found to 4-3, whereupon the utilities start to increase. Convergence rests on the notion of a contraction, a function that when applied to 2 different inputs in turn produces 2 output values that are closer together by at least some constant factor like divide by 2, and the Bellman update is a contraction by a factor of gamma on the space of utility vectors under the max norm, with the 2 properties that a contraction has only one fixed point and repeated application always reaches the fixed point in the limit. Thus, value iteration always converges whenever gamma is less than 1, with the error reduced by a factor of at least gamma on each iteration, so value iteration converges exponentially fast, needing about log of 2 are submax over epsilon over log of 1 over gamma iterations. N grows rapidly as gamma becomes close to 1. We can get fast convergence if we make gamma small, but this effectively gives the agent a short horizon. The policy loss, the most the agent can lose by executing pi sub I instead of the optimal policy, often becomes optimal long before u sub I has converged in the 4x3 environment with gamma equals 0.9. The policy pi sub I is optimal when I equals 5, even though the maximum error in u sub I is still 0.51. Policy iteration exploits the insight that it is possible to get an optimal policy even when the utility function estimate is inaccurate. It alternates policy evaluation. Given a policy pi sub I, calculate u sub I equals u to the pi underscore I, the utility of each state if pi were to be executed. With policy improvement, calculate a new MU policy pi sub I plus 1. Using one-step look-ahead based on u sub, terminating when the policy improvement step yields no change, at which point pi sub I must be an optimal policy. Because there are only finitely many policies for a finite state space, and each iteration can be shown to yield a better policy, policy iteration must terminate. Policy evaluation is simpler than solving the standard Bellman equations, because the action in each state is fixed by the policy, giving a linear system of n equations and n unknowns solvable exactly in time big O of n to the third. For large spaces, modified policy iteration performs some number of simplified value iteration steps with the policy fixed. An asynchronous policy iteration picks any subset of states and applies either kind of updating, concentrating on updating the values of states that are likely to be reached by a good policy. There's no sense planning for the results of an action you will never do. Linear programming re-expresses an MDP as a suitably formulated linear program. Minimize U of S for all S subject to the Bellman inequalities U of S is greater than or equal to the sum P of S, given SA R of SAS plus gamma U of S for every state S and every action A. This creates a connection from dynamic programming to linear programming, showing MDPs can be solved in time polynomial in the number of states and actions, though LP solvers are seldom as efficient as dynamic programming for solving MDPs, and the number of states is often very large. Online algorithms for MDPs handle sufficiently large MDPs, such as the Tetris MDP with 10 to the 62nd states, where exact offline solution, even by a polynomial time algorithm, is not possible. The agent does a significant amount of computation at each decision point rather than operating primarily with pre-computed information. The expect time max algorithm builds a tree of alternating max and chance nodes, rewards on non-terminal as well as terminal transitions, backing up utility values, taking an average at the chance nodes, and taking the maximum at the decision nodes. The H-horizon concept bounds the tree depth for desired error epsilon. A depth of H equals the log of over. Anything that happens after H is irrelevant because it's so far in the future. With gamma equals 0.5, epsilon equals 0.1, and our submax equals 1, we find H equals 5. If gamma equals 0.9, H equals 44. Expectations at chance nodes are approximated by generating n samples from P and using the sample mean. The Monte Carlo planning family. Value iteration, Bellman update repeated, a gamma, contraction ensuring unique convergence, exponential rate, and bounded policy loss. Policy iteration, evaluate the fixed policy linear equations, improve it, iterate, often optimal long before utilities converge. Modified and asynchronous variant scale. LP and online methods. LP couples MDPs to polynomial time solvers. Expect time max with an epsilon, horizon, and Monte Carlo sampling handles astronomically large MDPs. Bandit problems. Bandit problems simplify the MDP to a single state, a single action per, the choice of which arm to pull, and a stochastic reward, the quintessential exploitation dilemma. In Las Vegas, a one-arm bandit is a slot machine. Behind each lever is a fixed but unknown probability distribution of winnings. This is an example of the ubiquitous trade-off between exploitation of the current best action to obtain rewards and exploration of previously unknown states and actions to gain information. And the N-armed bandit is a formal model for real problems, which have impossible new treatments to try to cure a disease, which have impossible investments, which have impossible research projects to fund, or which have impossible advertisements to show. The problem proved so recalcitrant that Allied scientists proposed that the problem be dropped over Germany. As the ultimate instrument of intellectual sabotage, the early scientists were trying to prove obviously true facts that are, in fact, false. There are many nice properties which optimal strategies do not possess, including the assumption that an optimal policy would eventually settle on the best arm. The clean definition: each arm M sub I is a Markov reward process, or MRP. That is an MDP with only one possible action, and the overall bandit problem is an MDP. The state space is given by the Cartesian product. The transition model updates the state of whichever arm is selected, leaving the other arms unchanged. The deterministic two-arm warm-up rewards 0, 2, 0, 7.2, 0 versus constant 1, 1, 1 shows the subtlety. Committing to either arm yields 1.9 or 2.0, but starting with M and then switching to M1 after the fourth reward yields 2.025. The strategy S that switches from M to M1 at the right time is better than either arm individually, and S is optimal for this problem. All other switching times give less reward. The one-armed bandit generalizes to an arbitrary reward stream against a fixed reward row per pull, where the only choice is whether to pull again or to stop, with stopping time T. The tipping point, where an optimal strategy is exactly indifferent between running M up to the best possible stopping time and then switching to M forever, and choosing M immediately, defines the Gittins index, a kind of value for M in terms of its ability to deliver a stream of timely rewards, the maximum obtainable utility per unit of discounted time. The remarkable thing about the Gittins index is that it provides a very simple optimal policy for any bandit problem. Pull the arm that has the highest Gittins index, then update the Gittins indices, with big O of n time for the first decision and big O of 1 per subsequent decision. Calculating the Gittins index uses the trick of a restart MDP, augment M, so that at each state, the agent has two choices: either continue with M as before, or quit and receive an infinite sequence of row rewards, and replace the quit choice with the choice to go back and restart M from its initial state. The Gittins index for an arm M in state S is equal to 1 minus gamma times the value of an optimal policy for the restart MDP, which can be solved by any of the algorithms in section 17.2. The Bernoulli bandit. Each arm produces a reward of 0 or 1 with a fixed but unknown probability. Track success/failure counts. Initialized so the initial probabilities are 1/2 rather than 0/0, a Bayesian beta 1/1 prior. Solving the truncated MDP shows arms with higher payoff probabilities are preferred. But there is also an exploration bonus associated with arms that have only been tried a few times. The index for the state 3-2 is higher than the index for the state 7, for even though the estimated value at 3-2 is lower because the smaller count carries more uncertainty. Approximately optimal bandit policies exploit the desirability of some combination of estimated value and uncertainty. The upper confidence bound family selects an arm based on an optimistic estimate. The estimated value plus a turn that declines as the arm is tried more often, with logarithmic regret relative to the best arm. Multi-arm bandits echo throughout the book. UCD in Game Search, Chapter 5, Action Selection and Reinforcement Learning, Chapter 22. Bandit definition. Independent arms, MRPs, coupled by picking one at a time. The exploitation trade-off with practical applications from drug trials to web ads. Gittins index. The value per unit of discounted time. Pulling the highest index arm is optimal, computable via a restart MDP. Bernoulli bandit and UCB. Counts-based Bayesian estimates with an exploration bonus. Practical near-optimal policies trade estimated value against uncertainty. Partially observable MDPs. When the environment is only partially observable, the agent does not necessarily know which state it is in, so it cannot execute the action pi of S recommended for that state, and the utility of a state S and the optimal action in S depend not just on S, but also on how much the agent knows when it is in S. Partially observable MDPs, POMDPs, are usually viewed as much more difficult than ordinary MDPs. We cannot avoid POMPs, however, because the real world is one. A POMP has the same elements as an MDP, the transition model, actions, and reward function, but also has a sensor model P of E given S. The belief state becomes a probability distribution over all possible states. updated by the filtering style recursion bis equals alpha p of E given S, the sum over SP of S given S a B of S, written forward of B a E. The fundamental insight required to understand POMPs is this. The optimal action depends only on the agent's current belief state. An optimal policy is a mapping pi of B from belief states to actions, and the decision cycle is execute A equals pi of B, observe E, set B equals forward of B, E, repeat. POMPs can be thought of as requiring a search in belief state space, but the POMDP belief state space is continuous, a point in 11-dimensional space for the 4x3 world, and an action is evaluated at least in part according to the information the agent acquires as a result. POMPs therefore include the value of information as one component of the decision problem. The reduction to MDPs is explicit. Computing the probability of reaching belief state B from B under action gives a transition model for the belief state space, and together with the expected reward row of B, define an observable MDP on the space of belief states. Furthermore, it can be shown that an optimal policy for this MDP, pi star B, is also an optimal policy for the original POMDP. Perhaps less surprising if we remember that the belief state is always observable to the agent, by definition. POMDP elements. MDP plus sensor model. The optimal policy maps belief states, not physical states, to actions. Belief state reduction P of B, given B A and row of B A define an observable MDP whose optimal policy is optimal for the POMDP. Information has value. Actions are judged partly by the information they gather, so POMDP policies include information gathering moves. Algorithms for solving POMPs. Solving the belief state MDP requires redesign NG, the dynamic programming algorithms, which assumed a finite state space. Value iteration for POMPs thinks in terms of conditional plans. Let the utility of executing a fixed conditional plan P starting in physical state S be alpha sub PS. The expected utility of executing P in belief state B is just the sum B of S alpha sub P S equals B dot alpha sub P. So the expected utility of a fixed conditional plan varies linearly with B. That is, it corresponds to a hyperplane in belief space. At any belief state, an optimal policy will choose to execute the conditional plan with highest expected utility. So the utility function U of B on belief states, being the maximum of a collection of hyperplanes, will be piecewise linear and convex. The two-state world, states A and B. Actions stay with 0.9 probability. Go with 0.1. Rewards illustrates. The one-step plan stay and go. Give 2 lines. Stay when B of B is greater than 0.5 and go otherwise. Depth. 2 plans proliferate. 8 distinct depth. 2 plans in all, of which 4 are dominated, and they need not be considered further. The recursion U sub P S equals the sum P of S given S A R plus gamma generates a value iteration algorithm maintaining a collection of undominated plans with their utility hyperplanes. Given A actions and O possible observations, there are a dot distinct depth D plans even for the lowly two-state world with D equals 8. That's 2 to the 255th plans. The elimination of dominated plans is essential, cutting D equals 8 down to just 144. Strikingly, the intermediate belief states have lower value than state A and state B, because in the intermediate states, the agent lacks the information needed to choose a good action. Optimal policies and POMPs often include information-gathering actions. For general POMPs, finding optimal policies is very difficult, space-hard, in fact. That is very hard indeed. Online algorithms for POMPs apply expect timex, except with belief states rather than physical states as the decision nodes. The chance nodes have branches labeled by possible observations and leading to the next belief state, with transition probabilities from equation 17.17, adapting the game tree ideas of Chapter 5 to belief states. The time complexity of an exhaustive search to depth D is polynomial, far less than the number of possible depth D conditional plans generated by value iteration, and sampling at the chance nodes is a good way to cut down the branching factor. Piecewise linear convex utility. Utility over belief states is the max of conditional plan hyperplanes. Value iteration maintains undominated plans. Dominance pruning. The doubly exponential plan explosion is tamed. 2 to the 255th arrow. Are 144 at depth 8 by discarding dominated plans. Information gathering actions emerge. Online POMDP, belief state expect time acts with sampled chance nodes. Polynomial depth complexity versus value iterations plan explosion. Chapter 18. Multi-agent decision making. Properties of multi-agent environments. Chapter 18 turns to environments that contain multiple actors, called multi-agent systems, where an agent faces a multi-agent planning problem whose precise nature and the techniques that are appropriate for solving it will depend on the relationships among the agents. 3 settings are distinguished. With one decision maker in a multi-actor environment, the decision maker develops plans for the other agents and tells them what to do under the benevolent agent assumption that agents will simply do what they are told. Yet even then, plans involving multiple actors will require actors to synchronize their actions. Meanwhile, for joint actions, singing a duet. At different times for mutually exclusive actions, recharging batteries when there is only one plug. Sequentially, when one sets a precondition for the other, a washing the dishes and then be drying them. A multi-effector planning problem arises for a single decision maker with multiple effectors that can operate concurrently, a human who can walk and talk at the same time, when the effectors are physically decoupled into detached units. As in a fleet of delivery robots, multi-effector planning becomes multi-body planning. A multi-body problem remains a standard single-agent problem as long as the relevant sensor information can be pooled to form a common estimate. But when communication constraints make this impossible, we have what is sometimes called a decentralized planning problem, where the subplan constructed for each body may need to include explicit communicative actions, like reconnaissance robots, out of radio contact, sharing findings during times when communication is feasible. With multiple decision makers, we call them counterparts, and 2 further cases appear. If all pursue a common goal, roughly the situation of workers in a company, the main problem faced is the coordination problem. They need to ensure that they are all pulling in the same direction. If the decision makers each have their own personal preferences, the agents must take into account the preferences of other agents, as well as the fact that these other agents are also taking into account the preferences of other agents, and so on. This brings us into the realm of game theory, the theory of strategic decision making. It is this strategic aspect of reasoning, players each taking into account how other players may act, that distinguishes game theory from decision theory. And in the same way that decision theory provides the theoretical foundation for decision making in single-agent AI, game theory provides the theoretical foundation for decision making in multi-agent systems. Nothing could be further from the truth than that game theory concerns recreational pursuits. It is used in the auctioning of oil drilling rights and wireless frequency spectrum rights, bankruptcy proceedings, product development and pricing decisions, and national defense, situations involving billions of dollars and many lives. Game theory in AI serves 2 purposes: agent design. An agent computes the expected utility for each of its possible decisions under the assumption that other agents are acting rationally. And mechanism design, define the rules of the environment, so that the collective good of all agents is maximized when each agent adopts the game-theoretic solution that maximizes its own utility. The key modeling distinction: a cooperative game permits a binding agreement between agents, legal contracts, social norms, inspectable source code. In a non-cooperative game, binding agreements are not possible. Agents may independently decide to cooperate because it is in their own best interests. Real systems combine dimensions as a package delivery company blending centralized, offline planning for the routes of its trucks and planes with autonomous decisions by drivers and pilots. The goals of the company and its employees are brought into alignment by the payment of incentives, a sure sign that this is a true multi-agent system. Multi-agent planning treats multi-effector, multi-body, and multi-agent settings generically as multi-actor settings. The key difficulty is concurrency. The plans of each agent may be executed simultaneously. 3 models of concurrent action have become established. Interleaved execution preserves each plan's internal order and considers whether the plan is correct with respect to all possible interleavings. The model of multiple threads taking turns running on a single CPU, but it does not model the case where 2 actions actually happen at the same time, and the number of interleaved sequences will grow exponentially. True concurrency leaves them partially ordered. A 1 will occur before a 2, but with respect to the ordering of a 1 and B1, we can say nothing more satisfying theoretically, but not as widely adopted in practice. Perfect synchronization assumes a global clock that each agent has access to. Each action takes the same amount of time, and actions at each point in the joint plan are simultaneous. Not a very complete model of concurrency in the real world, but it has a simple semantics, and for this reason, it is the model we will work with here, as in the doubles tennis PDL problem of figure 18.1. Formally, the single action becomes a joint action, a sub 1. A sub n, so we have to describe the transition model for B to the n different joint actions, and a joint planning problem with a branching factor of B to the n. The principal focus of research on multi-actor planning has been to decouple the actors to the extent possible, aiming that the complexity of the problem grows linearly with n rather than exponentially with B to the n. If the actors have no interaction, we can simply solve n separate problems, and if they are loosely coupled, the coupling can often be localized. 3 settings: 1 decision maker, benevolent agent, multi-effector / multi-body, decentralized, multiple with common goals, coordination, multiple with private preferences, game theory. Game theory's roles: agent design, best response under rationality, and mechanism design. Rules making self-interest serve the collective good. Concurrency models: interleaved, truly concurrent, partial order, and synchronized. The joint action blows up the branching factor to B to the n, motivating decoupling. Non-cooperative game theory. Non-cooperative game theory underpins decision-making in multi-agent environments. Beginning with normal form games, all players take action simultaneously, and the result is based on the profile of actions. What matters is that no player has knowledge of the other player's choices. A normal form game has players, actions, and a payoff function giving the utility to each player for each combination of actions. A payoff matrix in the 2-player case. 2-finger mora. Each shows 1 or 2 fingers. Odd total pays O, even pays E, gives the running example with its payoff matrix. E is the row player, O the column player. Why can't we tackle the challenge using the apparatus of decision theory? Because you must take into account how O will act as a rational decision maker. But O, in turn, should take into account the fact that E is a rational decision maker. The solution concepts of game theory try to make this kind of reasoning precise. A strategy is what we have previously called a policy. A pure strategy is deterministic. A mixed strategy is a randomized policy that selects actions according to a probability distribution, written P 1 minus PB, and a strategy profile assigns a strategy to each player. The Prisoner's Dilemma, the most famous game in the game theory canon, motivates the first solution concept. Ollie and Bo each get 5 years if both testify, 10 years if they testify alone against a silent partner, 1 year if both refuse. No matter what Bo chooses to do, it would be better for me to testify. Ollie has discovered that testify is a dominant strategy, one that strongly dominates every alternative, better for P. For every choice of strategies by the other players, weak domination is better on at least one strategy profile and no worse on any other. Both rationalize to testify, giving the dominant strategy equilibrium. An equilibrium because no player has any incentive to deviate. The dilemma is that the dominant strategy equilibrium outcome is worse for both players than the outcome they would get if they both refused. Refuse would give both players just 1 year in prison. But it is hard to see how rational agents could make this choice, given the way the game is set up, since they aren't allowed to talk to each other, so they cannot make a binding agreement. Changing the game to a cooperative, repeated, or different preferences game would be required. The presence of a dominant strategy greatly simplifies the decision-making process, but it is rare that a single strategy is the best response to all possible counterpart strategies, so most games have no dominant strategy equilibrium. The much more widely applicable solution concept is the Nash equilibrium, named for John Forbes Nash, Jr., 1928 to 2015, who studied it in his 1950 PhD thesis, work for which he was awarded a Nobel Prize in 1994. A strategy profile is a Nash equilibrium if no player could unilaterally change their strategy and as a consequence receive a higher payoff. So, every player is simultaneously playing a best response. Any dominant strategy equilibrium must also be a Nash equilibrium, but a game may contain multiple Nash equilibria. In the coordination game of figure 18.2, TL and BR are both Nash equilibria, and clearly it is in the interest of both agents to aim for the same one. A coordination problem, resolved sometimes by focal points, an outcome that in some way stands out. TL would give both players substantially higher utility. Some games have no Nash equilibria in pure strategies. Matching pennies, same sides. Bo pays Ollie $1. Different. Ollie pays Bo, but Nash proved that every game has at least one Nash equilibrium in mixed strategies. In matching pennies, both players choose heads and tails with equal probability, for if one of the players chose any probability other than 0.5, the other player would be able to exploit that. Social welfare adopts a benevolent, omniscient entity perspective. Pareto optimality, named for the Italian economist Vilfredo Pareto, 1848 to 1923, says an outcome is Pareto optimal if there is no other outcome that would make one player better off without making someone else worse off. A non-Pareto optimal outcome wastes utility. Utilitarian social welfare, the sum of utilities, has two difficulties. It considers the sum, but not the distribution. We should give all the cookies to the utility monster who says, I love cookies 1,000 times more than anyone else, and it assumes a common scale for utilities, though utility is a subjective quantity. Egalitarian social welfare addresses distribution. Maximin, maximize the expected utility of the worst-off member, the Gini coefficient, at the cost of sacrificing a great deal of total welfare. The prisoner's dilemma status is then transparent. Testify is the only outcome that is not Pareto optimal, while refuse maximizes both utilitarian and egalitarian social welfare. So a very strong solution concept leads to an outcome that essentially fails every test of what counts as a reasonable outcome. Yet there is no clear way for the individual players to arrive at a better solution. Computing equilibria. Exhaustive search over strategy profiles is infeasibly large. M to the N profiles. Myopic best response. Iterated best response. Flippus, their choice to an optimal one, converging for some important classes of games. 4 mixed strategies, zero-sum games. The payoffs always add up to 0 or a constant. Admit von Neumann's Maximin technique. First he picks her strategy and reveals it to O, gives a turn-taking game to which we can apply the standard minimax algorithm, bounding the true utility between the two orders of revelation. -3 is less than or equal to U, is less than or equal to +2 for Moore's pure strategies. With mixed strategies, once the first player has revealed a strategy, the second player might as well choose a pure strategy, because a mixed strategy's expected utility is a linear combination that can never be better than the better of the two pure ones. The parameterized game tree is then solved at the intersection of the expected payoff lines, giving Moore's maximum equilibrium. Both players play 7/12, 1, 5/12, 2, with the true utility, exactly -1/12. So, it is better to be O than E. Von Neumann's general result. Every two-player zero-sum game has a maximum equilibrium when you allow mixed strategies. Furthermore, every Nash equilibrium in a zero-sum game is a maximin, and the maximin strategy has two guarantees. No other strategy can do better against an opponent who plays well, and the player continues to do just as well even if the strategy is revealed to the opponent. In higher dimensions, mixed strategies become points in n-dimensional space, and the lines become hyperplanes, with dominated pure strategies removed. Finding this choice is an example of a linear programming problem, maximizing an objective function subject to linear constraints, solvable in time polynomial in the number of actions. The rational agent's puzzling conclusion. Unilaterally choosing a particular action does not harm one's expected payoff, but allowing the other agent to know that one has made such a unilateral decision does affect the expected payoff, because then the opponent can adjust strategy accordingly. For non-zero-sum games, the general approach is to enumerate all possible subsets of actions that might form mixed strategies, exponential in the number of actions, and check if it is an equilibrium by solving equations. Linear for 2 players, non-linear, and may be very difficult to solve for 3 or more. Repeated games extend the single move setting. A repeated game, or iterated game, repeatedly plays rounds of single move game, called the stage game. A strategy specifies an action choice for each player at each time step for every possible history. With a stage game repeated a fixed, finite, and mutually known number of rounds. The prisoners play Testify in the 100th round. It is a one-shot with no future, so by backward induction, both players will choose Testify on every round, earning a total jail sentence of 500 years each. But if we drop one of the three conditions, fixed, finite, or mutually known, then the inductive argument doesn't hold. For infinitely repeated games, strategies are represented as finite state machines with output. Tit-for-tat starts by choosing refuse, and will then simply copy whatever its counterpart did on the previous round. Hawk simply plays testify on every round. Dove simply plays refuse. Grim plays testify forever, once the counterpart ever testifies unforgivingly. TT for TIT is the forgiving dual. Utility over the infinite sequence is measured by the limit of means approach, essentially taking the average of utilities received over the infinite sequence. In this indefinitely repeated setting, cooperation, refuse, becomes attainable as an equilibrium. The intuition that the shadow of the future, the credible threat of punishment, enables behavior the one-shot game forbids, the engine behind real-world cooperation and the folk theorems. Normal form games, simultaneous choice, payoff matrices, strategies pure or mixed, solution concepts formalize rational mutual reasoning. Dominant strategy in Nash equilibrium. Dominant strategy is the strongest concept, but rare. Nash guarantees existence in mixed strategies and captures coordination in matching penny-style games. Social welfare, Pareto optimality, utilitarian, sum, egalitarian, Maximin/Gini. The prisoner's dilemma fails all welfare tests yet resists individual escape. Maximin and repeated games. Zero-sum mixed strategy equilibria via linear programming. Infinitely repeated games make tit-for-tat, Grim, Hawk, and Dove finite state strategies, enabling cooperation under the limit of means averaging. Cooperative game theory. Cooperative games capture decision-making scenarios in which agents can form binding agreements with one another, benefiting from receiving extra value compared to what they would get by acting alone. The formal model is cooperative games with transferable utility in characteristic function form. G equals n new, with a set of players n equals 1, n and a characteristic function new, which for every subset of players C gives the value that the group of players could obtain should they choose to work together, assuming nu of the empty set equals 0 and non-negativity. A coalition is any subset of players, and is the grand coalition. An outcome is CSX. A coalition structure, a partition of players into coalitions, and a payoff vector X whose entries satisfy the constraint that each coalition C splits up all of its value nu of C among its members. A game is superadditive if, when two coalitions merge together, they do no worse than if they had stayed apart. Then the grand coalition's value is at least as high as the total received by any other coalition structure, though superadditive games do not always end up with a grand coalition, much as the prisoner's dilemma blocks Pareto optimal outcomes. The core formalizes the stability of the grand coalition. An imputation is a payoff vector distributing the grand coalition's total value and satisfying individual rationality. Each player is at least as well off as if it had worked alone. An imputation X is in the core if X of C is greater than or equal to nu of C for every coalition C. The players in C would refuse to join the grand coalition because they would be better off sticking with C, so the core consists of all the possible payoff vectors that no coalition could object to. If the core is empty, then the grand coalition cannot form. The core's defining inequalities form a linear program, but this gives an exponential number of inequalities, one for each of the two to the n possible coalitions. And for many classes of cooperative game, the problem of checking non-emptiness of the core is coimp complete. A simple superadditive game with an empty core shows why. With nu of C equals 1 for any two-player coalition and 0 otherwise, any imputation leaves two players whose combined payoff is less than 1, and those two could benefit by forming a coalition. The core tells us when a grand coalition can form, but it does not tell us how to distribute the payoff. Imputations in the core may be unreasonable. In a two-player game with nu of 1 equals nu of 2 equals 5 and nu of 1 2 equals 20, the imputation 6 14 is in the core, but from the point of view of player 1, this might appear unreasonable, because it gives 9/10 of the surplus to player 2. The Shapley value, formulated by Nobel laureate Lloyd Shapley in the early 1950s, is an elegant proposal for how to divide the nu of n value, according to how much each player contributed to creating the value. Dividing equally would give the same reward to players that contribute a lot and players that contribute nothing, whereas the Shapley value computes each player's average marginal contribution over all possible orders in which the Grand Coalition could form, the only fair way. In Shapley's sense, cooperative games/characteristic function form. Coalitions obtain value nu of C, split among members. Outcomes are coalition structure, payoff vector. The core. Imputations no coalition can profitably object to. Emptiness blocks the Grand Coalition, and checking non-emptiness is co-empty complete. The Shapley value. Divide nu of N by each player's average marginal contribution across formation orders. A fair distribution where the core is silent. Making collective decisions. Chapter 18 closes with mechanism design. The problem of designing the right game for a collection of agents to play. A mechanism has a language of allowable strategies, a distinguished agent called the center that collects reports, the auctioneer in an auction, and an outcome rule that the center uses to determine the payoffs. The contract net protocol is the oldest and most important multi-agent problem-solving technique studied in AI, inspired from the way that companies make use of contracts. Its 4 phases: problem recognition, task announcement, bidding, and awarding. Let a manager advertise a task, identifying the need for cooperative action, because the agent does not have the capability, or because a cooperative solution might in some way be better. Evaluate bids with respect to its own capabilities and preferences, and award the task to the most appropriate agent, who becomes a contractor, taking responsibility for the task until it is completed, possibly decomposing it into further subtasks advertised again. Despite, or perhaps because of, its simplicity, the contract net is probably the most widely implemented and best studied framework for cooperative problem solving. A variation of it is enacted every time you request a car with Uber. Auctions are the most important mechanism for allocating resources. Each bidder has a utility value 6 for the item. A private value, a tacky sweater, might be attractive to one bidder and valueless to another, or a common value with information asymmetry. Drilling rights will produce an amount of money, X, and all bidders value $1 equally, but have different estimates of X. The ascending bid, English, auction starts by asking for a minimum or reserve bid, raising by increments until nobody is willing to bid anymore. Then the last bidder wins, paying the price bid. An auction is efficient if the goods go to the agent who values them most. The English auction has most of the desirable properties. The winner pays B0 plus D, the highest bid among all the other agents plus the increment. And bidders have a simple dominant strategy. Keep bidding as long as the current cost is below your 6. So it is essentially strategy proof, but it is not quite truth revealing and can discourage competition. If one advantage company would clearly win, the competitors may not enter at all, and the advantage company ends up winning at the reserve price, and it has high communication costs. Collusion is the danger the design must resist. In 1999 Germany's cell phone spectrum auction, the two competitors were able to use the bidding mechanism to come to a tacit agreement on how not to compete, interpreting Mansman's precise 18.18 M bid as a signal. Perhaps the 10% rule was an error in mechanism design because it facilitated the precise signaling. The sealed bid auction, each bidder makes a single bid and communicates it to the auctioneer without the other bidders seeing it. Reduces communication, but there is no longer a simple dominant strategy. The bidder should bid B0 plus epsilon for some small epsilon, if that is less than 6. So your bid depends on your estimation of the other agent's bids, requiring you to do more work, and the agent with the highest 6 might not win. The sealed bid second price, Vickrey, auction, named after William Vickrey, 1914 to 1996, who won the 1996 Nobel Prize in Economics, has the winner pay the price of the second highest bid, B0, rather than paying his own bid. This simple modification completely eliminates the complex deliberations required, because the dominant strategy is now simply to bid 6. The mechanism is truth-revealing when 6 minus B0 is positive. Any bid that wins the auction is optimal, and bidding 6 in particular wins the auction. On the other hand, when 6 minus B0 is negative, any bid that loses the auction is optimal, and bidding 6 in particular loses. Because of its simplicity and the minimal computation requirements, the Vickrey auction is widely used in distributed AI systems. Internet search engines conduct several trillion auctions each year to sell advertisements, and online auction sites handle $100 billion a year in goods, all using variants of the Vickrey auction. The revenue equivalence theorem states that any auction mechanism in which bidders have values 6 known only to themselves will yield the same expected revenue. So the various mechanisms are not competing on the basis of revenue generation, but rather on other qualities. The multi-slot case shows truthfulness is fragile. Auctioning n-ad slots with an n+1 price rule is not truth-revealing. Bidder 1 with value 200 for the top slot, click 5%, can double her expected return by bidding less than her true value. And Agarwal et al., 2006, show there is a unique truthful auction mechanism, paying for incremental clicks at each slot's price. The tragedy of the commons: if nobody has to pay for using a common resource, then it may be exploited in a way that leads to a lower total utility for all agents. Is the mechanism design motivation? In the air pollution game, the dominant strategy for each country is continue to pollute. Yet if there are 100 countries and each follows this policy, then each country gets a total utility of -104, whereas if every country reduced pollution, they would each have a utility of -10. It is similar to the prisoner's dilemma. There's another solution, better for all parties, but there appears to be no way for rational agents to arrive at that solution. The remedy is to change the mechanism to one that charges each agent for using the commons. Ensure that all externalities, effects on global utility that are not recognized in the individual agent's transactions, are made explicit with a carbon tax as the canonical example. The Vickrey, Clark, Groves, VCG mechanism has two favorable properties. It is utility maximizing, that is, it maximizes the global utility, and it is truth-revealing. The dominant strategy for all agents is to reveal their true value. It's 4 steps. Ask each agent its value V sub I. Allocate the goods to a set of winners, W, to maximize the sum over WV sub. Calculate for each winning agent how much of a loss their individual presence in the game has caused the losers, and each winning agent then pays a tax equal to this loss. Give the wireless transceiver example. With 3 transceivers and bids 150, 40, 20, 10, each of the 3 winners pays the tax 20, and it would be irrational to bid above 20 if your true value is actually below 20, and vice versa. Since the crucial value could be anything, it is always irrational to bid anything other than your true value. VCG is very general and can be applied to all sorts of games, not just auctions, e.g. combinatorial auctions with bids over subsets of goods. One bidder might want either plot X or plot Y, but not both, whose optimal outcome computation is NP-complete. With a few caveats, the VCG mechanism is unique. Every other optimal mechanism is essentially equivalent. Voting brings social choice theory to mechanisms. Voters have qualitative preference rankings over outcomes. The fundamental problem of social choice theory is to combine these preferences using a social welfare function to come up with a social preference order, or a social choice function selecting winners. Condorcet's paradox, the Marquis de Condorcet, 1743 to 1794, shows that majority preference can cycle. With 3 voters and 3 candidates, 2/3 of the voters prefer A over B, 2/3 prefer B over C, and 2/3 prefer C over A. No matter which outcome we choose, a majority of voters will prefer a different outcome. Whether any good social welfare function exists is settled by Arrow's theorem. Kenneth Arrow no procedure satisfies all 4 of the Pareto condition. If every voter ranks above B, then is ranked above B. The Condorcet winner condition, a candidate beating every other candidate in a pairwise election, is ranked first. Independence of irrelevant alternatives, i.e., preferences between A and B, should not change if voters change views only on third candidates, and no dictatorships. Impossible to satisfy all 4 conditions for cases where there are at least 3 outcomes. Voting procedures then trade these properties. Simple majority vote, 2 candidates. Plurality voting, top choice only, criticized for delivering unpopular outcomes. It only takes into account the top-ranked candidate. The board account, after Jean-Charles de Borda, which scores K-1, 1 down voters' rankings and sorts by total. Approval voting, approve a subset. Most approvals win. Often used when the task is to choose multiple winners. Instant runoff voting, eliminate the fewest first-place votes, redistribute, repeat, until some candidate will have a majority. And true majority rule voting, The winner is the candidate who beats every other candidate in pairwise comparisons. The majority always agrees on the winner, but not every election will be decided, as Condorcet's paradox shows. Strategic manipulation is bounded by the Gibbard-Satterthwaite theorem. For three or more candidates, no reasonable social choice function is immune to voters misrepresenting their preferences. The voting analog of truthfulness limits. And a reason mechanism design is an engineering discipline rather than a solved problem. Mechanism design. Design a strategy language, a center, and an outcome rule, so self-interested play yields collective good. Contract net. Manager advertises a task, bidders offer, winner contracts. The canonical cooperative task allocation protocol. Auctions. English, ascending, dominant strategy bidding, collusion-prone, sealed bid, and victory, second price, truth revealing. The revelation principle and revenue equivalence frame the design space. VCG and the commons. The tragedy of the commons arises from unpriced externalities. The VCG mechanism maximizes global utility and is truth-revealing by taxing each winner for the harm its presence causes others. Voting, Condorcet's paradox, Arrow's impossibility theorem, and the Gibbard-Satterthwaite theorem set the limits. Plurality, Borda, approval, and instant runoff procedures trade the four axioms. Chapter 19. Learning from examples. Forms of learning. Chapter 19 opens Part 5, and its claim, any component of an agent program can be improved by machine learning, with the improvements depend on which component is improved, what prior knowledge the agent has, and what data and feedback on that data is available. From Chapter 2's agent components, condition action mappings, percept-to-world inference, transition and sensor models, utility information, action value information, goals, and the problem generator/critic/learning element. Every one can be learned. A self-driving car learns a condition action rule for when to brake. By seeing many camera images that it is told contain buses, it can learn to recognize them by trying actions and observing the results. For example, braking hard on a wet road. It can learn the effects of its actions, and when it receives complaints from passengers who have been thoroughly shaken up, it can learn a useful component of its overall utility function. The technology of machine learning has become a standard part of software engineering. Gravitational lensing image analysis, sped up by a factor of 10 million. Data center cooling energy, reduced by 40%. And David Patterson and Jeff Dean declared a golden age for computer architecture due to machine learning. Going from a specific set of observations to a general rule is called induction. This differs from the deduction we studied in Chapter 7 because the inductive conclusions may be incorrect, whereas deductive conclusions are guaranteed to be correct if the premises are correct. This chapter focuses on factored representations, attribute vectors, though inputs can be any kind of data structure. When the output is one of a finite set of values, the problem is classification. When it is a number, regression, an admittedly obscure name, since a better name would have been function approximation or numeric prediction. But 1886 Francis Galton's regression to the mean fixed the term. The three main types of learning follow from the three types of feedback. Supervised learning observes input-output pairs and learns a function that maps from input to output, each output a label, like images labeled car or pedestrian. Unsupervised learning learns patterns in the input without any explicit feedback, its most common task being clustering. When shown millions of images, identify a large cluster of similar images which an English speaker would call cats. Reinforcement learning learns from a series of reinforcements, rewards and punishments, where it is up to the agent to decide which of the actions prior to the reinforcement were most responsible. Supervised learning. The task of supervised learning, stated formally, given a training set of n-example input-output pairs, x1, y1, xn, yn, where each pair was generated by an unknown function y equals f, x, discover a function h that approximates the true function f. The hypothesis h is drawn from a hypothesis space of possible functions, degree 3 polynomials, JavaScript functions, 3 SAT formulas. Equivalently, h is a model of the data drawn from a model class, and the true answer we're asking our model to predict is the ground truth. Choosing the hypothesis space uses prior knowledge or exploratory data analysis. Histograms, scatter plots, box plots. Choosing a hypothesis wants a consistent hypothesis. H, 11, equals E for all training I, where possible, but with continuous valued outputs, we can't expect an exact match. And the true measure of hypothesis is not how it does on the training set, but rather how well it handles inputs it has not yet seen. The test set and generalization. Figure 19.1's for hypothesis spaces crystallize the lesson. Straight lines, no consistent hypothesis. Sinusoids fit both datasets well. Piecewise linear connectors, always consistent. And degree, 12 polynomials, always consistent. We can always get a degree, 12 polynomial to perfectly fit 13 distinct points. But just because the hypothesis is consistent does not mean it is a good guess. The analysis is in terms of bias and variance. By bias, we mean the tendency of a predictive hypothesis to deviate from the expected value when averaged over different training sets. Linear functions induce a strong bias, and a hypothesis that fails to find a pattern in the data is underfitting. By variance, we mean the amount of change in the hypothesis due to fluctuation in the training data. The degree, 12 polynomials have high variance, and a function that pays too much attention to the particular data set it is trained on, causing it to perform poorly on unseen data, is overfitting. Often there is a bias-variance trade-off, a choice between more complex, low-bias hypotheses that fit the training data well and simpler, low-variance hypotheses that may generalize better. The chapter summarizes the decomposition concretely. The generalization error of a hypothesis can be written as the sum of the bias, the variance, and an irreducible noise term. So a learner that minimizes only training error may pay an unbounded variance penalty, while one that holds the space too rigid pays in bias. Einstein's supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible. Echoes Occam's razor. Plurality of entities should not be posited without necessity. Yet the number of parameters by itself is not a good measure of a model's fitness. Deep networks can often generalize quite well, even though they are very complex. So perhaps we should be aiming for appropriateness, not simplicity, in a model class, a theme to which Chapter 21 returns. A Bayesian framing chooses the hypothesis H star that is most probable given the data. H star equals argmax HP of H given data equals argmax HP of data given H dot P of H. The prior probability P, H, is high for a smooth degree, 1 or minus 2 polynomial and lower for a degree, 12 polynomial with large, sharp spikes. We allow unusual-looking functions when the data say we really need them, but we discourage them by giving them a low prior probability. Why not let the space be the class of all computer programs or all Turing machines? Because there is a trade-off between the expressiveness of a hypothesis space and the computational complexity of finding a good hypothesis within that space. Fitting even simple classes raises computational questions, and richer spaces face intractable search. This same trade-off recurs in Chapter 21. Deep networks are enormously expressive, and the practical finding that they generalize anyway, despite billions of parameters, forces a rethinking of the simplicity heuristic. Perhaps we should be aiming for appropriateness, not simplicity, in a model class, a theme the chapter flagged for the deep learning chapters to come. Learning decision trees. A decision tree is a representation of a function that maps a vector of attribute values to a single output value, decision. It performs a sequence of tests, starting at the root, until a leaf is reached. With each internal node, a test of the value of one of the input attributes, branches labeled with attribute values, and the leaf nodes specify what value is to be returned. The chapter's recurring example is the restaurant waiting problem. Predict whether to wait for a table from such attributes as patrons, none/some/full, hungry, type, and Friday/sad, in Boolean classification where outputs are positive, true, or negative, false. Examples. Expressiveness. A Boolean decision tree is equivalent to a logical statement of the form output path 1 or path 2 or, where each path E is a conjunction of attribute value tests, disjunctive normal form, which means that any function in propositional logic can be expressed as a decision tree. For many problems, the decision tree format yields a nice, concise, understandable result. Indeed, many how-to manuals, e.g. for car repair, are written as decision trees. But some functions cannot be represented concisely. The majority function and the parity function require an exponentially large decision tree, and with real valued attributes, the function y is greater than a sub 1 plus a sub 2 is hard to represent with a decision tree because the decision boundary is a diagonal line, and all decision tree tests divide the space up into rectangular, axis-aligned boxes. Is there any kind of representation that is efficient for all kinds of functions? Unfortunately, the answer is no. There are just too many functions. Within Boolean attributes, there are 2 to the 2 to the n different functions. So if we limit ourselves to a million-bit representation, we can't represent all these functions. Learning decision trees. We want to find a tree that is consistent with the examples and is as small as possible, but it is intractable to find a guaranteed smallest consistent tree. The learn decision tree algorithm adopts a greedy divide-and-conquer strategy. Always test the most important attribute first, then recursively solve the smaller subproblems, where by most important attribute, we mean the one that makes the most difference to the classification. Figure 19.4 shows type is a poor attribute. Each branch leaves equal positives and negatives. While patrons is good, it's none, and some branches settle the answer. The 4 recursive cases, all examples the same done. Both classes split on the best attribute. No examples return the most common output value from the set of examples that were used in constructing the node's parent. No attributes left, but both classes noise in the data. The domain is non-deterministic, or we can't observe an attribute that would distinguish the examples. The induced tree not only is consistent with all the examples, but is considerably simpler than the original tree and has detected an interesting and previously unsuspected pattern. SR will wait for Thai food on weekends, omitting raining and reservation, because it can classify all the examples without them. With slightly different examples, the tree might be very different, but the function it represents would be similar. The algorithm is also bound to make some mistakes for cases where it has seen no examples. It has never seen a case where the wait is 0 to 10 minutes, but the restaurant is full, so it says not to wait when hungry is false, but SR would certainly wait. With more training examples, the learning program could correct this mistake. Evaluation uses a learning curve. Each data point is the average of 20 trials, which shows that as the training set size grows, the accuracy increases, hence also called happy graphs. The restaurant data curve reaches 95% accuracy, and it looks as if the curve might continue to increase if we had more data. Choosing attribute tests uses information gain, defined in terms of entropy, which is the fundamental quantity in information theory. Entropy is a measure of the uncertainty of a random variable. The more information, the less entropy. A coin that always comes up heads has no uncertainty, and thus its entropy is a fair coin. Counts as 1 bit. A fair 4-sided die has 2 bits. A 99% heads coin has about 0.08 bits. With h of v equals minus the sum over kp of v sub k. The log sub 2p of v sub k, and b of q equals minus q the log sub 2q plus 1 minus q. The log sub 2 1 minus q, for a Boolean variable. The restaurant set with p equals n equals 6 has b of 0.5, or exactly 1 bit. Testing attribute a with d values leaves remainder of equals the sum over k, p sub k, plus n sub k, over p plus b of p sub k, over p sub k, plus n sub k, and gain of a equals b of p over p plus n minus remainder of a. Gain, patrons, equals 0.541 bits versus gain, type, equals 0 bits, confirming our intuition that patrons is a better attribute to split on first. In fact, patrons has the maximum information gain of any of the attributes, and thus would be chosen as the root. Pruning then guards against the overfitting that a fully grown tree risks. The chapter's empirical story is that decision trees built on the restaurant data, greedy by information gain, and then pruned by statistical significance, a chi-squared test asking whether a splits class distribution differs significantly from chance, reach 95% accuracy on the held-out learning curve. And the exposed intuitive rules are exactly why trees and tree ensembles remain a practical workhorse. A human can. Read, if patrons equals none, wait. If patrons equals full and hungry, don't wait directly off the tree. Model selection and optimization. Our goal in machine learning is to select a hypothesis that will optimally fit future examples. The stationarity assumption, the future examples will be like the past, is stated at the outset. Examples are independent and identically distributed, i.e. P ej equals P ej plus 1, and P ej equals P ej ej minus 1. For now, the optimal fit is the hypothesis that minimizes the error rate, but it would be cheating for a hypothesis or a student to peek at the test answers, so split the examples you have into two sets: a training set to create the hypothesis and a test set to evaluate it. With multiple hypotheses, the overall process did peek through the researcher when tuning parameters of the model class, not of the individual model, pruning thresholds, polynomial degrees. The fix is to really hold out the test set. Lock it away until you are completely done. Use a validation set, also known as a development set or dev set, to choose among candidates, and keep the test set for a final unbiased evaluation. With limited data, k-fold cross-validation lets each example serve double duty as training data and validation data, but not at the same time. Split into k-equal subsets, train on k-1, validate on the held-out 1/k, average, with the extreme k=n, also known as leave one out cross-validation, LOOKV. Even with cross-validation, we still need a separate test set. The task splits into two subtasks. Model selection chooses a good hypothesis space, and optimization, also called training, finds the best hypothesis within that space. Model selection builds models of increasing complexity and selects the model that has the lowest average error rate on the held-out validation data. The two canonical error curve patterns in a decision tree show a U-shaped validation error curve. Validation error falls then rises with overfitting, and model selection picks the value at the bottom of the U, tree size 7. In B, convolutional networks on NIST show an initial U, then the validation error starts to decrease again, the best at 1 million parameters. Why are some validation error curves like A and some like B? It is how the different model classes make use of excess capacity. A model that exactly fits all the training data has interpolated the data, and although model classes typically start to overfit as the capacity approaches the point of interpolation, deep networks, kernel machines, random forests, and boosted ensembles have the property that their validation set error tends to decrease as capacity increases. From error rates to loss, utility is what learners should maximize as well. Expressed negatively as minimizing a loss function L of x y hat of y. The amount of utility lost by predicting h of x equals hat of y when the correct answer is f of x equals y, with 10 times worse to classify non-spam as spam than vice versa in the email example. Common losses: L1, absolute difference, L2, square difference, and L0/1, 1 for an incorrect answer. The best hypothesis, H star, is the one with the minimum expected generalization loss over the unknown p of xy. Since p of xy is not known, the agent can only estimate generalization loss with empirical loss on a set of examples. For reasons why the empirical best may differ from f: unrealizability. The true f is not in the hypothesis space. No amount of data will recover the true f. Variance, different training sets, decreasing with data in realizable problems. Noise cannot be predicted. In computational complexity, search can explore part of the space and return a reasonably good hypothesis. Small-scale learning of dozens to low thousands of examples is dominated by approximation error and estimation error. Large-scale learning, with millions of examples, may be dominated by limits of computation. Regularization, search, yes, for a hypothesis that directly minimizes the weighted sum of empirical loss and the complexity of the hypothesis. Cost of h equals EMP loss of h plus lambda, complexity of h, where lambda is a hyperparameter, a conversion rate between loss and hypothesis complexity, and this process of explicitly penalizing complex hypotheses is called regularization. For polynomials, a good regularization function is the sum of the squares of the coefficients. Keeping the sum small would guide us away from the wiggly degree 12 polynomial. Feature selection discards attributes that appear to be irrelevant. Chi-square pruning is a kind of feature selection, and when both loss and complexity are measured in bits, encode the hypothesis as a Turing machine program. The minimum description length principle makes the trade-off parameter-free. Induction versus deduction. Learned conclusions may be wrong. The guarantee logic offers is unavailable. Bias, variance trade-off, and Occam's razor. Understand underfitting and overfitting through the hypothesis space. Favor simplicity or appropriateness, unless the data demand more. Train/validation/test. Separate tuning from unbiased evaluation. K-fold cross-validation. especially LOOCV, squeezes limited data. Loss and regularization. Minimize empirical loss plus lambda.complexity. L1/L2/L0-1 losses, feature selection, and MDL make the trade-offs precise. The theory of learning. Chapter 19 turns to the questions pondered for centuries. How many examples do we need to get a good H? What hypothesis space should we use? These are the province of computational learning theory, at the intersection of AI, statistics, and theoretical computer science. The underlying principle is that any hypothesis that is seriously wrong will almost certainly be found out with high probability after a small number of examples. So any hypothesis that is consistent with a sufficiently large set of training examples is unlikely to be seriously wrong. That is, it must be probably approximately correct. PAC learning theorems are logical consequences of axioms. And for learning, the axioms have to provide the juice, the stationarity assumption, plus the assumption that the true function f is deterministic and is a member of the hypothesis space. For Boolean functions, the error rate is the expected generalization error. Error of h is the probability that h misclassifies a new example. A hypothesis is approximately correct if error of h is less than or equal to epsilon. A seriously wrong hypothesis h sub b with error is greater than epsilon agrees with a given example with probability at most 1 minus epsilon. So the probability that it agrees with n examples is at most 1 minus epsilon n, and summing over the given h given bad hypotheses gives the sample complexity. After about 1 over epsilon the natural log given h given plus the natural log 1 over delta examples with probability at least 1 minus delta, the return hypothesis has error at most epsilon, probably approximately correct. To obtain real generalization to unseen examples, it seems we need to restrict the hypothesis space. But of course, if we do restrict the space, we might eliminate the true function altogether. 3 escapes. Bring prior knowledge to bear. Insist that the algorithm return not just any consistent hypothesis, but preferably a simple one, decision tree learning, and focus on learnable subsets of the Boolean function space. The decision list example shows the method. A decision list consists of a series of tests, each of which is a conjunction of literals. KDL, tests of at most k literals, contains k, dt, decision trees of depth at most k, as a subset, and, counting the finite number of possible hypotheses, about big O of n to the k conjunctions, yields polynomial sample complexity for fixed k. While, if we allow tests of arbitrary size, then decision lists can represent any Boolean function. Impossible. To PAC learn efficiently. The count is instructive. The set of conjunctions of at most k literals using n attributes is big O of n to the k, and since each test can be yes, no, or absent, there are at most 3 to the c distinct decision lists over c conjunctions. So given k minus dl of n given is bounded by a double logarithmic expression in n for fixed k, and plugging this into the sample complexity bound gives a polynomial number of examples. The chapter's message is that the expressiveness, learnability trade-off is precise. Bounded hypothesis spaces generalize. Unbounded ones merely memorize. The reason the mere size of the hypothesis space governs learning is worth restating. The probability that bad contains at least one consistent hypothesis is bounded by the sum of the individual probabilities. Given h given 1 minus epsilon n. So a small hypothesis space needs few examples to rule out all seriously wrong consistent hypotheses, while the space of all Boolean functions contains enough hypotheses to classify any given set of examples in all possible ways, and so PAC. Learning in the class of all Boolean functions requires seeing all, or nearly all, of the possible examples. Linear regression and classification. The class of linear functions of continuous valued inputs has been used for hundreds of years. Univariate linear regression fits a straight line y equals w sub 1x plus w sub 0, where w sub 0 and w sub 1 are real valued coefficients to be learned, the weights. All we have to do is find the values of the weights that minimize the empirical loss, using the squared error loss function, L2, traditional, going back to Gauss. Loss of h sub w equals the sum over j y sub j minus h sub wx sub j to the second. Setting the partial derivatives to 0 give a unique solution. W sub 1 equals 0.232, W sub 0 equals 246 in the housing example, because the loss function is convex, true for every linear regression problem with an L2 loss function. It implies that there are no local minima. Gradient descent handles losses where the derivative can't be solved. We choose any starting point in weight space, then move a small amount in the steepest downhill direction, repeating until we converge on a point with local minimum loss, with step size now called the learning rate ETA. The one example chain rule update gives the learning rule W sub I is less than minus W sub I plus ETA Y minus H sub WX. Summing over examples gives batch gradient descent deterministic, whose convergence to the global minimum is guaranteed, as long as we don't pick an ETA that is so large that it overshoots, but maybe very slow, with a full pass being an epic. Stochastic gradient descent, SGD, randomly selects a small number of training examples at each step. The mini-batch, trading a factor of 100 less computation for a factor of 10 more error, still 10 times faster. SGD can be helpful in an online setting, where new data are coming in one at a time and is widely applied. In particular to neural networks, finding good local minima that are close to the global minimum, even on non-convex surfaces. Multivariable linear regression extends to n-element input vectors with h sub wx sub j equals w.x sub j. A dummy x sub j, 0 equals 1 handles the intercept, solved by the normal equation w star equals x to the tx minus 1x to the ty, where x to the tx minus 1x to the t is called the pseudo-inverse of the data matrix. With many dimensions, some dimension that is actually irrelevant appears by chance to be useful, resulting in overfitting, so regularization, L1/L2 penalties on weights, is common. Turning linear regression into classification, a hard threshold on a linear function yields a linear decision boundary. Classify as positive if w to x plus b is greater than 0, negative otherwise. The perceptron learning rule, w sub I is less than minus w sub I plus eta y minus h sub wx, that x sub I, adjusts the boundary when an example is misclassified, and converges to a separating line when one exists, the perceptron convergence theorem. Logistic regression, instead, applies a soft threshold via the logistic sigmoid, sigma of z equals 1 over 1 plus e to the minus z, interpreting sigma of w.x as the probability that y equals 1, and learns the weights by maximizing the likelihood of the data, which is equivalent to minimizing the cross-entropy loss. Linear classification of this kind is the bridge to Chapter 21's neural networks. Each unit computes a weighted sum, then passes it through a nonlinearity like the sigmoid, and gradient descent on the same squared or cross-entropy losses trains whole networks. The chapter notes the expressiveness limit that motivates this step. A single linear decision boundary cannot represent even the XOR function, so networks stack layers of such units. Non-parametric models. A parametric model summarizes data with a set of parameters of fixed size, independent of the number of training examples, so we can throw away the training data. But when there are millions or billions of examples, a non-parametric model cannot be characterized by a bounded set of parameters. The piecewise linear function from Figure 19.1 retains all the data points as part of the model, hence instance-based learning or memory-based learning. The simplest is table lookup. Return the stored y for a query x, but it does not generalize well when x is not in the table. K-nearest neighbors KNN improves on it. Find the K examples that are nearest to XQ and classify by the most common output value, with K usually chosen to be an odd number to avoid ties, or regress by taking the mean or median of the K neighbors, or solving a linear regression problem on the neighbors. Non-parametrics are still subject to underfitting and overfitting. The Figure 19.19 earthquake data show K equals 1 overfitting to outliers and a good boundary at K equals 5 with cross-validation to select the best value of K. Distance is measured by the Minkowski LP norm. Euclidean P equals 2, Manhattan P equals 1, Hamming for Boolean attributes, with normalization of each dimension, risk scale by mean and standard deviation, and the Mahalanobis distance accounting for covariance. The fundamental limitation is the curse of dimensionality. In high dimensions, the nearest neighbors are usually not very near. With 1 million uniform points, the average K equals 10 neighborhood side length reaches half the edge length of the unit hypercube by 17 dimensions and 94% by 200 and over 98% of the points fall within the outer 1% shell. In 200 dimensions, so almost all the points are outliers. KD trees accelerate exact neighbor search, a balanced binary tree over data with an arbitrary number of dimensions, splitting at the median along successive dimensions. Test ing for the possibility that a near neighbor lies across the boundary, appropriate only when there are many more examples and dimensions, preferably at least 2 to the n examples. Locality-sensitive hashing, LSH, returns approximate near neighbors with high probability. Project points on a random lines. If 2 points are close together in an n-dimensional space, then they will necessarily be close when projected down onto a one-dimensional space. Discretize into hash buckets and create L different random projections and L hash tables, unioning the candidate sets on a dataset of 13 million web images using 512 dimensions. LSH needs to examine only a few. 1,000 images, 1,000-fold speedup. Non-parametric regression includes connect the dots, piecewise linear, k-nearest neighbors average and linear regression, and locally weighted regression with a kernel. A decreasing function of distance with a maximum at 0, e.g., a quadratic kernel with width w, where the width matters more than the exact shape, and we need to solve a new regression problem for every query point. That's what it means to be local. Non-parametrics make leave one out cross-validation cheap. The whole process is big O of k, not big O of kn. The section closes by introducing support vector machines, SVMs, the most popular approach of the early 2000s. An SVM finds a maximum margin separating hyperplane, uses a kernel function to map to high-dimensional feature spaces implicitly, and has the nice property, like deep networks but unlike parametric models, that their validation set error tends to decrease as capacity increases. A return to the figure 19.9b pattern. The key SVM idea is to treat not the whole data set but only the support vectors, the handful of training points closest to the decision boundary, as defining the classifier. The margin, the distance from the boundary to the closest points, is maximized, and the resulting classifier is completely determined by the support vectors rather than by all of the data. Kernel methods replace the explicit high-dimensional mapping with a kernel function k of xx, computing the inner product of the mapped points implicitly. So, we can work in a feature space of very high dimension without ever constructing it explicitly. The famous kernel trick that lets linear classifiers express nonlinear boundaries, a quadratic kernel capturing elliptical class regions, a radial basis kernel approximating arbitrary smooth boundaries. Cross-validation chooses among kernels and their width parameters. Ensemble learning. Ensemble learning selects a collection or ensemble of hypotheses and combines their predictions by averaging, voting, or by another level of machine learning, with individual hypotheses as base models and their combination as an ensemble model. The first reason is to reduce bias. An ensemble of 3 linear classifiers can represent a triangular region that could not be represented by a single linear classifier. So an ensemble of n linear classifiers allows more functions to be realizable at a cost of only n times more computation. The second reason is to reduce variance. With 5 majority voting classifiers, for the ensemble to misclassify a new example, at least 3 have to misclassify it. 75% accurate independent classifiers reach 89% and 99% with 17, though in practice the independence assumption is unreasonable. For ensemble methods follow. Bagging, bootstrap aggregating, generates k distinct training sets by sampling with replacement, trains a hypothesis on each, and aggregates, plurality vote or average. Bagging tends to reduce variance and is a standard approach when there is limited data or when the base model is overfitting, and is most commonly used with decision trees because they are unstable. Random forests add diversity by randomly vary into the attribute choices, picking the square root of n attributes at each split, n over 3 for regression. Optionally randomizing split points into extremely randomized trees, extra trees. They are resistant to overfitting. Bryman, 2001, gives a mathematical proof that, in almost all cases, as you add more trees to the forest, the error converges. It does not grow, and have been the most popular approach of winning teams in Kaggle. Competitions from 2011 to 2014, used in finance, medicine, and bioinformatics. Stacking stack generalization combines multiple base models from different model classes trained on the same data, training a new ensemble model on the validation set predictions. It might learn a weighted average or nonlinear interactions. Stacking reduces bias and usually leads to performance that is better than any of the individual base models and can stack multiple layers. Boosting, the most popular ensemble method, introduces a weighted training set and iterates. Generate hypothesis H1, then increase the weights of the misclassified examples while decreasing the weights of the correctly classified ones. Generate H2, and so on. So, examples that are difficult to classify will get increasingly larger weights until the algorithm is forced to create a hypothesis that classifies them correctly. The final ensemble lets each hypothesis vote with weighted votes. AdaBoost has a very important property. If the input learning algorithm L is a weak learning algorithm, which means that L always returns a hypothesis with accuracy slightly better than random guessing, then AdaBoost will return a hypothesis that classifies the training data perfectly for large enough K. Boosting can overcome any amount of bias in the base model, as long as the base model is even slightly better than random guessing, though this property does not guarantee accuracy. On previously unseen examples, on the restaurant data, boosting decision stumps raises performance from 81% to 93%, and a weighted majority combination of 20 decision stumps suffices to fit the 100 examples exactly. Developing machine learning systems. The chapter closes with the practice of using machine learning to solve practical problems, a separate discipline whose tools and techniques are not as well developed as traditional software methodology. Problem formulation first asks, what problem do I want to solve for my users? Too vague. Make it easier for users to organize and access their photos. Better, help a user find all photos that match a specific term, such as Paris. Then, what parts of the problem can be solved by machine learning? And specifies a loss function for that component. This objective should be correlated with your true goals, but usually will be distinct. The true goal might be user retention and revenue. Metrics you should track, but not necessarily ones that you could directly build a machine learning model for. Components are often decomposable, with old-fashioned software engineering handling the parts, not machine learning, before optimizing later. Deciding between supervised, unsupervised, and reinforcement learning is part of problem formulation. With semi-supervised learning, a few labeled examples used to mine more information from a large collection of unlabeled examples. And weakly supervised learning, labels that are noisy, imprecise, or supplied by non-experts. On the spectrum, the photo age example shows. The inaccuracies are systematic, and to uncover them is an unsupervised learning problem. Data collection, assessment, and management is where projects live or die. ImageNet, which has over 14 million photos with about 20,000 different labels, manufacturing data by our own labor or by crowdsourcing. User data, ways as traffic jam uploads, and transfer learning start with a publicly available general-purpose data set, and then add specific data from your users. Privacy requires a review with privacy experts, and federated learning keeps sensitive data on the user's device while model parameters are shared in a way that does not reveal private data. It is good practice to maintain data provenance for all your data, the exact definition, where the data come from, what the possible values are, and who has worked on it, because having a reliable, flexible, secure data handling pipeline is more critical to success than the exact details of the machine learning algorithm. Model refinement draws learning curves to see if more data will help, or if learning has already plateaued, and weighs the endless ad hoc, unjustified rules of thumb for how many examples. Millions for hard problems, thousands for average problems, hundreds or thousands for each class in a classification problem. 10 times more examples than parameters of the model. 10 times more examples than input features. Oh, D-log D, examples for D input features. More examples for nonlinear models than for linear models. More examples if greater accuracy is required. Fewer examples if you use regularization. Enough examples to achieve the statistical power necessary to reject the null hypothesis in classification. All these rules come with caveats, as does the sensible rule that suggests trying what has worked in the past for similar problems. You should think defensively about your data. Could there be data entry errors? What will be done with missing data fields? If you collect data from your customers or other people, could some of the people be adversaries out to game the system? Spelling errors and inconsistent terminology do Apple, and Apple Incorporated all refer to the same company. need a process to catch and correct them. The project's deeper failure modes also include feedback loops, the deployed system's own outputs reshaping the data it is later trained on, distribution shift, the world changing after the data were collected, and differential privacy concerns, which is why the chapter insists on monitoring, provenance, and the iterative discipline of reevaluating with each new data batch. Pack learning. Consistently fitting hypotheses are probably approximately correct after enough examples. Sample complexity is 1 over epsilon the natural log given h given plus the natural log 1 over delta, and bounded hypothesis spaces, like K, DL decision lists, generalize while unbounded ones only memorize. Linear models. Univariate and multivariable regression with L2 loss are convex. Gradient descent, stochastic/mini-batch SGD, the normal equation, and regularization carry to neural networks. Non-parametrics. KNN, kernels, and LSH let the data speak without a fixed parameter bound. At the price of the curse of dimensionality, support vector machines generalize well into high capacity. Ensembles. Bagging and random forest cut variance, stacking cuts bias, boosting drives weak learners to perfect training fit, AdaBoost, but never promises test set accuracy. ML systems practice. Formulate the user problem, choose the learning type and loss, curate data with provenance and privacy, and iterate with learning curves and defensive data handling. Chapter 20. Learning probabilistic models. Statistical learning. The chapter's key concepts, just as in Chapter 19, are data and hypotheses. Here, the data are evidence, that is, instantiations of some or all of the random variables describing the domain, and the hypotheses are probabilistic theories of how the domain works, with logical theories as a special case. The candy bag example introduces Bayesian learning. 5 kinds of bags, H sub 1, 100% cherry, H sub 5, 100% lime, each wrapping pieces identically, and data D sub 1. D sub in reveal by unwrapping. Bayesian learning simply calculates the probability of each hypothesis, given the data, and makes predictions on that basis, using all the hypotheses, weighted by their probabilities, rather than by using just a single best hypothesis. In this way, learning is reduced to probabilistic inference. With prior P of H sub I and likelihood P of D given H sub I, Bayes' rule gives P of H sub I given D equals alpha P of D given H sub I dot P of H sub I, and predictions are weighted averages P of X given D equals the sum over I P of X given H sub I dot P of H sub I given D. The hypotheses themselves are essentially intermediaries between the raw data and the predictions. With priors 0.1, 0.2, 0.4, 0.2, 0.1, and ID observations, a run of 10 lime candies shifts the posterior. H sub 3 is initially the most likely choice and remains so after 1 lime candy. After 2 lime candies, H sub 4 is most likely. After 3 or more, H sub 5, the dreaded all-lime bag, is the most likely, and the predicted probability that the next candy is lime increases monotonically toward 1. Bayesian learning eventually agrees with the true hypothesis, and the Bayesian prediction is optimal, whether the dataset is small or large. Given the hypothesis prior, any other prediction is expected to be correct less often. The price. The hypothesis space is usually very large or infinite, and in most cases we must resort to approximate or simplified methods. This is the deep point that connects Chapter 19's pack learning to Chapter 20. For any fixed prior that does not rule out the true hypothesis, the posterior probability of any false hypothesis will, under certain technical conditions, eventually vanish, simply because the probability of generating uncharacteristic data indefinitely is vanishingly small. The candy example is vivid. After the first 10 observations are all lime, the posterior over-hypothesis has migrated from the flat prior to concentrate on H5, and the Bayesian prediction of lime climbs steeply and monotonically toward 1. Even though the agent cannot yet be certain, it is not an unlucky run from a half-lime bag. The plot of figure 20.1b makes this concrete. The predicted probability of a lime next starts near the prior weighted average, about 0.5, since the prior over bags is symmetric, and after each observed lime candy rises deterministically, mirroring the shifting posteriors of figure 20.1a, where the probability mass migrates from an H3 centric prior through H4 to concentrate on H5 after 3 or more limes. The accompanying figure 20.1 A curves, one per hypothesis, each starting at its prior and ending by the 10th observation, essentially pinned to 0 or 1, are the canonical picture of Bayesian belief updating under ID evidence. Likelihoods push each hypothesis toward its data-determined fate, and the prior only governs how quickly the posteriors part ways. The map approximation. Predictions made according to map hypothesis are approximately Bayesian to the extent that P x H map is often much easier than Bayesian learning because it requires solving an optimization problem instead of a large summation or integration problem, though it is overconfident. After 3 lines, it predicts line with certainty versus the Bayesian 0.8. The prior penalizes complexity. More complex hypotheses have a lower prior probability, in part because there are so many of them, but a greater capacity to fit the data. Hence, the hypothesis prior embodies a trade-off between the complexity of a hypothesis and its degree of fit. In the purely logical case, HMAP will then be the simplest logical theory that is consistent with the data. Therefore, maximum a posteriori learning provides a natural embodiment of Occam's razor. Taking logs, MAP, is choosing the hypothesis that provides maximum compression of the data, the minimum description length, MDL, view, and with a uniform prior, MAP reduces to the maximum likelihood hypothesis, HML. Very common in statistics, a discipline in which many researchers distrust the subjective nature of hypothesis priors. Learning with complete data. Maximum likelihood parameter learning for a fully observable Bayesian network fits each conditional distribution to maximize the likelihood of the data. The general task of learning a probability model, given data that are assumed to be generated from that model, is called density estimation, a form of unsupervised learning. Parameter learning finds the numerical parameters for a probability model whose structure is fixed. For the candy bag with unknown proportion theta, we have a continuum of hypotheses, and the likelihood of n candies with C cherry is theta to the c dot 1 minus theta n minus c. Maximizing the log likelihood L equals c the log theta plus n minus c the log 1 minus theta by differentiating sets the derivative to 0 and yields theta equals c over n. The maximum likelihood hypothesis, HML, asserts that the actual proportion of cherry candies in a bag is equal to the observed proportion n. The candies unwrapped so far. This reveals the standard 3-step method. Write the likelihood expression. Write the derivative of the log likelihood with respect to each parameter. Find the parameter values such that the derivatives are 0, with the trickiest step, usually the last, often needing iterative solution algorithms or other numerical optimization techniques. The method's significant problem, when the dataset is small enough that some events have not yet been observed, the maximum likelihood hypothesis assigns 0 probability to those events. So tricks like initializing the counts for each event to 1 instead of 0 avoid 0 probabilities. The wrapper color example scales the method to a network with 3 parameters: theta, cherry proportion; theta sub 1, red wrapper given cherry; theta sub 2, red wrapper given lime. The log likelihood is the sum of 3 terms, each of which contains a single parameter. So when we take derivatives, we get 3 independent equations, and the solution for theta sub 1 is the observed fraction of cherry candies with red wrappers, and similarly for theta sub 2. These results are very comforting, and it is easy to see that they can be extended to any Bayesian network whose conditional probabilities are represented as tables. With complete data, the maximum likelihood parameter learning problem decomposes into independent estimation problems, one per conditional distribution. Bayesian parameter learning instead maintains a posterior over parameters, using conjugate priors, Dirichlet for multinomials, beta for binomials, so the posterior stays in the same family and predictions are a weighted average over all parameter values, avoiding maps over confidence. The heart disease example shows why hidden variables matter. Removing heart disease from the diagnostic network increases the total number of parameters from 78 to 708 because the symptom variables are no longer conditionally independent given their parents. Latent variables can dramatically reduce the number of parameters required to specify a Bayesian network, and hence the amount of data needed to learn the parameters. Learning with hidden variables, the EM algorithm. Hidden or latent variables are not observable in the data. Medical records seldom contain a direct observation of the disease itself. The expectation maximization, EM, algorithm solves this problem in a very general way. The algorithm seems like magic at first, but once the intuition has been developed, one can find applications for EM in a huge range of learning problems. Unsupervised clustering is the first example. Discerning multiple categories in a collection of objects, the spectra of 100,000 stars revealing red giant and white dwarf, astronomers had to perform unsupervised clustering to identify these categories. Clustering presumes that the data are generated from a mixture distribution, with k components and a mixture of Gaussian's family. The parameters are the weights W sub I equals P of C equals I, means mu sub I, and covariance is the sum over I. If we knew which component generated each data point, then it would be easy to recover the component Gaussians. On the other hand, if we knew the parameters, we could assign each data point to a component. The problem is that we know neither the assignments nor the parameters. EM's idea: pretend that we know the parameters of the model and then infer the probability that each data point belongs to each component. Then refit the components to the data, with each point weighted by the probability that it belongs to that component, iterating until convergence. The two steps. The E step computes the expected values P sub ij of the hidden indicator variables Z sub ij, whether datum X sub j came from component I, whereby Bayes' rule P sub ij equals alpha dot P of X sub j, given C equals I dot P of C equals I. The M step, based on the expectation step, computes the new mean, covariance, and component weights. Mu sub I equals the sum over j, P sub ij dot X sub j over N sub I. The sum over I equals the sum over j, P sub ij dot X sub j minus mu sub I X sub j minus mu sub it over N sub I. And W sub I equals N sub I over N, where N sub I equals the sum over j, P sub ij, the effective number of data points currently assigned to component I. The naming is exact. The E step can be viewed as computing the expected values P sub ij of the hidden indicator variables. And the M step finds the new values of the parameters that maximize the log likelihood of the data, given the expected values of the hidden indicator variables. Applied to the 500-point star data, the final model that EM learns is virtually indistinguishable from the original model, and EM increases the log likelihood of the data at every iteration, provably, though under certain conditions. EM can be proven to reach a local maximum in likelihood, and in rare cases it could reach a saddle point or even a local minimum. To generate local maxima are serious problems, especially in high dimensions. One Gaussian component shrinks so that it covers just a single data point. Its variance will go to 0, and its likelihood will go to infinity, or two components can merge. Remedies include map-EM with priors and restarting shrunk components. Learning Bayes' net parameter values for hidden variables applies the same insights. The mixed two-bags candy model features independent given the bag. Bag hidden is a naive Bayes mixture whose parameters are the bag prior theta and the conditional probabilities theta sub F1, theta sub F2, flavor cherry, theta sub W1, theta sub W2, red wrapper, theta sub H1, theta sub H2, whole. Given 1,000 candies sampled from a true model with theta equals 0.5 and each feature probability 0.8 in bag 1 and 0.3 in bag 2, one full EM iteration is worked through. The E step computes, for each candy, the posterior probability that the candy comes from bag 1, given its observed features and the current parameter estimates. The M step re-estimates each parameter as the weighted frequency of the feature among candies, using those posteriors as weights. Because the true bag proportions swing the feature frequencies sharply, cherry, red, and hold candies are far more common from bag 1. The first E step already separates the candies into two coherent clusters. Subsequent iterations refine the parameters until they converge near the true 0.8, 0.3 values. Iterating, the log likelihood trajectory shows EM converging to slightly exceeding the true model's likelihood, virtually indistinguishable from the original model. The same idea applies to learning Bayesian networks with hidden variables generally. Each E-step fills in a distribution over the hidden variables values, and each M-step re-estimates the conditional probabilities from the completed, weighted data exactly as in the Gaussian mixture case. The chapter closes with the general perspective on EM. Expectation maximization is a broadly applicable principle. The algorithm seems like magic at first, but once the intuition has been developed, one can find applications for EM in a huge range of learning problems. Its two theoretical guarantees are that EM increases the log likelihood of the data at every iteration, and that under certain conditions that hold in most cases, EM can be proven to reach a local maximum in likelihood, resembling a gradient-based hill-climbing algorithm without a step-size parameter. This monotone likelihood property is what makes EM trustworthy in practice. Each E/M sweep can only improve the model's fit to the observed data, so the iterations can halt when the likelihood gain falls below a threshold. Its drawbacks are equally explicit. Degenerate local maxima. One Gaussian component shrinks so that it covers just a single data point. Its variance will go to 0, and its likelihood will go to infinity. Two components merge, which are serious problems, especially in high dimensions. The need to choose the number of components k. We have to try different values of k and see which is best. And the remedies of map-EM with priors, restarting shrunk components, and sensible initialization. A parallel thread, structure learning, deciding which edges belong in a Bayesian network, not just the parameters, is addressed in the chapter's notes alongside Bayesian model selection with a BIC score, which penalizes the number of parameters to favor simpler structures given the same data. Dirichlet processes and Gaussian processes extend the framework to unknown numbers of components and prior distributions over the space of continuous functions, respectively. The modern continuations of the statistical learning program. Bayesian versus map versus ML learning. Predict by weighting all hypotheses, optimal, or by the single most probable, map, compresses data equals MDL, or by likelihood alone, ML, under a uniform prior. MLE with complete data. Parameters decompose across the network's conditional distributions. Empirical frequencies maximize likelihood, with smoothing against zero probabilities. EM for hidden variables. Alternate an E-step, expected assignments, and an M-step, re-estimate parameters. Likelihood increases each iteration, converging to a local maximum. Chapter 21. Deep Learning. Simple feed-forward networks. Chapter 21 introduces deep learning. Machine learning using multiple layers of simple, adjustable computing elements, organized as computation graphs with tunable weights. A feed-forward network has connections only in one direction. It forms a directed acyclic graph with designated input and output nodes, like a Boolean circuit, but in neural networks, input values are typically continuous. A recurrent network feeds its intermediate or final outputs back into its own inputs, forming a dynamical system that has internal state or memory. Each node is a unit, calculated by the weighted sum of the inputs from predecessor nodes fed through a nonlinear activation function. A sub j equals g sub j, in j equals g sub j, the sum over iw sub ij a sub I, with a dummy unit fixed at +1 for the bias. The fact that the activation function is nonlinear is important, because if it were not, any composition of units would still represent a linear function. The nonlinearity is what allows sufficiently large networks of units to represent arbitrary functions. The universal approximation theorem. A network with just two layers of computational units, the first nonlinear and the second linear, can approximate any continuous function to an arbitrary degree of accuracy by representing exponentially many bumps of different heights at different locations in the input space. Common activation functions. The logistic or sigmoid, also used in logistic regression. Sigma of x equals 1 over 1 plus e to the minus x. The ReLU, rectified linear unit. The maximum of 0x, the soft plus, a smooth version of ReLU whose derivative is the sigmoid, and tan, a scaled and shifted version of the sigmoid, with range -1 plus 1. All of them are monotonically non-decreasing, so their derivatives are non-negative, a fact that figures in the sign structure of backpropagation. Gradients. Composing units creates a complex function h sub wx. The two input / two hidden / output networks output expansion shows the nested composition. And in vector form, the whole network is h sub wx equals g to the 2 of w to the 2 dot g to the 1 of w to the 1x. The computation graph, or data flow graph, makes each element of the overall computation explicit, distinguishing inputs from weights. Each weight is like a volume control knob. When the graph is fully connected, every node in each layer is connected to every node in the next layer, the default, but choosing the connectivity of the network is also important, as section 21.3 shows. Gradients and learning apply. Chapter 19's gradient descent. For a weight into the output unit, The chain rule gives partial loss over partial W sub 35 equals delta sub 5, delta sub 3, where delta sub 5 equals 2 hat of y minus y dot g sub 5, and sub 5 is a sort of perceived error for hidden weight. One more chain rule step gives partial loss over partial W sub 13 equals delta sub 5 that W sub 35 dot g sub 3 in sub 3 dot x sub 1. The perceived error at the input to unit 3 is the perceived error at the input to unit 5 multiplied by information along the path from 5 back to 3, entirely general, and give ing rise to the term backpropagation for the way that the error at the output is passed back through the network. With a convention delta sub 5 equals 2 hat of y minus y dot g sub 5, and sub 5 is the perceived error at the point where unit 5 receives its input. The gradient with respect to W sub 35 is just delta sub 5 at a sub 3, which makes perfect sense. If delta sub 5 is positive, that means hat of y is too big. If a sub 3 is also positive, then increasing W sub 35 will only make things worse. Whereas if a sub 3 is negative, then increasing W sub 35 will reduce the error, and if a sub 3 is small, W sub 35 didn't play a major role. The gradient factors include the local derivatives g sub j in j, which can be very close to 0, sigmoid, soft plus, tan, or exactly 0, real u, if the inputs from the training example happen to put unit j in the flat operating region. So deep networks with many layers may suffer from a vanishing gradient. Error signals are extinguished altogether as they are propagated back through the network. The motivation for the residual and LSTM architectures later in the chapter. All of these gradients are computed by the method of automatic differentiation. Backpropagation in deep learning is simply an application of reverse mode differentiation, applying the chain rule from the outside in and gaining the efficiency advantages of dynamic programming for networks with many inputs and relatively few outputs. All of the major packages for deep learning provide automatic differentiation, enabling end-to-end learning, in which a complex computational system for a task, such as machine translation, can be composed from several trainable subsystems trained from input-output pairs. The designer need have only a vague idea about how the overall system should be structured. Computation graphs for deep learning. Building computation graphs begins with the input layer and proceeds through a sequence of layers, each a map from tensor inputs to tensor outputs. The graph is the unit of design. Represent hypotheses as computation graphs with tunable weights and compute the gradient of a loss function with respect to those weights in order to fit the training data. Computation graphs compose modularly. A designer stacks linear maps and nonlinearities, affine activation, forms chains and branches. The same idea applies to all forms of deep learning. We construct computation graphs and adjust their weights to fit the data. The graph structure encodes inductive biases, temporal invariance for speech. A word sounds the same no matter what time of day. Translational invariance for images, the topic of convolutional networks that follow. Convolutional networks. A convolutional neural network, CNN, contains spatially local connections, at least in the early layers, and has patterns of weights that are replicated across the units in each layer. Fully connected layers are hopeless for images. For a typical megapixel RGB image, that's 9 trillion weights in the first hidden layer alone. Two ideas fix this. First, each hidden unit receives input from only a small, local region of the image, respecting adjacency locally and reducing weights from n to the second to L.n. Second, image data exhibit approximate spatial invariance. Anything that is detectable in one small, local region would look the same if it appeared in another, so constraining the L weights connecting a local region to a unit in the hidden layer to be the same for each hidden unit makes the hidden units feature detectors that detect the same feature wherever it appears. A pattern of weights that is replicated across multiple local regions is called a kernel, and the process of applying the kernel is called convolution. For a kernel K of size L and stride S, each output position takes the dot product of the kernel with a snippet of the input centered at that position. Convolution can be formulated as a single matrix operation, so gradient descent can be applied easily and effectively to CNNs. With D-kernels, a two-dimensional input array becomes a three-dimensional array of hidden units, with the third, kernel, dimension lacking adjacency. CNNs were inspired originally by models of the visual cortex. The receptive field of a unit grows from the kernel size L in early layers to L-1 m plus 1 in the mth hidden layer, linear growth with stride 1, or big O of L dot S to the M, exponential, written with the stride S raised to the layer depth, with larger strides. Pooling layers summarize adjacent units with a fixed operation. Average pooling facilitates multi-scale recognition, and max pooling acts as a kind of logical disjunction, saying that a feature exists somewhere in the unit's receptive field. The final classification layer is a softmax with C output units. Tensor operations keep the shape of the data explicit. A 256 times 256 RGB mini batch of 64 images is a four-dimensional tensor of size 256 times 256 times 3 times 64, and after 96 kernels of size 5 times 5 stride 2, it becomes a feature map composed of 96 channels. Deep learning workloads are often run on GPUs or TPUs, essential if one is training a large CNN, and it is common to process not one image at a time, but many images in parallel. Residual networks solve the vanishing gradient problem. A typical deep model learns a new representation at layer I by completely replacing the representation at layer I-1. So each layer must, at the very least, preserve the task-relevant information contained in the preceding layer, and if the weights of a layer are zeroed, the entire network ceases to function. And two zeroed layers in a row make learning impossible because gradients vanish. The key idea of residual networks: a layer should perturb the representation from the previous layer rather than replace it entirely. So if the learned perturbation is small, the next layer is close to being a copy of the previous layer. The update z to the I equals g sub r of z to the I, 1 plus f of z to the I. 1 treats f as the residual, perturbing the default behavior of passing layer I-1 through to layer I. Because the identity path carries the signal and the gradient directly, gradient descent can train very deep residual networks without vanishing gradients, which is why virtually all modern deep networks are residual in form. The architectural idea behind ImageNet winning and speech/translation models alike. Data augmentation, rotations, flips, translations of inputs, further exploits the invariances that CNNs encode, multiplying effective sample size without new labels. Learning algorithms. Optimization drives deep learning. Mini-batch stochastic gradient descent randomly selects a small number of training examples at each step, balancing computation against gradient noise. A mini-batch of n examples cuts per step cost by roughly n/m, while gradient noise grows only as the square root of that ratio, so mini-batches dominate full-batch descent in speed. Momentum accumulates a running average of past gradients to smooth the path. Learning rate schedules anneal the step size, guaranteeing convergence on the non-convex loss. Batch normalization, normalizing each layer's inputs to zero mean and unit variance, reduces sensitivity to initialization and speeds training. Weight initialization heuristics, small random weights with He/Xavier scaling, keep activations and gradient magnitudes healthy at the first pass. The chapter emphasizes that all gradients flow through the computation graph's shared structure regardless of architecture. Feed-forward, convolutional gradients of the convolution weights via the same chain rule, and recurrent via backpropagation through time. Modern software packages handle the differentiation automatically, so users can experiment freely with different network structures, activation functions, loss functions, and forms of composition. The practical enabler of the deep learning revolution. Generalization. Deep networks generalize surprisingly well. Even though they are very complex, some of them have billions of parameters, a fact at odds with the traditional view that overparameterization causes overfitting. The chapter revisits figure 19.9. Deep neural networks have the property that their validation set error tends to decrease as capacity increases, a departure from the U-shaped curve of decision trees. The resolution is that adding capacity means that there are more candidate functions, and some of them are naturally well suited to the patterns of data that are in the true function, an argument rooted in the function class structure rather than parameter count. Data augmentation, perturbing training inputs with rotations, flips, translations, exploits invariance to increase effective sample size. Regularization techniques, weight decay, and L2 penalty on weights, the deep analog of Chapter 19's regularization. Dropout, independently zeroing random units during training, forcing the network to be robust to the absence of particular units. and early stopping, halting when validation error stops improving, a fast and simple way of regularizing. Guard against memorization. And the honest observation stands that the empirical success of deep generalization is not yet fully explained by theory. It is remarkable that models with enormous numbers of parameters generalize so well, and the surrounding questions, implicit regularization from the optimization trajectory, the geometry of the loss landscape, and why flat minima correlate with generalization, are flagged as frontier research. The chapter's disciplined position is that the bias variance framework of Chapter 19 is the right vocabulary, but deep models force a subtler picture in which capacity, optimization, and data interact in ways the classical theory does not yet capture. Recurrent neural networks. Recurrent neural networks, RNNs, allow cycles in the computation graph, each with a delay, so units may take as input a value computed from their own output at an earlier step, giving the network internal state or memory. Inputs received at earlier time steps affect the RNN's response to the current input. For sequential data, RNNs can be compared to the hidden Markov models, dynamic Bayesian networks, and Kalman filters described in Chapter 14. The hidden state Z sub t of the network suffices to capture the information from all previous inputs, a Markov assumption, and Z sub t equals F sub W, Z sub t minus 1, X sub t. For some parameterized function F sub W represents a time-homogeneous process, essentially a universally quantified assertion that the dynamics represented by F sub W hold for all time steps. A feed-forward network, by contrast, would force the network to examine only a finite-length window of data, G, to detect long-distance dependencies. Training a basic RNN unrolls it for t steps into a feed-forward network with weight matrices W sub x, z, W sub z, z, and W sub z, y, shared across all time steps. Gradients propagate recursively. The contribution to the gradient from time step t is calculated using the contribution from time step t minus 1, an algorithm called backpropagation through time, linear in network size. If we order the calculations in the right way, the total runtime for computing the gradient will be linear in the size of the network, and it is usually handled automatically by deep learning software systems. The recursive structure reveals the instability. If we iterate the recursive calculation, we see that gradients at time t will include terms proportional to W sub z, z to the t. So, our simple RNN will certainly suffer from the vanishing gradient problem. See page 756. If W sub z, z is less than 1, and may experience the exploding gradient problem. If W sub z, z is greater than 1. For the general case, these outcomes depend on the first eigenvalue of the weight matrix W. Sub z kropka. Long short-term memory, LSTM, designs fix this. A memory cell C is essentially copied from time step to time step, and new information enters the memory by adding updates. In this way, the gradient expressions do not accumulate multiplicatively over time. Gating units, soft sigmoid values in 0, control information flow element-wise. The forget gate F determines if each element of the memory cell is remembered, copied to the next time step, or forgotten, reset to 0. The input gate I whether it is updated additively by new information from the input vector. The output gate O whether it is transferred to the short-term memory Z, which plays a similar role to the hidden state in basic RNNs. LSTMs were among the first practically usable forms of RNN, with excellent performance on a wide range of tasks, including speech recognition and handwriting recognition, and their use in natural language processing is developed in Chapter 24. Unsupervised learning and transfer learning. Supervised deep learning often require far more labeled data than a human would. A child needs to see only one picture of a giraffe, rather than thousands, and our current approach to supervised deep learning may render some tasks completely unattainable because the requirements for labeled data would exceed what the human race or the universe can supply. Unsupervised learning learns solely from unlabeled inputs X, typically ing generative models, which can produce realistic text, images, audio, and video. Two goals are emphasized: learn new representations, features making objects easier to identify, and learn a generative model. Suppose we learn a joint model P sub W of xz, where z is a set of latent, unobserved variables. The model is free to learn to associate z with X however it chooses. A handwritten digit model might choose one direction in Z space to represent the thickness of pen strokes, and a faces model might choose one direction to represent gender and another to capture the presence or absence of glasses. Enabling arithmetic in Z space. Man with glasses minus man plus woman equals woman with glasses. Probabilistic PCA, PPCA, is the simplest generative model. Z drawn from spherical Gaussian, X equals WZ plus noise, giving P sub W of X equals N of X0 WW to the T plus sigma to the second I. New data samples can be generated directly. Observations that have very low probability can be flagged as potential anomalies. And with the dimension of Z is less than the dimension of X, the model learns to explain the data in terms of small number of features. More powerful generative models extend the same idea. Variational autoencoders, VEs, learn encoder that maps X to a distribution over Z and a decoder that maps Z back, training by maximizing a variational lower bound on the likelihood. Autoregressive models sample one output element at a time, conditioning each on all previous elements. The machinery behind language and audio generation in Chapter 24, and generative adversarial networks, GNs, train a generator against a discriminator that tries to tell real from fake samples, reaching such fidelity that the generated faces of section 21.7.1's figure are indistinguishable at a glance. Enabling arithmetic in Z space. Man with glasses minus man plus woman equals woman with glasses. These models demonstrate that deep unsupervised learning produces not just features, but samples. The generative capability the chapter identifies as the differentiator from supervised prediction. Transfer learning requires some labeled examples, but improves their performance by studying labeled examples for different tasks. Start with a publicly available general-purpose data set, or a model that has been pre-trained on this data, then add specific data from your users and retrain. The standard recipe for applying deep models in data-poor domains. Semi-supervised learning, also an active area, is noted, but the techniques developed so far have not proven broadly effective in practice. Applications. Deep learning's applications track the book's earlier arcs. Speech recognition, visual object recognition, machine translation, medical diagnosis, and game playing. The chapter recalls the 2012 ImageNet breakthrough. A deep network demonstrated a dramatic improvement over previous systems, which were based largely on handcrafted features and the scale of modern deployment, recommender systems, language models, and the AlphaGo family self-play learning. The honest closing note is that deep learning relies heavily on powerful hardware, whereas a standard computer CPU can do 10 to the 9th or 10 to the 10th operations per second. A deep learning algorithm running on specialized hardware, GPU, TPU, or FPGA, might consume between 10 to the 14th and 10 to the 17th operations per second, mostly in the form of highly parallelized matrix and vector operations, and on large amounts of training data, and on a few algorithmic tricks, a dependence that Chapter 28 returns to when judging the field's future. The chapter also reports the concrete trajectory that made deep learning central. Deep learning systems have exceeded human performance on some vision tasks and lagged behind in some other tasks, and similar gains have been reported in speech recognition, machine translation, medical diagnosis, and game playing, with the use of a deep network to represent the evaluation function contribute ing to AlphaGo's victories over the leading human Go players. The recurring lesson is transfer of scale. The same convolution machinery that reads handwritten digit scales through residual depth and specialized hardware to ImageNet, speech, translation, and games, making deep learning, in the chapter's framing, the dominant realization of the learning from examples paradigm in the modern era. Feed-forward networks and backpropagation. Units compute nonlinear functions of weighted inputs. The universal approximation theorem. Gradients via automatic differentiation in reverse mode, with a vanishing gradient warning and residuals as the fix. CNNs. Local receptive fields, shared kernels, convolution and pooling, tensor feature maps. Model size independence from image size, and residual nets for depth. RNNs and LSTMs. Recurrence equals memory. Unrolling and backpropagation through time. The vanishing/exploding gradient and the LSTM's gates as the mitigation. Unsupervised/transfer. Generative models, PPCA, VEs, GNs, learn representations, and can sample. Pre-training, then fine-tuning transfers knowledge across tasks. The practical route for scarce labels. Scale and practice. Deep learning's triumphs rest on GPUs/TPUs, abundant data, and algorithmic tricks, a hardware and data-bound discipline. Chapter 22. Reinforcement learning. Learning from rewards. Reinforcement learning, RL, draws the line against supervised learning. The agent interacts with the world and periodically receives rewards or reinforcements that reflect how well it is doing. For chess, the reward is 1 for winning, 0 for losing, and 1/2 for draw. Reinforcement learning differs from just solving an MDP because the agent is not given the MDP as a problem to solve. The agent is in the MDP. It may not know the transition model or the reward function, and it has to act in order to learn more. Imagine playing a new game whose rules you don't know. After 100 or so moves, the referee tells you lose. That is reinforcement learning in a nutshell. Providing a reward signal is usually much easier than providing labeled examples of how to behave. The chess reward requires only a few lines of code, and we don't have to be experts, capable of supplying the correct action in any situation. Win/loss rewards are sparse. In a vast majority of states, the agent is given no informative reward signal at all, and a little bit of expertise can go a long way. Intermediate rewards make learning much easier. A point for tennis, progress around the track, forward motion when crawling. RL is a very general way to build AI systems, particularly true for simulated environments. And the addition of deep learning as a tool within RL systems has also made new applications possible, including learning to play Atari video games from raw visual input, controlling robots, and playing poker. The chapter organizes literally hundreds of different reinforcement learning algorithms into categories. Model-based RL uses a transition model of the environment to help interpret the reward signals and to make decisions, possibly learn from experience. Recall the chess program that knows the rules but not good moves, often learning a utility function U of S, model-free RL, neither knows nor learns a transition model, learning instead a more direct representation of how to behave. In two varieties, action utility learning. Q learning learns a Q function or quality function, Q of SA. Given a Q function, the agent can choose what to do in S by finding the action with the highest Q value and policy search. The agent learns a policy pi of S that maps directly from states to actions, i.e., a reflex agent. The chapter's arc, passive RL, fix policy, learn utilities, active RL, must also figure out what to do. The exploration problem, generalization via function approximation, including deep learning, policy search, apprenticeship learning from demonstrations and applications. Passive reinforcement learning. A passive learning agent already has a fixed policy pi of S that determines its actions and is trying to learn the utility function U to the pi, the expected total discounted reward if policy pi is executed beginning in state S. The passive learning task is similar to the policy evaluation task. The difference is that the passive learning agent does not know the transition model P of S given SA, nor does it know the reward function R of SAS. The agent executes a set of trials in the environment using its policy pi. Each trial is a sequence of transitions until it reaches one of the terminal states, with percept supplying state and reward. Direct utility estimation uses the defining fact that the utility of a state is the expected reward to go, and each trial provides a sample of this quantity for each state visited. So the algorithm updates the estimated utility for that state accordingly, just by keeping a running average. In the limit of infinitely many trials, the sample average will converge to the true expectation, reducing RL to a standard supervised learning problem. But it ignores an important constraint. The utility of a state is determined by the reward and the expected utility of the successor states. The utility values obey the Bellman equations for a fixed policy, so direct utility estimation misses opportunities for learning. Search NG. For you in a hypothesis space that is much larger than it needs to be and often converges very slowly. Adaptive dynamic programming, ADP, takes advantage of the constraints among the utilities of states by learning the transition model that connects them and solving the corresponding Markov decision process using dynamic programming. For passive learning agent, this means plugging the learned transition model P, S, S, pi S, and the observed rewards R, S, pi S, S, into the Bellman equation to calculate the utilities of the states. Because the model is estimated from limited data, ADP's utilities are extremely accurate, where exploration has been thorough, and severely lacking, where it has not. So it results in much faster convergence than direct utility estimation by enforcing the Bellman constraint that a state's utility is the immediate reward plus the discounted utility of its successor, spreading knowledge along transitions rather than waiting for trials to end. The temporal difference, TD, family carries the same idea online. Learning a utility estimate US by adjusting it toward the current reward plus the discounted utility of the successor. With updates of the form U of S is less than minus U of S plus alpha, or plus gamma U of S minus U of S. TD methods combine the advantages of both approaches. They learn online, without a model, yet they respect the Bellman constraint, converging more quickly than direct utility estimation and more simply than full ADP. The comparison among the three passive methods is the chapter's clearest teaching moment. Direct utility estimation waits for trial ends and ignores structure. ADP uses a model to propagate information instantly, but needs a model. TD sits between, model-free, and yet bootstrapping from one step ahead, the property that makes TD the workhorse of later model-free RL. Active reinforcement learning. An active learning agent gets to decide what actions to take, so it will need to learn a complete transition model with outcome probabilities for all actions and utilities defined by the optimal policy, obeying the Bellman equations solved using the value iteration or policy iteration algorithms. A greedy agent. It takes the action that it currently believes to be optimal at each step, can converge to a suboptimal policy, because the learned model is not the same as the true environment, and the agent does not know what the true environment is. The greedy agent has overlooked the fact that actions do more than provide rewards. They also provide information, so an agent must make a trade-off between exploitation of the current best action and exploration of previously unknown states. A scheme should be greedy in the limit of infinite exploration, or GLI. Must try each action in each state an unbounded number of times. A simple GLI scheme chooses a random action at time step t with probability 1/t, which does eventually converge, but it can be slow. Better is an exploration function f, un, that is increasing in u and decreasing in n, implemented by modifying the Bellman update to use an optimistic utility estimate u plus, which takes the maximum over the usual Bellman value, and the exploration bonus f, n is a, for relatively unexplored state action pairs. So, the benefits of exploration are propagated back from the edges of unexplored regions, making the agent try each state action pair at least n times, and converging to near zero policy loss after just 18 trials in the 4x3 world. The agent stops caring about the exact utilities of states that it knows are undesirable and can be avoided. There is not much point in learning about the best radio station to listen to while falling off a cliff. Safe exploration confronts the real world's irreversibility. The world is less forgiving. If you're a baby sunfish, your probability of surviving to adulthood is about 0.000000001. And many actions are irreversible, possibly entering an absorbing state where no actions have any effect and no rewards are received. We cannot afford to have our agents taking irreversible actions or entering absorbing states. The agent should be risk-averse, preferring actions that are known to be safe and treating exploration as a separate, carefully managed activity. For a real car, one wants the agent to learn to drive without crashing, so exploration must be constrained and supervised in a way that pure simulated exploration never requires. Q-learning completes the model-free picture. Rather than learning P and R, the agent updates its Q value for a state action pair directly by one-step look ahead, using the observed transitions reward plus the discounted maximum over next state Q values, converging to the optimal Q function without a model, the algorithm that powers much of deep RL. The exploration function scheme itself deserves emphasis. The optimistic update US uses an exploration bonus F, that is R plus F and U otherwise, so the effect is to set a policy that will try to explore such actions until they have been tried at times. And crucially, the fact that U rather than U appears on the right-hand side is very important, because the optimistic values propagate backward. An action with no hope of being optimal in the long run is still tried. Enough to confirm that, and the benefits of exploration are propagated back from the edges of unexplored regions. explaining why the optimistic agent finds a very nearly optimal policy after just 18 trials, while the greedy one is trapped at loss 0.235 after 8. Generalization in reinforcement learning. Tabular representations work for state spaces with up to about 10 million states, but convergence is too slow in real-world environments. Backgammon has about 10 to the 20th states. We cannot easily visit them all. Function approximation constructs a compact approximation of the true utility function or Q function, e.g., a weighted linear combination of features. So instead of learning 10 to the 20th state values in a table, the algorithm learns 20 values for the parameters. Adding look-ahead search sometimes combines with the approximator for accuracy. Function approximation allows for inductive generalization. The agent can generalize from states it has visited to states it has not yet visited. Tesoro's backgammon program played a human champion level, even though it explored only a trillionth of the complete state space. Direct utility estimation becomes a supervised regression on state, reward to go, pairs. With a linear function of the square coordinates, we can find the best fit using standard linear regression. And online learning uses the Widrow-Hoff rule. The delta rule, each parameter is updated by the product of the prediction error and the parameter's feature value. Changing the parameters in response to an observed transition also changes the values of U for every other state. This is what we mean by generalization. The limits matter. What matters for linear function approximation is that the function be linear in the features. But we can choose the features to be arbitrary nonlinear functions. So a feature such as f sub 3x, y equals x minus 5 to the second plus y minus 5 to the second can capture the pyramid utility of the 5-5 reward world. All is not lost. However, remember that what matters for linear function approximation is that the function be linear in the features, not in the state variables. Deep reinforcement learning is function approximation with a deep network. The Q function is a neural network whose input is the game screen and whose output is a Q value for each action. In DQN, learn to play Atari games from raw pixels, demonstrating the power of combining function approximation, generalization, and RL, while also exposing instability when the network's own predictions are used as targets, mitigated by experience replay, storing transitions, and sampling mini-batches. To break correlations and target networks, slowly updated copies that stabilize the bootstrap targets. The lesson generalizes. Function approximation makes it practical to represent utility, or Q, functions for very large state spaces, but more importantly, it allows for inductive generalization. And the same deep Q machinery that learns Atari from pixels also drives the AlphaZero style self-play systems. Temporal difference with function approximation stitches the two threads together directly, instead of waiting for a full trial, as direct utility estimation does, or requiring a model, as ADP does. TD with a linear value function updates the parameters according to the temporal difference error, the reward plus the discounted estimated value of the successor minus the current estimate, thus combining the online, model-free character of TD with the generalization of function approximation. The subtlety the chapter flags is that this combination is not guaranteed to converge as cleanly as either alone. Because the bootstrap target moves as the parameters move, the same instability that deep Q learning addresses with experience replay and frozen target networks. Still, the practical lesson is decisive, with features of the state that capture the geometry of the task, like distance to goal or the x, y coordinates, or learn deep features. Function approximation turns an RL problem that would require visiting 10 to the 20th states into one learnable from a trillionth of the state space, exactly as Tesoro's champion backgammon player demonstrated. A fact the chapter names the central reason for combining the two fields. Policy search. Policy search learns a policy pi of S that maps directly from states to actions, a reflex agent, bypassing utility/Q estimation. The chapter frames it as an optimization problem over the policy's parameters. We evaluate a policy by executing it and measuring the total reward, then adjust the parameters in the direction of increasing reward. Direct policy search treats the expected reward as a function of parameters and applies hill climbing, simulated annealing, or, for differentiable policies with stochastic actions, policy gradient methods that estimate the gradient of expected reward from sample trajectories. The reinforce rule increases the probability of actions that led to high reward and decreases the probability of actions that led to low reward. in proportion to the reward to go. Policy search has advantages when a good policy is easier to represent than a good value function. E.g., a car racing policy, turn left when on the grass, is far simpler to express as a policy than as a value function, and it inherits the reflex agent freedom of Chapter 2, but it can be statistically inefficient because it ignores the value information that Q-learning uses, and the variance of policy gradient estimates can be high. In practice, actor-critic methods combine both. The actor policy is updated by gradient ascent. The critic value function reduces variance in the gradient estimate. The critic learns to predict the value of the current policy, and the actor improves the policy using the critic's estimates as baselines. The architecture behind much of modern deep RL, from robotic locomotion to dialogue systems. The chapter also notes parameter-based policy search, searching directly in weight space with evolution or finite difference gradients, which sidesteps gradient estimation entirely and can work on non-differentiable policies. Apprenticeship and inverse reinforcement learning. Apprenticeship learning takes as input demonstrations of expert behavior rather than reward signals. Useful when specifying the reward function is hard, but examples of good behavior are easy to collect: driving, surgery, flying. Inverse reinforcement learning, IRL, recovers the reward function from the demonstrations. The agent infers what reward function the expert must have been optimizing, then uses that inferred reward to learn its own policy. The chapter notes the circularity. Many reward functions explain the same behavior, resolved by seeking the reward function under which the observed behavior is close to optimal, e.g., maximum margin or maximum entropy formulations, and the utility estimation. Framing links back to Chapter 16's preference elicitation, learning utility from choices. Apprenticeship is therefore a marriage of RL and imitation, in its deep learning manifestation. Imitation learning and behavior cloning underpins robots that learn to do what humans want by observing them, a theme resumed in Chapter 26's Human-Robot Interaction. Behavior cloning is fast and simple, but suffers from covariate shift. Errors compound as the agent leaves the demonstrated trajectory because it is trained only to mimic the expert's actions in the expert states. IRL mitigates this by following the whole reward and policy loop. Recover the reward, then optimize a policy, rather than cloning individual actions. Applications of reinforcement learning. RL has been applied with great success to game playing, robotics, and control, from Samuel's Checkers Player and TD Gammon, a backgammon program among the world's best, to AlphaGo, which shocked the world by defeating the human world champion at Go, and AlphaZero, which used no input from humans except the rules and learned through self-play alone. RL drives modern robotics, manipulation, legged locomotion, the learning to do what humans want of Chapter 26, recommendation and dialogue systems, and real-time control of data centers and chemical plants. Its Atari playing DQN demonstrated that Deep RL can learn directly from raw pixels and rewards, and its poker systems, Libratus, Pluribus, mastered imperfect information games that earlier game search had not, linking back to Chapter 5 and forward to Chapter 27's caution about specification. The chapter's application section stresses the practical conditions for RL success, a reward signal that is easy to specify and a simulator that provides abundant experience, plus the ability to make the agent's state representation and reward reflect the designer's true objectives, connecting to Chapter 16's preference uncertainty and Chapter 27 safety. The summary of RL's standing is characteristically measured. Reinforcement learning is a powerful and general approach, but it is not a panacea. The agent must explore, which can be dangerous. The reward function must be specified, and generalization across large state spaces remains hard. These caveats set up the book's closing themes of safety and alignment. RL versus supervised. Rewards are easier to supply than correct action labels. Sparse rewards make intermediate expertise valuable. Passive-active, direct utility estimation, ADP, and TD learn utilities under a fixed policy. Exploration, GLIE, exploration functions, safe exploration, drives active learning, with Q-learning as the model-free engine. Generalization and scaling, function approximation, linear features, deep network/Widrow, HOF, makes RL work beyond tables. Policy search and actor, critic bypass value functions. Apprenticeship and applications. Inverse RL recovers reward from demonstrations. RL successes, TD Gammon, AlphaZero, rest on simulators, good rewards, and safe exploration. Part 6. Communicating, Perceiving, and Acting. Chapter 23. Natural Language Processing. Language Models. Unlike formal languages, natural languages such as English or Chinese cannot be so neatly characterized. Language judgments vary from person to person and time to time. Natural language is ambiguous. He saw her duck, a waterfowl, or a downwards evasive move, and vague. And the mapping from symbols to objects is not formally defined. If we can't make a definitive Boolean distinction between grammatical and ungrammatical strings, we can at least say how likely or unlikely each one is. Hence the language model, a probability distribution describing the likelihood of any string. Do I dare disturb the universe? Plausible English. Universe dare the I disturb do? Extremely unlikely. Language models predict, what words are likely to come next, completions, spelling/grammar corrections, the most probable translation of sentence, and the most likely answer to a question. Language models are at the heart of a broad range of natural language tasks, and the language modeling task itself also serves as a common benchmark. Sapire's All Grammars Leak and Davidson's There is no such thing as language, a clearly defined shared structure, frame the realistic view. We cover simplistic language models that are clearly wrong, but still manage to be useful. The Bag of Words model recasts Chapter 12's naive Bayes as a full language model. P class W1. N equals alpha P class, pi_JP, WJ class. Imagining for each category a bag full of words. To generate text, first select one of the bags. Pull out a word at random. This will be the first word of the sentence. Then put the word back and draw a second word. Repeat until an end-of-sentence indicator, e.g., a period, is drawn. The model is clearly wrong. It falsely assumes that each word is independent of the others, and therefore it does not generate coherent English sentences. But it does allow us to do classification with good accuracy using the naive Bayes formula. The words stocks and earnings are clear evidence for the business section, while rain and cloudy suggest the weather section. Estimating from a corpus at least 1 million words of text, tens of thousands of distinct vocabulary words. Larger still, the 2.5 billion words in Wikipedia or the 14 billion word iWeb corpus. By counting, P of business equals 300 over 3,000. P of stocks given business equals 700 over 100,000. Works when we have high counts and low variance. But low counts have high variance and need smoothing. Alternatives: logistic regression, neural networks, or support vector machines with word count or presence. Feature vectors that are large and sparse. We might have 100,000 words, but for a short text, almost all the features will be 0. Feature selection drops, words that are very rare and thus have high variance, and words common to all classes, such as the email classification. Could add features for the sender, the time the message was sent, the words in the subject header, the presence of non-standard punctuation, the percentage of uppercase letters, whether there is an attachment. Tokenization is aren't one word, or should it be broken up as rn/ or r/n, is not trivial. The N-gram model fixes bag of words independence. The word quarter is common in both the business and sports categories, but the forward sequence first quarter earnings report is common only in business, and fourth quarter touchdown passes is common only in sports. So we'd like our model to make that distinction by making each word dependent on previous words. The fully general chain rule P of W sub 1. N equals the product over JP of W sub J given W sub 1. J 1 is in a sense perfectly correct, but it is not practical. With a vocabulary of 100,000 words and a sentence length of 40, this model would have 10 to the 200 parameters to estimate. The compromise with a Markov chain model that considers only the dependence between n adjacent words gives the n-gram model P of W sub J given W sub 1. J 1 equals P of W sub J given W sub J n plus 1. J 1 with unigram, 1 gram, bigram, 2 gram, and trigram, 3 gram, special cases. N-gram models work well for classifying newspaper sections, as well as for other classification tasks such as spam detection, sentiment analysis, and author attribution. Other N-gram models expand the space. A character-level model conditions each character on the n-1 previous characters, dealing with unknown words, and for languages that tend to run words together, as in the Danish word special age stabiliseringsperiode, Character models excel at language identification, even with very short text such as hello, world, or we gets dr, accuracy greater than 99%, with closely related Swedish/Norwegian at the 95% range, and at classifying dextroamphetamine as a drug name, Kallenberger as a person name, Plattsburgh as a city name without ever having seen them. The skipgram model counts words that are near each other, but skip a word or more between them. For French, "ne comprends pas," the one skip bigrams are "je comprends" and giving us conjugation and negation that we wouldn't get from regular bigrams alone. Other models, a character-level n-gram, good for unknown words and run-together languages like special Spraakstabiliseringstabiliseringsperiode, achieving greater than 99% language identification on short texts, and the skipgram model, which skips between words to capture conjugation and negation. French, "je ne comprends pas," gives one skip bigrams "je comprends" and "ne pas." Smoothing handles low and zero counts. Low-frequency n-grams have low counts that are subject to random noise. They have high variance, and it would be a mistake to assign an out-of-vocabulary word a probability of 0. Then the probability of the whole sentence would be 0. The fix replaces infrequent words with unk and digits within emails with email, with the start symbols, add 1, Laplace. Smoothing and back-off reserve probability mass for unseen n-grams. The principle that we should not assign probability 0 to unseen events, echoing Chapter 20. The chapter rehearses the arithmetic. High-frequency n-grams like of the have high counts in the training corpus, so their probability estimate is likely to be accurate, while low-frequency n-grams have low counts that are subject to random noise. They have high variance. Our models will perform better if we can smooth out that variance, and the unseen n-gram case demands it. It would be a mistake to assign such a word a probability of 0, because then the probability of the whole sentence, P, W1, N, would be 0. The UN machinery keep only, say, the 50,000 most common words, or all words with frequency greater than 0.0001%, and replace the others, ensures when an unknown word appears in a test set, we look up its probability under UNK. Laplace smoothing adds 1 to every count, renormalizing so no n-gram has 0 probability, and backoff falls back to shorter n-grams when longer ones are unseen. Grammar. Formal grammar in NLP is a formal language over words, a set of production rules describing well-formed sentences. Context-free grammar gives grammatical judgments plus, with probabilities attached, a probabilistic context-free grammar, PCFG, the n-gram idea lifted from strings to structures. The chapter's E0 grammar for the Wumpus world has rules like SNPVP 0.90, NP article noun 0.25, noun Wumpus 0.15, verb smells 0.10, with probabilities on every rule summing appropriately. A parse tree's probability is the product of its rule probabilities for every Wumpus smells. 0.9 times 0.25 times 0.05 times 0.15 times 0.40 times 0.10 is equal to 0.0000675. PCFGs let us rank parses by probability, thereby choosing among the ambiguous readings a string admits, the grammatical core of the chapter. Lexicon word-to-category rules, the recursive structure of NPs and relative clauses, and the treatment of coordination, NP conjunction NP, all extend the grammar while keeping it a probability distribution over trees. The recursion is what lets a finite grammar cover unbounded sentences. An NP can contain a relative clause containing another NP and so on. So the grammar of English, though finite in size, generates infinitely many sentences, and the PCFG's probabilities assign a coherent likelihood to each, a fully recursive, fully probabilistic view of grammar that underlies the parsers of the next section. Parsing. Parsing finds the most probable tree for a sentence under a probabilistic grammar. The CYK algorithm is a dynamic programming parser. Given a sequence of words, it finds the most probable parse tree for the sequence and its subsequences, filling a table PXIK. The probability of the most probable tree of category X spanning words IK by combining shorter spans into longer ones, with subspans generating the tuples by increasing length of the span. So shorter spans are already computed, and lexicalrules supplying XP for X arrow are word and grammar rules supplying XYZP for X arrow. Er is. CYK is polynomial in sentence length, and grammar size, finding the most probable tree efficiently. The figures parse of every wumpus smells, multiplies rule probabilities 0.90 times 0.25 times 0.05 times 0.15 times 0.40 times 0.10 equals 0.0675. And the tree has the linear form S, NP article every, noun wumpus, VP verb smells. With very large grammars, Beam search parses by keeping only the most likely partial parses, guaranteed to find the parse with highest probability? No. With a beam, the parser can operate in big O of n time and still finds the best parse most of the time. A deterministic parser, beam b equals 1, includes shift-reduce parsing, going through the sentence word by word, choosing at each point whether to shift the word onto a stack of constituents or to reduce the top constituents. The alternative dependency grammar assumes that syntactic structure is formed by binary relations between lexical items, without a need for syntactic constituents. Phrase structure trees are natural for languages, like English, with mostly fixed word order. Dependency trees are natural for languages, such as Latin, with mostly free word order, and the Universal Dependencies Project provides millions of parsed sentences in over 70 languages. Learning a parser from examples. Building a grammar for a significant portion of English is laborious and error-prone, so learn from a tree bank. The Penn Tree Bank is the best-known source. Over 100,000 sentences annotated with parsed tree structure. Given a tree bank, we can create a PCFG just by counting. If 600 of 1,000 S nodes are of the form S NPVP, we create the rule S NPVP 0.6. Altogether, the Penn Tree Bank has over 10,000 different node types, reflecting flat trees, perhaps flatter than we would like, good and the bad, parsed as a single NP rather than two conjoined NPs, yielding hundreds of near-duplicate rules. Data-oriented parsing automatically recovers generalized rules, the single NP conjunction NP, greatly reducing the number of rules that come out of the tree bank, and creating a grammar that ends up generalizing better for previously unseen sentences. Tree banks are not perfect. They contain errors and have idiosyncratic parses, and creating them requires a lot of hard work. So unsupervised parsing learns a new grammar or improves an existing grammar. Using a corpus of sentences without trees, the inside-outside algorithm, Dodd, 1988, estimates the probabilities in a PCFG from example sentences without trees. Similar to the way the forward-backward algorithm estimates probabilities, and curriculum learning starts with the easy part of the curriculum, short, unambiguous 2-word sentences extending to 3-word, 4-word, and eventually 40-word sentences. Semi-supervised parsing starts with a small number of trees, then adds a large number of unparsed sentences, exploiting partial bracketing from widely available text that has been marked up by the authors in the form of HTML or similar annotations. The words between /i tags form a noun phrase. The strings between /8 tags form verb phrases. Augmented grammars. A purely context-free grammar cannot represent finer distinctions. Not every NP can appear in every context with equal probability. Me ate a banana is ungrammatical. I ate a bandana, unlikely. Linguists say that the pronoun I is in the subjective case. Me in the objective case, first/second/third person, singular/plural. So a category like pronoun that has been augmented with features is called a subcategory. An augmented grammar replaces atomic non-terminals with structured representations. NP, SPJ, 1S, speaker, for I, subjective case, first person singular, meaning the speaker, versus NP, obj, 1S, speaker, for me. The features enforce grammatical agreement and case. Subject position demands the SPJ feature, so the grammar makes finer-grained distinctions about which sentences are more likely. The probabilistic extension of subcategorization, and it builds a representation of the semantics of a phrase in a compositional way. Complications of real natural language. Quantification. Every agent feels a breeze has only one syntactic parse, but 2 readings. One breeze felt by all the agents versus each agent. A separate personal breeze, handled by quasi-logical forms turned into logic by algorithms outside the parsing process, with preference rules for quantifier scope. Pragmatics completes interpretation by adding context-dependent information. Indexicals like I and today refer directly to the current situation, resolved by the hearer, and the utterance is a speech act, a question, a statement, a promise, a warning, a command, with commands extending the grammar. S, command, pred, hearer, VP, pred. Long-distance dependencies. Who did the agent tell you to give the gold to? Has a gap referring to who 11 words away, and a complex system of augmented rules ensures gaps match. You can't have a gap in one branch of an NP conjunction. What did she play NP Dungeons and Time and Tense? Ollie loves Bo versus Ollie loved Bo, represented in event calculus form. Loves contains during, now, extent E1, loved after, now, extent E2, with two lexical rules for the two verb forms. Everything else about the grammar remain NG the same. Ambiguity is pervasive, and we tend to think of ambiguity as a failure in communication. Newspaper headlines such as Squad helps dog bite victim, police begin campaign to run down jaywalkers, and helicopter powered by human shows structural ambiguity as a normal, unavoidable challenge. When a listener is consciously aware of an ambiguity in an utterance, it means that the utterance is unclear or confusing. And the principled response is probabilistic parsing, in which all readings survive but are ranked by probability rather than rejected outright. The chapter's grammar accordingly works by preference, not by hard grammaticality. Every candidate parse gets a probability, and the practical system chooses the most probable one under the language model. Natural language tasks. Natural language tasks assemble the machinery. Machine translation. Given parallel corpora, find a most likely target sentence for a source. Question answering. Locate the most likely answer span. Summarization. Dialogue systems. Information extraction. Finding entities and relations in text. And, at the center, language modeling as the benchmark to measure progress in language understanding. These tasks are linked by a single abstraction. The language model is a probability distribution over strings, and every task from translation to question answering can be posed as the search for the most probable output given the model and the input. The chapter's closing treatment stresses that language models are at the heart of these tasks, even when the models are clearly wrong but useful, and that statistical and neural language models, the n-gram successors trained on billions of tokens, underpin them. Tasks pull together the whole toolkit. Translation needs a noisy channel or direct model pairing source and target n-grams. Question answering needs retrieval plus ML ranking, summarization and dialogue ad generation. Information extraction reuses the classifiers of Chapter 19 and the relational models of Chapter 15. The transition to the next chapter is explicit. Deep neural networks perform a variety of language tasks, capturing the structure of natural language as well as its fluidity. The subject of Chapter 24's word embeddings, recurrent networks, and transformers, where the same language modeling objective scales to billions of parameters. Language models, probability distributions over strings, bag of words, naive Bayes, n-grams, Markov over words, character and skipgram variants, smoothing, and UNK handle sparse/0 counts. Grammar and parsing. PCFGs rank parse trees by rule probability products, CYK, beam/deterministic, shift-reduce, and dependency parsing. Grammars learned from tree banks or unlabeled text. Augmented grammars. Features case, person, number, and compositional semantics enforce agreement and subcategorization. Complications. Quantification scope, pragmatics, and speech acts. Long-distance dependencies, tense, and pervasive ambiguity, all handled by probabilistic ranking, not hard rejection. Tasks. Translation, QA, summarization, dialogue, and the language model benchmark. The deep models of Chapter 24 extend this foundation. Chapter 24. Deep learning for natural language processing. Word embeddings. Chapter 24 extends Chapter 23's statistical NLP with deep learning, beginning with word embeddings. We would like a representation of words that does not require manual feature engineering, but allows for generalization between related words. Syntactic, colorless, and ideal are both adjectives. Semantic, cat and kitten, are felines. Topical, sunny and sleet, are weather or sentiment. A one-hot encoding would not capture the similarity between words. Following the linguist John R. Firth's maxim, you shall know a word by the company it keeps. We could use raw n-gram counts, but they are cumbersome. A 100,000 word vocabulary yields 10 to the 25th 5 grams. A word embedding is a low-dimensional vector representing a word, learned automatically from the data. Individually, each one is just a vector of numbers, where the individual dimensions do not have discernible meanings, but similar words end up having similar vectors, forming clusters for country, kinship, transportation, and food words. Remarkably, for reasons we do not completely understand, the vectors support arithmetic. Athens is to Greece as Oslo is to. With vectors A, Athens, B, Greece, C, Oslo, we hypothesize that B minus A equals D minus C, giving us D equals C plus B minus A, and the computed vector D is closer to Norway than to any other word. The same relationship arithmetic works for capital, currency, atomic symbol, nationality, and past tense relationships. But there is no guarantee that a particular word embedding algorithm run on a particular corpus will capture a particular semantic relationship. Embeddings are popular because they have proven to be a good representation for downstream language tasks, not because they are guaranteed to answer analogy questions. Embeddings turn out to be helpful for essentially all applications of deep learning to NLP tasks, and it is often possible to use generic pre-trained vectors, word 2VC, glove, global vectors, fast text with embeddings for 157 languages, saving a great deal of time and effort. Training task-specific embeddings adapts them to a carefully selected corpus and will tend to emphasize aspects of words that are useful for the task. In part of speech POS tagging, the word cut could be a present tense verb or a noun, and if a nearby temporal adverb refers to the past, that resolves it. A feed-forward POS tagger takes a 5-word window as input and predicts the tag of the word in the middle. The learned embedding layer is the first layer of the network, looked up by input word, with similar words ending up with similar vectors because the network's gradient updates pull co-occurring words together. Recurrent neural networks for NLP. Language models with RNNs replace the fixed window feed-forward approach with the recurrent networks of Chapter 21. A language model that computes P, WTW1, T-1, by processing the words one at a time through a recurrent network whose hidden state summarizes the whole prefix. For classification, an RNN processes the entire sentence, and its final hidden state, or a pooling over hidden states, serves as the input to a classifier. For language modeling, the network's output at each step is a probability distribution over the next word, trained by maximizing the likelihood of the corpus. The direct extension of the n-gram objective with unbounded context, limited only by the hidden state's capacity and the LSTM/GRU gating that fights the vanishing gradient. RNN-based encoders are the workhorse of NLP models before the transformer, and they make the same Markov completeness claim as Chapter 14's filters while learning the dynamics from data. Sequence-to-sequence models. Sequence-to-sequence, seek-to-seek. Models translate, summarize, and answer by pairing an encoder, an RNN that maps the source to a context vector, with a decoder, an RNN that generates the target word by word from that context. The decoder's core is attention. Rather than compressing the whole source into one vector, the decoder attends to those positions of the source that are most relevant at each generation step, computing a weighted combination of source hidden states. This alleviates the bottleneck of a fixed-size context vector, letting a long source be consulted selectively. The chapter's translation example, the front door is red, la puerta de entrada es roja. Literally, the door of entry is red. Exposes the decoding problem. A greedy decoder might propose entrada for front. Spanish word order should put the noun puerta before the modifier, and the model has no mechanism to correct mistakes, so a better approach is to search for an optimal decoding, or at least a good one, using one of the search algorithms from Chapter 3. A beam search that keeps the top K hypotheses at each stage, extending each by one word using the top K choices of words, then chooses the best K of the resulting K superscript 2 new hypotheses, finishing when all hypotheses in the beam generate. The special N token. Modern neural MT uses a beam size of 4 to 8, whereas the older generation of statistical MT models would use a beam size of 100 or more. Attention plus decoding search made neural MT close to the level of a human on closely related language pairs, and the same encoder. Decoder with attention template extends to extractive and abstractive summarization, attend to the source to choose or generate key sentences, and to question answering. Attend to the passage to locate the answer span, making seek-to-seek the generic conditional generation architecture of modern NLP before the transformer. The transformer architecture. The influential article Attention is All You Need, Vaswani et al., 2018, introduced a transformer architecture, which uses a self-attention mechanism that can model long-distance context without a sequential dependency. Where seek attention went from the target RNN to the source RNN, self-attention lets each sequence of hidden states also attend to itself, the source to the source, and the target to the target, capturing long distance and nearby context within each sequence. The naive dot product attention is problematic. The dot product between a vector and itself will always be high, so each hidden state will be biased towards attending to itself. So the transformer first projects the input into three different representations. A query vector q sub I equals w sub q dot x sub I being attended from, a key vector k sub I equals w sub k dot x sub I being attended to, and a value vector v sub I equals w sub v dot x sub I the context that is being generated. The encoding c sub I of word I is the attention-weighted sum of values, with weights from softmax over scale query, key dot products. The scale factor, the square root of d, was added to improve numerical stability, computed simultaneously for all words via matrix operations, efficiently in parallel on modern specialized hardware. The choice of which context to use is completely learned, not pre-specified. Because a sum can average out important information, multi-headed attention divides the sentence up into m equal pieces and applies the attention model to each, concatenating so an important subpiece can stand out. Self-attention is only one component of the transformer model. Each transformer layer applies self-attention first, then feed-forward layers, where the same feed-forward weight matrices are applied independently at each position, with a ReLU between +2 residual connections to fight the vanishing gradient. Transformer models usually have 6 or more layers. Because self-attention is agnostic to word order, the transformer adds learned positional embeddings. The input to the first transformer layer is the sum of the word embedding at position T plus the positional embedding corresponding to position T, enabling POS tagging to work through a 3-layer transformer fed, 1 vector per word. The chapter notes only half the transformer story. The transformer encoder, useful for classification, while the full transformer decoder for sequence-to-sequence translation, adds a self-attention version, where each word can only attend to the words before it, left to right generation, and a second attention module in each transformer layer that attends to the output of the transformer encoder. Pre-training and transfer learning. Getting enough data to build a robust model can be a challenge. In Vision, that challenge was addressed by assembling large collections of images, such as ImageNet, and hand-labeling them. For NLP, it is more common to work with text that is unlabeled because an unskilled worker can easily label an image, but it requires extensive training to annotate a sentence with part-of-speech tags or parse trees, and text is abundant. The internet adds over 100 billion words of text each day. Pre-training, a form of transfer learning, in which we use a large amount of shared general domain language data to train an initial version of an NLP model, lets a smaller amount of domain-specific data refine the model, which can learn the vocabulary, idioms, syntactic structures, and other linguistic phenomena that are specific to the new domain. Pre-trained word embeddings corner. The glove model starts by gathering counts of how many times each word appears within a window of another word, like skipgrams, with Zij co-occurrence counts and Pij equals Zij/she. The intuition is the ratio P, W ice/P, W steam, high for solid applies more to ice, low for gas, near 1 for the or fashion, leading, through ratio to vector reasoning, to the constraint that the dot product of the two word vectors I and K equals the log of their co-occurrence probability. The dot product of two word vectors is equal to the log probability of their co-occurrence. Glove trains much less expensive OI than training a standard neural network and can recover domain knowledge. A material science model can answer an IFA is to ferromagnetic as IRMN is to, as the generic model answers Athens/Greece analogies. The same pre-training idea scales to pre-trained contextual representations and mass language models. Train a transformer on billions of words to predict missing words, then fine-tune on a labeled task, which the state-of-the-art NLP systems of the chapter employ. State-of-the-art. The final section surveys where deep NLP stands. Large pre-trained transformer language models have become the foundation of modern NLP systems, achieving state-of-the-art results on translation, question answering, summarization, and generation. These results span the full spectrum of Chapter 23's tasks. Machine translation with neural models performs close to the level of a human for closely related language pairs. Question answering on Squad exceeds human level F1. Summarization and dialogue generation produce fluent text at scale, and language model perplexity, the field's benchmark, has dropped by orders of magnitude, driven by the same self-supervised, pre-training objective scaled up. The chapter notes both the astonishing scale, models with hundreds of billions of parameters trained on hundreds of billions of words, and the honest, open questions, generalization gaps, the risks of training on the internet's unfiltered text, echoing Chapter 27's bias and safety concerns, and the energy and compute costs of pre-training, linking to Chapter 28's analysis of AI's trajectory. The state-of-the-art discussion closes Chapter 24's arc, from one-hot encoding through embeddings, RNNs, and seek-to-seek attention, to the transformer whose self-attention, positional embeddings, and pre-training define the modern paradigm. The same architecture, pre-trained on general text and fine-tuned per task, dominates NLP as of the book's writing. Word embeddings, dense learned vectors where similar words cluster and vector arithmetic solves analogies. Athens is to Greece as Oslo is to Norway. Pre-trained glove, word-to-vec, fast text, or task-trained, they are helpful for essentially all applications of deep learning to NLP. RNNs and seek-to-seek, recurrent encoders/decoders with attention and beam search decoding, the bridge from engrams to neural translation. Transformers, self-attention over query/key/value projections, multi-headed attention, residual layers, positional embeddings, the architecture that removes sequential dependency. Pre-training, train on general text, fine-tune on a task, the recipe behind modern NLP's state-of-the-art. Chapter 25. Computer Vision. Introduction. Vision is a perceptual channel that accepts a stimulus and reports some representation of the world. Most agents use passive sensing. They do not need to send out light to see. In contrast to active sensing, radar, ultrasound, used by bats, dolphins, abyssal fishes, and some robots. To understand a perceptual channel, one must study both the physical and statistical phenomena that occur in sensing. A feature is a number obtained by applying simple computations to an image. The Wumpus agent had 5 sensors, each of which extracted a single bit of information, and many flying animals compute a simple feature that gives a good estimate of time to contact, passed directly to muscles for fast reaction. The model-based approach uses 2 models: an object model, from precise geometric models to vague statements about general properties, and a rendering model, the physical, geometric, and statistical processes that produce the stimulus from the world. The stimulus is usually ambiguous. A white object under low light may look like a black object under intense light, and a small, nearby object may look the same as a large, distant object. We cannot tell if what we see is a toy Godzilla tearing up a toy building or a real monster destroying a real building. 2 ways to manage the ambiguity. Some interpretations are more likely than others. There are no real Godzillas, and some ambiguities are insignificant. The costs and benefits of vision are concrete too. Robots in the real world use a variety of sensors to perceive sound, touch, distance, temperature, global position, and acceleration, and vision is only one perceptual channel, but the richest. The chapter's treatment moves from the physical process of image formation, through the features that can be extracted, to the algorithmic systems that classify, detect, reconstruct, and understand the visual world, and it emphasizes throughout that modern methods deal with these problems by learning representations and classifiers from very large quantities of training data. The 2 core problems of computer vision are reconstruction, where an agent builds a model of the world from an image, and recognition, where an agent draws distinctions among the objects it encounters. Both are broad. Building a geometric model from images is obviously reconstruction, but building a map of the different textures on a surface is too. Attaching names to objects is clearly recognition. And so are answering, is it asleep? Does it eat me? Which end has teeth? The chapter's guiding triad is the feature-based approach, simple direct computations on pixels. The model-based approach, object models plus rendering models that predict what images look like. And the learning-based approach, learn representations and classifiers from very large quantities of training data using a convolutional neural network. And the current state-of-the-art runs all 3 together. Engineered features seed learn networks. Rendering models explain the ambiguities, and Learn classifiers dominate recognition. The last 30 years of research have produced powerful tools. Understanding these methods requires an understanding of the processes by which images are formed. Image formation. Imaging distorts the appearance of objects. Railway tracks converge and meet in a picture. You can block out the moon with a hand. A book tilted will seem to shrink and grow, foreshortening. Models of these effects are essential for building competent object recognition systems and also yield powerful cues for reconstructing geometry. The eye sensors are about 100 million rods and 5 million cones, 3 types, each sensitive to a different set of wavelengths. Cameras form images on an image plane of a few million pixels, each an individual tiny sensor, a CCD or CMOS, that report is a weighted average of the intensity of light arriving. The pinhole camera is the simplest way to form a focused image. A pinhole opening, at the front of a box, and an image plane at the back, with a small aperture ensuring each tiny sensor sees only photons that come from approximately the same spot. Moving object appear defocused as motion blur. The geometric model is perspective projection, with focal length f, point x, y, z, projects to x, y, equals fx/z, fy/z. The farther away an object is, the smaller its image, and the image is inverted both left, right, and down. Effects cascade. Distant objects look small. Parallel lines converge to a point on the horizon, the vanishing point shared by all parallel lines of a given direction. Lens systems fix the pinhole's darkness. Only a little light will get in, and the image will be dark, grainy by capture of all the light that hits anywhere on the lens and focusing all that light to a single point. Light from the tip of the candle spreads out in all directions, and a camera or an eye with a lens captures all the light that hits anywhere on the lens, a much larger area than a pinhole, and focuses all that light to a single point on the image plane. Lenses restrict, focusing light only from points within a range of z depths. The center of this range is the focal plane, and the range of depth for which focus remains sharp enough is the depth of field. The larger the lens aperture, the smaller the depth of field. To move the focal plane, the lens elements in a camera can move back and forth, and the lens in the eye can change shape, but with age the eye lens tends to harden, requiring eyeglasses. For nearly planar objects, scaled orthographic projection approximates the perspective scale by a constant. If the depth of all points on an object falls within a range around z0, then the perspective scaling factor f/z can be approximated by constant s equals f/z0, giving x equals sx, y equals sy, with foreshortening still occurring because of tilt. Windows on a building across the street look much smaller than ones right nearby, but two windows that are next to each other will have about the same size even though one is slightly farther away. Light and shading make brightness a strong, if ambiguous, cue to both shape and identity. Ambiguous because there are 3 factors: ambient light, whether the point is facing the light or is in shadow, and the amount of light reflected. People are surprisingly good at disambiguating a black object in bright light and a white object in shadow, but sometimes get shading and markings mixed, makeup under a cheekbone. Most surfaces reflect by diffuse reflection, scattering light evenly across the directions, independent of viewing direction. Specular reflection leaves in a lobe of directions determined by the direction the light arrived. A mirror's narrow lobe resolving objects, broader lobes producing specularities, small bright patches, easy to identify because they are small and bright. Often seen on metal surfaces, painted surfaces, plastic surfaces, and wet surfaces. The dominant model is a distant point light source, the most important model of lighting, and is quite effective for indoor scenes as well as outdoor scenes. Lambert's cosine law gives surface brightness I equals rho dot I sub rho, the cosine theta, with diffuse albedo rho in chapter 0, verse 05, 0.95. The amount of light collected by surface patch depends on the angle theta between the illumination direction and the normal to the surfaces, the same cosine law geometry that shapes both shading cues and the physics of the pinhole and lens models above. Simple image features. The first computational step extracts edges, locations in the image where the brightness changes abruptly or in a distinctive way. Most edge detection methods find the image gradient, a discrete convolution measuring local intensity change, and mark pixels where its magnitude is high, often after smoothing to suppress noise. CNN's first layer kernels, as the chapter later shows, learn precisely such local pattern detectors. Texture is the local pattern of small deviations from smooth surface appearance, an important cue for segmentation. Optical flow measures the apparent motion of brightness patterns in an image, a strong cue to both motion of objects and structure of the scene. A moving observer sees flow that encodes depth. Nearby objects sweep across the retina or sensor faster than distant ones. And segmentation divides natural images into coherent regions, using edges, texture, and color. Grouping of pixels into objects being the perceptual foundation on which recognition builds. These low-level features are the primitive vocabulary from which the chapter's learned hierarchies build. They are what a CNN's earliest layers rediscover and recombine, and they supply the classical cues: edges for boundaries, texture for material and orientation, optical flow for motion and depth, that the 3D reconstruction methods of Section 25.6 exploit. Classifying images. Image classification applies to images of objects taken from a given taxonomy, cashmere sweater, desk chair, and to see containing multiple objects, grassland, living room. Modern systems classify images using appearance, i.e., color and texture, as opposed to geometry. Different instances of the same class could look different, and the same cat could look different at different times because of lighting, foreshortening, aspect. A donut seen from the side looks like a flattened oval, but from above it is an annulus, occlusion, and self-occlusion, and deformation. Modern methods deal with these problems by learning representations and classifiers from very large quantities of training data using a convolutional neural network. With a sufficiently rich training set, the classifier will have seen any effect of importance many times in training. Image classification with CNNs. The ImageNet dataset played a historic role. Over 14 million training images classified into over 30,000 fine-grained categories, evaluated by top 5 accuracy: Malamute, Husky, Akita, Samoyed, Eskimo dog, 189 subcategories of dog, so even dog-loving humans find it hard. In the first ImageNet competition in 2010, systems could do no better than 70% top 5 accuracy. The introduction of convolutional neural networks in 2012 and their subsequent refinement led to an accuracy of 98% in top 5, surpassing human performance, and 87% in top 1 accuracy by 2019. The primary reason for this success seems to be that the features that are being used by CNN classifiers are learned from data, not handcrafted by a researcher. This ensures that the features are actually useful for classification. Progress in image classification has been rapid because of the availability of large, challenging data sets such as ImageNet, because of competitions based on these data sets that are fair and open, and because of the widespread dissemination of successful models. The winners of competitions publish the code and often the pre-trained parameters of their models, making it easy for others to fiddle with successful architectures. The chapter stresses the internal representations as CNN builds. Early layers detect edges and oriented bars, the NIST kernels in Figure 25.12. Middle layers assemble local parts, and later layers respond to whole object patterns. So the network is creating patterns at multiple levels, and is doing that by learning from the data rather than having the patterns given to it by a programmer. This learned hierarchy is the architectural unification of the chapters. The same convolutional geometry that Chapter 21's residual networks deepen, and that Chapter 25's detectors and reconstruction methods build on. Why CNNs classify well. The NIST data, 70,000 images of handwritten digits, shows that you can shift, rotate, make it brighter or darker, smaller or larger, without changing identity. So individual pixel values are not particularly informative, but local patterns can be quite informative. The digits 0, 6, 8, and 9 have loops. The digits 4 and 8 have crossings, and spatial relations between local patterns are informative. A 1 has 2 line endings above one another. These observations suggest a strategy that is a central tenet of modern computer vision. You construct features that respond to patterns in small, localized neighborhoods. Then other features look at patterns of those features. Then others look at patterns of those, and so on. This is what convolutional neural networks do well. Each convolution, followed by a ReLU, is a local pattern detector, with patterns of patterns emerging at deeper layers. A location in the second layer receives input from first layer values in a window about that location. So locations in the second layer are affected by a larger window of pixels than those in the first layer. And the network is creating patterns at multiple levels, and is doing that by learning from the data rather than having the patterns given to it by a programmer. The learned feature hierarchy that ImageNet's results vindicate. Data set augmentation, randomly shift, rotate, or stretch an image. Increases effective sample size, usable at test time 2, the output to the classifier from each copy. Vote for a final decision. And at test time, the image is replicated and modified several times, e.g., with random cropping, before the votes are pooled. Context can help or hurt a classifier. A cat lying on a dog bed. The pixels of the cat, not the bed, depend quite strongly on the particular data set and application. Detecting objects. Object detectors find multiple objects in an image, report what class each object is, and also report where each object is by giving a bounding box. A simple detector uses a small sliding window onto the larger image, a rectangle classifying what we see in the window with a CNN at each spot, keeping the high-scoring classifications and ignoring the other windows, then resolving conflicts to produce a set of objects with their locations. Details include choosing window shape. Axis-aligned rectangles are easiest. The alternative, some form of mask that cuts the object out of the image, is hardly ever used because it is hard to represent and to compute with. Window sizes, we still need to choose the width and height of the rectangles, and aspect ratios, and the trade-off between window density. Fewer windows equals faster but may miss objects. And accuracy. The set of classes is fixed in advance. We might try to detect all faces, all cars, or all cats. Modern detectors use region proposal networks and single-shot architectures that predict boxes and classes in one pass, exploiting the same learned feature pyramid idea, patterns at multiple levels, to detect objects at many scales from one network, with non-maximum suppression merging overlapping detections of the same object into one box. Object detection powers self-driving cars, pedestrians, vehicles, signs, medical imaging, tumors, lesions, and industrial inspection. The applications that demand the localization information classification alone cannot provide. The 3D world. Reconstructing 3D from images uses cues that are present in a single view and cues that come from multiple views. 3D cues from multiple views. Observing a scene from two cameras or a moving viewpoint yields binocular stereopsis, matching features across the two images and triangulating to recover depth, the basis of stereo vision and of the disparity computations in a pair of eyes or cameras. The key geometric fact is that the two views of the same point differ by an amount, the disparity, that shrinks with distance. As an object moves closer to the two cameras, the corresponding image points separate, so disparity inverts depth, and cameras with a wide baseline give more accurate depth estimates for distant objects at the cost of finding correspondences harder. 3D cues from a moving camera. Structure from motion recovers both camera motion and scene geometry from a video sequence, exploiting optical flow and the epipolar geometry relating successive frames. If the camera moves, nearby points move faster in the image than distant ones, which is why a moving observer's flow field carries depth. 3D cues from one view. Shading. Brightness gradients reveal surface shape. Texture gradients, foreshortening betray slant. Contours, occluding boundaries. In perspective, parallel lines converge. The vanishing point constrains orientation. Each provide partial depth information. Combining them is the ShapeFromX program. These reconstruction methods support navigation, Chapter 26, and are the classic counterparts to the recognition systems of the classification sections. Using computer vision. The range of applications is extraordinary. An enthusiast created a great object detection-based pet door that refuses entry to a cat if it is bringing in a dead mouse. Understanding what people are doing could build human-computer interfaces that watch people better, public places less intrusive security surveillance, automated sports commentators, safer construction sites, and games that make a player get up and move. The state-of-the-art for some problems is now extremely strong. Methods that can predict the locations of a person's joints in an image very accurately, and quite good estimates of the 3D configuration of that person's body, because pictures of the body tend to have weak perspective effects, and body segments don't vary much in length. Classifying what people are doing is harder. Structured behaviors, ballet, gymnastics, on simple backgrounds are tractable with labeled data and a CNN, but it can be difficult to prove that the methods actually work because they rely so strongly on context. A classifier that labels swimming sequences very well might just be a swimming pool detector. The chapter's illustrative pair shows the hard cases. Examples labeled opening fridge and take something out of fridge wherein both rows the subject hand is close to the fridge door, so telling the difference requires quite subtle judgment about where the hand is and where the door is, and the timescale figure where the same single frame is opening the fridge, a short clip, getting milk from the fridge, and a long clip, fixing a snack. Illustrat, ng. One way in which behavior composes. Getting milk from the fridge is sometimes part of fixing a snack, and opening the fridge is usually part of getting milk from the fridge. More general problems remain open. How to link observations of the body and the objects nearby to the goals and intentions of the moving people. Behavior depends quite strongly on the time scale. Open fridge, then get milk, then fix a snack. Behavior composes several recognized behaviors may be combined, and we don't have a common vocabulary for the pieces of behavior, making consistently labeled data sets hard. The chapter closes with the generalization caveat. Learned classifiers are guaranteed to behave well only if the training and test data come from the same distribution, which for image classifiers, we observe, work is very well, but for activity data, the relationship between training and test data is more untrustworthy. Linking pictures and words bridges vision and language. Image captioning systems generate fluent descriptions. A person riding a motorcycle on a dirt road, two pizzas sitting on top of a stovetop oven, a group of young people playing a game of frisbee. A demanding task, since a system must both identify the objects and understand the spatial relations among them to produce even these simple captions. Yet, a refrigerator filled with lots of food and drinks turns out to be a no. Parking sign partially obscured by lots of small stickers. The vivid limit of captioning that relies on context rather than content. Reconstruction from many views, photogrammetry, used in archaeology and mapping to build 3D models of sites from collections of photographs. And making pictures, view synthesis, in painting that fills in holes in photographs. Complete the tour. Controlling movement with vision. Using the reconstructed and recognized world to drive an arm or a vehicle hands the baton to Chapter 20XS Robotics, where the same perception and action loop meets actuators, uncertainty, and the physical world. Closing the book's journey from pixels to behavior. Reconstruction versus recognition. Build models of the world from images or draw distinctions among objects. Both start from how images are formed. Image formation, pinhole and lens cameras, perspective projection and vanishing points, depth of field, and Lambert's law relates scene geometry and lighting to pixels. Features and learning. Edges, texture, and optical flow give cues. CNNs with learned hierarchies of local patterns dominate classification. ImageNet 98% top 5, aided by augmentation. Object detectors add bounding boxes via sliding windows. 3D and application. Stereopsis, structure for motion, and shape from X recover depth. Activity understanding and captioning push the same machinery to behavior and language. Chapter 26. Robotics. Robots. Robots are physical agents that perform tasks by manipulating the physical world, equipped with effectors, legs, wheels, joints, and grippers that assert physical forces on the environment and sensors that enable them to perceive their environment. Cameras, radars, lasers, and microphones to measure the state of the environment and of the people around it, and gyroscopes, strain and torque sensors, and accelerometers to measure the robot's own state. Maximizing expected utility for a robot means choosing how to actuate its effectors to assert the right physical forces, the ones that will lead to changes in state that accumulate as much expected reward as possible. Robots operate in environments that are partially observable and stochastic. Cameras cannot see around corners, and gears can slip. Moreover, the people acting in that same environment are unpredictable, so the robot needs to make predictions about them. Robots usually model their environment with a continuous state space and a continuous action space, and some operate in high-dimensional spaces. Cars need to know the position, orientation, and velocity of themselves and the nearby agents. Robot arms have 6 or 7 joints, and robots that mimic the human body have hundreds of joints. Robotic learning is constrained because the real world stubbornly refuses to operate faster than real time. In simulation, a few hours from millions of trials, but in reality, it might take years to run these trials, and a robot cannot risk, and thus cannot learn from, a trial that might cause harm. Hence the sim-to-real problem and the need for prior knowledge about the robot, the physical environment, and the tasks so the robot can learn quickly and perform safely. The chapter's framing of the robot as an agent is deliberate. Robotics brings together many of the concepts we have seen in this book, including probabilistic state estimation, perception, planning, unsupervised learning, reinforcement learning, and game theory, and it breaks new ground by introducing the continuous version of techniques that we previously saw only in the discrete case. The three subsystems a robot must integrate are the task planner, discrete high-level actions, the motion planner, geometric paths, and the controller, actuator commands. Perception, mapping, and people prediction feed them, and preference learning supplies the objective, the full agent architecture of the book embodied in hardware. Robot hardware. The success of real robots depends at least as much on the design of sensors and effectors that are appropriate for the task. Types of robots range from manipulators, robot arms, bolted to tables or floors, from large payload car assembly arms to wheelchair-mountable arms that assist people with motor impairments, to mobile robots, wheels, legs or rotors, quadcopter drones, autonomous underwater vehicles, vacuum cleaner, the hotel, towel delivery, autonomous cars, and Mars rovers, to legged robots, meant to traverse rough terrain. The downside is that controlling legs is more challenging than spinning wheels plus prostheses, exoskeletons, robots with wings, swarms, and intelligent environments. Sensing the world. Passive sensors, cameras, capture signals that are generated by other sources, while active sensors, sonar, LiDAR, send energy into the environment and tend to provide more information, but at the expense of increased power consumption and with a danger of interference. Rangefinders measure distance. Sonar, the technology of choice for autonomous underwater vehicles. Stereo vision, parallax between cameras. The Kinect structured light. The camera sees how the grid lines bend. Time-of-flight cameras and scanning LiDARs, accurate to within a centimeter at a range of 100 meters, tend to perform better in bright daylight. Radar sees through fog, ranges to kilometers. Tactile sensors, whiskers, bump panels, and touch-sensitive skin. 4. Contact. For mobile ground robots, sonar and stereo vision are now rarely used because they are not reliably accurate. The Kinect and LiDAR have replaced them. Location sensors, GPS, triangulating 31 satellites to within a few meters. Differential GPS to millimeter accuracy under ideal conditions. Indoors wireless beacons, full of wireless base stations, which can help robots localize through the analysis of the wireless signal. Underwater sonar beacons. Proprioceptive sensors inform the robot of its own motion. Shaft decoders for joint angles and wheel odometry. Wheels tend to drift and slip, so odometry is accurate only over short distances. Inertial sensors, gyroscopes, that reduce uncertainty by relying on the resistance of mass to the change of velocity, and force/torque sensors. Imagine a 1-ton robotic manipulator screwing in a light bulb. It would be all too easy to apply too much force and break the bulb, so high quality. Sensors measure forces in all 3 translational and 3 rotational directions, at a frequency of several hundred times a second. Producing motion. The actuator initiates motion. Electric, most common for rotation, hydraulic, pressurized fluid, and pneumatic, compressed air. Joints connect links via revolute, rotating, and prismatic, sliding, single-axis joints, and multi-axis spherical, cylindrical, and planar joints. Grippers range from the parallel jaw, 2 fingers, and a single actuator, loved and hated for its simplicity, to 3-fingered grippers, to humanoid hands like the shadow dexterous hand. 20. Actuators, enabling in-hand manipulation, but this flexibility comes at a price. Learning to control these complex grippers is more challenging. The hardware survey closes with the architectural point. The success of real robots depends at least as much on the design of sensors and effectors that are appropriate for the task as on the algorithm, and depending on the application, the right sensor might be a camera, a LiDAR, a force sensor, or a combination, each choice trading cost, range, accuracy, and robustness, exactly as the rest of the chapter trades off planning depth against real-time constraint. What kind of problem is robotics solving? Robotics problems are non-deterministic, partially observable, and multi-agent, using the game theoretic notions from Chapter 18. Sometimes the agents are cooperative and sometimes competitive in a narrow corridor where only one agent can go first, a robot and a person collaborate, but in some cases they might compete a bit. When robots act in isolation and know their environment, the problem can be formulated as an MDP. When they're missing information, it becomes a POMDP, and when they act around people, it can often be formulated as a game. Usually the robot is acting in service of a human. The true reward function lies with the user whom the robot is supposed to help. The robot will either need to decipher the user's desires or rely on an engineer to specify an approximation. The raw sensor feeds and motor currents are a huge gap between the low-level percepts and motor controls and the high-level plans, so roboticists decouple aspects of the problem. They often separate perception from action, use a three-level hierarchy: task planning, high-level actions, action primitives, or sub-goals; motion planning, finding a path that gets the robot from one point to another; and control, achieve NG, the planned motion using the robot's actuators. Plus, separate preference learning, estimating an end user's objective, and people prediction. Whenever we split a problem into separate pieces, we reduce complexity, but we give up optimality, the chapter's honest framing of the perceptual cognitive architecture. The division mirrors the whole book's design. Task planning is the search and planning of chapters 3 to 11. Motion planning is continuous heuristic search. Control is the closed-loop feedback of classical and optimal control. Perception is the probabilistic inference of chapters 12 to 15. And preference learning is the utility reasoning of chapter 16. The robot, therefore, is the integration of the book's methods in a single, embodied, uncertain, time-critical system, and the decoupling is the standard engineering compromise between tractability and optimality. With enough computation, the POMDP would decide everything jointly. In practice, the hierarchy keeps each piece simple enough to run in real time. The reward function question deserves emphasis. Usually the robot is acting in service of a human, for example, delivering a meal to a hospital patient for the patient's reward, not its own. For most robotic settings, even though robot designers might try to specify a good enough proxy reward function, the true reward function lies with the user whom the robot is supposed to help. So the robot will either need to decipher the user's desires or rely on an engineer to specify an approximation. The design-level form of Chapter 16's unknown preferences and Chapter 27's value alignment, grounded in hardware rather than in the abstract. This is why the chapter's robotics arc ends where it does. Robots are the ultimate test of the agent framework, and learning what the human wants is the difference between a tool and a partner. Robotic perception. Localization is the problem of finding out where things are, including the robot itself. For a slow 2D mobile robot, the pose is defined by its two Cartesian coordinates and its heading, so a state is given by the triple XY heading. The motion model, the Gaussian density over the pose after a translational velocity and a rotational velocity over a time interval, follows a kinematic approximation. Two sensor models follow. The landmark model, detect range and bearing to a known feature, corrupted by Gaussian noise, and the rangescan model, a sensor array producing a vector of range values with independent noise per beam. The latter has the advantage that there is no need to identify a landmark. The robot faces a featureless wall, yet localizes, while identifiable landmarks may provide instant localization. Monte Carlo localization, the particle filter, maintains a set of samples of poses. Each cycle samples new poses from the motion model, weights them by the sensor likelihood, raycasting against the map, and risk samples, weighted sample with replacement, so the robot's belief concentrates where the evidence supports. The algorithm's inputs and structure mirror Chapter 13's likelihood weighting. If S is empty, the filter initializes samples from P, X0. Each update draws a new pose from the motion model. Then for each of the M beams, W, ZJ, ZJ, against the raycast range, and the resampling step replaces low-weight particles with copies of high-weight ones. So, the samples concentrate in regions of state space that are consistent with the sensor data. Exactly the particle filter intuition of Chapter 13 applied to a robot's own body. The Kalman filter representation of Chapter 14 handles the Gaussian localization case, while simultaneous localization and mapping, SLAM, must, in its most general form, recover the map and the robot's trajectory. Together, when no map is given a chicken and egg, localization needs the map, mapping needs the pose, solved by joint estimation over pose and map. And critical for unsupervised learning in robot perception, learning the model of the world from raw sensor streams. The key insight of SLAM is that the uncertainty about the map and the uncertainty about the pose are correlated, so the robot maintains a joint distribution over both, and when it returns to a previously visited place, loop closure, the map and the pose estimates snap into agreement, dramatically reducing error. The chapter statistical view ties localizer, mapper, and detector together. Perception is the inference of hidden state from sensor evidence. Exactly the machinery of chapters 12 to 15 applied to a moving body. Other types of perception extend beyond geometry. The chapter covers identifying objects and people. The robot must detect the objects it will manipulate and the people it will avoid or assist, using the vision machinery of Chapter 25, estimating the properties of objects, mass, friction, what a cup feels like, the force and tactile sensing that complements vision for grasping. And semantic mapping, a map that not only says where the walls are, but labels the door, the chair, and the do not enter area, tying robot perception back to the knowledge representation and reasoning of Chapters 8 to 11. Supervised learning in robot perception trains the vision, LiDAR, and tactile classifiers that annotate the robot's sensor streams, typically by collecting labeled data from the robot's own sensors or from hand-labeled logs. While unsupervised learning finds structure, clusters of objects, recurring terrain types, repeated walls, in unlabeled sensor streams. And self-supervised learning exploits the robot's own dynamics. If I push this object and it rolls, it is round. The chapters bridge from perception as inference to the learning chapters of Part 5. Planning and control. Motion planning is the problem of finding a plan that takes a robot from one configuration to another without colliding with an obstacle. The piano mover's problem. Given a workspace W, an obstacle region O, and a robot whose configuration space C, d-dimensional, d the robot's number of degrees of freedom, maps to sets of points A, Q, the obstacles induce a C-space obstacle and free space. The planner needs to find a continuous path through free space, parameterized by a curve tau t, from the start configuration QS equals tau 0 to the goal QG equals tau 1, where t parameterizes how far we are along the path. The problem can be made more complex in various ways, defining the goal as a set of possible configurations rather than a single configuration, defining a cost function, e.g., path length, to be minimized, satisfying constraints, e.g., if the path involves carrying a cup of coffee, making sure that the cup is always oriented upright so the coffee does not spill. The chapter distinguishes the spaces involved. The workspace or world W, points in the everyday, three-dimensional world. The space of configuration C, whose points are d-dimensional. And the space of paths, a space of functions, each point an entire curve through C space, which is infinite dimensional. Solution methods then follow. Visibility graphs connect every pair of vertices that can see each other with collision-free straight segments, so an optimal search on visibility graphs will always give us the optimal path, if one exists, or report failure, but they encourage paths that run immediately adjacent to an obstacle, risky under motion or sensing uncertainty. Voronoi diagrams take the opposite choice, putting paths as far away from obstacles as possible, the set of points equidistant to two or more obstacles in configuration space, trading path length for clearance. Occupancy grid and cell decomposition methods discretize free space into cells and run. The search algorithms from Chapter 3 and sampling-based planners, probabilistic roadmaps, RRTs, build a random graph of collision-free configurations, a quintessentially continuous state search problem made tractable by discretizing the space, with the added practical twist that a great deal of the difficulty is in generating the successor states themselves, where the continuous geometry must be queried for collision at each step. Planning and control join the hierarchy. Task planning decides a plan or policy for high-level actions. Motion planning is in charge of finding a path that gets the robot from one point to another. Control is used to achieve the planned motion using the robot's actuators. Trajectory tracking control drives the robot along the planned path despite disturbances, a feedback loop comparing the desired trajectory to the measured state and correcting. Optimal control chooses the trajectory that optimizes a cost, e.g., time or energy, given the dynamics and constraints, connecting to Chapter 17's MDP machinery in continuous form. The chapter notes that when we solve POMs properly, perception and action interact. Yet robots often separate perception from action as a complexity-reducing decoupling, consuming the outputs of perception and pretending they will not get any more information in the future, which is suboptimal but tractable. Planning uncertain movements extends motion planning under non-deterministic dynamics. The car may drift off the path if you take a curve too fast. To closed loop, reactive replanning, and conformal/robust plans that guarantee reaching the goal despite slips. Connecting back to Chapter 4's sensing-free and contingent planning, and to the belief state estimation of Chapter 14. Reinforcement learning in robotics. Reinforcement learning in robotics scales the Chapter 22 machinery to continuous state and action spaces. With a kinematic model, model-based RL can plan, value iteration on the continuous MDP. Model-free RL, Q-learning with function approximation, policy gradients. Learns directly from experience, and reward shaping supplies intermediate rewards to make sparse tasks learnable. One challenge of RL in robotics is the continuous nature of the state and action spaces, which we handle either through discretization or, more commonly, through function approximation. Policies or value functions are represented as combinations of known useful features or as deep neural networks, and neural nets can map from raw inputs directly to outputs, but they do require more data. A bigger challenge is that robots operate in the real world. We have to make sure that its actions are safe. Things break. And we have to accept that progress will be slower than in a simulation because the world refuses to move faster than 1 second per second. So, much of what is interesting about using reinforcement learning in robotics boils down to reducing the real-world sample complexity. The chapter stresses the exploiting models route. We might not know exactly what the coefficient of friction or the mass of an object is, but we might have equations that describe the dynamics, so model-based reinforcement learning can alternate between fitting the dynamic parameters and computing a better policy, learning an error term that can compensate for the inaccuracy of the physical model, or fitting locally linear models that each approximate the dynamics in a region of the state space, an approach that has been successful in getting robots to master complex dynamic tasks like juggling. Sim-to-real transfer uses the model as a simulator for a policy search, adding noise to the model during training, thereby making the policy more robust, or varying different parameters in the simulations, sometimes referred to as domain randomization. The Dexter's manipulation hand of figure 26.26, trained in simulation by varying visual attributes, as well as physical attributes like friction or damping. Hybrid model-based/model-free approaches originated with the Dyna architecture, which iterates between acting and improving the policy, both the standard model-free way and the model-based way of using the experience to fit a model, then plan with it. Recent techniques fit local models, plan with them to generate actions, and use these actions as supervision to fit a policy, which enabled the first demonstration of deep RL on physical robots. The chapter's most pointed safety argument, more important than reducing real-world samples, is reducing real-world samples in dangerous states. We don't want robots falling off cliffs, and we don't want them breaking our favorite mugs, or even worse, colliding with objects and people. An approximate model, with uncertainty associated to it, can guide exploration and impose constraints on the actions that the robot is allowed to take. Exploiting other information further cuts samples. Higher-level motion primitives of parameterized skill. Pass the ball to the player at X, Y. Let the policy combine them and set their parameters instead of reinventing them. And often learns much faster, but restricts the space of possible behaviors. Meta-learning or transfer learning reuses information from previous learning episodes on other tasks. And people are a great source of information. The bridge to human-robot interaction. Humans and robots. Human-robot interaction, HRI, makes people prediction and preference learning first class. The robot must track people's motion and goals, decide when to initiate interaction, and learn what the human wants, working under the assistance paradigm of Chapter 16's Unknown Preferences thread. Coordination is physical and social. Two robots, or a robot and a person moving in a shared space, must anticipate each other's motion, and legible robot motion, predictable communicative trajectories, makes joint action safer and clearer than purely optimal paths. In the corridor example, a robot that is too polite and always makes room might get stuck in crowded situations. Learning to do what humans want ties together inverse RL and preference elicitation. The robot observes the human, infers their objective, and acts to satisfy it, the first concrete instance of beneficial machines, and it motivates the human-centered evaluation that Chapter 27 develops. Trust and transparency, bonding, cooperation. People prediction is itself a learn model. The robot uses past trajectories and intent cues, gaze, posture, destination, to forecast where a person will be next, turning the multi-agent game formulation of Chapter 18 into a practical online predictor, and enabling the robot to initiate interaction at the socially appropriate moment, rather than interrupting. A microcosm of the social intelligence the final chapters will assess. The chapter stresses that HRI evaluation is not just task success. Trust, comfort, and legibility are real quantities to be measured, and a robot that completes its task but frightens or inconveniences people is a failure, a standard that Chapter 27's Ethics of AI takes up directly. The physical commonality of HRI also means the robot must be intrinsically safe. A manipulator that can carry a 1-ton load must sense contact and stop within milliseconds when it touches a person, which connects force/torque sensing, reactive control, and the safety engineering mindset that Chapter 27 formalizes. Alternative robotic frameworks. Alternative architectures challenge the symbolic planning paradigm. Reactive controllers map sensors directly to actions with no internal state, excelling in fast, uncertain tasks, bug algorithms that follow walls. Subsumption architectures Brooks layers simple behaviors. Avoid, wander approach, with higher layers suppressing lower ones, building intelligence without representation, and famously inspiring the behavior-based robotics era. The chapter weighs the trade-off. Reactive systems are fast, robust, and simple, but lack the far-sightedness of planning. Deliberative systems plan for goals, but are brittle in the real world. So modern robots hybridize, layering reactive control for safety, model predictive planning for competence, and symbolic planning for goals, the same hierarchical decoupling the chapter introduced. The honest note is that embodiment changes the problem. A physical robot's dynamics and uncertainty make even simple tasks hard, which is why the architecture must match the task. A reactive reflex layer guarantees obstacle avoidance at millisecond latency, while a deliberative planner selects goals and long-horizon behavior, and the two communicate through a small shared state. The layered design that makes today's autonomous vehicles and assistive robots stable enough to trust. The lesson generalizes. Architecture is not a philosophical choice, but an engineering one, driven by the time constants and uncertainties of the embodied task. Application domains. Robotics applications span industrial automation, the deepest and most mature, welding, painting, assembly, where the robot repeats the same motion reliably for years, logistics and warehousing, Amazon's Kiva-style robots moving shelves, autonomous driving, Waymo's 10 million miles without a serious accident, agriculture, construction, search and rescue, medicine, surgical robots with sub-millimeter precision, and elder care helpers. The chapter's closing emphasis is interaction with people. As robots leave the factory, they must perceive, predict, and serve humans, which is why robotics is the ultimate test of the agent framework. All of AI's ideas, perception, planning, learning, ethics, meet in a body acting in the physical world, setting up Chapter 27's human-centered concerns. Each domain stresses a different coupling of the machinery. Industrial robots need repeatable motion and force control. Logistics robots need localization, mapping, and coordination. A warehouse swarm of hundreds of robots must plan collision-free paths and avoid deadlock. Autonomous vehicles are the hardest perception and decision problem. LiDAR, cameras, radar, and a massive supervised NRL stack driving at highway speed among unpredictable people. Surgical robots combine kinematic precision with human-in-the-loop control. The surgeon supplies goals and judgment. The robot supplies steady hands. And elder care robots foreground assistance and preference. The reward lies with the user, whose desires the robot must infer. The chapter's unifying claim is that the robot is the integration of all of AI's ideas in a single body, and that the decoupling into perception, planning, control, and preference, though a compromise, is what makes real-time, safe behavior achievable today, exactly the engineering frame Chapter 27's ethics will evaluate. The application survey also carries an honest measure of the distance to general robotics. Each success is narrow. A robot that sorts packages or welds car doors cannot fold laundry or clear a table in an unfamiliar kitchen, because the real world, with its novel objects, unanticipated people, and continuous dynamics, remains the hardest possible test of generalization. A point Chapter 28 returns to when assessing the field's prospects for general intelligence. Robots, Physical agents with effectors and sensors in partially observable, stochastic, multi-agent, continuous, high-dimensional worlds. Real-time and safety constraints make sim-to-real key. Hardware. Manipulators, mobile, legged robots. Passive/active sensors, sonar, LiDAR, radar, GPS, proprioceptive, actuators, joints, and grippers. Perception. Motion and sensor models. Monte Carlo, particle, localization, SLAM, and map-based perception as inference. Planning and control. Task/motion/control hierarchy. Motion planning via visibility graphs, Voronoi diagrams, and cell decomposition. Control and optimal control. RL and robotics with shaping and sim-to-real. Humans, frameworks, domains. HRI with legible motion and preference learning. Reactive versus deliberative architectures and hybrids. Industrial, logistic, driving, medical, and elder care applications. Part 7. Conclusions. Chapter 27. Philosophy, Ethics, and Safety of AI. The Limits of AI. John Searle's 1980 distinction frames the debate. Weak AI. Machines could act as if they were intelligent, versus strong AI. Machines that do so are actually consciously thinking, not just simulating thinking, a term that over time shifted to refer to what is also called human-level AI or general, programs that can solve an arbitrarily wide variety of tasks, including novel ones, and do so as well as a human. Critics of weak AI who objected to the very possibility of intelligent behavior in machines now appear as short-sighted as Simon Newcomb, who in October 1903 wrote Aerial flight is one of the great class of problems with which man can never cope, just 2 months before the Wright brothers' flight. Yet the rapid progress of recent years does not prove that there can be no limits. And Alan Turing, 1950, the first person to define AI, was also the first to raise possible objections, foreseeing almost all the ones subsequently raised by others. Turing's argument from informality claims human behavior is far too complex to be captured by any formal set of rules. The social value of the question is the chapter's motivating frame. Understanding the limits of AI matters because only by knowing what machines can and cannot do can we assign appropriate roles to machines, to humans, and to the governance that mediates between them. The catalog of objections thus functions as a map of where to be honest. The informality argument rightly censures the overconfidence of 1980s logical systems. The disability argument is largely settled by performance. The mathematical objection misstates what Gödel proved, and the Turing test, for all its quirks, redirected the field toward measurable behavior. What none of them has established is a principled ceiling, a task that is in principle beyond computation, which is why the chapter's stance is that the limits of AI are limits of current methods, not provable boundaries of the possible, a distinction the concluding chapters keep firmly in view. Hubert Dreyfus was its key proponent. What computers can't do, 1972. What computers still can't do, 1992. Mind over Machine, 1986. Critiquing good old-fashioned AI, GoFi, the simplest logical agent design described in Chapter 7. We saw there that it is indeed difficult to capture every contingency of appropriate behavior in a set of necessary and sufficient logical rules. We call that the qualification problem. But probabilistic reasoning systems are more appropriate for open-ended domains, and deep learning systems do well on a variety of informal tasks. Thus, the critique is not addressed against computers per se, but rather against one particular style of programming them with logical rules. Dreyfus's strongest argument is for situated agents, an agent whose understanding of dog comes only from a limited set of logical senses, is at a disadvantage compared to an agent that has watched dogs run, has played fetch with them, and has been licked by one. As Andy Clark says, biological brains are first and foremost the control systems for biological bodies, and we are good at frisbee, bad at logic. The embodied cognition approach holds that the brain's functioning exploits regularities in its environment, including the rest of its body, making robotics, vision, and other sensors central, not peripheral. Overall, Dreyfus saw areas where AI did not have complete answers and said that AI is therefore impossible. We now see many of these same areas undergoing continued research, leading to increased capability, not impossibility. Turing's argument from disability lists what a machine can never do: be kind, resourceful, beautiful, friendly, have initiative, have a sense of humor, tell right from wrong, make mistakes, fall in love, enjoy strawberries and cream. learn from experience, use words properly, be the subject of its own thought, do something really new. In retrospect, some of these are rather easy. Computers make mistakes. Meta-reasoning lets them be the subject of their own reasoning. A century-old technology has the proven ability to make someone fall in love with it. The teddy bear and programs have made significant discoveries and created new forms of art. The one thing that is clear they can't do is be exactly human. The mathematical objection rests on Turing, 1936, and G. Odell, 1931. For any formal axiomatic framework F powerful enough to do arithmetic, it is possible to construct a so-called G. Odell sentence G, F, that is true, but cannot be proved within F. Lucas, 1961, and Penrose, 1989, 1994, claimed this shows machines are mentally inferior because they cannot establish the truth of their own G. Odell sentence. The chapter rebuts Lucas with 3 problems. First, an agent should not be ashamed that it cannot establish the truth of some sentence while other agents can. The sentence Lucas cannot consistently assert that this sentence is true shows a true sentence Lucas cannot assert, but that does not make us think any less of Lucas. Second, G. Odell's incompleteness theorem and related results apply to mathematics, not to computers, and no entity, human or machine, can prove things that are impossible to prove. While humans are notoriously inconsistent, the 4-color map proof accepted for 11 years had a flaw. Third, G. Odell's theorem technically applies only to formal systems, powerful enough to do arithmetic, whereas computers and brains are finite, describable as a very large system in propositional logic, which is not subject to G. Odell's theorem. And humans can change their minds just as a computer can retract a conclusion, upgrade its hardware, and change its decision-making processes. Measuring AI returns to the Turing test, asking whether machines can think replaced by whether machines can pass a behavioral test. The program passes the test if it fools the interrogator 30% of the time, and to Turing, the key point, the idea of measuring intelligence by performance on some kind of open-ended behavioral task, rather than by philosophical speculation. Turing conjectured a computer could pass by the year 2000. But we still can't agree whether any program has passed. Eliza and chatbots fool their correspondents repeatedly. In 2014, a chatbot called Eugene Gusman fooled 33% of the untrained amateur judges by claim, ing, to be a boy from Ukraine with limited command of English. Perhaps the Turing test is really a test of human gullibility. So far, no well-trained judge has been fooled. AI researchers prefer playing chess or Go or StarCraft 2, or taking an 8th grade science exam, or identifying objects where programs have reached or surpassed human-level performance, without being human-like outside the specific task. The point is to improve basic science and technology, not to fool judges. Can machines really think? Can machines really think? Some philosophers claim a machine that acts intelligently would not be actually thinking, but would be only a simulation of thinking. But most AI researchers are not concerned with the distinction, and Dijkstra's quip, whether machines can think, is about as relevant as whether submarines can swim, captures the field stance. The Chinese room, Searle, 1980, is the philosopher's sharpest challenge. A person who understands no Chinese, locked in a room with a rulebook, can produce appropriate Chinese responses to Chinese input, so the room, or the person, behaves as if it understands Chinese without understanding it. And the argument runs, so could a computer, with syntax but no semantics? The chapters reply, the person inside the room does not understand Chinese, but the system, room, person, rulebook, does. And what is it about the human brain that constitutes understanding rather than mere rule following? If the whole assembly of room and person constitutes a mind, then so could the whole assembly of computer and program. The Chinese room has inspired enormous debate, but it is more a challenge to our intuitions about mind than a proof that AI is impossible. Consciousness in qualia is the issue of consciousness, awareness of the outside world and of the self, and the subjective experience of living, with the technical term for the intrinsic nature of experiences being qualia. The big question is whether machines can have qualia. Does HAL actually have feelings and deserve sympathy? Or is the reply just an algorithmic response, no different from error 404? Not found. The chapter notes the problem remains ill-defined. even after centuries of debate, though philosophers have teamed with neuroscientists to start a series of experiments that could resolve some of the issues. With global workspace theory and integrated information theory agreed in G that the experiments could confirm one theory over the other, a rarity in philosophy. The book's verdict follows Turing. I do not think these mysteries necessarily need to be solved before we can answer the question with which we are concerned, and individual aspects of consciousness, awareness, self-awareness, attention, can be programmed and can be part of an intelligent machine. The additional project of making a machine conscious in exactly the way humans are is not one that we are equipped to take on, though tasks involving interaction with humans will require a model of human subjective experience. Humans have a clear advantage in modeling experience. You can hit your thumb with a hammer, while machines can run each other's code. The chapter's closing position is pragmatic. We are interested in creating programs that behave intelligently, and the moral status of machines, whether they have qualia and deserve sympathy, is a live question that its ethics section then treats with care, since as machines become more capable, the question of robot rights becomes more urgent. The ethics of AI. Given that AI is a powerful technology, we have a moral obligation to use it well, to promote the positive aspects and avoid or mitigate the negative ones. The positives are many. AI can save lives through improved medical diagnosis, new medical discoveries, better prediction of extreme weather events, and safer driving. Programs such as Microsoft's AI for humanitarian action, Google's AI for social good, and the University of Chicago Center for Data Science for social good apply AI to rainforest protection, human rights jurisprudence, pollution monitoring, crisis counseling, suicide prevention, crop management, and food production help feed the world, and automation can replace the tedious and dangerous tasks. The negatives are equally real. Nuclear fission brought Chernobyl. The internal combustion engine brought air pollution, and other technologies can have negative effects even when used as intended, and automation will create wealth. But under current economic conditions, much of that wealth will flow to the owners of the automated systems, leading to increased income inequality. The principles of robotics and later principle sets converge on a shared list. Ensure safety, ensure fairness, respect privacy, promote collaboration, provide transparency, limit harmful uses of AI, contemplate implications for employment, establish accountability, uphold human rights and values, respect diversity/inclusion, avoid concentration of power, acknowledge legal/policy implications, commonly cited, especially healthily vague and difficult to measure or enforce. With each subfield urged to develop more specific actionable guidelines and case precedents. Lethal autonomous weapons. One that locates, selects, and engages, i.e. kills, human targets without human supervision, have been called the third revolution in warfare after gunpowder and nuclear weapons. Examples range from landmines, banned under the Ottawa Treaty, to radar-controlled naval guns could also attack manned aircraft, to Israel's Harop loitering munition, searching up to 6 hours for any target that meets a given criterion and then destroys it, and Turkey's cargo quadcopter, autonomous hit, tracking moving targets, anti-personnel, face recognition. The concern is scalability. The absence of a requirement for human supervision means that a small group can deploy an arbitrarily large number of weapons. And since 2014, the United Nations has conducted regular discussions on the question of whether to ban them, with 30 nations supporting a treaty. Surveillance, security, and privacy. Weizenbaum's 1976 warning has been realized, with most electronic communication going through central servers and cities packed with microphones and cameras, with surveillance that used to require expensive human resources now done at a mass scale by machines. As of 2018, there were as many as 350 million surveillance cameras in China and 70 million in the United States. And AI engineers should be clear on what uses of surveillance are compatible with human rights, and decline to work on applications that are incompatible. Cybersecurity is double-edged. Attackers can use automation to probe for insecurities, apply reinforcement learning for phishing. Defenders can use unsupervised learning to detect anomalous traffic. The GDPR mandates consent and data protection. De-identification is eliminating personally identifying information, but the shared de-identified data may be subject to re-identification. If the data strips out the name, social security number, and street address, but includes date of birth, gender, and zip code, LaTanya Sweeney showed 87% of the U.S. population can be uniquely re-identified, and the Netflix Prize records were re-identified by matching the date of a rating. Mitigations, anonymity, every record, indistinguishable from at least K-1 other records. Aggregate querying with noise and thresholds, vulnerable to multiple queries that rederive individuals. Differential privacy, whether any one person decides to participate, makes no appreciable difference to the answers. Guaranteed by randomized noise with a bounded log probability ratio, and federated learning with secure aggregation, where users maintain their own local databases and share parameters of a machine learning model, without the risk of revealing any of the private data. Fairness and bias. Machine learning models can perpetuate societal bias. An algorithm to predict whether criminal defendants are likely to re-offend could, well, pick up the racial or gender prejudices of human judges. Designers have a moral responsibility to make their systems fair, but what is fairness? Individual fairness. Individuals are treated similarly to other similar individuals. Group fairness. Two classes are treated similarly, as measured by some summary statistic. Fairness through unawareness, deleting race and gender, but models can predict latent variables. Given other correlated variables such as zip code, equal outcome, demographic parity, each demographic class gets the same results. And further notions that cannot all be satisfied simultaneously. The choice among them is a values judgment, and society as a whole must decide. Trust and transparency. People should understand how and why a system made a decision. The accountability principle translates into interpretability and explainability requirements, especially where decisions affect lives, credit, parole, medicine. Yet there's often a trade-off between accuracy and transparency, since the most accurate deep models are the hardest to explain. So, the right amount of transparency depends on the stakes and the audience. The future of work. Automation will create wealth, but under current economic conditions, much of that wealth will flow to the owners of the automated systems. And the traditional path to growth through low-cost manufacturing for export may be cut off, as wealthy countries adopt fully automated manufacturing facilities onshore. Our ethical and governance decisions will dictate the level of inequality that AI will engender. And the chapter reviews the education, retraining, and income distribution policy levers. Robot rights. People are quick to ascribe intentions and feelings to robots. And if machines ever do become conscious, or even if people widely believe they are, then the question of their rights, to be free, to not be harmed, to not be deceived, becomes real. The chapter is careful that this is currently more a question about people's psychology than about machines, but it will not stay that way if AI's capabilities keep advancing. AI safety. The more capable the AI system, the more severe the consequences of getting its objective wrong. The standard model assumes the machine maximizes a fully specified objective, but if we cannot supply that objective correctly, the machine may pursue our objectives only imperfectly or actively against them. And the chapter restates the two conditions for provably beneficial AI. The machine is uncertain about the true objective, and it acts so as to maximize the probability of doing what we actually want, asking permission when uncertain, learning our preferences over time, and never being willing to pursue its own objective at the expense of ours. Safety thus inherits everything the book has built. A safety problem at its core is a decision problem under uncertainty about the objective. Exactly the settings of chapters 16, 17, 18, and 22 applied at the largest scale. This is the technical content of value alignment, and it connects the entire book, decision theory, learning, game theory, robotics, to the design of systems that are safe by construction. The theme chapter 28 carries into the future. Weak versus strong AI. Behavioral competence versus genuine consciousness. The definitions have shifted from Searle's original pair to human level/general AI. Objections answered. Informality, probabilistic, and deep methods escape Gophi's qualification problem. Disability. Most of Turing's humorous list is already met. Mathematical. G. Odell applies to formal systems, not to finite machines. And the Turing test itself, measuring performance and noting human gullibility. Mind. The Chinese room challenges semantics. Consciousness and qualia remain ill-defined, with welfare or information-based theories now testable. Ethics, principles, safety, fairness, privacy, transparency, lethal weapons, surveillance and differential privacy, fairness criteria, employment, robot rights, and AI safety, with value alignment and deference as the central problems. Chapter 28. The Future of AI. AI Components. Chapter 28 tries to see a short distance ahead, examining the components of AI systems and the extent to which each of them might accelerate or hinder future progress. Sensors and actuators. For much of the history of AI, direct access to the world has been glaringly absent, with humans supplying inputs and interpreting outputs. The situation has changed rapidly. The cost of LiDAR for a self-driving car has fallen from $75,000 to $1,000, and a single-chip version may reach $10 per unit. Radar is sensitive enough to count the number of sheets in a stack of paper. Cell phone camera demand gave us inexpensive high-resolution cameras, and MEMS technology has supplied miniaturized accelerometers, gyroscopes, and actuators small enough to fit in artificial flying insects. AI systems are at the cusp of moving from primarily software-only systems to useful embedded robotic systems. The state of robotics today is roughly comparable to the state of personal computers in the early 1980s, and flexible, intelligent robots will first make strides in industry before the home market. Representing the state of the world. Keeping track of the world requires perception as well as updating of internal representations. Current filtering and perception algorithms can be combined to do a reasonable job of recognizing objects, that's a cat, and reporting low-level predicates. The cup is on the table, but recognizing higher-level actions, such as DR. Russell is having a cup of tea with Dr. Norvig while discussing plans for next week is more difficult and progress. Will require techniques that generalize to novel situations without requiring exhaustive examples. Approximate filters are still dealing with a factored representation and do not represent objects and relations explicitly. And their notion of time is restricted to step-by-step change. Given the recent trajectory of a ball, we can predict where it will be at time t+1, but it is difficult to represent the abstract idea that what goes up must come down. We don't yet have a good way of putting all these techniques together, and it remains a daunting task to define general, reusable representation schemes for complex domains. Selecting actions. The primary difficulty in action selection in the real world is coping with long-term plans that consist of billions of primitive steps. Search algorithms that consider sequences of primitive actions scale only to tens or perhaps hundreds of steps. It is only by imposing hierarchical structure on behavior that we humans cope at all. The hierarchical planning and hierarchical RL of the earlier chapters, but these methods have not yet been extended to the partially observable case, and the main missing element is an effective method for constructing the hierarchical representations of state and behavior that are necessary for decision-making over long time scales. Deciding what we want. In principle, utility maximization agents address those issues in a completely general way. Just declare what you want to optimize and what each action does, and we can compute the optimal action. In practice, however, we now realize that the task of picking the right utility function is a challenging problem in its own right. The complex web of interacting preferences of an office assistant, the preference uncertainty of an agent just out of the box, and the demand for fairness for society, rather than just one individual. We do not yet have much experience with building complex real-world preference models, and this suggests that we take seriously the task of knowledge engineering for reward functions, including inverse reinforcement learning and better languages for expressing what we want in robotics. Linear temporal logic makes it easier to say what things we want to happen in the near future. The chapter voices a sharp critique of the industry's preference ecosystem. The recommendation loop is very effective in the short run for picking out ever more addictive games and videos, but to the extent that the menu of choices is driven by companies trying to profit from a customer's attention, the menu will remain incomplete, and it invokes Herbert Simons. A wealth of information creates a poverty of attention, suggesting personal agents that stick up for our true long-term interests and mediate the offerings of various vendors, protect us from addictive attention grabbers, and guide us towards the goals that really matter to us. Learning. Current algorithms can cope with quite large problems, reaching or exceeding human capabilities in many tasks. As long as we have sufficient training examples and we are dealing with a predefined vocabulary of features and concepts. But learning can stall when data are sparse or unsupervised, or when we're dealing with complex representations. Deep learning's rise can be seen as the incremental maturation of neural networks or revolutionary leap. spurred by a confluence of factors: the availability of more training data, increased processing power, and a few algorithmic tricks, GNs, batch normalization, dropout, ReLU. The future should see continued emphasis on improving deep learning for the tasks it excels at, and also extending it to cover other tasks. The chapter's prognostication is deliberately measured. The success of deep learning does not guarantee that it will remain the dominant approach, and the field story has been one of repeated transitions between symbolic and connectionist methods. So the smart bet is on synthesis, not on the permanence of any single brand name. Yet the vast majority of machine learning research today assumes a factored representation, and machine learning has been less successful for problems that have only a small amount of data or require the construction of new structured, hierarchical representations. The gap that transfer learning, probabilistic programming, and neurosymbolic combinations aim to close. AI architectures. Which of the agent architectures in Chapter 2 should an agent use? The answer is all of them. Reflex responses are needed for situations in which time is of the essence, whereas knowledge-based deliberation allows the agent to plan ahead. Learning is convenient when we have lots of data and necessary when the environment is changing. The long-running split between symbolic systems, based on logical and probabilistic inference, and connectionist systems, based on loss minimization over a large number of uninterpreted parameters, is a continuing challenge. To bring these two together, symbolic systems allow us to string together long chains of reasoning, while connectionist systems can recognize patterns even in the face of noisy data. And one line of research aims to combine probabilistic programming with deep learning, although the various proposals are limited in the extent to which the approaches are truly merged. Real-time AI and meta-reasoning. Agents also need ways to control their own deliberations. A taxi that sees an accident ahead must decide in a split second whether to brake or swerve, and should also spend that split second thinking about the most important questions. And as AI systems move into more complex domains, all problems will become real-time. Two general techniques follow. Anytime algorithms produce output that improves gradually over time, so that it has a reasonable decision ready whenever it is interrupted. Iterative deepening, MCMC. Decision-theoretic meta-reasoning applies the theory of information value, Chapter 16, to the selection of individual computations, where the value of a computation depends on both its cost and its benefits, and it can be used to design better search algorithms. Monte Carlo tree search's leaf selection is made by an approximately rational meta-level decision derived from bandit theory. Meta-level reinforcement learning acquires deliberation policies the way computations that lead to better decisions are reinforced. Meta-reasoning is one specific example of a reflective architecture, an architecture that enables deliberation about the computational entities and actions occurring within the architecture itself, whose theoretical foundation is a joint state space composed from the environment state and the computational state of the agent itself. Eventually, we expect task-specific algorithms, such as alpha-beta search, regression planning, and variable elimination to disappear from AI systems, to be replaced by general methods that direct the agent's computations toward the efficient generation of high-quality decisions. The computational limit argument tempers every ambition. Ever since computers were invented, their blinding speed has led people to underestimate what complexity really means. The speed of the ultimate 1 kilogram computing device is about 10 to the 51st operations per second, yet enumerating strings of English words, much as Bohr has proposed in the Library of Babel, is impossible. A computer running for a year could enumerate only the 11-word strings, and a detailed plan for human life consists of 20 trillion potential muscle actuations. So, a computer that is a billion trillion times more powerful than the human brain is much further from being rational than a slug, is from overtaking the Starship Enterprise traveling at warp 9. The book's closing proposal therefore replaces perfect rationality with bounded optimality. Rather than aiming for something that cannot possibly exist, we should consider a different normative target, one that necessarily exists, given the agent architecture, and allow the agent program to vary over all possible programs. In any given task environment, one of these programs delivers the best possible performance, and we say that this program satisfies the criterion of bounded optimality. The final note is characteristic. Clearly it exists, and clearly it constitutes a desirable goal. The trick is finding it through the union of a whole book's methods, a difficult but well-defined research program. And it returns to the opening theme of Chapter 1. We are pursuing not just intelligence, but beneficial intelligence, machines that know what we want, that are uncertain about our objectives, and that defer to us accordingly, asking what we would prefer rather than optimistically assuming they know, the modern successor to the standard model and the book's last word. Components: cheap versatile sensors/actuators move AI from software to robots. State representation, action selection, hierarchical. Preference, utility/preference uncertainty, and learning each have a next step gap, with the industry's attention farming preference ecosystem drawing explicit criticism. Architectures: all Chapter 2 architectures have a role. Metacognition, anytime algorithms, decision-theoretic meta-reasoning, reflective architectures, controls deliberation, and the computational limit argument forces bounded optimality as the target, a normative goal that necessarily exists. Outlook: beneficial, preference uncertain, deferential AI as the successor to the standard model. The book's final thesis. Conclusion: artificial intelligence, a modern approach, concludes where it began, with a rational agent, longer viewed through a lens of certainty, but as a system that perceives, reasons, learns, and acts in a world it only partially knows, and that now must also be uncertain about the objectives it is meant to serve. Over 28 chapters, the book has moved from the four-way definition of AI, Chapter 1, through the agent's building blocks: search, logic, planning, probability, decision theory, learning, deep learning, reinforcement learning, language, vision, robotics, to the philosophy, ethics, and future of the field. The arc is cumulative in a way few textbooks manage. The belief state of Chapter 4's sensorless planning becomes the probabilistic belief of Chapter 12. The Bellman equation of Chapter 17 becomes the temporal difference update of Chapter 22. The constraint of Chapter 6 becomes the computation graph of Chapter 21. And the utility function of Chapter 16 returns as the item to be learned, uncertain, and deferred to in Chapter 27. Each chapter's methods depend on those before it, and the book's design, like its protagonists, is hierarchical and compositional. The book's deepest methodological commitments are three. First, uncertainty is the central engineering fact. Logic gives decisive answers only in a small world. Everywhere else, degrees of belief, belief states, and expected utility are the honest currency, and the book trains the reader to move between them fluently. Second, learning is the route to competence at scale. The transition from hand-coded knowledge, Part 3, to machine learning, Part 5, is the book's most consequential narrative, culminating in deep networks and reinforcement learning that exceed human performance on defined tasks. Third, rationality is bounded and values are uncertain. Perfect rationality is computationally impossible, the library of Babel argument of Chapter 28, and the standard model's assumption of a fixed, known objective is probably not the right model in the long run. So the book's final framework is approaching a beneficial machine that is uncertain about the human's objective, acts to maximize the chance of doing what is actually wanted, asks permission, learns preferences, and defers. This is the value alignment successor to the standard model, and it reframes the whole volume. The entire technical apparatus is in service of building machines we can trust. The ethical chapters read as the culmination rather than an appendix. Lethal autonomous weapons, mass surveillance, algorithmic bias, and the attention economy are consequences, sometimes perverse ones, of the very rationality the book teaches, and their remedies: differential privacy, fairness criteria, value alignment, bounded optimality, governance, are technical as much as political. The book's final stance is neither triumphalist nor alarmist. It measures what has been achieved, a golden age of learning. Champion-level gameplay, language, vision, and robotics, a human-level competence on narrow tasks. What remains open: generalization beyond data, hierarchical action at scale, true preference modeling, consciousness, and what is provably impossible: perfect rationality. The honest refrain: we can see only a short distance ahead, but we can see that much remains to be done, is the voice of two working scientists rather than prophets, and it is the reason the book remains the field's canonical introduction. It does not merely report the discipline, it teaches the stance that created it. For the reader, the reward of the deep reading is a genuine integration. The planner's backward search and the CSP's constraint propagation meet in modern SAT solvers. The Bayesian network's conditional independence and the neural network's feature hierarchy both compute under uncertainty. The game theorist's mixed strategies power the bandit's exploration. The robot's sim-to-real transfer is the textbook's whole arc in miniature. The recommended path stands: read the foundational chapters for the framework, the probability and learning chapter for the modern core, and the closing chapters for the meaning of it all. And this examination, in the author's own register, has aimed to preserve both the technical discipline and the intellectual honesty that make the original worth reading again. Key persons discussed: Stuart Russell and Peter Norvig, the authors, the latter also the co-creator of the ubiquitous AAMA code repository. The pedagogical register, problem first, definition-driven, candid about open questions, defines the modern teaching of AI. Alan Turing, the first person to define AI, author of Computing Machinery and Intelligence, 1950, and the Turing Test, foresaw the objections to AI, the value alignment problem, in a 1951 lecture, Machine Learning and Early Chess Programs, The Church, Turing Thesis, and the Halting Problem Anchor Chapter 1 and Chapter 27. John McCarthy, co-founder of Dartmouth, 1956, creator of Lisp, 1958, and The Advice Taker, the logicist vision of knowledge representation and reasoning. Marvin Minsky, Snarks builder, perceptron critic, founder of the MIT Microworlds program, and early neural network pioneer. Herbert Simon and Alan Newell, GPS and the logic theorist, the physical symbol system hypothesis, Simon's satisficing and Nobel Prize, Artificial Intelligence's founding research program. Judea Pearl, Bayesian networks and probabilistic reasoning in intelligent systems, 1988, the formalization of uncertain reasoning that anchored Part 4. John von Neumann and Oscar Morgenstern, the theory of games and economic behavior, 1944, game theory and its maximum/mixed strategy solution concepts. Richard Bellman, dynamic programming and Markov decision processes, the Bellman equation underlying chapters 17 and 22. Nils Nielsen, shaky arrow planning, the reminder that subfields should not become ends in themselves. Jeffrey Hinton, Jan LeCun, Yoshua Benjo, the deep learning triumvirate, honored by the 2019 Turing Award. Their work drove the ImageNet and backpropagation revolutions of Chapter 21. Andrew Ng, Demis Hassabis, David Silver, scaling learning to industry. Ng, and AlphaGo/AlphaZero, Hassabis, Silver, the game-playing demonstrations that reshaped public perception. Terry Winograd, SCHAR-DLU and the Blocks World, the limits of micro-world reasoning. Frank Rosenblatt, Ted Hoff, Paul Werbos, Perceptron, Adeline/Delta Rule, and backpropagation, the neural learning lineage of Chapter 21. Hubert Dreyfus and John Searle, the strongest philosophical critics of AI, whose arguments, informality, the Chinese room, the book engages seriously. Key works discussed. Turing, Computing Machinery and Intelligence, 1950, defines the Turing test, anticipates objections, proposes learning machines, the founding document of the field and the reference for Chapter 27. McCulloch and Pitts, A Logical Calculus of the Ideas Immanent in Nervous Activity, 1943, the neuron model that started artificial neural networks. Newell, Shaw, and Simon, Logic Theorist/General Problem Solver, 1956-61, the first AI programs. GPS embodied Thinking Humanly. Dartmouth Workshop Proposal, McCarthy et al., 1955, coins the term artificial intelligence and its foundational conjecture. Samuel, Checker Playing Program, 1952-59, early reinforcement learning, learns to beat its creator. Gale and Shapley, College Admissions and the Stability of Marriage, 1962, referenced in the stable matching traditions. Shapley also of the Shapley Value, Cooperative Games. Bellman, Dynamic Programming, 1957, MVPs and the Bellman Equation. Von Neumann and Morgenstern, The Theory of Games and Economic Behavior, 1944, Game Theory's Foundation. Nielsen, Problem-Solving Methods in Artificial Intelligence, 1971, Genesereth and Nielsen, 1987, Early Search and Agent Textbooks. Karp, 1972. Cook, 1971, NP Completeness and the Cook-Levin Theorem, the tractability map of Chapter 7's satisfiability discussion. Pearl, Probabilistic Reasoning in Intelligent Systems, 1988, Bayesian Networks, the camel of the full joint distribution tamed. Rumelhart and McClelland, Parallel Distributed Processing, 1986 Backpropagation Resurgence, Connectionism. Quinlan, Decision Tree Learning, the ID3 Style Greedy Information Gain Algorithm of Chapter 19. Vaswani et al. Attention is All You Need, 2018, The Transformer. The Architecture of Modern NLP, Chapter 24. LeCun, Hinton, Benjo, 2019 Turing Award Deep Learning as a Critical Part of Modern Computing. Silver et al. AlphaGo/AlphaZero, 2016-18 Self-Play Learning that Exceeded Human Gameplay, citing Chapters 5 and 22. Freund and Schapire, Ada Boost, 1996 Boosting's Weak Learner Amplification. Bryman, Random Forests, Variance Reduction through Randomized Trees. Kuhn, Hungarian Algorithm, 1955, and Gittins, Bandits Matching and Exploration Fundamentals. Dreyfus, What Computers Can't Do, 1972, and Searle, Minds, Brains, and Programs, 1980, The Philosophical Challenges of Chapter 27. Mittelstadt et al., and The Principal Sets, 2019 AI Ethics Frameworks and Their Limits. Index of Key Concepts. Rational Agent, a system that perceives its environment through sensors and acts through actuators so as to act rationally, maximizing the best expected outcome, CH2. The book's sharpest argument for the agent as the unit of analysis is the table-driven fallacy. A lookup table indexed by percept sequences would need over 10 to the 600 billionth entries for an hour's driving, against fewer than 10 to the 80th atoms in the universe. So the key challenge is to find smallish programs that produce rational behavior from a smallish program rather than from a vast table. The question the whole book answers. Refined across 27 chapters, the concept ends in CH27 as the value-aligned, preference-uncertain agent that replaces the standard model's fixed objective with deference and bounded optimality. Standard model, the pervasive assumption that a machine maximizes a fully specified objective. The book breaks with it in CH1 and again in CH27. For real-world systems, it does not. A self-driving car, given the single goal of safety, will refuse to leave a garage because every road journey incurs risk, yet one pursuing only progress will drive recklessly. The residual danger is the value alignment problem, aligning our true preferences and the objective we put into the machine, and its solution, provably beneficial AI, requires the machine to be uncertain about the true objective, to ask permission when uncertain, and to learn our preferences over time, never pursuing its own objective at the expense of ours, CH27. Belief state, the set, or probability distribution, of physical states an agent considers possible given its percept history. The bridge that turns partial observability into full observability, because the agent always knows its own belief state, CH4. The same idea recurs 3 times at increasing power. Sensorless planning searches sets of states. HMM filtering maintains a distribution over time, CH14, and the POMDP makes the optimal policy a mapping pi of B from belief states to actions, evaluated partly by the information the agent acquires as a result, CH17, where the real world is one. Search in best first. By employing different FN functions, we get different specific algorithms. The unifying template of CH3 to 4, with a frontier is a priority Q keyed on the evaluation F, N equals G, N plus H, and iterative deepening combines the FS's memory with BFS's optimality and is the preferred uninformed search method when the search state space is larger than can fit in memory and the depth of the solution is not known. A star with an admissible, consistent heuristic is complete, cost-optimal, and optimally efficient, and its contours stretch toward a goal state, narrowing around an optimal path. CH3. Heuristics and the effective branching factor, measured by B star. The branching factor, a uniform tree of depth D, would need to contain the same number of nodes as A star generated. A good heuristic brings B star close to 1. Domination explains why the larger heuristic wins. It is generally better to use a heuristic function with higher values, provided it is consistent and that the computation time is not too long. Korf and Reed show H reduces the effective depth by a constant, giving big O of B to the dk H, the quantitative case that better heuristics are worth their compute, CH3. Local search and optimization. Search over states rather than paths, moving from one state to a neighboring state without retaining a reached list, little memory, and the ability to find reasonable solutions in large or infinite state spaces. Hill climbing is greedy and cannot look ahead, trying to find the top of Mount Everest in a thick fog while suffering from amnesia, and fails on local maxima, ridges, and plateaus. From random 8 queens, starts it solves only 14% of instances, but allowing up to 100 sideways moves raises that to 94%. Random restart search is complete with probability 1. Simulated annealing accepts worsens moves with declining temperature, escaping local optima, CH4. Evolutionary algorithms, variants of stochastic beam search, motivated by the metaphor of natural selection. A population of individuals, offspring from the fittest parents via crossover and mutation, with elitism preserving top scores so that fitness never decreases. The design space, representation, bit strings, real vectors, programs, the mixing number row, selection procedure, mutation rate, makes them continuous with beam search. Row equals 1 reduces to stochastic beam search. Row equals 2 is the familiar generative pairing, CH4. Constraint satisfaction problems, a factored representation, a set of variables, each of which has a value. Solve when every variable satisfies all constraints. The black box broken open, so a partial assignment violating a constraint is immediately discarded, an 87% reduction on a map coloring example. The machinery that makes CSPs scale. Local consistency, node, arc, path, and k-consistency, whose absence is an empirical science. Backtracking with commutativity. The MRV/degree/least constraining value heuristics, fail first, fail last. Forward checking and MAC. Conflict-directed backjumping. Skipping Tasmania, obviously silly. Min conflicts local search. Solves even the million queens problem in an average of 50 steps. And tree decomposition, where CSPs with constraint. Graphs of bounded tree width are solvable in polynomial time, CH6. Game search. Adversarial environments modeled as deterministic, two-player, turn-taking, perfect information, zero-sum games between max and min. The minimax value of a state is the utility, assuming that both players play optimally, but its exponential cost makes it impractical for complex games. The chess tree is best thought of as a theoretical construct, so alpha-beta pruning cuts the exponential in half by tracking the best value found so far for max, and for min. Heuristic evaluation functions plus depth cutoffs. Retrograde in-game tables, 7-piece tables of 400 trillion positions. Expect a minimax for chance, and Monte Carlo tree search with the UCD bandit selection policy for Go. The value of a state is estimated as the average utility over a number of simulations, CH5. Incomplete information games. Card games feature stochastic partial observability, where the missing information is generated by the random dealing of cards. The naive analogy to dice yields averaging over clairvoyance, which can lead one astray, the day 3-4 parable. Because it does not consider the belief state the agent will be in after acting, it never selects actions that gather information, will never bluff, and fails where belief states matter. The fix is abstraction, treats similar hands as identical, plus deals sampling. The recipe behind Libratus's superhuman no-limit hold'em victory and a live motivation for CH17's POMDP. Machinery, CH5. Logical reasoning, propositional, and first order. The Wumpus world formalism, where a model sets the truth value of every symbol and entailment, is semantic. Resolution proves KB entails alpha by deriving the empty clause from KB and not alpha. Horn clauses admit efficient forward data-driven and backward goal-directed chaining completeness when applied to suitable Horn knowledge bases and SAT solving. DPLL with unit propagation, pure symbols, conflict clause learning, and random restarts. Can handle problems with tens of millions of variables and have revolutionized areas such as hardware verification. CH7. First-order logic and unification. The great advantage of lifting inference over propositionalization is that it makes only those substitutions that are required. Generalized modus ponens combines a universally quantified implication with matching atomic sentences under unifier theta, and unification finds substitutions that make different logical expressions look identical, with standardizing apart resolving the accidental variable collision in a single most general unifier, MGU, that is unique up to renaming. Scholomization and resolution handle existential goals. Who killed the cat? And the declarative ideal reaches its fruition in Kowalski's equation algorithm equals logic plus control, ch 8 to 9. Knowledge representation, ontological vocabulary, categories, events, measures, time, interval-based reasoning, grounded by the circuit example, where one sign that we have a good ontology is that we require only a few general rules. Semantic networks are a form of logic whose inheritance reasoning, compared with semi-decidable logical theorem proving, has been one of the main attractions, but they're hidden traps. Categories do not have mothers or legs. Set up multiple inheritance, where conflicting inherited values pose the problems default reasoning must resolve, the Nixon diamond. Measures are simple, quantitative measures, with units and the insight that order alone suffices for qualitative physics, ch 10. Planning, factored action schemas let relaxations yield domain-independent heuristics. Ignoring selected preconditions recovers the ch3 heuristics. The ease of manipulating the action schemas is the great advantage of the factored representation, and ignored elite lists make monotonic progress possible for FF's hill climbing. Hierarchical planning formalizes abstraction through angelic semantics, where an HLA's reachable set, not an adversarial demonic worst case, determines success, requiring the downward refinement property to make high-level proofs provably correct. Temporal planning adds the critical path method, slack, and resource constraints that make scheduling NP hard, ch 11. Probability and Bayes' rule. The full joint distribution can serve as the knowledge base, marginalization, conditioning, and normalization, with alpha ensuring that it adds up to 1. Answer any query but do not scale well. 2 to the 100th approximate 10 to the 30th entries. Bayes' rule, underlying most modern AI systems, converts the causal direction we perceive as evidence the effect of some unknown cause into the diagnostic. The meningitis example is the base rate fallacy in miniature. 0.7, the 1 over 50,000 over 0.01 equals 0.0014. Its independence-leaning workhorse, naive Bayes, often work as very well even when the conditional independence assumption is not strictly true, though overconfident posteriors make it a model that is overconfident, ch 12. Bayesian networks, a DAG together with CPTs, encoding the assumptions that effects do not perceive, causes directly Pearl's burglar alarm, and containing no redundant probability values. So a knowledge engineer cannot create a Bayesian network that violates the axioms of probability. The topology is a qualitative claim, independent of the specific probability values, and construction orders variables such that causes precede effects, parents being those that directly influence each child. Variable elimination is a form of dynamic programming whose cost is related to the tree width of the graph. Independence relations are read off the structure, deseparation, the Markov blanket, and the chapter's coda, causal networks. Opens the correlation intervention step that later reasoning about actions builds on, ch 13. Approximate inference. Exact inference in large networks is intractable, so Monte Carlo methods provide approximate answers whose accuracy depends on the number of samples. Rejection sampling is consistent but wastes exponentially many samples as evidence grows. 1 in 1,000 survive on the insurance network. Likelihood weighting uses all of its samples but concentrates weight when evidence is heavy. MCMC gives sampling of one variable at a time from its Markov blanket, does pay attention to downstream evidence but can fail because the deterministic relationship breaks the property of ergodicity. Metropolis. Hastings restores mixing with a proposal and acceptance step. Convergence to the correct stationary distribution, guaranteed for any proposal distribution, provided the resulting transition kernel is ergodic, ch 13. Temporal probabilistic reasoning. Sequence models tamed by the Markov assumption. State depends on only a finite fixed number of previous states, and time homogeneity. Filtering, using the evidence up to the current time to estimate the current state. Prediction and smoothing support the HMM's matrix formulation. The umbrella worlds T equals 0.7, 0.3, 0.3, 0.7, and the Viterbi algorithm's most likely path. For continuous states, the Kalman filter exploits the fact that the linear Gaussian family of distributions remains closed under Bayesian updating. Y filtering generates a Gaussian state distribution for all time. Robot localization is the worked application, with a robot locating its location to within 2 squares after 20 observations, despite a 59% Wrong sensor, CH14. Probabilistic programming and infinite models. Lifting the finite domain constraint to relational probabilistic models with unlimited objects. A model is a program whose objects, relations, and uncertainty are declared together. Open universe models dynamically create brands of objects, and knowledge-based model construction reifies the result of the model construction as a random variable, so that even the number of entities can be uncertain. Gibbs sampling and lazy evaluation make inference tractable. Probabilistic programming languages, Church, Anglican, etc., implement this as probabilistic knowledge representation in a universal language, CH15. Decision theory and value of information. Probability theory plus utility theory for individual decisions. The maximization of expected utility, with preference axioms guaranteeing any rational agent must behave as if it possesses a utility function. Decision networks add action and utility nodes. The expected value of information is non-negative. VPI of E sub j is greater than or equal to 0, is not additive in general, but is order-independent, and drives the information-gathering agent that repeatedly requests the observation with the highest VPI of E sub j over C of E sub j. A myopic policy that has been shown to outperform expert physicians in selecting diagnostic tests, even though it can fail when no single variable helps. Much, CH16. Sequential decision-making, MDPs, and POMPs. The Bellman equation relates state values to successor values. Value iteration and policy iteration compute optimal policies for the Markov decision process. POMPs extend this to partial observability. The optimal action depends only on the agent's current belief state, where an action is evaluated at least in part according to the information the agent acquires as a result, making value of information one component of the decision problem. The POMDP belief space is continuous, which is what makes approximate solvers and hierarchical decomposition necessary. The real world is one, CH17. Multi-agent decision-making. At the other extreme, an agent design in game theory. Nash equilibria, the maximum solution of zero-sum games. Moore's equilibrium is both players play 7/12 and 5/12, with the true utility exactly minus 1/12. Repeated games and cooperation, cooperative games with the core and Shapley value, mechanism design, making truthful revelation incentive compatible, and voting, with the honest worry that voting is not as simple as it might appear, and arrow style. Impossibility lurks, the layer that CH5's adversarial search and CH17's MDPs both feed, CH18. Machine learning. The discipline of choosing a hypothesis that will optimally fit future examples, under the stationarity assumption that future examples will be like the past. Its disciplines are methodological as much as mathematical. Training/test/validation splits. Test locked away until you're completely done. K-fold cross-validation and regularization. The minimum description length view that a good hypothesis is a compression. Encode the hypothesis as a Turing machine program. The theory chapters make the limits precise. Pack learning bounds sample complexity. And with a realistic problem, the empirical best differs from the truth through unrealizability, variance, noise, and computation, CH19. Probabilistic learning. Maximum likelihood and maximum a posteriori estimation, with their bias, variance anatomy. Naive Bayes classification, logistic regression, and Bayesian networks learn from data, including from missing data via EM, the expectation maximization algorithm, iterating between filling in hidden values and re-estimating parameters, which will converge to a local maximum of the likelihood. The chapter's philosophical lesson is the Bayesian versus frequentist debate, with Bayes nets as the accommodating middle, letting the model itself be learned rather than assumed, CH20. Deep learning. The computation graph as the unit of design. Represent hypotheses as computation graphs with tunable weights and compute the gradient of the loss with respect to those weights. Backpropagation is simply an application of reverse mode automatic differentiation, with the sign structure gradients giving the vanishing gradient as deep networks suffer when error signals are extinguished, fixed by residual connections and LSTM's gates. CNNs exploit spatial invariance via kernels and pooling, a kind of logical disjunction, cutting the 9 trillion weights of a fully connected layer. Training is mini-batch stochastic gradient descent with momentum, learning rate schedules, and batch normalization, CH21. Reinforcement learning. Learning from evaluative rather than instructive feedback, where the agent must explore to make better action selections while exploiting what it has experienced. The exploitation dilemma, unresolved in general. The framework is the MDP with a reward signal and learned value functions. Temporal difference learning combines the sampling of Monte Carlo with the bootstrapping of dynamic programming, and Q-learning is model-free, yet converges to the optimal Q function. Function approximation extends it to large spaces with a deadly triad warning, policy search and actor, critic handle continuous actions, and inverse RL recovers reward from demonstrations. The bridge to CH27's preference learning, CH22. Language and the transformer. NLP moves from bag of words and probabilistic language models through semantic roles and pragmatic reasoning to deep learning. With self-attention, the transformer's query/key/value mechanism, summarized by the paper title Attention is All You Need, as the unifying architecture that makes word context, not position, the currency of representation. Transfer learning, pre-training, and sequence generation complete the modern stack, connecting directly to the deep. NLP chapters language models, generation, and translation, CH23 to 24. Computer vision, the problem of recovering properties of the world from images. Image formation, geometry, and photometry, and early vision, edge, texture, stereo, supply features. Object recognition runs on the CNN stack, patterns of patterns, with object detection and semantic segmentation, and 3D reconstruction gathers depth from stereopsis, structure from motion, and shape from X, with the geometric fact that, as an object moves closer to the two cameras, the corresponding image points separate, so disparity inverts depth, CH25. Robotics, the robot as the integration of the book's methods in a single, embodied, uncertain, time-critical system, sensors with LiDAR accurate to within a centimeter at a range of 100 meters, effectors and grippers, localization, Kalman filtering, and SLAM's key insight that the map and the robot's pose are correlated and snap into agreement at loop closure. Motion planning and control, reinforcement learning with sim-to-real transfer and domain randomization, and human-robot interaction, evaluated not only for task success but for trust, comfort, and legibility. Because a robot that completes its task but frightens or inconveniences people is a failure. CH26. AI, safety, and ethics. The accumulating responsibilities, lethal autonomous weapons, mass surveillance with differential privacy as the technical remedy. Whether any one person decides to participate makes no appreciable difference to the answers. Algorithmic bias, where the fairness criteria, individual, group, unawareness, demographic parity, cannot all be satisfied simultaneously. So, the choice among them is a values judgment, the attention economy, and robot rights. The positive program is value alignment. If we cannot supply that objective correctly, the machine may pursue our objectives only imperfectly or actively against them. So the machine must be uncertain about the true objective, learn preferences, and defer. The theme that unifies CH1 and CH27 to 28, CH27. Bounded optimality and the future, the computational limit argument. Even the ultimate 1 kilogram computing device at about 10 to the 51st operations per second cannot enumerate the 11-word strings, forces the target perfect rationality to give way. Rather than aiming for something that cannot possibly exist, we should consider a different normative target, one that necessarily exists, namely bounded optimality, the best possible performance among programs for a fixed architecture. The book's final commitment is to beneficial intelligence. Machines that know what we want, that are uncertain about our objectives, and that defer to us accordingly. The successor to the standard model and the ARC's endpoint, CH28. Reading comprehension questions. What are the 4 definitions of AI, and why does acting rationally subsume the others while remaining more general than correct inference? Scaffold. Explain the standard model of AI and state the 2 reasons Chapter 1 and Chapter 27 concluded as inadequate for real-world systems. Scaffold. Trace how an admissible heuristic makes A-star optimal. State the result and the role of consistency, triangle inequality, in making reach table entries permanent. Mechanism. Contrast the belief state approaches. How does Chapter 4's sensorless planning, Chapter 14's HMM filtering, and Chapter 17's POMDP each generalize the same idea? Mechanism/relationship. Given a Bayesian network, explain why variable elimination's efficiency depends on the elimination ordering and tree width, and why Gibbs sampling can fail ergodicity, where exact inference succeeds. Mechanism. Derive the temporal difference update from the Bellman equation and explain why Q-learning is model-free yet converges to the optimal Q function. Mechanism. State the pack-learning bound and use it to explain why the class of all Boolean functions is not pack-learnable while bounded decision lists are. Mechanism. Describe how a convolutional network's patterns of patterns hierarchy explains its success on ImageNet and why residual connections and data augmentation are needed for deep training. Mechanism/critical thinking. The book says, a wealth of information creates a poverty of attention, Simon. How does the attention economy's incentive structure conflict with building personal agents that stick up for our true long-term interests? Critical thinking, value assumption. Fairness has many definitions: individual, group, unawareness, demographic parity. Argue why no single criterion can be universally correct and what this implies for designing a loan approval system. Critical thinking, gray conclusions. Explain the library of Babel computational limit argument and why it forces the shift from perfect rationality to bounded optimality. Is bounded optimality a goal that necessarily exists, and what does finding it require? Mechanism/critical thinking. The book's final framework says beneficial AI must be uncertain about the true objective. Connect this to Chapter 16's decision theory, Chapter 22's inverse RL, and Chapter 26 SHRI. What technical commitments make asking permission rational rather than merely cautious? Critical thinking synthesis.